All right. This is CS50, Harvard University's Introduction to the Intellectual Enterprises of Computer Science and the Art of Programming. My name is David Malan, and I actually took this course myself back in 1996. I was a sophomore at the time. I was actually concentrating in government because a year prior, as a first year, I'd come into Harvard thinking that I liked history and constitutional law and sort of similar classes in high school. And so when I got here, I rather gravitated toward that which was familiar. I figured if I liked and if I were good at that particular subject in high school, then that's presumably who I'm supposed to be here. But it wasn't until sophomore year that I got up the nerve to step foot in the CS50 classroom. And even then, it was only out of curiosity. Like, I had no intention of studying computer science, of even taking CS50 when I got to campus. But people were talking about it, and there was a lot of beware, and it was perhaps for the initiated only. And I didn't really know ultimately what computer science was. But for me, the sort of light bulb went off, and I found that contrary to what I'd seen in high school, where I saw friends of mine programming away in the computer lab, heads down, sort of antisocially, just doing whatever it was they were doing, it really wasn't that once I got to this particular class in this particular place. It was much more about problem solving more generally and just learning how to express yourself in code in different languages so that you can actually solve problems of interest to you, even if you have no intention of being a computer scientist or an engineer, but just want to be able to solve problems, analyze data, do interesting things in the arts, humanities, social sciences, physical sciences, or really any other field. And indeed, this particular path led me to computer science, but the hope for CS50 more generally is that indeed you just find your way to applying principles that you'll learn over the coming months to whatever field is of interest to you. With that said, it was definitely a lot of work, and not without its frustrations for me, but there was no better feeling than banging your head proverbial against the wall for some number of hours, even days, trying to fix a bug, a mistake in your code. And then, oh my God, the rush of emotion, of accomplishment, of pride, of exhaustion when you finally solve some problem that's really been weighing on you. It's just so incredibly gratifying, but also empowering. Because unlike a lot of fields, computer science was built by humans themselves. And so if a human built this, surely you, another human, can understand it as well. And so even though there's going to be some distractions along the way, you're going to see what looks incredibly cryptic if you've never programmed before. Over time and with practice, everything just starts to make more sense. And with time and with practice, you just get better at this particular field. And indeed, really, the key to success in programming in general is just to allow yourself enough time. And so at least, thankfully, I quickly got into the habit of starting early in the week, for instance, when writing actual code. Why? Because you're going to run up against a wall. You're not going to see some bug. Something's not going to jump out at you, and that's fine. That's when you sort of call it a day, take a break, move on to something else, and then just come back to it. And that's what keeps programming fun for me, even all of these years later, whether it's teaching or actually applying it. But there's down the road a history of an MIT hack, and it looked a little something like this in yesteryear. And there was a little sign the MIT students, when they made this hack, on the wall that says, "Getting an education from MIT is like drinking from a fire hose," which indeed they have connected to what should have been otherwise just a water fountain. And that's going to be what it feels like sometimes, not just in computer science per se, but just an unfamiliar field. If you're not from STEM, if you're not from CS, that's fine. But so much of it ultimately is going to be absorbed by you and going to be within your grasp by term's end. So just keep in mind that's very much the intent, but you'll be amazed what you're able to create, to accomplish just 3 or so months hence. Indeed, 2/3 of you, contrary to what you might think or assume, have never taken a CS class before. So it's absolutely not the case that the person to the left and to the right surely must know more than you. Indeed, it's quite the opposite. And as you'll see in the coming weeks, as you write your own code and solve your own problems, what ultimately matters in this course is not so much where you end up relative to your classmates, but where you end up relative to yourself when you began. And it really is all about that delta, whether you've programmed or not, just getting something out of a class like this. And if it does take time, and if you do feel those frustrations, but you simultaneously eventually feel that sense of accomplishment, that just means it's all working. And indeed, hopefully, all the more worthwhile and gratifying ultimately as a result. So what are we going to do in the coming week? So here we are in week 0. We'll soon see why computers and computer scientists start counting, if you will, from 0. 0, but week 0 is one in which we explore computational thinking, sort of thinking like a computer and starting to clean up your thought processes, getting you to think, to solve problems more methodically, and then ultimately translating that into code. And some of you might recognize this environment here, aka Scratch, coincidentally also from MIT. You might have used it in grade school. We'll use it today and a little bit this weekend in the course's first homework assignment or problem set, but not so much to kind of play around in a way that you might have if you did use it in yesteryear, but to explore ideas of computer science and programming that we're going to use and reuse every week hereafter as well. Thereafter, we're going to transition just next week to week 1, so to speak, whereby we'll introduce you to a more traditional language, a lower level language, an older language called C. And in C, you're going to use your keyboard, not so much your mouse and pointing and clicking, but you're going to write code that soon is going to look a little something like this. And if you've programmed before, you can probably glean what this is going to do. If you've never programmed before, which is the case for most of you, this too will soon make sense. But this is the most canonical program that most any programmer ever writes, called Hello World. And indeed, that and all of the surrounding syntax above and below just that sentence, Hello World, will soon make all the more sense. You'll learn how to use industry standard tools, so to speak. Pictured here is something called Visual Studio Code or VS Code. You'll use a cloud-based version of it initially, so you don't have to suffer with any technical difficulties or headaches like that. It'll just work right off the bat. But we'll use that tool and others ultimately to then explore ideas in computer science, principles that you can apply, and we'll take a look underneath the hood, so to speak, of your computer at your memory, or RAM, random access memory, where all of the data is ultimately going to be stored. We'll also take a look thereafter at bugs. A bug is a mistake in a program. Here is an actual bug in an actual computer in yesteryear, but we'll teach you how to debug programs, find your own mistakes, find others' mistakes, and improve that code as well. We'll transition then to algorithms, step-by-step instructions for solving some problems, which we'll touch on today too. And if you picture here, this is actually a pretty representative problem. Odds are you haven't had to deal with something like this, but it's representative sorting, for instance. If you think of each of these small bars as being a small number, each of the bigger bars as being a bigger number, you might wonder, well, could you as a human sort all of these bars? Like get all the short bars over here, all the big bars over there. Well, odds are if you're like me, you would probably kind of eyeball it. And if you could physically interact, you might just start grabbing the smallest elements first, put them over on the left, maybe grab the biggest elements, put them over on the right. But what's your algorithm there? Like, how would you teach someone younger than you who's never done that before how to do it? How would you compel your Mac or PC or phone to do something like that? You can't just kind of wave your hand and say, oh, figure it out, move things around. You have to express yourself more methodically. So we'll translate even ideas like this into code too. And that's what the Googles and others of the world are doing constantly as they sort and organize the world's information. We'll use metaphors along the way if it helps. We'll talk about your computer's memory as kind of being like a postal address. Like every mailbox in the world has some form of postal address, street, city, state, country, and the like. And it turns out that's how your Mac, your PC, and your phone also work. You've got a whole bunch of memory, like the picture before, but you can think of it really as individual mailboxes. And you can put anything you want in those mailboxes, and you can go to a mailbox to grab information that's from it. So at the end of the day, that's really all your computer's doing with information. It's just kind of organizing it, not into mailboxes per se, but a term you probably know called bytes, for instance, instead. We'll talk about problems that arise, even nowadays. In fact, most of you are familiar with your Mac, PC, even phone, like spontaneously rebooting sometimes, crashing, the little annoying spinning beach ball or hourglass icon that happens. Like, what is with that? Well, those are just bugs in programs that humans at Apple and Google and Microsoft and others, they screwed up. And they wrote buggy code, and your computer, when it encounters those mistakes, doesn't know what to do. And so 9 times out of 10, so to speak, it just crashes or freezes or the like. But that kind of stuff will make more sense. So even the real world will make sense. And pictured here are some lower level terms we'll eventually get to mid-semester. But generally speaking, when something is going this way, as per this arrow, and something is going this way, as per this arrow, like that does not end well. And that often is what happens when your computer crashes. Someone's using memory up here, but someone else is using memory down here. And then they're not really talking left hand and right hand. So that is just a high-level overview of some of the problems we'll encounter. But we'll focus too on data ultimately. So pictured here is something fairly technical called a hash table. It's an amalgam of something we're going to soon call an array and also something we call a linked list. And these are just fancy terms for describing how you can organize information even more flexibly than just putting individual values in mailboxes, like how could you build structures, like actual data structures, so to speak, two-dimensional structures at that? And so what you're seeing here is a glimpse, as some of you might have recognized, of some Harry Potter universe names, but they're organized somewhat alphabetically. And notice that anytime there's multiple people with a name that starts with H, like Hermione, Harry, and Hagrid, well, they can't all fit in that mailbox if each of these squares along the left is that same mailbox. So you have to kind of chain them together. Well, we'll learn how to do that in code so that even if you get more data than you expect, if your business is booming and you're some web-based business, how do you keep adding and adding information to your software to actually keep up with it? But this, again, is what code's going to soon look like, as soon as next week in week 1, this here being C. But we'll transition in a few weeks to a more modern, higher level language, so to speak, called Python. Indeed, the course very deliberately, back in my day and now this, introduces you first to C, which, funny enough, many people don't tend to program in certainly every day. I use C generally September, October, November, December when teaching CS50 itself, but it's everywhere nonetheless. In fact, even today's other languages with which you might be familiar, like Python and Java and yet others still, use C, this same primitive language underneath the hood, because it's so darn fast. And as you'll learn over the coming weeks, it really gives you access to and an understanding of what's going on conceptually down here, so that thereafter, after CS50, when you're writing code, you can sort of think at a very high level what's actually going on. So in fact, in just a few weeks, what looks like this in C is going to look instead like this in Python. And you'll better understand what's going on underneath the hood. And odds are, after this class, you'll reach for a language like Python more frequently than C, but you're going to benefit from that bottom-up understanding thereof. Thereafter, and towards term's end, we'll introduce you to a few other ideas, like where do you put large amounts of data in things called databases. Not things like spreadsheets like here, but actual databases where using those same kinds of data structures, you lay things out in an interesting way in memory. Thereafter, we'll transition to a very familiar environment that you and I use every day, the web. Like the web has become rather the user interface or UI that we use everywhere on the laptops, desktops, and even mobile devices nowadays. Well, pictured here is a language called HTML. It's not a programming language. It's a markup language. And some of you might have made home pages or portfolios in the past. But you'll understand what's going on here. But more powerfully, you'll understand how the computer sees that same kind of code, builds up a hierarchical family tree type structure in memory, and then you can manipulate that tree with code to actually add more and more information, chat messages, anything on the screen that you like. And finally, we'll tie all of this together by introducing what are called frameworks and libraries, third-party code that makes it a lot easier to solve problems of interest to you. And so in particular here, this is the very first web app that I myself made back in like 1997. I was part of the first-year intramural sports program, not as an athlete, but as the programmer, and I was teaching myself how to build web applications. I only knew C and maybe a little bit of something else at the time, but this became, for Harvard at least, the very first website for the first-year intramural sports program. And it wasn't just a static website with links and images and the like. It was interactive. You could register for sports. We could input exactly who was in a tournament bracket or the like, and it could actually automatically keep track of this data. So there too, after just 3 months of a class like this, you'll go from writing quite simply this week and next hello world to building things like this for whether it's web, mobile, or other platforms as well, if you so choose. But we'll get you off of the course's infrastructure by the end of the term. You won't be using any toy environments along the way. We'll empower you ultimately to write code after CS50, especially if this is the only CS class you ever take on your own Mac or PC using the same software, but not the cloud-based version thereof. But all of this software is itself free and can be used by you powerfully after the course's own end. But along the way, as you may know, is there this tradition within the class, particularly in healthy times, of a number of events that really brings people together, not just collaboratively academically, but to just solve problems and generally engage with each other as well. Coming up first, CS50 Puzzle Day, which is meant to be not jigsaw puzzles, but logic puzzles that require no prior experience with computer science or programming, but it's just an opportunity to sort of quietly work on a packet of puzzles with some number of friends for prizes and more. Later in the semester, once you tackle your final projects, the capstone of the course, where we don't give you a homework to write, you yourself come up with something to build. We'll get together generally around 7 p.m. in the evening, wrap up around 7 a.m. if you so choose, and it's an evening, a 12-hour opportunity to collaborate with classmates on your very own final project in a large space on campus that ends, if you're awake with us, at 5 a.m. We can hop on some CS50 shuttles and go down the road for some pancakes at IHOP around 6. Of course, this is 6, 7 a.m. at that point, but it's an opportunity finally to lead into what's called the CS50 Fair, which is an end-of-semester celebration and exhibition of everything that you'll accomplish over the coming months. And in fact, pictured here are some of your predecessors in healthy times. The CS50 Fair allows you to come with your laptop or phone and exhibit to students, faculty, and staff across campus, put together something in person and on video that people can delight in seeing as you exhibit what it is you created and what you learned over the course of the several weeks, and ultimately a chance to just share and inspire others as well. And you'll all walk home ultimately with your own I Took CS50 t-shirts saying as much as well. So with that high-level overview of the course, I propose that we begin to take a look at what computer science itself is and what it is we're going to be doing over the next several weeks at this lower level than 2. So what is computer science, right? If you're maybe like me or new people like my friends in high school, you probably assume that it means programming. And that's absolutely a big part of it for a lot of people, because with code you can write, you can express ideas and solve actual problems, especially involving data. But computer science itself is really the study of information, if you will. How do you represent it, and how do you actually process it? And in that sense, computational thinking is just the application of ideas from computer science, a course like this, to problems of interest to you. Again, in the arts, humanities, sciences, social sciences, whatever the domain of interest is to you. So with that, if computer science is all about information and with it the solving of problems, well, what does it actually mean to solve a problem? Let's see if we can't propose a model into which all of the lessons learned will ultimately follow. And I'd propose that this is problem solving. You've got some input, which is like the problem you want to solve. The goal is to solve it, so that's the so-called output. And then somewhere in here, the proverbial black box, is some kind of secret sauce that gets the work done. And in the coming months, we'll have to decide, well, how are we going to represent these inputs and outputs? And really, how do we code up? How do we write solutions for what it is that's solving the problem of interest to us? So when it comes to representation of information, there's a lot of ways we can do this. And for instance, if the problem at hand quite simply is to take attendance at the beginning of class on the first day of school, well, how could we go about doing this? Well, we could actually use a system called unary. Well, what is that? Well, that's a fancy way of saying 1, 2, 3, 4, 5, maybe 6, 7, 8, 9, 10. And I can use my digits, pun intended, on my fingers to actually count everyone up. And eventually you need toes and whatnot if you have to count so high. But unary is a very simple system of using a single symbol, a human finger in this case, to just solve some problem, like counting the number of people in the room. Let's make this slightly more technical for a moment, a little more mathy. That's just called base 1, where the base under which you're operating has 1 digit in it, like literally a human finger, and maybe multiple such fingers if you need to count higher. But of course, most of you, if not all of you, generally vaguely know that computers use something other than unary. And even you and I probably don't use this that often. They use what language or alphabet instead? Yeah, so binary. So binary is indeed the system that computers somehow use. So in this case, bi implying 2. And so computers have 2 digits, it turns out, at their disposal. And in fact, if you've ever heard the technical term bit, which is like a smaller version of a byte, more on that soon, well, a binary digit is the origin of that term bit, because if you get rid of some of the letters and you're left from binary digit with just bit, thus is a bit. A bit is just a 0 and 1. It's 2 more digits than you might have on your own finger. And of course, it's fewer, though, than you and I have. You and I typically use, as humans, the decimal system. Dec meaning 10, because you and I generally use 0 through 9. So on the one hand, another pun intended, you've got unary. Computers use binary. We humans generally think and talk in terms of decimal. But at the end of the day, these are fundamentally going to be the same thing, which is to say that it's all pretty accessible to us. Even if you're not a computer person, I dare say you're about to be. So what is a bit? Well, a bit then is a 0 or a 1. That is a so-called binary digit. But how do computers only speak in binary? How do they solve problems, represent information using only binary? Well, at the end of the day, if they want to represent 0 and 1 we need to do so physically somehow. And I dare say that maybe the simplest way to think about a bit, a 0 or 1, is like a light bulb. And so by human convention, let's just assume that if you are a computer, be it a laptop, desktop, phone, or the like, and you want to represent the number 0, you know what? You just keep a light switch off. You keep a light bulb off. If by contrast, you're that same computer and you want to represent the number 1, you take that same switch, that same light bulb, and just turn it on. So a light bulb that's on represents a 1, and a light bulb that's off represents a 0. So why is this relevant to computers? Well, at the end of the day, you and I are charging our laptops or phones at night. So there's some like physical resource being replenished there, whether you're on battery or some power cord. And so inside of a computer are just thousands, millions of tiny little switches nowadays. You can think of them metaphorically as light bulbs, but they don't yet actually shine light. But there are tiny, tiny little switches. And those switches, if you've ever heard the term, are just called transistors. So like computers have millions of transistors that can either be flipped on to represent 1s or flipped off to represent 0s. And from that very simple mechanism, electricity is there or it's not, a 1 or a 0, computers can actually count obviously from 0 to 1, but it turns out even higher if they use a little more electricity as well. So how might I do this? Well, let me go ahead and propose that I just grab one of our own light bulbs here on stage. This one's off. So for instance, if this were miniaturized inside of your Mac, PC, or phone, this would be a transistor. And indeed, here's the little switch on the bottom. And if your computer wants to represent a 0, it just leaves the switch off, and the light is not shining. If you want to represent a 1, well, now I've counted as high as 1 because the switch is now on. I've grabbed a little electricity. I'm holding on to it inside of the computer. And so now I see that this is a 1. All right, but unfortunately, with just one switch, one light bulb, I can only count from 0 to 1. How do I count out higher, might you think, intuitively? Say again? Yeah, so more light bulbs. So let me do this. Let me just grab something to put these on so I can use a few of them at a time. And let me propose that here, instead of having just one light bulb, let me give myself maybe 3 in total. So all of them are initially off. And if you think of this in miniature form in your mind's eye, this is like a computer with 3 transistors, 3 switches, representing now the number you and I know as 0. Why? They're just all off. So how does a computer go about representing the number 1? Well, it turns on one of these light bulbs. And how does the computer represent the number 2? Well, you might think, if I may, you just turn on a second light bulb. And if you might think, how does a computer represent 3? You just turn on the third light bulb. And so as such, with 3 bits, a computer would seem to be able to count from 0 on up to 1, 2, 3. But it turns out if I'm a little smarter here, I can actually count higher than that. Why? Well, I'm just considering like the combination of bulbs being on here. What if I do something like this? This is still 0, I will claim. But what if I propose now that this will be how a computer represents 1? On, off, off. This, though, will be how the computer represents 2. Notice I didn't turn on the same 2. I'm just turning on the 1 in the middle. This, I now claim, will be how a computer represents 3. This is going to be, in just a second, how a computer represents the number we know as 4. And yet I'm still only using 3 bulbs. This is going to be the number the computer represents as 5. This is going to be how the computer represents the number 6. And then lastly, it turns out with 3 light bulbs, if you're smart about it, you can count, it seems, as high as 7. Now, even if you kind of lost track of like what I was turning on and why, I claim there were 8 different patterns, from all of them off to all of them on. But notice that I started to permute them. I took into account which ones were on and which ones were off. Why, though, do these represent the numbers we know as 0 through 7? Well, let me go ahead and maybe let's do this. Instead of just considering there to be light bulbs, let's assign some special significance to each of them based on where it is. And maybe for this, could we get maybe 3 volunteers? 3 volunteers? OK. You're being volunteered. OK, come on up if you want to go over to the stage there. Yeah, you want to come on up as well? And over here as well. So there's some stairs on either end. Maybe a round of applause for our first volunteers of term. All right, so you are number 1. And if you want to go ahead and stand roughly right here. How about you want to be number 2? OK, come on over and right to the right of here. And you'll be number 4, it turns out. And if you want to come over here on this end, let's give you all a moment to introduce yourselves briefly to your classmates if you'd like.
Hi, I'm Ellie. I'm a senior.
Nice to meet.
I'm Rayhana, and I'm a first year.
Welcome.
Hi, I'm Joseph, and
I am a first year.
Welcome. All right, so glad to have all three of you up here. Thank you. Let me propose now that we'd like you three to represent, how about the number 0? And I claim now that if each of you now represents a switch, you have sort of fancier light bulbs now. One is a 1, one is a 2, one is a 4. But each of you are still just has a switch on the bottom, in fact, of your plastic devices. I claim these three volunteers are representing the number 0. Let me ask you all now, how might you represent the number 1? How should you cooperate here? OK, so we would have on, off, off, which I think matches what I did with my 3 light bulbs as well. If you want to go ahead and turn yours off, how might you all 3 represent the number 2? OK, so off, on, off now, from right to left. How would you 3 represent the number 3? So that's why my 2 light bulbs went on at the end. How would you 3 represent the number 4? Perfect. Number 5? Number 6? And number 7? All right, and give us one more. How would you represent 8? OK, you can't. How about then one more volunteer? One more volunteer. OK, come on up. All right. What's your name?
My name is Moeen.
If you want to say it there.
My name's Moeen.
All right. And Moeen, you're going to be number 8. And if now you all actually, let's make this, how would you represent number 8? All collectively as 4 bits or 4 switches. OK, 8. And now lastly, give me 15. Everyone's awkwardly doing arithmetic in their head. Oh, using unary. 8, yeah, is everyone? 8, yes, OK, round of applause. OK, thank you all. If you want to leave your numbers over here, we have a CS50 stress ball for you. But thank you for volunteering. You can turn those numbers off and leave them over here. So thank you. So how do we go from there to creating these patterns? Well, even though we still had 3 bits initially and 3 switches, later 4 bits and 4 switches ultimately, we still used the same approach fundamentally to actually representing information. And now why were they those patterns, and why did I very deliberately have our volunteers line up in that way? Well, I wanted them using base 2, aka binary. But with binary, there come certain rules. And even if you're not familiar with binary beyond that it exists and relates somehow to computers, it's actually pretty much identical to the system you and I use every day, known as base 10, aka decimal. So let's consider, if you will, by rewinding to primary school for just a moment, like how decimal works. And you'll see that even if you're not a computer person, you actually are. You just have to tweak your mental model ever so slightly. So here is the number that you're probably viewing as 123. But why is that? Well, it's not really 123. These are just this is just a pattern of 3 symbols on the screen. 1, 2, 3. And your mind is sort of rapidly assigning mathematical meaning to them. 123. But why is that? Well, if you're like me, you probably learned back in the day when you have a 3-digit number like this, the rightmost number is in the ones place. The middle digit is the tens place. The leftmost digit is in the hundreds place. And why is that relevant? Well, if you then quickly do some mental math, as you and I just do instantly nowadays, that just means 100 times 1 plus 10 times 2 plus 1 times 3. Of course, 100 plus 20 plus 3 gives us the number you and I know as 123. But beyond that, how do we get to just 2 digits instead of as many as 9 in the decimal system? Well, let's generalize this. In the decimal system, you and I know if we've got 3 digits represented by these hashes here, yes, it's the ones place, tens place, hundreds place. And if we keep going, thousands, 10,000s, and so forth. But why is that? Well, base terminology is now a little more germane. That's technically the 10 to the 0th column, the 10 to the 1, 10 to the 2. So these are powers of 10, where 10 is your base. Computers just simplify things a little bit, because computers at the end of the day only have access to electricity, on or off. They don't have access to like 10 different types of electricity, just 2, on or off, if you will. Well, they just use a different base. And the rightmost digit would be in the so-called 2 to the 0s. Then the middle digit is 2 to the 1. The leftmost is 2 to the 2, aka 1's place, 2's place, 4's place. And as we kept going, 8. And if we keep going, 16, 32, 64, 128, and so forth. But the idea is fundamentally the same. So why is this how the computer represents the number you and I know as 0? Well, off, off, off from right to left, or in this case, left to right, is just 0. Why? Because that's 4 times 0 plus 2 times 0 plus 1 times 0 is, of course, 0. This is why 0, 0, 1 represents 1. This is why 0, 1, 0 represents 2, and 3, and 4, and 5, and 6, and 7 on up. And why did we need a 4th bit to represent 8? Well, we kind of needed to carry the 1, so to speak, using our familiar human terminology. But for that, we need a 4th bit, another transistor. And this now represents the number 8. And that's why we ended with on, from left to right, off, off, off. So I keep saying on and off, or the light bulb is on or off. But really, I just mean 1 or 0. And so computers and we humans think of things digitally as just being zeros and ones. But mechanically, you can think of it indeed as these light bulbs. Now, a bit's not very useful. Even 3 bits, 4 bits, not that useful. You can count to 7 or 15. Generally speaking, bytes are a more useful unit of measure. And anyone familiar? How many bits is in a byte? Yeah, so 8 bits are in a byte. You can think of it as an octet equivalently. In some contexts, there are nuances there. But think of a byte as just being 8 bits. And that's just a more useful measure. So what does this mean in real terms? Well, if you've ever downloaded like a music file or a photograph or a video, those are measured in bytes. Probably not small numbers of bytes. Probably kilobytes for thousands of bytes, megabytes for millions of bytes, gigabytes for billions of bytes, especially for video. That just means you have a lot of patterns of 8 bits, some combination of zeros and ones on your computer's hard drive. Here then, with a byte of bits, 8 bits is how a computer would typically represent the number 0. And if that same computer uses all 8 of its bits, its full byte to change it to 1, anyone who's quick with math or have seen this before, how high can a computer count with 8 bits or 1? Yeah, 255. Why is that? Well, we're not going to turn this into a constant math exercise. Indeed, after today, we're not really going to think about or talk about bits at this low level. But this is the ones place, 2s, 4s, 8, 16, 32, 64, 128. And if I do all of that math from left to right, that indeed gives me 255. It ignores how we might represent negative numbers, but perhaps more on those some other day. But computers, of course, do so much more than numbers and math and all of this low-level stuff. We send text messages, write documents, emails, and the like. So how might a computer represent something like the letter A? I claim at the end of the day, your Mac, your PC, your phone just has lots of transistors, lots of switches that it can use in units of 8, in units of bytes. How, though, if it's already using those patterns of zeros and ones apparently to represent numbers from 0 on up, how do you go about representing letters of the alphabet, might you think? Yeah. OK, so we could assign a number to every letter. OK, so let me just conjecture. Well, let's just call A 0 for simplicity, B 1, C 2. And now let me play devil's advocate. OK, how do I now represent 0 or 1 or 2? Well, we've maybe created a problem for ourselves. If now we have to steal some numbers to represent letters, we kind of have to pick a lane. But there's a solution to that, too, that we'll see. And it turns out the world is not quite as simple as A being 0. A typically is represented by computers everywhere, phones everywhere, with the number 65, the decimal number 65. Using 8 bits, if we turn some of the zeros to ones, let me just stipulate, you can represent the letter A using 8 bits by turning certain ones on and certain ones off. But we will try not to focus on that binary level too much. So if A is 65, it turns out that B is going to be 66, and C is going to be 67, and so forth. And so where does that get us? Well, it turns out there's a whole system that maps numbers to letters. And here, as I alluded to verbally a moment ago, is the pattern of zeros and ones via which you'd represent 65. And just quick check here. We won't constantly do math. Ones place, that's easy. 2s, 4s, 8, 16, 32. 64's place, so 64 plus 1 gives us 65. So once I do that, how do I get to all of the others? Well, it turns out a bunch of Americans years ago came up with this, ASCII, the American Standard Code for Information Interchange. Now, what does that mean? Well, it's just an acronym describing what really you proposed, a mapping between numbers and letters. Not quite as simple as 0, 1, 2. Starts at 65, 66, 67 for capital letters. But here are most of the letters in use today, at least with this system. So this is just a big chart from online. And you'll see in the middle of this chart here, here's my 65A. Here's my 66B, C. And let's see, 72 is H. 73 is I, and so forth. So there's a mapping, at least for English, between all of these numbers and all of these letters. And if we focus here, those are the beginning of our uppercase alphabet. So suppose then that today, tomorrow, you receive a text message from someone. And underneath the hood, now that you're a computer person, you figure out a way to see what pattern of zeros and ones was sent. In this case, it's wireless as opposed to wired, but it's still some pattern of zeros and ones. And your phone is turning some switches of its own on and off to represent that message from a friend. Suppose that the 3 patterns you received were these 3 bytes from left to right, spelling out a 3-letter word. Well, if we do out the math, 1's place, 2's place, and so forth, I'll spoil it for you. Suppose that you received a text message that doesn't literally say 72, 73, 33, but you received a pattern of 8 plus 8 plus 8, 24 bits that, if you do out the math, represent the decimal number 72, 73, 33. Anyone recall what message you might have received from the green and white charts? Yeah. Hi. But yes, hi is the message. But 72, 73 gives us H and I. What's 33? Any guesses to 33? Yeah, over here. Yeah, so it's an exclamation point. How would you know that? Well, you really do need some kind of cheat sheet, aka ASCII in this case. And if we look elsewhere, let me highlight the left of the chart. You can see that next to 33 in decimal is indeed the exclamation point. So back in the day, a bunch of humans got in a room, decided that, hey, when we start building PCs and later Macs and phones, we all just have to agree on this form of representation of letters of the English alphabet in this case. We just need to agree on this mapping. But somewhat curiously, notice this. It turns out that once you paint yourself into this corner and start using 65 for A, 66 for B, well, how do you represent 65 the number and 66 the number if you want to do math or use Excel or something like that? Does anyone kind of see the solution perhaps? How do you represent the number 1 in ASCII? Yeah, in the middle? Yeah, so this is getting a little maybe Inception or something, but you could represent numbers with other numbers. And so if you want to represent the number you and I know as 1, like when you type it on your keyboard, turns out the computer stores that as the decimal number 49. If you hit 2 on your keyboard, the computer's not storing 2 per se, it's storing the decimal number 50. Now, thankfully, the paradox kind of stops there. We just have a mapping now of numbers to numbers. But really, at the end of the day, and you're going to learn this when we start writing code in that other language, C, next week, it's just context dependent at the end of the day. Inside of your Mac, PC, and phone, there's just all of these permutations of bits, all of these patterns of zeros and ones. And generally speaking, when you open up a text message that you've received from someone, it's zeros and ones. But obviously, if it's a text message, the whole point of text messages is to send text. And so those patterns of zeros and ones by default will typically be interpreted as letters of the alphabet. So you won't see zeros and ones. You won't see decimal numbers. You'll see the English message that your friend intended. By contrast, if you open up something like Excel, that same pattern of zeros and ones might indeed work out to be 72, 73, 33. You might see cells in your spreadsheet with literally those 3 numbers. Why? Because spreadsheets are all about numbers and number crunching and math in many cases. If by contrast you open up Photoshop and try to look at that same pattern of zeros and ones, it's not going to be 72, 73, 33. It's not going to be zeros and ones. It's not going to be high. It's going to be some color of the rainbow. You're going to use those patterns of zeros and ones, it turns out, too, to represent colors. And indeed, so long as you and I just agree, as humans long have, what these patterns are going to be, all of our systems, many of our systems nowadays are indeed interoperable. But I'm being very biased here. And indeed, the A in ASCII is very American-centric. What do you not see in this chart? If you speak any other language than English, odds are you're not seeing characters you know and love and need every day to type or send messages. Well, there's a huge character set that's not supported here, whether it's accented characters and a lot of Asian alphabets. You have many more symbols than can fit even on this screen here. And so humans kind of painted themselves into a corner early on, or really Americans did. But on a typical keyboard, US English keyboard, yeah, you have A's and B's and C's, uppercase and lowercase. But you also have accented characters here. And nowadays, not sure if this is maybe necessary, but nowadays you have other characters on your keyboard, like these. And these are kind of a playful incarnation of what's actually a technical solution to this problem. If I claim for the moment that ASCII historically used 7 bits to represent letters, and let's just round that up to a byte, 8 bits to represent letters, ASCII can represent as many as 255, or really 256 total characters. Why 256? Well, if you have them all 0, that's 0. And the highest number I claimed a moment ago was 255. So that's 256 total possibilities. That's not many letters. It's fine for English, but not a lot of human languages. So what might the intuitive solution be if you want to represent accented characters, Asian characters, emoji, even like these, which are just keys on a keyboard nowadays? What's the intuitive solution if a byte's too few? Yeah, so add another digit. Just like we had a 4th volunteer come on up to give us a 4th bit, let's just throw hardware at the problem and use a few more bits. So maybe instead of 1 byte, let's use 2. Or heck, let's use 3 or 4 bytes. Even though it's getting a little expensive, we're going from 8 to 16 to 24 or 32 bits. That's how computers do things these days. And thankfully, we have so much memory inside of our computers and phones, we can certainly spare a few to represent these things. And the solution then to ASCII is what we'll call Unicode. So Unicode is also just a mapping of letters to of numbers to letters, but in many different languages. And indeed, the Unicode Consortium is a bunch of people from all different companies and a lot of different companies and countries and cultures whose mission as an organization is to capture digitally all forms of human language in this case, and to ensure that especially smaller demographics of humans speaking lesser known languages are nonetheless represented and preserved digitally using some mapping of these 0s and 1s. It turns out, though, if you start using 32 bits, as many as 32 bits to represent characters on a keyboard, that's 4 billion possible permutations of 0s and 1s. That's way more than we need for most human languages. So there's a little bit of room in there for some of those more playful things, like those emoji. So for instance, suppose you got a text message with this pattern of 0s and 1s. Or if we do out the math, suppose you receive a text message that if you do out the math in decimal is 4,036,991,106. Anyone know what emoji you're looking at? It'd be weird if you do, but what is this? Well, it turns out that as of this past year, this is the most popular emoji to be sent by many measures, face with tears of joy. So that is the pattern that a bunch of humans in the Unicode Consortium decided would represent this. But you'll notice many of you might have iPhones, some of you might have Android devices too, and sometimes these don't actually look quite the same. This happens to be the current version of face with tears of joy on iOS. On Android, it tends to look a little something more like this. And here's kind of a curiosity. Even though you and I look at these things and they look like images, they're not images. They're characters, at least as we've defined them now in Unicode. And iOS and Android and Windows and Facebook and other companies and apps nowadays really just have different fonts, if you will. So just like fonts with English and other languages can give you different characters with serifs or not, emoji are themselves, yes, drawings that someone made, but they're really just a font. And so that same pattern of 0s and 1s might just render slightly differently on someone's phone or another. If you've ever gotten like an icon on your phone that's broken and you've been sent an emoji, but it's like a square or something arbitrary and not sensible, it might just mean that you have not updated to the latest version of iOS or Android, which just updates the font of supported emoji, because those folks at Unicode pretty much every year nowadays are adding more and more emoji to that particular character set. Now, I went down the rabbit hole figuring out the other day just which are the most popular emoji these days. On Twitter specifically this past year, the most popular emoji, by contrast, was loudly crying face. I don't know if that says more about 2021 or about Twitter, but you'll see different trends certainly in how these are used. But even humans themselves didn't necessarily think 2 steps ahead. And now a lot of the emoji are this sort of default yellow color, but there's a lot of emoji that aren't sort of these cartoon characters, but they're meant to represent humans in various professions or gestures or the like. And nowadays, too, you've probably noticed on your phone and Macs and PCs, there are different skin tones that you can assign to certain emojis. If it's supported by the company and by Unicode, you can actually like touch and hold on a certain emoji, and then you can choose the appropriate skin tone to represent yourself or someone else, and that then modifies the display. Well, let's just think for a moment here, how did Apple and Google and Microsoft and others go about implementing support for emoji with different skin tones? How could you do this? if you want to represent some smiling emoji, but in 5, in this case, different skin tones, you could come up with what? 5 different patterns that are identical structurally, except for the skin tone used in places in that image. But that's a little inefficient, right? To kind of just do copy, paste, 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 and like change the color in Photoshop, if you will. That's going to use more bits, more information than you might need to. How else, if you now start to think a little bit more like a computer scientist, if at the end of the day all you have are zeros and ones, how else could you implement skin tones, might you think? Yeah. OK, so RGB, we'll come to that in just a moment. That stands for red, green, blue. That's one way. In this case, though, I'm seeking an alternative to just using 5 different patterns of zeros and ones to represent the same emoji, but different skin tones. So not quite RGB. Yeah. OK, so store one copy of the emoji and then store different variants of the color that you want to assign to that emoji. Yeah, so this is actually an example of, do you want to elaborate? OK, so you can use a loop to actually output these things. More on that in a moment. Let me go down this road for just a moment. This would be, in some sense, sort of a better design, if you will. But why? Yeah. OK, so filter, if we think sort of in the Instagram sense, you can sort of change the color of something. And that could be related here, too. Oh, interesting. So maybe it could be just a completely different font. And you have 5 different fonts that are almost identical, except for the various interpretations of skin tone for those same emoji. Let me spoil. I think if we go down this one particular road, the way the Unicode folks decided to do this some years ago were the first byte or bytes that you receive via text or email just represent like the structure of the emoji, the default yellow version thereof. But if it's immediately followed by a certain pattern of bits that these humans standardized to represent each of these different shades of skin tone, then the phone, the Mac, the PC will change that default color, yellow in most cases, to whatever the more apt human tone is. So you just use twice as many bits, but you don't use 5 times as many bits. So what do I mean? You don't have 5 completely distinct patterns, per se. For each of these possible variants, you have a representation of just the emoji itself structurally, and then reusable patterns for those 5 skin tones. Unfortunately, that wasn't quite versatile enough for other features that were in the pipeline. And nowadays, too, and there's a double meaning now to representation, emojis had tended to focus on certain professions. And early on, too, were certain professions associated with certain genders and vice versa. And you couldn't necessarily be one gender or another in a certain profession or another. There were these combinatorics that just weren't possible. But nowadays, as you might have seen, you can have couples in love, for instance, that actually look a little more like 3 emojis, but just kind of combined into one. And indeed, this is just one key press on your phone. And you can combine different emoji on the left and on the right with an emoji in the middle. And so it turns out how computers nowadays represent these patterns are one set of bits for the character on the left, one set of bits for a character on the right, one set of bits for whatever emoji you want in the middle, and then you assemble more complicated compositions of emoji by just reusing those same patterns and bits and bits. Emoji doesn't, the Unicode folks don't have to come up with a whole new representation for some very specific incarnation. They can create one for person, for male, for female, for other characters that you might want to display, and reuse those same patterns of zeros and ones. And so here you see sort of the imperfection of, or lack of foresight of humans for building a system early on that was entirely American-centric, no characters, emoji, or the like, that's evolved too. And so that's an important detail in computing nowadays. It too is evolving. And the languages you're about to learn in the coming days, those too are evolving as well. And new features are getting added. And even programming languages have version numbers. You might have a different version of an app on your phone. Programming languages too have different versions as well. Questions then thus far on how information is represented using ASCII or Unicode or anything in between. Yeah? Oh, good question. So to recap, why can't you just, let me summarize that as, why can't you similarly use different patterns to change the context of what these patterns of bits represent, whether it's a number or a letter or a graphic? In actuality, that's kind of what's happening underneath the hood. It's not standardized in quite the same way, but starting next week when we transition from Scratch to C, you'll learn about types, data types, where the onus initially is going to be on you, the programmer, to tell the program whether or not this pattern of bits should be interpreted as a number or as a letter or as a color or something anything else. Nowadays, though, and toward the end of the semester, you'll use languages like Python, where the computer just figures it out for you by context, which makes it even easier and faster to program as well. Other questions on Unicode, ASCII, or the like? All right, well, how about just a few other forms of information? RGB was called out earlier, red, green, blue. How do images get represented in computers? Well, in fact, it's typically an assembly of some amount of red, some amount of green, some amount of blue. But there are other representations. If you're a graphic designer, you might know them. But RGB is still pretty common. What does this mean? This means to represent every dot on your phone or every dot on your TV or your laptop or desktop, there is a number representing how much red that dot should show, a number representing how much green, and a number representing how much blue it should show, red, green, blue, respectively. So for instance, if a dot on your screen, we're using these three numbers, these three values or bytes, 72, 73, 33, in a text message or email, that would be interpreted as I claimed hi. But in Photoshop or in some graphical program, that same pattern would be interpreted as, let's call it a medium amount of red, a medium amount of green, and a little bit of blue. And why medium and little? Turns out that each of these are bytes. The smallest value you can have in a byte, we said, is 0. The largest value you can have in a byte is 255. So I'm just kind of spitballing here. This is like medium, medium, and a low amount of red, green, blue, specifically. Those three colors, like wavelengths of light, are combined in such a way that you would have this dot on the screen, a sort of murky shade of yellow or brown. That is how a computer would store precisely that color. And in fact, we've seen this color. When you type in "faced with tears of joy," generally on your screen it looks like this, typically much smaller. But let's zoom in. Or let's zoom in a little more. What are you starting to see, if you know the term? So pixels, it's getting very pixelated. A pixel is just a dot on the screen. And if you really zoom in on it, you can literally see all of the dots that compose an emoji, in this case on iOS, in the font that Apple's using to represent this particular pattern of zeros and ones. So one of those yellow dots, and there's many of them, all that kind of blend together here, each dot on the screen, I claim, is 3 bytes. How much red, green, blue for this dot? How much red, green, blue for this dot? How much red, green, blue for this dot? And you'll notice, too, that when it gets to be sort of brownish here, the dots really stand out. The 3 values, the 3 bytes, aka 24 bits, are just slightly different. And so underneath the hood, this is why images, photographs that you take, or GIFs that you download get so darn big, potentially, because you have a number representing every dot on the screen. Well, if this, I claim, is indeed how images are typically represented, using pattern of bits that are assigned to some amount of red, green, or blue, how do you get video? What is a video if at the end of the day all we have are zeros and ones? What's a video, perhaps? Yeah. Oh, let's go here. Way in back. Yeah, pixels really changing values over time. And do you want to confirm or deny the hand that went up here? Yeah, or equivalently, a sequence of images that over time are changing on the screen. So both of those are valid interpretations. And just for fun, if you grew up with these sort of picture books, you might remember a little something like this. If we could dim the lights. That's sort of the old school analog way to implement a video, in the sense that that artist wrote out like hundreds of pieces of paper with almost identical images, but where the ink from their pencil or pen was slightly moving. And if you digitize that such that each of those strokes are represented with dots instead, that's really what you're seeing, is a sequence of all of these images flying across the screen. And if we dive into the real world, if you've ever watched a film, a Hollywood movie is typically 24 FPS, frames per second. That really means you're seeing 24 images per second. Or on TV or in soap operas, it's often 30 frames per second. That makes things look a little more smooth. So it's not actual motion picture, if you will. It's sequences of pictures. And your brain and mine are kind of interpolating that, oh, this is smooth movement, even though we're just seeing a lot of pictures really fast. Now, that gets really big. And we'll talk later in the semester how you can compress information so that you're not using way more bits than you actually need to. And there's fancy algorithms that folks have developed. But at the end of the day, that's really all a video might be, is a sequence of images. Conversely, if you want to represent the music that accompanies that or something else, if any of you play an instrument and can read sheet music, how could you digitize this? Like, how could you represent musical notes in a computer? You and I hear them when we play files, but what's really going on underneath the hood? Any musicians? Piano players? Anyone? Yeah. OK, so hertz value, so some frequency. So sound is some frequency, and it's kind of hitting your eardrum, and that's what makes it sound low or high or somewhere in between. So maybe we could assign, just like there's letters A through G here, maybe we could assign specific frequency values, which are just going to be numbers measured in something called hertz, something per second. And maybe we could have a few other numbers for each of these notes, not just the note or the frequency. Maybe we could represent the loudness of it, like how hard or how softly a human might equivalently press it. Maybe a third number, like duration, like how long is their finger on the keyboard. So you could imagine quantizing something like music that in the real world is perfectly continuous as something more discrete by representing each note over time as just some sequence of values. And there's so many different ways to do this. MIDI, if you've heard, MP3s, AAC. I mean, almost all of the file extensions you see on your Mac or PC, if you see them at all, ultimately just mean there's a different form of representation for, in this case, something like sound. So let me just stipulate, there are these and many more ways to represent inputs and outputs. And thankfully, humans have standardized a lot of this. They don't always disagree. And this is why we have different file formats for Apple numbers and Microsoft Excel and Google spreadsheets and sort of stupid incompatibilities like that. But generally speaking, humans have standardized how we represent the inputs and outputs to and from problems. But let's now focus on this black box, so to speak, in the middle, this abstraction. So abstraction is technically a term that you'll see all over the place in computer science and really problem solving that just refers to the simplification of something so that you don't focus on the lower level implementation details. You really just focus on the high level goals or the process itself. Therefore, your car, if you have a license and have driven or have been in a car, so far as you're concerned, is probably an abstraction. Most of us, if you're like me, probably don't really know or care how the engine works and all the parts that are moving. To you, it's just a way of getting from point A to point B. It's an abstraction. But someone, hopefully, the mechanic, does know those lower level implementation details. If you had to understand how a car works every time you want to go to school or to the store, it's probably going to be a pretty slow process. You just want to think and operate at this higher level of abstraction. And we're going to do this all the time when writing code and solving problems. So what then is in this black box, this abstraction at the moment? Well, generally, it's what a computer scientist would call an algorithm. Step-by-step instructions for solving some problem. Now let's consider the implementation details. That is to say, how you might solve certain problems. And let's take a sort of old school example, but in modern form. This icon, if you have an iPhone, is of course for your contacts application. And if you've got a whole bunch of family members or friends or colleagues in your phone book, you have some kind of contacts pictured here. And it's alphabetized typically by first name and last name. And odds are you and I are in the habit, if they're not already a favorite, of like clicking on search and then using autocomplete. And what happens when you start typing autocomplete? Well, if you type in the letter H, you'll see only, presumably, Hagrid, Harry, Hermione, and so forth. If you type in HA, that shows you only Hagrid and Harry, and it all happens super fast. So how is that happening? Well, typically, you could just start at the top and look to the bottom searching for all of the H's or all of the HA's. But for larger data sets, that's going to get slow. For the Googles of the world, that's going to get really slow. And even on our phones, when you have hundreds, thousands of contacts eventually, even that kind of approach, that algorithm step by step might be slow. So how might we go about searching for someone in a phone book like this? Like, say, John Harvard, well, here's an old school incarnation of this. And odds are you might not have had occasion to even physically use this thing nowadays. And in fact, this is a bit of a white lie, because this is the Yellow Pages, which means this is a book of companies, not people. But this is all you can find. And at that, it's even hard to find this. But this is the same thing in analog form, physical form. So if I wanted to search for someone like John Harvard, how could I do that? Well, I could start on page 1. And I could start searching for page 2. Page 3, page 4, page 5. A little hard to do physically, especially since no one's used this phone book in a lot of years. But is this algorithm correct, turning page by page? Very inelegantly. Is this correct? Will I find John Harvard if he's in here? All right, so yes, I mean, this is a little stupidly tedious because if there's like 1,000 pages, he might be a few hundred pages into this, but it's correct. At some point, I will find him, and if he's on the page, I'll be able to call. Why? Because presumably the names are alphabetized in here, and there's no like cheat sheet on the edge, so I have to search for John Harvard from left to right, searching for H if it's alphabetized by last name. Well, what would be marginally better? Well, how about 2 pages at a time? It's hard to do with a 20-year-old phone book where the pages are kind of grown together, but 2, 4, 6, 8, 10, 12. This algorithm, is this correct? All right, so no, why? Yeah, so I'm skipping every other page. So if I don't consider that and I find myself in like the I section or the J section, well, I might accidentally conclude, nope, I haven't found John Harvard yet, just because I skipped him because it was sandwiched between 2 pages. Now, I can fix this, I think. If I do hit the I section, well, let me just double back 1 page, just in case he was in that last page. So it's recoverable, but it's almost twice as fast, minus that hiccup there. But what most of us would do, and what your phones are doing, albeit digitally, is they open up roughly to the middle of the phone book. And they look down and they say, oh, I'm in roughly the M section. So I'm roughly halfway through this 1,000-page phone book. But what do I now know about John Harvard? Where is he? To my left or to my right? All right, so alphabetically, he's presumably to my left. And so here I can both metaphorically and physically tear the problem in half. You don't need to be impressed. It's really easy down the spine that way. But I know that John Harvard is to the left here. But now I can throw, unnecessarily dramatically, half and page 1 out of the way. And what do I now know? I've gone from 1,000 pages to like 500. I can kind of repeat roughly the same algorithm, go to the half of this. And so this time I went back a little too far. I'm in now the E section. So what do I know? Is John Harvard to my left or to my right? To my right. So I can, again, tear the problem in half, throw this half away, and now I'm really flying. I'm doing it verbally slowly, but that went from 1,000 pages to 500 to now 250. And now I can do it again, 125. I do it again, roughly like 67, and keep doing it again and again and again until I get left with, hopefully, just 1 single page, or in this case, an ad for, ironically, a mechanic. OK, so what is the implication for our performance? Well, let's just do this, sort of in the abstract, if you will. If that first algorithm were to be plotted just quickly on a chart without even numbers, here's my x-axis, size of problem on the x-axis. So the bigger the problem, the farther out that way. Time to solve the problem, the higher you go up on the y-axis, the more time you're taking to solve it. How would we draw the running time, the amount of time taken to run that first algorithm? Well, it's going to be a straight line. Why? Because if you add 1 more page next year, because more people move to Cambridge, you're going to add 1 more page turn potentially. So 1 more second, 1 more unit of time. So it's a straight line, and we'll abstract it away as n. If there's n pages in the phone book, the slope of this line is essentially n. The second algorithm, wherein I was doing 2 pages at a time, was twice as fast, but it's still a straight line. And in fact, let me just draw some dotted lines here. If the phone book is this big, with my first algorithm, it might take this many units of time, this many steps, this many page turns. But with that second algorithm, notice that the intersection is with much lower on the yellow line than on the red. So n over 2 means there's half as many pages here, if n is the number of pages. So indeed, that algorithm, the second one, is twice as fast, minus the little hiccup that I have to double back 1 page. But that's not a big deal if I'm still doing things twice as fast. But the third algorithm looks fundamentally different. It looks like this. Logarithms, if you recall from high school or prior. If you don't, that's fine too. It's just a fundamentally different function, a different shape. And notice that the green line is going up and up and up, but a much slower rate of increase, which means crazy things are possible. If 2 towns in Massachusetts, like Cambridge and Allston across the river, merge next year, for instance, in terms of their phone book just got twice as big. For the first algorithm, that's going to take me twice as many steps to go through. The second algorithm, almost twice. It's going to take me 50% more steps to go through, 2 at a time. But the third algorithm that I ended with, tearing things again and again, dividing and conquering, if you will, in half and in half and in half, how many more steps will my third algorithm take if Cambridge and Allston merge into a phone book that's twice as big? Just 1 more step, right? No big deal. You just take a really big bite out of the problem once you decide if John Harvard is to the left or to the right. And so you've made much faster progress. And so this, in essence, is what your computer, your phone, is probably doing underneath the hood when searching for Harry or Hermione or Hagrid or anyone else, because it's that much faster, especially when you have large data. If you don't have that many contacts, it probably doesn't matter if you search from top to bottom or more in the form of this divide and conquer algorithm. But if you're the Googles of the world or you're analyzing large data sets, indeed, this is going to add up quite quickly. So where do we go with this? Well, we're going to introduce next something called pseudocode. How can I translate what I did verbally there sort of intuitively to actual code? Well, this won't be Scratch, this won't be C or Python just yet. It's just going to be an English-like syntax. And this is how many programmers would start solving a problem. They don't start typing out code in C or Python or the like. They use English or whatever their human language is to jot down an outline for their ideas. My first step really was picking up the phone book. My second step was opening to the middle of the phone book. My third step was somewhat different. Look at the page, because why? My fourth step was, if person I'm looking for is on the page, I then do what? Never happened in my example, but I call the person, so I'm done. Else if the person is earlier in the book alphabetically, as John Harvard was in the case of my H, then I should search to the middle of the left of the phone book. And then I should go back to step 3. Step 3 is look at the page, thereby repeating the same process again and again. Step 9, though, might be else if the person is later in the book, then let's go ahead and open to the middle of the right half of the book, and then go back to line 3. Else there's a fourth scenario we should probably consider, lest my search process freeze or crash or give me one of those spinning beach balls with a bug. Yeah, what if John Harvard isn't in the phone book? I'd prefer that my algorithm, my phone, not just reboot or freeze. I should handle that with some kind of catch-all. Else, so to speak, let's just quit the program. So there's well-defined behavior for every possible scenario of the 4. Now let's call out a few of these salient terms. It turns out if I highlight in yellow here, there's a pattern to what I've been doing here. These are all of my English verbs. And in a moment, we're going to start calling those verbs functions. When you program or write code and you want the program or the computer to do something for you, some action or verb, we're going to refer to those actions or verbs as these things called functions, like those here. By contrast, I've just highlighted instead my if, my else if, my else if, and else. This is going to represent what we're going to start calling a conditional, a proverbial fork in the road, where you can either go this way or that way, do this thing or this other thing. And you're going to decide which of those things to do based on what I've now highlighted here, which are going to be called Boolean expressions. Bool referring to a mathematician last name Boole. A Boolean expression is just a question with a yes, no, a true, false, a 1 or a 0 answer, if you will. And it governs whether you do this thing or this thing or this thing or that. The indentation in this case is important. The fact that I've indented line 5 implies, by convention in programming, that I should only do line 5 if the answer to line 4 is a yes or a true. And same for these other indented lines as well. And the last characteristic here is this here. Someone called this out earlier, in fact. These lines 8 and 11 are now highlighted and represent what? What might we call these in code if you've done that? Yeah, so these are loops, some kind of cycles that result in my doing the same thing again and again. But there's a key detail with this algorithm in pseudocode. Even though it's telling me to go back to line 3, why is this algorithm eventually going to stop? Why do I not constantly keep looking for John Harvard forever by nature of these loops telling me to keep going back to line 3? Good. Eventually, he'll be on the page, or to your point earlier, he won't be at all, and we're out of pages. And so we just quit. And that's the key about going to the left half or the right half. It doesn't matter if you do the same thing again and again. You're not going to get stuck in a so-called infinite loop so long as you keep dividing the problem and shrinking it into something smaller, smaller, smaller. Eventually, there's going to be no problem left to solve. So even if you don't think of yourself as a computer person, even if you've never written code, what you'll find in the coming days is that these ideas that we've just kind of harnessed from real life are at your fingertips already. And a lot of the process of learning to code is just going to be a bumpy road, some bumps in the road because you can't quite see the new syntax in a familiar way. But you'll find that the ideas, in fact, are going to be more familiar than you might otherwise think. And so we'll see in a bit, and we'll take a break in a moment to take a breather, that you will see these same ideas in a moment in the context of Scratch, an actual programming language via which we'll drag and drop puzzle pieces to make actual code work. We'll see some variants of these ideas, things called arguments and return values and variables, but we'll ultimately convert it into this somehow. Anyone want to wager what this program will do if fed to your Mac or PC or phone? Here's just a massive pattern of zeros and ones. It will indeed say, rather disappointingly apparently, just hello world. And indeed, baked into all of these zeros and ones are not just the H-E-L-L-O, but also the verbs, the action of printing something to the screen. And there's other stuff too, so that the program knows how to start and how to stop. A lot of stuff that we won't have to worry about that whoever designed the computer or the language did. But at the end of the day, you're never going to be writing these zeros and ones yourselves, though our ancestors once upon a time did in some form. We'll be using a much higher level language like this in C, or better yet, in just a moment, like in Scratch, like this. And indeed, this is why today we focus on and begin with Scratch, this graphical programming language, so we have a way of expressing ourselves with functions, conditionals, loops, and more, but in a way that doesn't have stupid parentheses and curly braces and all of these visual distractions in the way. And we'll translate that thereafter to this lower level language. But for now, that was a lot. That was definitely a fire hose. Let's go ahead and take a 10-minute break. Feel free to get up or stay here, and we'll resume in a bit with some actual code. So this then is Scratch, a graphical programming language from our friends down the road at MIT's Media Lab that indeed some of you might have used in grade school or the like for playing and writing code and the like, but you maybe didn't necessarily think about how some of these primitives ultimately worked. And in fact, everything you've done, if you've used Scratch before, and everything you'll see today is going to apply to all of the weeks to come as we explore these things called functions and loops and conditionals, Boolean expressions, and more. With Scratch, because it's so graphical and animated, can you create animations like this one, interactive art, and software more generally. But you'll do so by dragging and dropping puzzle pieces that only lock together if it makes logical sense to do so. And what you won't have to deal with in this first week of class is curly braces, parentheses, all of the weird symbology that you might recall seeing when we just wanted to say hello world. Now, this particular program, Raining Men, was written by a former CS50 teaching fellow, Andrew Barry, who's actually now the general manager of the Cleveland Browns, the American football team. And so these are just some of the programs that some of your predecessors in the class have created. And you'll see in the remainder of class here a couple of others as well and more in the course's first assignment, namely problem set 0. So how do we get there? Well, first, a quick tour of what it is we're going to do. This, in Scratch, is perhaps the simplest program you can write. And even if you've never seen Scratch or any programming language before, can probably guess that this just says on the screen somehow, hello world. But what you don't have to do is type esoteric commands and weird syntax, those curly braces and parentheses I keep alluding to. You just drag this yellow puzzle piece, you drag this purple puzzle piece, let them magnetically lock together, so to speak, click a button, and boom. With those same building blocks and several others, can you make exactly the sorts of things that Andrew brought to life as well. So here's what we're about to see. At scratch.mit.edu is a cloud-based programming environment on MIT servers. You can also download it offline on your own Mac or PC. And it gives you an interface like this. On the left-hand side of the screen, you'll see a blocks palette. These puzzle pieces, aka blocks, come in different colors which rather categorize them. So pictured here, for instance, in blue, are a whole bunch of motion-related blocks. So Andrew used a whole bunch of those to have the singer and the men moving around on the screen in synchronicity with the song that was playing in the background. Meanwhile, in the middle of this interface is going to be the code area. And this is where Andrew and soon you will drag and drop some of those puzzle pieces and other colors as well and lock them together to get your characters, soon to be invented, to do something on the screen. Indeed, at the bottom right here, will you see ultimately a sprite area, where a sprite is a technical term for like a character in a video game or a programming environment like this. By default, historically, Scratch is the cat, the mascot, if you will, for this programming environment. And so here we see by default just one sprite selected, because on the top right of the screen is the stage for that sprite. And you can click and zoom in to make it full screen. But this is the world in which Scratch, by default, the cat, will live. But you can change Scratch's costume so that it looks like a singer or a man falling from the sky or the like, or anything else, either creating the art yourself or importing some of the things that come with it or elsewhere online. So what is this world that Scratch rather lives in? Well, generally speaking, we won't have to care too much about numbers, because we'll be able to ask questions like interactive ones, like is Scratch the cat or any character otherwise, touching the edge of the screen, touching something else. But Scratch does exist in this two-dimensional coordinate system world. So when the cat or any character is dead center in the middle, that would be xy location 0, 0, if you will. Meanwhile, over here is 240 pixels or dots all the way to the right. So this would be 240, 0, where y is 0 because it's right on that midline. So it's neither up or below. Over here to the left, of course, would be negative 240 and 0. Above the cat would be x equals 0 because it's right on that vertical midline, and 180. And then down here, as you might guess, would be 0, negative 180. Generally speaking, we don't have to care about those precise pixel coordinates, but it's helpful ultimately if you do want the cat to move up, down, left, or right, having some sense of direction according to the x-axis and y-axis as well can help you express your ideas ultimately. So what might some of those ideas be? Well, let's do this. I'm going to go ahead and create on scratch.mit.edu just an empty screen like this one here. And so this is the exact same interface, but now I'm in my browser, full screen, so that I can start writing some code. And let's get that cat to say something actually on the screen. Now, this takes a little bit of practice, but honestly, just by scrolling through these puzzle pieces, can you quickly get a sense of what's possible, not just categorically, but specifically? And I'll jump around because I've done this, of course, before, but I'm going to go to events in yellow first, and I'm going to drag and drop this first block called when green flag clicked. And I've zoomed in there just to make it a little more legible. And notice that the shape of this green flag just so happens to mirror this green flag here at top next to this red stop sign of sorts. And the green flag is going to mean go, and the red stop sign is going to mean stop, to start or stop our program. Next week, you're going to be writing a textual command at your keyboard to do the exact same idea, but for now it's a button. So when green flag clicked, what do I want Scratch to do? Well, how about we have Scratch just initially say something like hello world, which indeed historically is the first program that most any programmer might write. So anything related to what the cat looks like it's doing is actually going to be under looks here in purple. So I'm going to drag over say hello. And you'll notice something curious and different about this purple block. It says, of course, say in purple, but then there's this white oval and some text that by default is hello, because MIT just decided that by default the placeholder will be hello. But anytime you see this white oval, it's an opportunity to provide an input into the function called say. And so here I'm borrowing terminology from before. Problem solving, again, is all about inputs, producing outputs, and in between there is some algorithm. In a moment, we're going to start referring to algorithms quite frequently as functions. Why? Because it's the implementation of some algorithm. So let me override the default with hello, world. I'll zoom out. And now if I go to the top right of the screen and click the green flag, we'll see, hopefully, my very first program in code. Now, it wasn't a huge lift, right? It only was a matter of dragging and dropping puzzle pieces. But what has now happened? Well, it turns out that two things have happened. When I, the human, clicked on that green flag, I triggered what we're going to start calling now an event. An event is generally something graphical or interactive that just happens in a computer program. You and I trigger events on our phones all day long. Whenever you tap or drag or long press or pinch or any of those gestures in vogue nowadays on phones, you are triggering events. And people at Apple and Google and elsewhere have written code that listen for those events and do something when that event happens. That's what I just did. When green flag is clicked, I want something to happen. Namely, I want this purple function, this verb, this action called say, to do something. What do I want it to do? I want it to say what this input is. And I'm going to introduce another vocabulary term. The white ovals here are, yes, inputs very generically. But in a programmer's terminology, they're called arguments, otherwise known as parameters. And that just means an input to a function that modifies its behavior in some way. When I click stop, that's just another event. And that one is just built into Scratch. Scratch knows that when you click the green stop sign, everything should just stop automatically. I don't have to write code to support that feature. So that's all fine and good. Hello world. But if I keep doing stop and start and stop and start, it's going to do the same thing again and again. And it's really not that interesting at the end of the day. Maybe gratifying once, but it'd be nice if this were a little more interactive. So it turns out that we can do that too, but we need a different mental model instead. So in this case here, when we think about this function say in this input hello world, this actually maps pretty cleanly to this model earlier that I propose is problem solving, is computer science, if you will. The input to the current problem is going to be in white here, hello world. The algorithm is the say algorithm. Now, I don't know how MIT got it to print out the little pretty speech bubble on the screen, but they wrote those underlying low-level implementation details, and they gave me and you a purple function called say that just does that for you. You and I don't have to reinvent that wheel. The output of say is another technical term now called a side effect. A side effect is usually something visual that happens, like as a side effect of you calling a function. And so the side effect here is that the cat has this speech bubble magically appear, inside of which is hello world. So we have an input, we have an output, we have an algorithm, but now we're talking about these ideas in the context of programming. So now the input is an argument. The algorithm is a function, and the output in this case is a side effect. Terminology that you'll just hear more and more, and it'll eventually sink in. But not to worry if the terminology doesn't come naturally early on. So what more might I do with this? Well, let me go back to Scratch here and make this maybe perhaps more interactive and actually get the cat to say something a little more dynamically. So instead of hello world, why don't I get it to say hello to me or to you or anyone else? So let me do this. Let me go under, say, let me get rid of this first, and you'll notice this neat trick. As soon as you start dragging on a block, if it gets close to it, it kind of goes gray, and it can be magnetically snapped together. You don't have to do it very precisely. Conversely, if I want to get rid of a puzzle piece, I can just drag it anywhere on the left, let go, and that deletes it. Or you can right-click or control-click, and a little menu will let you delete it as well. Well, let me do this instead. Under sensing, which I know is there because I've done this before, are a whole bunch of things related to sensing, whereby the cat can kind of feel out its world in some sense. It can do things like ask this question. Am I touching the mouse pointer, like the user's cursor? Am I touching a specific color that you can override to be anything you want? Is the distance to the mouse pointer some specific value? But for now, I'm going to focus on this blue puzzle piece that asks a question, which itself is this white oval that I can apparently change, and then it's going to wait for a response. But this puzzle piece is a little different. It's a little special. It comes with a freebie. It comes with what we're going to call technically a return value. So some functions don't just do something on the screen. They hand you back, so to speak, a value that you can do anything that you want with. Nothing happens immediately unless you do something with that so-called return value. So let me go ahead and drag this thing over here. Ask what's your name. And I'll use the default question. That seems a reasonable place to start. I'm not going to override that default. And now let me go ahead and zoom out. Let me go back to looks. Let me go to say, and let me just form the English sentence I want. So let me zoom in here and type in hello, maybe comma, space. I could do David, but that's obviously not right because I'm asking for a name and then I'm like in advance hard coding my name. That's not what I want. I just want hello, comma. And now let me zoom out and grab one more say block. Let me maybe say here. OK, I don't want to say hello, hello. I don't want to just type in my own name because, again, then what's the point of asking the user for their name? But notice this. If I go back to the sensing block, this is where that oval that's blue called answer is useful. This will be the so-called return value of that function. So I'm just going to go ahead and do this and drag and drop. Even though it's not the right size, it is the right shape. And so Scratch will be smart about it and grow to fill that puzzle piece for you. Let me zoom out now. And now let me click the green flag. You'll see that Scratch is indeed prompting me with the speech bubble. What's your name? Notice the little text box below the cat is asking what's your name. So I'm going to type in DAVID and hit enter. Or I can click the blue check. Enter. OK, it's a little weird. I wanted him to say hello, not just my name. So let me stop. Let me start it again. All right, hello, what's your name? DAVID. Enter. Huh, kind of rude. Why is there this bug? Like I wanted to say hello, David, not just David. And yet twice it has failed to do so. Yeah, the computer is processing my directions, my actions really quickly. And so it actually is doing it. It's just you and I in the room are just way too slow to notice that it said, hello, David. It just seems to have just said David. So, all right, how can I fix this? Well, here's where you start to poke around and think about how you might solve this. Let me go back under looks. Maybe there's a smarter way to do this. Maybe I could do this. How about instead of just say hello, there's apparently another puzzle piece where I can time it. So I can maybe slow things down a little bit. So let me do this. Let me throw away all of this. Let me drag a say hello for 2 seconds. Let me drag another say hello for 2 seconds. Let me change the first one to indeed hello, comma. And then let me go back to sensing. Let me grab that same answer, because I threw it away a second ago, and I'll just change it. I don't even have to delete hello. I can just overwrite it like this. So now I think we'll kind of pump the brakes and see things more slowly. Let me stop. Let me start. DAVID, enter. Hello, David. OK, so it's better. Like, it seems to be working. I think your hypothesis was right. It just looks kind of stupid, right? Like the fact that it's saying, hello, David, like we can do better. And like literally every piece of software on your phone or Mac or PC is better than that. It adds words together in the user interfaces you and I are familiar with. So let's go a little more fishing here. Let me throw away these. Let me go back to looks and just get the simpler say. I want this to say hello, comma, name, where name comes from that answer return value. So how can I do this? Well, let me go under operations, which we haven't been before. There's a lot of stuff in here. Some of it's mathematically related, adding, subtracting, and so forth. You can generate random numbers, which might be useful. And if I keep scrolling down, there's this join apple and banana. But that's just placeholder text. You can join one piece of text with another piece of text. By default, apple and banana, but let's change it to hello and my name. So this too, wrong size but right shape. So let me let it snap into place. Let me go ahead now and do hello, comma. And now I think I just want to go grab that answer return value. Let me drag the same oval as before, clobber, that is overwrite banana. So now I'm kind of composing functions. The output of one function, join, is going to be the input of another function, say. So let's see what happens now that they're kind of stacked on top of each other or nested, so to speak. Click the green arrow, a green flag, DAVID, enter. Hello, David. All right, that was pretty fast. Let's just do it once more. Stop, start. Here we go, DAVID, enter. OK. Right, it's not the most exciting program in the world, but it's more correct. It's better designed just because that's what you would kind of expect the software to do and not be some kind of lame user interface that's just inserting random delays to just make it kind of work. Like that's a workaround, a hack, if you will. But there's some cool things you can do with Scratch. And we won't really go down the rabbit hole of all of the fun and family-friendly features that it has. But there is one that's kind of cool here. Let me go into the extensions button at the bottom left of my screen. And this one's kind of cool. Let me go to text to speech. And you'll notice that this one requires internet because it's cloud-based. But this just gave me some new puzzle pieces in a new category, text-to-speech. And these green ones do exactly what they say. So let me do this. Let me zoom out again. Let me keep the join block. And I'm just going to temporarily toss it over here. It's not going to delete itself because I didn't drag it over to the other side. But I'm going to get rid of the say block in purple. I'm going to do the speak block here in green and let it snap into place. And then I'm going to drag and drop this onto the input to speak. And now, perhaps a little more adorably, let's try this. Green flag. What's your name? DAVID. Enter. And?
Hello, David.
OK. It's a little robotic, but at least now it has synthesized speech. And I've kind of got my own like Siri or Google Assistant or Alexa thing going on here now, where it's now recognized whatever text it is and it's played it. Well, let's make this an actual cat that doesn't talk in that weird human voice. Let me go ahead and get rid of most of this stuff. And let's get the cat to actually meow like a cat tends to. And let me go under the sounds block. Now, MIT gives you a few sounds for free because it's designed around a cat by default. And I'm going to go ahead and grab this one. Play sound meow until done. And now, and we heard a teaser for this earlier in the crowd. It's a little piercing, admittedly. We can lower the volume a little bit there. But notice if I want the cat to meow a second time, I'll just click it again. OK, and over there too, I hear. OK. All right, so it's kind of cute now, right? So it's just meow. OK, yes, echo, echo. So it's meowing now every time I hit the green flag. Now that's great, but even a kid is probably going to would prefer that it just meow, perhaps, like again and again without having to keep hitting the button. So well, how might we do this? All right, well, if I want it to meow multiple times, why don't I just grab it another time and another time? Alternatively, you can right-click or control-click a puzzle piece and just duplicate it from a little menu that drops down. So here we go, 3 meows. All right, that's not really a happy cat, it sounds. Maybe hungry. So can we slow that down? Well, maybe. In fact, if I poke around, let me go under control. Looks like there's a wait block. Wait 1 second by default. And notice, Scratch will be pretty accommodating. If you just hover in between blocks, it will grow to fill that too. So I could change it to 1 or 2 or anything seconds. I'll just leave it at the default for now, 1. And now I'll go ahead and do this. OK, so cuter and less hungry and just more friendly. But this isn't the best design. It is correct. And let's use that as a term of art. Correct means the code does what you want it to do. I want the cat to meow 3 times, slowly, and it did. So I'd wager this is correct. But it's not the best design. And this is where things get more subjective, right? Like you could write accurate sentences in an essay for an English class, but otherwise it's just completely a mess. Like your arguments here and there, and you don't say anything wrong, but you don't say it well. In the context of code, we can do better than this. And copy paste or repeating yourself again and again tends to be bad practice. Why? Suppose that you want to change the wait to 2 seconds instead of 1. It's admittedly not a big deal. Fine, I click there, I change it to 2. I click there, I change it to 2. But what if you meow 5 times, 10 times? Now I have to change the wait like in 5, 10 different places? Like that's just stupid. It's taking unnecessary human time. And you're going to screw up eventually. Especially if your program's getting longer, you're going to miss one of the inputs. You're going to leave the number wrong, and that's a bug. So just based on what you've seen already, or if you've programmed before, which a few of you have, what's the term of art here that will solve this? How could we design this better? I heard it here. Yeah, so a loop, some kind of cycle that says do that again, do that again. Not infinitely many times necessarily, but some finite number. Well, you can perhaps see a spoiler on the screen. Under the same orange control category is a repeat block. And by default, it's proposing 10, but we can change that. So let me do this. I'm going to throw away most of this copy-paste as redundant. I'm going to detach this temporarily just to make room for something else. And I'm going to drag a repeat block over here and let that snap into place. And I'm going to change it for now just to be 3 for consistency. And this is the correct shape, even though it's too small, but Scratch will accommodate that for us. And now, same output, but arguably better designed. Why? Because if I want to change the number of meows, I change it in one place. No copy-paste messiness. If I want to change the weighting, one place. I don't have to change it in multiple places and not screw up. So let me hit the green flag. All right, so nice. Now, it would have been nice if MIT had just given us a meow block that just automates all of this for us. Let me wager they gave us the low-level implementation details. They gave us the play sound meow. But I had to implement like a decent number of blocks just to get a cat to meow again and again. I feel like we should have gotten that for free from MIT. Well, they don't have to be the only ones that invent blocks for us to use. You can write your own functions, your own verbs or actions. So how can we do this? Let's make our own puzzle piece called meow that uses this code but creates it in such a way that it's reusable elsewhere. So let me do this. Under my blocks in pink here, I'm going to go ahead and click literally make a block. Now, here's an interface via which I can give the block a name. MEOW will be the name of this block. And I'm just going to go ahead and quickly click OK. That just gives me a very generic pink puzzle piece that starts with the word define, because Scratch is asking me to define, that is, implement or create this new puzzle piece for me. Well, what does it mean to meow? I'm going to claim that it means to do these 2 steps, to play the sound meow and then just wait for 1 second. But what's powerful about this idea is look at this up top. Now that I've made a block, it exists in Scratch. MIT didn't need to create this for me. I created it for myself. And even you, if we end up sharing code. So I can now drag meow up in here. And what's nice about meow is that itself is, yes, a function, but it's also an abstraction. Like never again do I, or even you, need to worry or care about what it means to meow or implement it. I can sort of drag it out of the way. I didn't delete it. Drag it out of the way, out of sight, out of mind. Why? Because my code is now even better designed in some sense because it's more readable. What is it doing? When the green flag is clicked, repeat 3 times, meow. It just says what it means. And so it's a lot easier to read it, and it's a lot easier to think about it, especially if you're using meow in other projects too. Now, let me go ahead and hit click play. Same thing. So it's not really fundamentally any different. But I can make this custom puzzle piece, this own function of mine, meow, even more powerful. Let me kind of rewind a bit and go to my meow puzzle piece. And I am going to control click or right click on my pink puzzle piece. And I'm going to edit it. So I kind of regret making meow so simple. Wouldn't it be nice if meow took an input, aka an argument, that tells meow how many times to meow? Then I can get rid of that loop and just tell meow how many meows I actually want. So I'm going to click on another button here called literally add an input. And it's going to have placeholder here. So I'm just going to put a placeholder there. I keep using n for number, which is a go-to in computer scientist terms. And I'm going to add some descriptive text just so that it's a little more self-explanatory. I'm just going to say meow n times. But there's only one oval. times is just going to be explanatory text. And now notice what has happened. Now my puzzle piece takes an input, aka an argument, that will tell that function to meow some number of times. But it's not just going to work magically. I need to implement that lower level detail. So let me zoom out. I have to remind myself what this function was. So I'm going to drag it higher up just so they're on the screen at the same time. I'm going to go ahead now and temporarily move this over here. I'm going to temporarily detach this over here. Why? Because what I think I want to do is move my loop into the function itself, move the play and the wait into the loop, but I don't want to hard code 3. Notice that n here is its own oval. I can drag a copy of n and just let it go there. So now I have a new version of meow that takes an argument, n, that tells meow how many times to meow. And now, let me again drag this out of sight, out of mind, because who cares how I implemented it? Once it's implemented, it's sort of done. Now my program is even better designed in some sense. Why? Because now it really just says what it means. There's no loop, there's no repeat, no like implementation details. When green flag clicked, meow 3 times. And so functions indeed let you implement algorithms, like they're just code that do something for you, but they're also themselves abstractions. Why? Because once a function exists, it has a name, and you can think about it in that term, and you can use it by its name. You don't have to care or remember how the function itself was built, whether it's by you or even MIT. So again, here, I'll click the green flag. It's the same thing. So still correct, but better and better designed. And so anytime here and out with Scratch or soon C and eventually Python, when you find yourself doing anything resembling copy-paste or again and again grabbing the same code, probably an opportunity to say, wait a minute, let me refactor this, so to speak. That is, rip out the code that seems to be repeated again and again and put it in its own function so you can give it a descriptive name and use and reuse it. Any questions just yet on now saying or these loops or these functions that we're using? Yeah. How did I make it so it meows 3 times? So I originally only had a puzzle piece called meow, and I decided to improve it. So I held down Control, and I right-clicked or Control-clicked on the pink puzzle piece at top left, and I clicked Edit. And that brought back the original interface that lets me add some arguments to the puzzle piece itself. And I clicked Add an Input on the left here, and then I clicked on Add a Label over here. So that just lets you customize it even further. All right, so we've done this. Let's add one of those other primitives too, to do something optionally. So how about we make the cat meow only if it's being petted by a human, as by moving the mouse to hover over the cat like a human would pet a cat. Well, let me go ahead and throw away the meowing for now. And let me simplify it by just using a sound. I'm going to go ahead and do this. I'm going to go ahead and have a control block that says if, because I want to implement the idea of if the cursor is touching the cat, then play sound meow. Or I could use my same pink puzzle piece, but I'm going to throw that away and focus only now on the sounds. And I'm going to do this. If touching mouse pointer, so I need to sense something about the world. And we saw this earlier. So if touching mouse pointer. So notice this shape here, way too big, but it is the right shape. So if I hover just right, it'll snap into place. And this now in blue is my Boolean expression, a yes/no question, true, false. If is a conditional. And what do I want to do? Well, if the cat is touching the mouse pointer, I want to go ahead and play sound meow until done. So let's do this. I'm going to hit green flag, click. Now nothing's happened yet because it's a conditional, right? It's only supposed to do something if I'm touching the cat. Let me move the cursor over to the cat and wait for it. Another bug. Why is the cat not meowing? Even though I very explicitly said, if touching mouse pointer, meow. Yeah, in the middle. Yeah, this is, again, my computer's just so darn fast. Like yours, I click the green flag. It asked the question, am I touching the mouse pointer? Well, no, because my cursor was up there, not touching the cat. It's too late. The cat's out of the bag. And so we have to instead solve this by some other means. How can we fix this? How do we fix that sort of race? Yeah. Yeah, so why don't we just keep asking the question until I eventually am or am not actually petting the cat? So let me detach this temporarily. Let me go under control. Let me go under, instead of repeat some finite number of times, let's just do it forever. So sometimes loops that do work forever are a good thing. Like the clock on your phone, that's in a loop forever because you want it to always tell time and not stop at the end of the day. So sometimes you do want code to loop forever, as in this case. So let me go ahead and drag and drop it there. Let me again click the green flag. Nothing's happening yet, but notice the program's still running. And so if I move my cursor, move my cursor, move my cursor, and oh, OK, so maybe we could add some waiting, but the cat does not want to be pet in this case. But it's indeed conditional. So there we have an incarnation in Scratch of doing something conditionally. Now, we can make this really cool, really fast, if you will. Let me stop this version. Let me go ahead and do this. Let me go ahead and throw all of this away. Let me go into my little extensions bucket over here. And let me do video sensing, since most laptops or phones these days have cameras. And there, indeed, I am with Sanders behind me. And let me do this. When video motion, and let me get out of the way. When video motion is greater than some value, so 10 is the default. This is just a number that measures how much motion there is or isn't. So small number is like no motion. Big number is lots of motion. So I'm going to choose 50 somewhat arbitrarily here. So 50. This is not normal to program off to the side. But I'm now going to say this. When video motion is 50, go ahead and play sound meow like this. So the cat is still in that world. I'm going to stop the program and rerun it. So here we go, green flag. And now, here come, all right, this is a little creepy the way I'm petting the cat, but, and, OK. There we go. OK, so 50 was too big of a number. I have to pet the cat faster. Whereas this, if, I don't know. Yeah, so, OK. So you can make things even more interactive in this way by just assembling different puzzle pieces. And honestly, there are so many different puzzle pieces in here. We're not going to even scratch the surface of a lot of them. But they generally just do what they say. And indeed, when you see on the screen here, this palette of puzzle pieces, really a lot of programming, especially early on when learning a language, is just trying different things and try and fail. And if it doesn't work quite, doesn't work quite right, look for an alternative solution there too, as even I just had to do a moment ago. Well, let's go ahead and use actually, how about another example of something a predecessor of yours made? Let me go ahead and grab a program I opened in advance here called Whack-A-Mole. Might we get a brave volunteer to come up who is willing to whack-a-mole with their head virtually? Maybe. OK, let's see. How about in way back? You want to come on down? All right, come on down. And in just a moment, sure, round of applause for our volunteer. All right. So here we have, come on down. Okay. What's your name? Oh, actually, say it into the microphone.
Hi, I'm Josh.
OK, nice. Welcome, Josh. Come on over. All right. So same idea here. I'll take the mic back. You'll have to stand in front of the camera. In just a moment, you're going to have to position your head in a box that your classmate from yesteryear created. And we'll start with beginner.
Okay.
So line your head up in the box in a moment.
All right, all right.
Nice. 12 seconds. Five seconds. Notice the score is up to 18 already. Pretty good. All right. A round of applause for Josh, if we could. So notice how using some fairly simple primitives, things do get interesting pretty fast. And how was that implemented? Well, there were probably at least 4 sprites. So you're not confined to just one cat. You can create more and more sprites, change what they look like so they actually look like a mole in this case. There's probably some conditionals in there, some loops for 30 seconds. That's checking if Josh's head's movement is exceeding some value over this way or over this way, then increment something called a variable. We'll see those too. Just like in algebra, you might have x and y and z storing values like numbers. So can computer programs have variables called x or y or z, or more descriptively called score, as in this case at top right, or another variable called countdown, typically 1 word in code, but in this case 2 words, that just store some value. So there's probably some math going on in there, whereby the author of this program just is incrementing, that is adding 1 and 1 every time it detected that a mole had been whacked, in this case with movement. So back in the day, I myself actually implemented my very first program in Scratch when I was a graduate student, actually, at MIT, cross-registered at MIT, taking a class from MIT's Media Lab, specifically the Lifelong Kindergarten group, which is the group that created Scratch itself. And the program I wrote all those years ago, and still rather cling to, is a little something here called Oscar Time that I thought I'd play just a quick excerpt of myself here. So in this case, consider as the music starts playing, how this program, which is much more sophisticated certainly than the earliest say hello examples we just did, might also be implemented. Let me go ahead now and click the green flag.
So some trash is moving, presumably in some kind of loop from the top. If I'm touching the mouse cursor, it follows me. If I hover over the trash can, it responds. If I let go, in some kind of loop, Oscar pops out, creates a variable with the current score, and it happens again. Pretty easy at first, but I don't need to keep playing this up on stage in front of everyone. So my score is already now up to some 6 or so. But in a moment, too, you'll see that it's going to escalate. So I'm taking into account some time, apparently. So now, more and more sprites are suddenly appearing. And notice that each time they're appearing from a different part of the screen. That's an illusion, perhaps, to that. Pick a random number between x and y. So you can actually pick some range of values to have the game constantly changing. And indeed, I'm going to go ahead and click stop, since I spent like
8 hours plus years ago making this, and I can never listen to the song again. Not that I should be anyway at this point in my life, but this song is synchronized then with a lot of the actions that's happening, and ultimately there's just a lot of building blocks. But I didn't sit down and implement Oscar Time, as I called it, all at once. I really did take baby steps, so to speak, and I figured out, well, how could I decompose this vision I had at the time to create this game ultimately, and how do I bite off maybe the easiest parts first? And honestly, the first thing I did was I found this image, and I just like dragged and dropped it into Scratch. So, okay, done. Like lamppost is installed. It doesn't do anything. It's not interactive, but I at least set the stage, so to speak, for the program. Then what else might I have done? Well, let me do this. Let me go ahead and open up in another editor here a early incarnation of Oscar Time by doing this. Let me go into Oscar Time here. Let me full screen this. And here you have, let me hide the trash for just a moment, is what I might call the second version of my program, wherein at the top right of the stage here, I had the lamppost, which I just dragged and dropped and got going, but then I added an actual sprite. And it has to be a sprite if you wanted to do things interactively. The lamppost, not a sprite. It's just an image, a costume, if you will, for the whole stage itself, a backdrop. But this thing is indeed a sprite because it needs to respond to code and events like dragging and dropping. So what might I have done early on with that code? Well, maybe the first version would have been something like this, whereby my very first version of Oscar Time might have said something like, oh, this. How about let me control the program as before, or rather events. When the green flag is clicked, what do I want to do? Well, I want to go ahead and forever do something like this, forever. So I want the lid to open up if I touch it. So if the cursor gets near the lid, I want the lid to open up. And then if I move away, I want it to close. So how can I do that? I want an if, but I just don't want one question. I really want two, a fork in the road that goes left or right, so to speak. And let me grab this puzzle piece here as I did long ago. So notice it grows to fill. what's the question I want to ask? Well, under sensing, I'm going to go ahead here and say if this trash can is touching the mouse pointer, what do I want to do? Well, I want to change what the trash can looks like. And this part I did in advance of class. If you go up here to costumes, this is where all the graphical stuff happens. And you'll see that I imported a whole bunch of different costumes that effectively, much like a video, when you play them quickly, creates the illusion of movement, some animation. But it's really just dot, 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 different images showing on the screen. Well, some of these costumes are called like Oscar 1, Oscar 2. Oscar 1 is closed. Oscar 2 is open. So let's just deal with those first. So if I'm touching the mouse pointer, let me go under, how about looks? And we didn't use this before, but there's this block. Switch costume to something else. I'm going to drag and drop this inside of the if, and notice it's a little bit indented. I'm going to change it not to Oscar 8, but Oscar 2. Otherwise, if not touching the mouse pointer, this is the other direction in the fork in the road, let's go ahead and switch the costume back to what I described as Oscar 1. So let me run this program, and not much of interest is happening yet, but notice if I move the cursor up, down. But how is that working? It's just changing the costume that's being overlaid on the sprite. So it looks like interactivity, but you're really just changing the aesthetics. And we humans are just kind of, assuming, oh, it's opening up. Well, no, it's just changing a costume. So here's the difference. The high-level abstraction, trash can opening, the lower-level implementation detail, costume changing, creating that illusion. And if I wanted to look prettier, I could just have many other costumes and go boom, 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 boom to create more frames per second, if you will. So I need to do one other thing. Maybe if I accidentally leave the trash can open, let me make one change here. Let me make sure that the very first thing I do when the green flag is clicked is always start with the trash can closed, because otherwise you might accidentally leave it open. So this gets me into some default state. So now it's always closed until I manually hover over it instead. Well, what might I have done next? Well, if I wanted to introduce something like the trash, I need a second sprite. And here in advance, I grabbed the image already. Let me pretend that this never happened. Let me drag this away here. And now I have nothing in my code area for this piece of trash. But it is a second sprite. And all I did was I clicked on the little cat plus icon here, created a second sprite. I named it trash. I added a costume for it, sort of the aesthetic stuff I did in advance. But here I'll do now the code. How do I want to do this? Well, how about when the green flag is clicked for the trash can, I want the trash can in parallel to do, or I want the trash, the piece of trash, to do its own thing. So what I want it to do is maybe, let's do motion, how about? And let's go to a specific coordinate. Now, there's a lot of options here. There's turning, go to a random position, go to x, comma, y, glide more elegantly. There's a lot of different ways to implement movement. I just wanted to go to a very specific location first. So I'm just going to go to x, comma, y first. And I'm going to say x, how about will be, let's not hard code this. Let's just have it be, well, let's do it at 0 initially, and then 240. So whoops, let's do 0, comma 240 so that this piece of trash always starts at the top middle of the screen. If you think back to that coordinate system, 0, 0 is in the middle, 240 is straight above it. All right, now after I do that, what do I want to do? Well, how about I control this thing by forever falling? Now, how do I make the trash move? We haven't seen this puzzle piece yet, but under motion, the very first thing is called move some number of steps. By default, it's 10, but we'll do it more simply. Let me go ahead and move. Move is going to move it in whatever direction it's facing. I only want it to move down. So here, even I'm getting confused as to how many different ways there are to do things. What I think I want to do is this. Let me only change my y-axis as follows. So here's another puzzle piece called change y. So again, y is the vertical. So let me just change y by 1 pixel downward at a time. So -1, 1 pixel at a time. So it's kind of slow. And I think that's it. Let me hit stop. Notice that my trash can is still going to be interactive. I haven't changed or deleted that code. I've just added now code for my trash piece of trash. If I click the green flag, notice that after I enable it, let me start that again. I had it hidden before class, but let me enable it now. Green flag, notice it starts dead center at x equals 0, y equals 240, and it's dropping 1 pixel at a time. If that seems a little boring, we can change it to -10 pixels at a time, and boom, it's done. So that's how you might change the speed of a program. But I'm going to leave it more simply as -1. And honestly, it would be nice if it doesn't always start from the top. Otherwise, this game is not going to be very interactive. I'm literally going to be grabbing the trash from the same place every time. So why don't I instead stop this? Let me go under operators, and let's pick a random number. So let me change the hard-coded, the manually inputted 0, and let's make x be somewhere between 0, so in the middle, and all the way over to, what was it, I got my numbers wrong, 240, and my y will be 180. Sorry, I got my x and my y confused. So let me play this again. And now we have a game that's more like games you might have played growing up, or even now, like there's some randomness to it. So the CPU, so to speak, is doing something more interesting. Let me run it again. Now it's a little to the left. Let me run it again. Now it's a little more to the left. Again, now it's back to the right. So randomness just makes games more interesting. And this is why when you play any video game, if different things are happening, there's probably just some randomness. And it's quantized as just a simple number. Now I think I just need one final flourish here, if I may. Let me go ahead and add this. How about events, or rather, yes, events. When green flag is clicked, I can do multiple things within the same sprite. They don't all have to be attached to the same one. Let me go ahead and forever go ahead and do something else. How about whenever the trash is, how about touching the trash can? So forever, if, let's see, I need a sensing block. So how about is touching, not the mouse pointer this time, but touching Oscar himself there. Now let's see what happens. All right, so let's go ahead and click the green flag. Now I go down over here and let go. OK, I kind of want it to go into the trash can. How do I make it go into the trash can? How can we take this high-level idea, put trash into the trash can, and make it seem to disappear? Logically, what could we do? Yeah. OK, so when it touches it, let's have it disappear. So I could hide it. Or honestly, if the game's going to be ongoing like it was, letting me drop more and more trash, let me just have it go ahead and pick a new random location. So let me do this. Let me go ahead and copy this puzzle piece up here and duplicate. And I don't want the whole thing. Sorry. Let me get rid of this. Let me just do this. Let me go back to some random location at the top. So now notice what happens. If I click and drag on it, here it goes, and I let go, it looks like it's going into the trash can because it snaps back up to some random location. Now, the only thing I'm not doing really is keeping track of any kind of score. And it turns out, if I full screen this, it's not going to be draggable by default. So just as a corner case, so to speak, something that you might trip over otherwise, let me go ahead and under, let's see, sensing, it turns out I also need this for the piece of trash. There's this way of setting in Scratch a sprite to be draggable or not draggable. I need to explicitly make it draggable so that when I do full screen this thing now, it still remains draggable. And someone like myself can play it again and again. Well, how about we supplement this with one final flourish? Why don't we keep track now of the user's score? So how about when the user actually drags the piece of trash to the trash can. Let me go under variables here, where in advance I've already made myself a variable called score. I could have called it x or y or z or abc, but that's not very descriptive. In programming, you typically give things a more descriptive English or some other language name. So I called this one score. So how do I want to do this in my score? Well, let me go ahead and initially set this game's score to 0 at the very top of one of these scripts, or one of these programs up here. And then any time my cursor, my piece of trash is touching Oscar, let's not just jump to the top. Let's change the score by 1 up here. So now notice, if touching Oscar, change the score, that is, add 1 to the score, and then pick a new random location. And now, green flag, let's do this slowly. Here it goes. It's the trash can opens. I let go. And now notice at the top left of my program, notice the score is now 2. Notice the score, if I do this again, is about to become 3. And so here we have building blocks, literally, of making this program better and better and better. And so indeed, that's how you generally approach solving any large program, any problem with code, be it in Scratch or C or Python or some other. You take this vision you might have, or some vision you've been assigned in a homework assignment, and try to break it down into these constituent parts. And just pluck off the easy ones first. Put the lamppost there first and at least feel like you're making some progress. Then pluck off something like the trash can and just make it do a little thing. And it doesn't have to be in some same order here. I could have done this in a million different ways. But figure out what the small pieces are that ultimately, like a few of the problems we've solved today, assemble into a greater solution there too. So that you have now a mental model for these types of blocks and others, let's return for a moment to this. we saw a moment ago that when I started saying, hello, David, and nesting those puzzle pieces, we had a whole different paradigm altogether. My input for that second version of hello world was to now pass in, for instance, what's your name, into my function called ask. That gave me not a side effect, but what I called, again, a return value called answer by default in Scratch. And now notice and recall, when I had that same output become the input to my next block, it looked a little something like this, say. So how does this type of block and this nesting, this stacking of blocks fit into the same mental model? Well, same idea. My input for that part of the story is now taking in not one input, but two arguments, hello and the answer from before. The function in this case is that new block called join. The output thereof is hello, David, which itself became, if we sort of animate this, the input to my final function, which indeed was still say. And this is only to say, no pun intended, that almost everything that you do with these puzzle pieces, be it in the context of Oscar time or the mole whacking or even just something simple like hello world, will ultimately fit into that relatively simple mental model there. Now, I thought we'd end by taking a look at just a couple of final examples, these ones too made by some of your predecessors. And for this, I thought we would not write code together, but read it instead. And so allow me to open up one other example here that will show us a few different versions of a program that a predecessor made. Give me just a moment here, and we'll see how we might build up to something even more interactive. And in just a moment, we'll see something they called Ivy's hardest game, focused here on these particular mechanics. So here is version 0, so to speak, of this program, wherein the goal was to create a game where you have to get out of some kind of maze. And you have to get out, in this case, the Harvard crest from this maze. Let me go ahead and just hit play on this green flag so you can see what the first building block for this program might have been. Notice that my hand here is actually on the arrow keys of my keyboard. And it seems that by moving up, down, left, or right, this little crest on the screen responds in exactly that way. Now let's hypothesize for just a moment, even though we've not done anything quite like this before, how might this code be implemented? How do you get a sprite, be it a cat or a crest, to respond to keys on a keyboard? Might you think intuitively? Yeah. Yeah, there could be something sensing what key you're pressing on. And if you do it again in a forever loop, you'll just constantly be listening for keystrokes. And this is how every piece of software nowadays works. It's constantly waiting for your phone to be tapped or something to be typed on the screen. So let me go ahead and look inside of this existing program here. And there's more going on, but we'll take a quick glance. What's actually going on? Well, up here at top left, notice we just have go to x equals 0 and y equals 0. That means put the Harvard crest dead center in the middle of the stage. Then we have forever two functions that we made in advance as custom functions. Listen for keyboard, feel for walls. So it's doing two things at once. It's forever listening for the keyboard, up, down, left, right, and feeling for the walls in the sense that if I get too far to the left, I don't want it to keep moving past that black wall. And if it moves too far to the right, I don't want it to blow through that wall either. So it's going to do two things constantly, listening for keyboard and feeling for walls, so to speak. And how are those implemented? Well, this one's a bit long, but on the left here is listen for keyboard. So this pink puzzle piece, listen for keyboard, first checks if the key up arrow is pressed, question mark, Boolean expression in a conditional, change y by 1. That means move it up 1. Else if the key down arrow is pressed, then change y by -1. And similar for left arrow, similar for right arrow. And even though there's not a loop in this pink function, there is where I'm using it. So it's constantly being asked again and again. How about feeling for walls? Well, over here to the right, it's a little cut off, but here you have if touching left wall, change x by 1. So if you hit the wall, it's too late. You're kind of blowing through it already. So I want to move it whack 1 pixel so it's no longer touching that wall. Similarly, if it's touching the right wall, I want to back it up 1 pixel so it's no longer touching that wall. So it's kind of like bouncing off ever so slightly so that it doesn't slip through that actual wall. And what are those walls? Well, notice down here, it's just a simple sprite with a black line that I've oriented vertically instead of horizontally. And that's just so that I can ask questions of these other two sprites. Now, that gives me that form of interactivity. What more can I now do? Well, what if we make things a little more interactive here? Let me go ahead and see inside version 1, our second. And let me propose what's going to happen here. Well, how might we add a little something like Yale into the mix? Well, what's Yale going to do when I hit the green flag now, based on this code? Any hunches? Here is the code for my Yale sprite. Yeah, it's going to be an adversary by blocking my path, theoretically, if I keep writing more code. So why? It, too, goes to the middle of the screen. It points in direction 90 degrees. So similarly, there's a whole degree system as well. And it forever asks this: if touching the left wall, or, notice the green block, touching the right wall, then just turn around 180 degrees. And indeed, if you think this through logically, that just means you're bouncing this way and this way by just flipping yourself around 180 degrees for just this Yale sprite. So if I go ahead and zoom in on this and click the green flag, I can still move up and down, but Yale is just kind of doing this all day long, back and forth forever. Nothing bad happens if I try to go through it, but we could add that, certainly, to the mix. In fact, let's add one final feature before we play this particular game. And let me go ahead and open up the final version of these building blocks that adds MIT to the mix. So here's MIT. Someone want to explain what this code does? And this is what we're doing. This itself is a skill. Reading someone else's code and understanding it is half of the part of programming besides writing. Yeah, it's chasing down the Harvard logo outline. So this is apparently the name of the costume that this student made, Harvard logo outline. And apparently it goes to a random position first, but then it forever points to Harvard. So no matter where I'm moving it, up, down, left, or right, MIT is being a little more strategic than Yale, bouncing back and forth like this. So let's go ahead and play this one in full screen. And here we have a green flag. So if I move up, MIT, rather strategically, is following me no matter where I go. All right, so still nothing bad happens, but and now it's struggling, right? It's going up, down, up, down. It's trying to follow me even though I'm not moving. So we need some final flourishes. And so I think for this, we need perhaps one final volunteer. After this, cake awaits for everyone outside, as is an end of first lecture CS50 tradition. Would you like to come up and be our volunteer? All right, and so this will be the actual version written by one of your predecessors that I'll full screen here. It's going to stitch together all of these same primitives and more, but add the notion of scores and lives so that there's actually a goal, which in this case is to move the Harvard crest to constantly pursue the character on the right-hand side so that your sprite touches that one. Would you like to introduce yourself?
Hi, my name is Mohammed.
All right, wonderful. Welcome aboard. And here we come with some instructions and final flourish if we want to keep the lights up but perhaps increase the music. This is CS50, and this is week 1, wherein we continue programming, but we do it in a different language, because recall last time we focused on this graphical language called Scratch. But we use Scratch not only because it's sort of fun and accessible, but because it allows us to explore a lot of these concepts here, namely functions and conditionals, Boolean expressions, loops, variables, and more. And so indeed, even if today's syntax, as we transition to this new language called C, feels a little bit cryptic, maybe a little intimidating at first, and you don't quite see all of the meaning of the symbols beyond the syntax itself, realize that the ideas are ultimately going to be the same. In fact, as we transition from what was last week, a Hello World program that looked a little something like this week, of course, it's going to now look a little more cryptic. It's going to look a little something like this. And now even if you can't quite distinguish what all of the various symbols mean in this code, turns out that at the end of the day, it's indeed going to do what you expect. It's just going to say Hello World on the screen, just like we did in Scratch. So let's start to apply some terminology to these tokens first. So what we're about to see, what we're about to write henceforth, we're going to start calling source code. Code that you, the human programmer, write is just henceforth called source code. Doesn't matter if it's Scratch, doesn't matter if it's C, doesn't matter if it's Python before long. Source code is the general term for really what you and I as human programmers will ultimately write. Of course, computers don't understand source code, it turns out. Computers don't understand Scratch and puzzle pieces per se, or C code like we're about to see. They only understand this, which we called what last week? Yeah, so this is binary, zeros and ones, but really it's just information represented in binary. And in fact, the technical term now for patterns of zeros and ones that a computer not only understands how to interpret as letters or numbers or colors or images or more, but knows how to execute as well, henceforth is going to be called machine code, to contrast it with source code. So whereas you and I, the humans, write source code, it's the computer that ultimately only understands machine code. And even though we won't get into the details of exactly what pattern of symbols means what, you'll see that in this kind of pattern of zeros and ones, there's going to be numbers, there's going to be letters, but there's also going to be instructions. Because indeed, computers are really good at doing things, addition, subtraction, moving things in and out of memory. And suffice it to say that the Macs, the PCs, the other computers of the world have just decided as a society what certain patterns of zeros and ones mean when it comes to operations as well. So not just data, but instructions. But those patterns are not something we're going to focus on in a class like this. We're going to focus on the higher level software side of things, simply assuming that we need to somehow output machine code. So it turns out then that this problem we have to solve, getting from source code to machine code, actually fits into the same paradigm as last time. But the input in this case is going to be source code on the one hand, like that's what you and I ideally will write so that we don't have to write zeros and ones. But we need to somehow output machine code because that's what your Macs, PCs, phones are actually going to understand. Well, it turns out there are special programs in life whose purpose is to do exactly this conversion, convert the source code you and I write to the machine code that our phones and computers understand. And that type of program is going to be called a compiler. So indeed, today, we'll introduce you to another piece of software, and these come in many forms. We'll use a popular one here that allows you to convert source code in C to machine code in zeros and ones. Now, you didn't have to do this with Scratch. In the world of Scratch, it was as simple as clicking the green flag, because essentially MIT did all of the heavy lifting there, figuring out how to convert these graphical puzzle pieces to the underlying machine code. But now, starting today, as we begin to study programming and computer science proper, now that power moves to you. And it's up to you now to do that kind of conversion. But thankfully, the fact that these compilers exist means that you and I don't have to program in machine code like our ancestors once upon a time did, be it virtually or with physical punch cards, like pieces of paper with holes in them. You and I get to focus on our keyboard as such. But it's not just going to be a matter today of like writing code. It's going to be a matter ultimately today onward of writing good code as well. And this is the kind of thing that you don't just learn overnight. It takes time. It takes practice. Just like writing an essay in any subject might take time and practice and iteration over time. But in a programming class like CS50, we're going to aspire to evaluate the quality of code along these three axes generally. Is it correct first and foremost? Like, does the code do what it's supposed to do? After all, if it doesn't, well, what was the point of writing it in the first place? So it sort of goes without saying that you want code you write to be correct. And it's obviously not always. Again, anytime your Mac or PC or phone has crashed, some human somewhere wrote buggy, that is code with mistakes. But code correctness is going to be the first and foremost goal. But then there's a more subjective goal we'll see in time, a matter of design. And we saw a little bit of this last week when I proposed that we could design even Scratch programs better, maybe by using loops instead of just by copying and pasting the same blocks again and again. So design is more subjective. It's more of a learned art whereby two people might ultimately disagree as to which version of a program is better designed, but we'll give you building blocks and principles over the coming weeks so that you can have a better sense for yourself if your own code is well designed And why is that valuable? Well, the better designed your code is, often the faster it's going to run, the more maintainable it's going to be by you or colleagues if you're working with others in the real world. So good design is a good thing. It helps you communicate your ideas, just like in a typical English essay. And then lastly, we'll talk this week onward about style. And this is really just the aesthetics of your code. It turns out that computers often don't care how sloppy your actual code is. In the world of code, it turns out that you don't really need to indent things in a beautiful way. You don't need to paginate things like you might in an essay. The computer generally does not care, but the human does. The teaching assistant does. You will care the next day when you're just trying to understand what your code does. So we'll focus lastly on style, the aesthetics of the code that you're writing. So where are we going to write code? Where are we going to compile code? So for this class, not only with C, but the other languages we use later in the term, we're going to use a free text editor that is programmed called Visual Studio Code, aka VS Code. It's super popular nowadays, not just for C, but for C++ and Python and Java and any number of other languages. It's a text editor in the sense that it lets you edit text, and that's all code is going to be. Now, strictly speaking, you could write code on paper pencil. In fact, in high school, if you took a class, you might have done that one or more times as sort of an in-class exercise. You can't run it on paper, of course, but you could write it certainly. You could use something like Microsoft Word or Notepad.exe or TextEdit on the Mac, but none of those programs are really designed to format the code in the best way for you, nor are they designed to let you compile and run the code. So VS Code is going to be a tool via which you can do all that and more. Write the code, compile the code, run the code. So that you all don't have to wrestle with stupid technical support headaches at the beginning of the course by installing this software and that on your Macs or PCs, we'll use a cloud-based version of VS Code at code.cs50.io, and that's going to be the exact same tool. And the goal then is by the end of the semester to sort of migrate you off of that cloud-based environment to your own Mac and PC, so that even if CS50 is the only CS class you ever take, you're 100% equipped to continue writing code after the class using not something that's even CS50 specific, but a de facto industry standard, at least for some time. So what's this program VS Code going to look like, be it on your Mac PC or initially in your browser? It's going to look a little something like this. And there's going to be several different regions to the screen. And pictured here is that very same code I keep proposing is the simplest program you can write in C. And what are these different regions of the screen? Well, there's essentially these four here. So first, highlighted up top, is going to be one or more tabs where you're going to actually write code. So much like in Google Docs or Microsoft Word, you can have tabs open with files. Similarly, in VS Code, or really any programming environment, you generally nowadays have tabs of some sort. And this is going to be a tab containing a file, it seems, called hello.c. And that's going to be the very first file we write in just a moment. Down here, though, is going to be an interface that many of you might not know. This is what's called a terminal window. And a terminal window provides what's generally called a command line interface, or CLI. And this is in contrast with a graphical user interface, or GUI. Now, you and I every day are using GUIs on our phones, on our PCs. And a GUI is literally graphical. So menus and buttons and icons. And you generally use your finger or a trackpad or a mouse or something like that to interact with it. But it turns out that many programmers, dare say most programmers, at least over time, come to prefer not a GUI, but a CLI, a command line interface where you actually do everything somewhat arcanely via keyboard alone. Why? Well, it turns out there's just more features built into most computers if you can access them with a keyboard. Turns out most of us can type faster than you can point and click, and so that ends up being an efficiency gain over time. So in time, will you get comfortable using this terminal window to do things like compile your code or make your program, as well as run it. So you won't be in the habit initially of just double-clicking icons like we do in our typical real world. You'll do it sort of the programmer's way, but it's not to the exclusion of adding icons and clickability and more. On the left-hand side of VS Code, there's going to be a somewhat familiar file explorer, some kind of hierarchical tree like on your Mac or PC where you can see all of the files in your account. Pictured here, for instance, is just hello.c, which I'll create myself in a moment. And then far away on the left is the so-called activity bar. And this is where you just get a lot of traditional menus and buttons. So VS Code itself gives you both a GUI and a CLI, but it's within the CLI, the terminal window, the bottom region of the screen, that we're actually going to type most of our commands. And in general in class, I'm going to hide all of the graphical stuff that's just not of all that much interest. So with that said, let me actually change over to a live version of VS Code. And I've indeed hidden the activity bar. I've indeed hidden the File Explorer. So what I have here, for visibility's sake, is a really big area for writing code and a really big terminal window at the bottom. You'll see in the terminal window, there's a $sign. And this doesn't mean any form of currency. This is just the standard symbol that represents type commands here. So the fact that there's just a $sign and a cursor means eventually that's where I'm going to type commands. But first, I'm going to actually create some code. So how might I program using VS Code, be it on my Mac PC or in this cloud-based environment that you'll get set up for problem set 1, go about writing my first file? Well, perhaps the easiest way is this. Literally run the command code, and then the name of the file you want to create. Notice that I deliberately end the file with .c in lowercase. Notice that I've deliberately lowercase the whole file name. And these are just conventions. You could use a capital H. You kind of could use a capital C. But just don't do that. Follow best practices so that it's consistent with what most everyone else would do. When I hit Enter, I just get an empty tab, just like the screenshot a moment ago. And it's in this tab where I can now write my very first program in C. Unfortunately, it's not quite as user-friendly as Scratch, where you drag and drop a couple of puzzle pieces and boom, it's done. So I'm going to do this from memory, but this too will become familiar to you over time. I'm going to include something called standardIO.h. I'm going to type int main void in parentheses. On a new line, I'm going to insert some curly braces, as we'll call them. And then I'm going to type printf, and then some parentheses, and then in quotes, hello, comma, world, then a backslash, then a lowercase n, then a close quote, and then a semicolon at the very end of the line. So all I've done is recreate, just from memory, that very first program. In a little bit, we'll make clear what most of this does. But for now, let's just actually run this thing. And just like I clicked the green flag last week for the first time, let's actually compile and run this program. If it were your Mac or PC and Google or Microsoft or someone else had made the software, at this point in the story, we'd be double-clicking an icon. But we can't do that yet. This is still source code. So I'm going to click back down in my terminal window. Notice I have a second $sign below the first, which just means it's ready for a second command. And now the command via which to make this an actual program, to compile it from source code to machine code, is going to be quite simply make, and then the name of the program I want to make. Slight subtlety. I'm omitting deliberately .c because the program I want to make, I just want to call hello. So don't write make hello.c, just write make hello. And this program make is essentially our compiler. Technically speaking, it's a program that automates the compilation of my program for me. But it is going to see that I've typed the word hello. It's going to automatically look now for a file on the hard drive called hello.c and convert it from source code in C to machine code in zeros and ones. So if I didn't make any typos, enter. Nothing seems to happen, and that's a good thing. Almost always, if nothing gets outputted on the screen, like you did good. Like you didn't make any mistakes. You didn't get yelled at. There's no error messages. So this is actually a good thing. How do I now run this program? Well, notice I've got a third $sign, which just means I'm ready for a third command. And now I'm going to go ahead and run /hello. And this is admittedly a little weird that you have to do /, but for now, just take on faith that this is how you run a program called hello in your current folder, in your current directory in this cloud-based environment. All right, crossing my fingers again, hitting enter, and voila, my very first program in C, hello world. And now let me go ahead and reveal the File Explorer that I proposed exist earlier. I'm just going to use the keyboard shortcut to reveal that. And generally, I keep it closed because I don't really need to know constantly what files are in my account. But you'll see now in the File Explorer, similar in spirit to a Mac or PC, but graphically a little different. Here's my file, hello.c. It's highlighted because I have that tab open. But now there's a second file here called just hello. That's the name of my program. So if you were on a Mac or PC, you would ideally double-click that thing. You can't do that in a command line environment. You have to run it down here, but that's all we've done. We've created a file called hello.c, and then my compiler made the program from that. Let me pause here and see if there's any questions, because it's a lot of magical phrases. Yeah. Yeah, so if you're currently following along, playing along at home, and you're getting some kind of error message, part of today will be for me to deliberately induce some of those error messages. For now, let me just propose that if you literally did what I did, you must have made a typo somewhere. And notice that it's indeed standard IO, stdio.h. Maybe you type studio.h. Okay, super common mistake. If I could call you out, like it is not studio.h. It is standard.io.h. So common, but this is exactly representative of like the kind of stupid headaches you're going to run into this week, probably for a few weeks, probably honestly for a few years. But you start to see past these sort of stupid mistakes over time, and it just gets easier and easier because the computer is going to be so regimented. Like it will only do what you tell it to do. And if you say, because it verbally sounds like studio.h, it's not going to know what the file is. So actually, thank you for tripping over that so early. That's super common to happen. Yeah. So why do I have 2 hello files? So why do I have 2 hello files? One is the one I created as the human called hello.c, and it's pictured right here. But then when I ran make hello, that process compiled my source code into machine code. So this second file, just called hello, is the file that contains all of those zeros and ones that the server actually understands. All right, so yeah, question. If you try clicking on the hello file, you'll see in this environment of VS Code, quote unquote, the file is not displayed in the editor because it is either binary, aka zeros and ones, or uses an unsupported text encoding. In this case, it's binary. It's zeros and ones. Now, you could use software to see those zeros and ones. It won't be intellectually enlightening to most any human. So VS Code just takes the choice of not showing it to you at all. So that would be a common mistake, too, clicking on a file you don't intend. But the source code is indeed going to be editable by us. All right, so I've written this program. It seems to sort of magically work, at least with some effort. If you get every single keystroke right, well, what is it that's going on and how is this working? Well, first of all, notice that even without my highlighting things or choosing buttons from menus, notice that it's already kind of color coded. And yet I wasn't highlighting along the way and sort of Google Docs style changing the color, certainly. Well, it turns out what VS Code and most programming environments nowadays do for you automatically is syntax highlighting. So syntax highlighting is just this feature of typical text editors nowadays that analyzes the code that you've typed. And when it notices certain types of keystrokes, things that represent functions or conditionals or loops or variables, a lot of the vocab from last week, it just highlights it ever so differently for you. So main, for instance, which we'll soon see, is in purple here. Int and void and include are in red. Hello world is in blue. My parentheses are in green. This will totally vary by programmer too. In fact, if you do want to change these colors for problem set 1 for your own environment, you can poke around VS Code settings via the gear icon. You can change to a different color theme. Syntax highlighting isn't some specific color scheme like it is in Scratch. It just generally is to each human their own preference. But that's all that's happening here is this notion of syntax highlighting at the moment. Well, what more is going on in this code before I run it, but rather write it? Well, it looks a little something like this if I take away all of the colors. And then just for discussion's sake, let me go ahead and color it a little more like Scratch. Recall that our very first Scratch program that just said hello world on the screen had a when green flag clicked icon, puzzle piece, roughly in orange, and then a purple say block beneath it. So whereas this is the C version, if we rewind to last week, this was the same program in Scratch. But what's happening now is exactly the same. So if you think back to last week and you've got some function, like the say function in purple, that might take one or more arguments, like inputs that influences what it says on the screen. And then functions, recall, can sometimes have side effects, right? Like the speech bubble appears on the screen. So last week, when we used the say block and we passed in an argument of hello world at left, we got this visual side effect on the screen that says now hello world in the speech bubble. And that's exactly what just happened in VS Code, but much, much more textually. And let's look a little closer now at the code itself. Let me wave my hand at the equivalent of the when green flag clicked part of my code. And let's focus only on the say block in Scratch and the corresponding function in C. So if I step through this and I wanted to convert what we did last week with the say block to C, I would first use the print function. Although that's actually a bit of a white lie. It's actually the printf function. Printf means formatted, and it's just a function that allows you to format text on the screen. There is no say function in C. There's a printf function. What MIT did down the road years ago was they took what existed historically as printf, and they simplified it for a broader audience by just calling it essentially say instead. But notice that now, if I want to convert the Scratch code at left to see code at right, it's sort of the same shape. So MIT deliberately used this white oval, if only because it kind of conjures this idea of having parentheses too. So on the right, if I want to pass an argument or an input to the printf function, I use an open parenthesis and a close parenthesis. In those parentheses, I then type whatever it is I want to print on the screen. In this case, hello, comma, world. But notice I've deliberately left some room because you need some extra keystrokes in the world of C. Anytime you type out some text, otherwise known as a string of text, to use computer science jargon, you need to quote it, in this case with double quotes. Double quote at the left, double quote at the right. And notice, too, I'm going to include some slightly cryptic symbol here, too, \n, which I also typed and said verbally earlier. And then one last nuisance at the end of this, which is a semicolon. So suffice it to say, this is why we start with Scratch. This, drag and drop, you're good to go. In a language like C, printf, parenthesis, double quotes, the text you want, \n, semicolon at the end. There's just so much syntactic overhead. But at the end of the day, it's just a function. And you'll get used to these sort of nuisances like the parentheses, the quotes, the semicolon, and the like. But things can very easily go wrong. And it's very easy to make mistakes even with lines of code like this. So let me do this. Let me go back to VS Code where I have the exact same code. Notice that on line 5 is exactly that line of code. So this is the equivalent of the say block. And let's consider what mistakes I may make early on, or even now, 20 years later after learning this, that are quite common in general. Suppose I forget the semicolon there. So easy to do. You will do this eventually. Let's see what happens now when I go back to my terminal window and try to compile my code again. Just to keep things tidy, I'm going to clear my screen. But that's just for lecture's sake so that we can focus only on the most recent command. But I'm going to go ahead now and rerun make hello. This will ensure that my program is recompiled. And this is a manual process. I changed my code. The zeros and ones on the hard drive have not changed. I need to recompile it to output the latest machine code. So here we go. I'm going to hit enter, crossing my fingers as before. But again, I removed the semicolon by accident. Oh my God, there's like more lines of errors now than there are of actual code. And this too takes some getting used to. The programs we're using were not necessarily written with the least comfortable audience in mind, but really professional programmers back in the day. But through practice and through experience and through mistakes, you'll start to notice patterns here too. So here's what I typed. Make hello after the $ prompt. Now I get yelled at with as follows. Hello.c :5:29. Well, what's that referring to? I've screwed up somewhere on line 5 on the 29th character on that line. Generally, the specific character is not that useful unless you actually want to count it out. But line 5 is a good clue. Why? It means I screwed up somewhere on line 5 here. All right, well, what is the error? Expected a semicolon after expression. And this error is actually pretty obvious now that I see it and I realize, oh, wait a minute. All right, here's my line of code. Here in sort of ASCII art, so to speak, textual text representing graphics, it wants me to put in green here this semicolon at the end of that line. One error generated, built in, so some esoteric stuff there. But my program did not compile. When you see an error like this, it means it did not work. So what's the fix? Well, obviously, the fix is to go back up here, put the semicolon there. And now, if I recompile my code with make hello, I won't clear my screen just yet, just to show you the difference. Now, it just worked. So we're back in business as before. All right, let me pause here, though, and ask if there's any questions about what I just did. These error messages will become frequent initially. Yeah? Really good question. Do you need a semicolon after every line or just some? It turns out just some. This is something you'll learn through practice, through demonstrations and examples today. Generally, you put a semicolon after a statement, so to speak. And this is the technical term for this line of code. It's a statement. And think of it as it's kind of the code equivalent of like an English sentence. So the semicolon in code is sort of like a period in English when you're done with that particular thought. You don't need semicolons for now anywhere else. And we'll see examples of where else you put them. But it usually is at the end of a line of code that isn't purely syntactic like curly braces instead. Other questions on the mistake I just fixed and created for myself? Yeah? Correct. So line 5 is where the error is most likely. Character 29 means it's sort of 29 characters that way. And then it's actually, in this case, giving me a suggestion. The compiler won't always know how to advise me, especially if I've made a real mess of my code. But often it will do its best to give you the answer like this. Yeah? So how come I first typed code space hello.c, and now I'm typing make hello? Two different processes. So when I typed code space hello.c, that was because I wanted to open VS Code and create a new file called hello.c. It's like going to file new in a Mac or PC. Thereafter, though, once the file exists and is actually open here, and it does autosave, you don't need to hit Command S or Control S all the time, I can now compile it with make hello again and again. So theoretically, I should never need to type code space hello.c again unless I want to create a brand new file called the same thing. All right, so what about this other piece of syntax here? Let me clear my terminal window here. You can also hit Control L just to throw everything away, just to clean it up aesthetically. Suppose that I omit whatever this sequence of symbols is, \n, since I'm not really sure at first glance why that's even there. Does anyone want to conjecture, especially if you've never programmed before, what might happen now if I recompile and rerun this version of the program? I left the semicolon, but I took away the \n. Any instincts? All right, well, yeah.
Will the next $sign appear straight after your hello world?
It will. The next $sign will appear right after my hello world, but what makes you think that?
Because the \n creates a new line.
Exactly. \n is actually a special sequence of symbols that creates a new line. And so, to your point, if I recompile this program, make hello, enter, no syntax error, so it did compile this time. So you don't need the \n, you do need the semicolon. But if you don't have the \n, watch what happens when I do /hello this time. Now, indeed, I see hello, comma, world, and then a weird $sign. And this is still a prompt. I can still type commands at it like clear, and everything gets cleaned up. But it just looks kind of stupid. If I run it again here with /hello, you know, it's just not very user-friendly. It is convention that when you're done running your program, you should ideally clean things up, move the cursor to the next line for the user. And so the \n is simply the special symbol, otherwise known as an escape sequence, that C knows means move the cursor to the next line. In other languages, Python among them, uses this same symbology as well. Now, if I go back to the code here, and for instance, I try to do this differently. Like, suppose I don't put the \n, I just hit enter, like a normal person would in Google Docs or Microsoft Word. Let me go ahead and try compiling this program. And this, you would hope, would work, right? You would hope this would print out hello world and then a blank line because I moved the cursor to the next line. But no, if I run make hello now and try to compile that, C does not like this. Now I get a different error, still on line 5, this time starting at character 12. Error missing terminating double quote character, and then some other esoteric stuff. And then this does not sound good. Fatal error this time. Too many errors omitted. Stopping now. So I really screwed up here. So why can't I do this? Just because, like the humans who designed C decided that if you have a string of text, it must stay on the same line. It can get really long. It can soft wrap, that is without you hitting enter, but you can't hit enter to create a new line. If you deliberately want a new line, you have to indeed use this \n escape character. So let me go ahead and do this. Let me put it back. Let me go back to my terminal window. I'll clear the screen again. Let me go ahead now and do make hello to recompile to that version, /hello, and voila, we're back in business with hello. All right, so now let's tease apart some other aspects of this code, because there's a lot going on just to get us to say hello world on the screen. For today, we're largely going to ignore this. Int main void and these curly braces here. We'll come back to that before long as to why it's there. But for now, just think of int main void and these curly braces here as really being the C equivalent of when green flag clicked. Like why? You just need it there. That's how you get your program going. And main is indeed going to be some special function. But more on that another time. But why do I have this line of code here? The correct spelling is indeed standardio.h, stdio.h. And they're angled brackets this time, so that's a little new. There's a hash and then an include keyword. If you don't know what something is, there's not really that much harm in just getting rid of it and see what happens. So let me delete that line. Let me go back to my terminal window, clear the screen, and then run make hello again. And let's try compiling this program now without that first line. Why? I don't understand it, so let's see what happens. All right, here's yet another error, but let's see. Hello.c, line 5, character 5, so it's pretty early on. Error, implicitly declaring library function printf with type int and then ... So implicitly declaring library function printf. So this is very cryptic sounding. You'll get better at understanding phrases like these. But apparently, I do need the include line for standard io.h. But why? Based on this symptom, what might your instinct be for what that first line of code is doing for us in the first place? Why intuitively must it be there? Exactly. It's like importing a library so that you can do things like print things out on the screen. Now, in Scratch, you didn't have to do this for most of the puzzle pieces, but you might recall that partway through week 0, I went to the extensions button at the bottom left of the Scratch screen, and I imported some extra puzzle pieces for text to speech that gave us the sort of creepy humanized voice that actually came out of the cat's mouth. Well, that was like adding a library, code that someone else wrote. In that case, it was a third party, but I gave myself access to it. Same here. Turns out that you don't really get printf automatically in C. You have to include a so-called header file that declares that function to exist. Now, the reason for this historically is just efficiency. Back in the day when computers were really slower and resource constrained, you don't want to just give yourself access to the entire kitchen sink of functionality. You only want to include only the functions you actually care about. Nowadays, it's sort of a copy-paste step because you almost always want to print something out on the screen, at least when writing programs like these. But these so-called header files contain enough information about all of the functions in what's called the standard I/O library. And standard I/O just means standard input and output. And that's appropriate, right? Because printing is pretty basic output. Turns out there's other functions for getting input from the human's keyboard. More on that in a bit. But anytime you want to print something on the screen in C, you indeed need to include this header file at the top of your code. And that's going to essentially inform the compiler, hey, compiler, I want to use functionality from the standard I/O library, including printf in this case. And if you omit the header file by accident, it's just not going to work because it doesn't know what printf is. It's sort of some unrecognized symbol in that case. All right, questions then about this line of code. This line of code here, or what these header files are. All right, you might wonder, well, how do you know what functions exist? How do you know what files you might indeed want to include? Well, it turns out that C is a many-year-old language, and it has ample documentation. A caveat is that its documentation isn't necessarily all that user-friendly, but what we have for the course is a simplified version of the official documentation for C at this URL here, manual.cs50.io. So in the world of C, and other languages too, there are what are called manual pages. And these are just like text-based documentation that honestly is typically written in a voice that you kind of have to be an experienced programmer to understand some of it. So what we've done at this version of the same documentation is we've imported all of the original official documentation, but we've added sort of less comfortable translations in English for a lot of the functionality that you might use in class just to help onboard you. So at the end of the day, you don't need this documentation long term, but just to get started, we'll translate it into terminology that you might appreciate from a teaching assistant, for instance, as opposed to the original author of these documents. And so for instance, if you were interested in reading up on what functions exist in the standard io.h header file, well, you could go to a URL like this, or you could search for it at manual.cs50.io. That would show you a list of all of the available functions in that library. And printf, indeed, would be one of them. And then you could click further on that, reaching a URL like this, that's just going to give you all of the documentation for how to use printf. It turns out you can do even more than than just printing out hello world. And we'll scratch the surface of that today. But it turns out that the documentation will always be your authoritative source, ultimately, for questions like, what can I do and how can I do it? Meanwhile, it turns out that CS50 has its own library accessible via a header file called cs50.h. It turns out in C that output is actually pretty easy, relatively speaking, once you get used to all the curly braces, parentheses, quote marks, and the like. But input is a little more difficult. And if you have programmed before, input's not that hard to do in Python. It's not that hard to do in Java. It's more difficult to do in C. And we'll see why in a couple of weeks. But for the first couple of weeks of the class, we actually provide you with some training wheels of sorts, whereby we have a number of functions that are declared in this file, cs50.h. It lives its documentation at a URL like this. And in a moment, we'll use a few of these. You'll see that cs50 provides you with some functions like getChar for get a single character from the user's keyboard, getInt to get an integer from the user's keyboard, getString to get a sequence of text from the user's keyboard, and a bunch of others as well. So let's actually use some of these functions, how about, by revisiting really the second program we wrote in Scratch last time, which adds some input to the output. So first version of Scratch was just hello world. Said the same thing every time you click the green flag. Version 2, recall, though, did this. It asked the user, what's your name? And then that somehow gave it back a return variable, a return value, we called it. And we then joined hello and that name to say something a little more interesting on the screen. So what did that model look like? Same thing as before. We've got a function in the middle, where function is like the code implementation of our algorithm. That takes in one or more arguments, like what is it you want to say on the screen ultimately. And return value in this case is going to be actually a value that comes back. So in the case of getting input, we can consider this ask block again, like last week. The input to it is whatever words of English you want to ask the user. And then it returns a value. And this was called by default in MIT's world answer, though we'll see in C you can call these return values anything you want ultimately in variables. But this is different from a side effect. A side effect is just something visual often that happens on the screen, like the speech bubble or hello world. A return value is actually a value you get back from a function that you can use or reuse. So how do we convert this Scratch block from last week to C code this week? Well, if you want to ask the user for something like their name, you can do this. You use a cs50 function called getString. And you use the parentheses to represent, here comes the inputs there too. You can then put the sentence you want to ask the user, quote unquote, what's your name? But you do indeed need the quotes literally in C, so I'll go ahead and add those as well. Subtle, but I've deliberately included a space after the question mark, but before the double quote, just so that the cursor moves one step over, because in this case, we're not going to get a special speech box like we did in Scratch. It's just going to leave the cursor where it is. So we'll see that aesthetically, that just moves the blinking cursor one space after the sentence on the screen. All right, but the catch is with Scratch, we just automatically got back the answer from the user in a special variable called answer. In C, you're going to have to be a little more specific. In C, if you want to get back a return value from a function like getString, you have to use an equal sign and then the name of a variable on the left. The choice of variables is up to you. I could have called this anything, x, y, z. I'm going to more descriptively call it answer for parity with what MIT did with Scratch. But notice that this doesn't represent equality per se. This is assignment in this case. So in C, when you use a single equal sign, that means copy the value on the right over to the value on the left, from right to left. So what does this do for us? Well, if getString is a function that prompts the user with, quote unquote, what's your name, and it has, I claim, a return value, that means it kind of hands me back some value. But it's up to me in C to do something with that value. So if I want to copy that value into a variable that I can use and reuse, I use an equal sign, and I invent on the left-hand side of that equal sign any variable name I want. There's certain rules, there's certain conventions, but generally if you use a single word with all lowercase, you're in good shape. But C is a little more pedantic than that. And those of you who have programmed before might not be used to this, for instance, in Python, which is a world we'll get to in a few weeks. You also have to tell C what type of value you're storing. So if I do want a string of text from the user, so not an integer, not a single character, I want a whole string of text, like a phrase, a sentence, a name in this case, I have to tell C that this variable is of type string. So it's a little wordy, but you get used to it, and you just have to be precise. You're informing the computer what type of value is going in this variable. All right, it's so close to being correct, but I have omitted something that's annoyingly important still. What's missing still? Yeah. So semicolon. This is a statement. This is like a full thought, if you will, in code. I do need to end it ultimately with the semicolon at the end there. All right, so this was more of a mouthful, but let's try using this in now my code. Let me go back to VS Code, where I have version 0 of my code here. Let me go ahead and include one other file at the top of hello.c, namely include cs50.h, so that I have access now to getString and anything else I might want. Now let me go ahead and add a line of code here inside of these curly braces. And let me go ahead and do this. String answer equals getString, quote unquote, what's your name, question mark. I'm going to add an extra space before the double quote. I'm going to indeed end my thought with a semicolon. And now let me deliberately make a mistake just to make a point here. Let me now try changing hello world to hello, comma, answer. All right, now perhaps, even though this is some new lines of code, you can see where I've erred already. But let me try making this program now. So far, so good. So no error messages. So that's a good thing. Let me go ahead and run /hello. And you'll see the prompt. What's your name? Question mark. And notice the cursor's indeed one space to the right, just because I thought it would look prettier to put a little blank space there, as opposed to leaving it right after the question mark. Let me type my name. But even if you've never programmed before, I have screwed up here. What are we going to see on the screen when I hit enter? Yeah, hello answer, most likely. Why? Because the computer is going to take me literally. And if I say, quote unquote, hello answer, that is the string of text followed by a new line that's going to be outputted to the screen. So we need some way of actually plugging answer into this line of code. It's not quite as simple as Scratch, where you could just grab like a second say block and drag and drop the variable there. We actually need a new syntax. And it's going to look weird at first, but it is everywhere in software nowadays, especially in the world of C and certain other languages. So let me go ahead and propose that I solve it as follows. Well, back when we did this in Scratch, remember that the most elegant solution was this here. We used the say block still, which is going to be analogous to printf today. But I used the join puzzle piece in Scratch to combine hello, comma, space, and then the name of the human. So how do we translate this code to C? Well, it's going to look a little different now. I'm going to start with printf with some parentheses and a semicolon representing the say block. But how do I now do this joining? This is where the puzzle pieces don't quite translate perfectly. This would be the way to do this. You put hello, comma, and then a placeholder. So this is what's known as a format code in C, specifically for printf. And it just means this is a placeholder for a string. Again, a string is just text. So this means, hey, computer, print out literally hello, comma, space, and then not literally %s. %s is treated specially to mean plug in some value here. All right, so what else do I still need? Well, this is still some text. So I'm still going to surround the whole thing with double quotes. I'm still going to include my \n just to keep things tidy and move the cursor to the next line. So the last step here in C is to somehow join the answer with that word hello. And the way you do this is with printf, passing it not one argument, which is what I keep doing. I keep passing it one string of text, quote unquote. I'm going to now add a comma and then the name of the value that I want printf to go back and plug into that %s. And printf is just smart about this. If you have 1%s and one additional argument after a comma, it just does from right to left, it plugs it in. If you have 2%s's and two variables after the comma, that's OK too. If you separate them with commas, it'll plug the first into the first %s and the second variable into the second %s. So it's just left to right order of operations. It's not as pretty or as simple as this, but this is how it's done in C. All right, let me pause, because this is a lot of symbology. Any questions on this technique here? Yeah? Yeah, really good question. Why did I exclude the \n a moment ago? Really just my sense of aesthetics, if you will. No good reason beyond that. So if I look back at my code, you quite rightly notice that I didn't have a \n there. That's just because for whatever sense of style that I have, I wanted the name to be typed right after the question. I totally could have added a \n there instead of a space. That would have just allowed me to type down here. Totally fine. Just wanted to show you something different. Good catch. Yeah? Can I show an example with 2%s's? Surely. So let me, in VS Code, do this. Let me clear my terminal window to clean things up. And let me do this. Instead of calling the variable answer all over the place, let me call it first. And I'll ask two questions. What's your first name? And now let me do string last equals get string, quote unquote, whoops, capitalization matters. So let me fix my capital S there. Quote unquote, what's your last name? Question mark, semicolon. And now we'll plug in 1%s and a second %s. And now I'm going to plug in first, and last, coincidentally. And now I'm going to go back to the terminal window. Make hello, crossing my fingers. All good. /hello. Here's my first question, David. Here's my second question, Malin. And again, hello, David Malin. So it just inserts them left to right. All I was doing for parity with Scratch, though, and let me go ahead and undo this again. I'll go back to answer like this. I'll go back to just asking for the person's name. I'm going to delete mention of last. I'm going to delete mention of the second %s. And now if I recompile this simpler version, I did screw up. Didn't intend it. What did I do wrong? Yeah, so just newbie mistake. So I changed my variable back to answer just to be consistent with week 0, but I didn't change it here. So I have a use of undeclared identifier first. It's undeclared in the sense that I declared answer a line prior. I didn't declare first. So indeed, intuitively, I want to just change that to that. Let me now do make hello again. /hello. Type in just my first name this time, and there it is. Hello, David. Questions on this then syntax with printf? Yeah? The placeholder, I'll zoom in, is just a single % and then an s. So inside of my string here is %s. And then I have a comma outside the quotes, and then the name of the variable whose value I want to plug in for that %s. And now notice there's technically 2 commas inside of these parentheses on line 7. And yet I claim that printf at the moment is only taking in 2 arguments. Why is there then 2 commas but only 2 arguments? If there were 2 commas, you would think there'd be 3 arguments, right? Exactly. The comma in between the quotes is just an English thing. It's separating the hello from the name. So that's why, indeed, it's not only in quotes. That's also why programs like VS Code tend to syntax highlight it a little differently, just so that it sort of jumps out as different to you, even though in this case it's a little subtle, a light blue versus white. But indeed, it's trying its best. Other questions now on this placeholder? Yeah? Good question. If I wanted to add an exclamation point after the name, would I have to add another placeholder and so forth? I could actually do that much more simply. I can just put the exclamation point right after the %sign. I don't need an additional placeholder per se. If I zoom out now and run make hello again, /hello, and type in just my name, no exclamation point, now you'll see more excitedly hello, comma, David. So printf is smart. It will figure out where the %s is and then go and replace it. Now, let me propose that a common thing in programming is that as soon as we make a decision as to how to design something, we often paint ourselves into a corner and sort of regret a decision. Can anyone think of a problem that arises from using %s as a placeholder in this string to printf? What could go wrong if we're using % in this special way? Yeah, if you literally want to say, for whatever weird reason, %s on the screen, or honestly, even just a single %. It turns out that a % is treated specially inside of printf strings. So what's the solution here? There's different patterns of solutions to problems like these. But suppose you wanted to say, I got 100%, for instance. Let me go ahead and change this completely. So I got 100% on your test or whatever. All right, let me go ahead and run make hello, enter. All right, so invalid conversion specifier. I mean, I have no idea what this means, but it's underlining the % is problematic. Well, it turns out that humans years ago decided, oh, all right, damn it, we already used %. Well, 2% signs will mean 1% literally. So now if I rerun make hello, Aha, /hello, I got 100%. So there's going to be things like that, honestly, that you have to ask someone, you have to Google, you have to look it up in the documentation. But there's always a solution to those kinds of problems. And thankfully, they don't come up all that often. Yeah. Oh, just pointing. Other questions? Yeah. If you have multiple variables, it is in the left-right order. So printf will analyze the first string of text that you pass in between quotes, and whatever the first % is, the first variable that's passed in after a comma gets plugged in there. And then the second gets plugged into the second, third into the third, and so forth. So it's just based on left to right. Yeah? It's just a placeholder. It's called a format code. And it just means, colloquially, plug in some value here. And printf, the humans who wrote printf decades ago decided to treat %s special. Why? Just because. They needed some placeholder. They decided that, no one's ever going to really want to type %s. And if they do, they can just do %s. So they decided to implement printf in such a way that they have code that analyzes whatever text comes in, looks for %s, and then somehow plugs in the subsequent values into that placeholder. And just as, question? Sorry? So what if you wanted to do single characters like initials like DM or DJM for first, middle, last? Absolutely. And that, too, is a perfect segue from the two of you to what in general are going to be called data types in C. So it turns out in C, there's not only strings as text, and we'll see in more detail and over the next couple of weeks what a string really is underneath the hood, but strings of text are not the only thing that programs can output. They can indeed output single characters, as for initials. They can output integers as well. Turns out that printf has different format codes for all sorts of different data types. And just some of the data types we'll see in the coming weeks will be this list here, which you'll notice it almost perfectly lines up with the CS50 functions that I rattled off earlier, like getChar, getInt, getString. The reason we called those functions that is because each of them is designed to return to you a different type of value. We've used getString already in this example here. We'll soon see getInt, and we'll see opportunities to use others. But these indeed are the menu of available data types, plus others, ... that you can use when writing a program in C. The onus, therefore, is on you to decide in advance, do I want to store an int in this variable, or a string, or heck, when writing fancier code, an image, or a sound, or a video even. Those can all be different data types, ... But for now, we'll focus really on just these primitives. That was a lot. Let's go ahead and take a 5-minute break here. No cookies yet, but in 5 minutes, we'll come back, dive into more detail. In our second break today, we'll have cookies. All right, we are back. And so if you have been playing along at home but hitting some bumps in the road, that's totally normal. And indeed, the goals of lecture generally will be to give you a sense conceptually of where we'll be going during the course of the week. But it's indeed through the hands-on labs and problem sets that you'll really have an opportunity at your own pace to work through some of those same bumps in the road. But for today, let me give you a few more building blocks. And these two will translate from scratch initially, namely like conditionals, like how now in C, after knowing now how we can use functions, at least getString and printf, and we can use variables like the string I created earlier. How can I now add to the mix things like decision making and conditionals at that? Well, with conditionals in Scratch, we had this kind of syntax. On the left, here in Scratch is how you might express if two variables, x and y, have this relationship. If x is less than y, then say on the screen x is less than y. Well, let me translate that to the right now in C code. So in C, the corresponding code is going to look like this, assuming x and y already exist. More on that later. And notice a pattern we're going to see again and again. There is going to be parentheses around the x and less than y. So parentheses around the Boolean expression, recall. The Boolean expression is the true, false, the yes, no answer, a question that you're trying to ask in order to decide whether or not to do something. So you use parentheses there. So similar in functions where we used parentheses for printf and parentheses for getString. And this is just a weird inconsistency stylistically. When using the keyword if, you should, as a matter of best practice, put a space after the word if. When using a function like printf or getString, you shouldn't. Both will work, but you'll find that these are conventions stylistically that most people adhere to. So space when using an if here. All right, now inside of the curly braces is where the actual code goes that you want to execute conditionally. So if you want to print out x is less than y only if x is actually less than y. In C, you use this open curly brace, which up until now you've probably rarely used on your keyboard, and the closed curly brace down here. And those are kind of hugging, if you will, the one or more lines of code underneath the if. Very similar in spirit to how the orange block here kind of hugs the purple puzzle piece here. So there's no graphics in C. It's all text. So you can think of those curly braces as really representing the same idea. As a side note, if you only have one line of code inside of the if condition, if you will, you strictly speaking don't need the curly braces, but as a matter of good style, do include them. It will make more obvious what your intent is. How about in Scratch if you wanted to express this? Two ways in the road that you might go, left or right, so to speak. Well, if x is less than y, I want to say x is less than y. Else, I want to say the opposite. X is not less than y in this case. So I'm making a decision based on that Boolean expression. In C, it's almost the same, but you're adding to the mix the keyword else. So MIT borrowed for Scratch the same keyword there, and a second pair of curly braces, open and close respectively. And you might guess now what goes inside of those. Well, you print out x is less than y, or you print out x is not less than y. All right, what if there's a three-way fork in the road? In Scratch, this actually gets a little unwieldy graphically, if you will. But notice that in Scratch, this is how we could express if x is less than y, say x is less than y. Else if x is greater than y, say x is greater than y. Else if x equals y, then say x is equal to y. Now, minor inconsistency here. Just a little bit ago, I claimed in C that an equal sign represents what operation? Assignment from right to left. Insofar as Scratch is really meant for kids and they didn't really want to get into the weeds of this kind of semantic, equal sign in Scratch means equality. However, we're going to need to fix this in C in just a moment. In C, equal sign means assignment right to left. In Scratch, it literally means what you would expect. All right, let's translate this code then to C. On the right, this code would correspond really to this. And you can perhaps see somewhat goofily what the solution was, not unlike the %% solution earlier when humans painted themselves into one other corner. You say if, you say else if, and you say else if. And how did we resolve the use of a single equal sign already? In C, when you want to express equality, is the thing on the left equal to the thing on the right? You literally use two equal signs right next to each other, no space in between them. But now, this code would be correct on both the left and the right, whether you're doing this in Scratch or C respectively. But now we can kind of nitpick our code, specifically the design thereof. Logically, can anyone critique the design of this code, either in Scratch or C? Like, I feel like we could do better. How about in back?
The only option after it being greater than or less than is or.
Perfect. Logically, it's got to be the case that x is less than y, or x is greater than y, or by conclusion, it's got to be equal to y. So why are you wasting my time or the computer's time asking a third question? You don't need to ask this final else if, because logically, as you note, it should go without saying. So it's a minor tweak, like you're doing extra work potentially in the cases where x equals y. So we can just refine that. And just like in Scratch, you could just use an else block. Similarly, in C, could we simplify this code to just an else, a sort of catch-all logically that just handles the reality that, of course, that's going to be the final situation instead. All right, so we have this ability now to express conditionals with Boolean expressions. Let's actually do something with this next here. So let me go back to VS Code. I've closed hello.c, and I want to create a second file for the sake of some demos now. Recall that you can create new files by typing code space and then the name of the file you want to create. For instance, I might do compare.c. I want to write a program that's going to start comparing some values for demonstration's sake. But before I do that, let me just show you by opening the File Explorer at right. This is similar in spirit to a Mac or PC. Like you can go up here and click on an icon, and you can click on the plus icon, and you'll get a blue box, and I can type in compare.c, and I can just manually create it that way. Notice that opens the tab even without my having typed code. So again, on the left, you have a GUI, a graphical user interface, albeit a simplistic one. On the right, and at the bottom here, you have a command line interface, but they're one and the same. What's nice, though, is that if I close this file, accidentally, intentionally, whatnot, I can reopen it without creating a new one by just running that same command, code space compare.c. So code is a VS Code thing. It's just a user-friendly shortcut, but it's just creating a file or opening an existing file like that. I'm going to hide the File Explorer just to make more room for code here. And let's go ahead and do this. Let's write a program that compares two values that the human inputs, but not strings this time. Let's use some actual integers. All right, I'm going to go ahead and include the CS50 library's header file at top, cs50.h. I'm going to also include standardIO.h. Why? One gives me user-friendly input via getString, getInt, and so forth. One gives me user-friendly output via printf in the case of standardIO.h. Now I'm just going to kind of blindly type this line of code, which we'll come back to in future weeks. But for now, that's analogous to the when green flag clicked code in Scratch. And now let's go ahead and do this. Let me go ahead and get an int from the user and ask the user, what's x, question mark. I'm not going to bother with a new line. I want to keep it all in one line just for aesthetics sake. But when I get back an int, just like I get back a string, I get back a return value. So if I want to store the result of getInt somewhere, I had better put it in a variable. And I can call the variable anything I want. Previously, I used answer or first or last. Now I'm going to use x. But there's still two things left to do here, logically, even though we haven't technically done this yet. What do I still need to do? So I need the semicolon at the end and the int at the beginning. You, the programmer, starting today, kind of need to decide what you're going to be storing in your variables. And you just need to tell the computer that so that it knows. Now, as a teaser for languages like Python, more modern languages, turns out humans realized, well, gee, this is stupid. Like, why can't the computer just figure out that I'm putting an int there? Why do I have to tell it proactively? So in some languages nowadays, like Python, we'll get rid of some of this syntax. We'll get rid of the semicolons. But for now, we're looking at really the origins of how this all worked. All right, so I've done this one line ending with semicolon. Let me do one other, and let me get a second int asking the user, what's y, question mark. So almost identical, but different responses from the user, hopefully. And let me just ask simply, if x is less than y, in parentheses, then some curly braces, let me go ahead and print out, quote unquote, x is less than y, \n. And now just as a side note, I seem to be typing kind of fast. Some of that is because VS Code is helping me. Let me go back to this first line with the if, hit enter, and now I'm only on my keyboard going to type the open curly brace. This is a feature of many text editors nowadays. It finishes part of your thought. Why? Just to save yourself a keystroke, to make sure you don't accidentally forget the closing one. So you'll notice sometimes that things are happening that you didn't type. It's just VS Code or future programs you use trying to be helpful for you. I'll go ahead and manually type out now printf, x is less than y, \n, close quote, semicolon. So let me go ahead now and try to run this. And we'll see. Let's see. So make, not hello, but make compare, because this file is called compare.c. Hitting enter. OK. No output is good because it means I haven't messed up. Let me do /compare instead of /hello. Enter. What's x? How about 1? What's y? How about 2? X is less than y. Well, let's try it again. And here I'll save you some keystrokes too. Let me clear my screen. Instead of constantly typing /this and /that, you can also use your keyboard's arrow keys in VS Code to scroll back through time. So if I hit up once, there's the last command I wrote. If I do it up twice, there's the second to last command I wrote. So sometimes if you see me doing things fast, it's just because I'm kind of cheating and going through my history like that. All right, let me go ahead, though, and rerun /compare. Enter. Let's reverse it this time. 2 for x, 1 for y. And now, of course, there's no output. All right, well, that's logically to be expected because we didn't have an else here. So let's add that. Else. Now let's open my curly braces, letting VS Code do one of them for me. Printf, quote unquote, x is not less than y, \n, semicolon. Let me go ahead and try this again. /compare. Enter. Again, 2 for x, 1 for y. And we should see, what did I do wrong? Why am I not seeing any else output? Yeah. Exactly. You got to get into the habit after you change your code of recompiling it. Otherwise, the zeros and ones in the server are the old ones until you manually compile. So let's fix this. Make compare, enter. No error messages. That's good. /compare, 2, 1. and now I get back the output. So x is not less than y. How about if I go and add in the third condition? Well, we can do this either efficiently or inefficiently. Let me go ahead and refine this. So else if x is greater than y, let's literally say x is greater than y. And now I could do else if x equals y, but I think we already claimed that that's unnecessarily inefficient. So let's just have our catch-all. And here I'm going to say, quote unquote, x is equal to y backslash n, close quote there. So I think now with this code, we've handled all three scenarios. Let me go ahead and recompile it properly, make compare, /compare, and now 1 and 2, x is less than y. Let me run it again. 2 and 1. X is greater than y. And lastly, 1 and 1, and x is equal to y. So for the most part, our code's getting longer. We're up to like 21 lines of code, though some of them are just single characters on the screen. Almost everything else is the same. I'm using the CS50 libraries header file for my getInt function, standardIO.h for my printf function, and the rest of this is just now new syntax for conditionals as well. Questions then on this C implementation of just some basic comparisons like this? Any questions? Yeah? Good question. Do the opening brackets need to be on a separate line? In CS50, yes. What you'll see is that as part of the submission process, we compare your code against a style guide, which is the norm in industry. A company would have its own sense of style and how its code should look. And there's generally automated tools within a company that help give feedback on the code or stylize it as such. There are alternative styles than what we use in the class. We deliberately keep and ask that you keep the curly braces on their own line, if only because it rather resembles like the hugging nature of Scratch's blocks and just makes clear that they're balanced, open and closed. However, another common paradigm in some languages and with some programmers is to do something like this on each of them. So you have the opening curly brace on the same line as here. We do not recommend this. This is in vogue in the JavaScript world and some others. But ultimately, in the real world, it's up to each individual programmer and or the company they're working for, if applicable, to decide on those things. All right, so beyond then these conditionals, what if we want to do something that's maybe pretty common? So almost every piece of software or website nowadays that you use has you like agree to some terms and conditions by typing like yes or no, or just Y for yes and N for no. So how could we implement some kind of agreement system? Well, let me do this. Let me create a new program, a third one called agree.c. So I'm going to write code agree.c just to give myself a new tab. I'm going to start as always now, include cs50.h. Let's include standardIO.h. And then let me do my int main void, which again, for today's purposes, we'll take at face value is just copy paste. And if I just want to get y or n, for instance, instead of yes or no, we can just use a simpler variable here. How about just a char? A character, a single character. So I can use getChar to ask the user, for instance, do you agree ? But as before, I need to store this somewhere. So I don't want a string because it's a single char. I don't want an int. I just want a char. And it's literally char. And then I could call this thing anything I want. It's conventional. If you have a simple program with just a single variable and it's of type char, call it C. If it's an int, call it I. If it's a string, call it S. For now, I'm just going to keep it simple and call it C. And now I'm going to ask a question. So if C equals, how about quote unquote y, then let me go ahead and print out agreed \n as though they agreed to my terms and conditions. Otherwise, let's see, else if the character equals quote unquote n, then let me go ahead and print out, say, not agreed as though they didn't, quote unquote. And let's leave it at that, I think, here initially. Now, you'll notice one curiosity, one inconsistency, perhaps. Does anyone want to call it out, though it's somewhat subtle? I've done something ever so slightly differently without explaining it yet. Do you see it? Yeah, so I've suddenly used single quotation marks for my single characters and double quotes for my actual strings of text. This is a necessity in C. When you're dealing with strings, like strings of text, like someone's name, a sentence, a paragraph, anything really more than one character, you typically use double quotes, and indeed you must. When dealing with deliberately single characters, like I am here for y or n, you must use single quotes instead. Why? Because that makes sure that the computer knows that it's indeed a char and not a string. So double quotes are for strings, single quotes are for chars. So with that said, let me go ahead and zoom out. Let me go ahead in my terminal window, run make agree, enter. Seems to work OK, so let me go ahead and do /agree. Let me go ahead now and type in y. Here we go. Enter. Let me try that again. Rerun /agree. How about no? Enter. Why is it not behaving as I would have expected? Yeah, I kind of cheated there, and I hit the caps lock key just as I started typing in input. Why? Because I deliberately wanted to type in uppercase instead of lowercase, which is kind of reasonable. Right? It's a little obnoxious if you force the user to toggle their caps lock key on or off when you just need a simple answer. That's not the best user experience or UX, but it would work if I cooperated. Let me run this again without caps lock on. Y, lowercase for yes. That worked. N, lowercase for no. That worked. But how could I get it to work for both? Well, how about this? Let me go ahead and just add two possibilities. So else if c equals quote unquote capital Y, then also do printf agreed \n. And down here, else if c equals single quote capital N, then go ahead and print out again, not agreed. OK, this I will claim now is correct. And I'll do make agree real fast. /agree, and I'll use capital. It now works. I'll use capital. It again works. But this is perhaps not the best design. Let me hide the terminal window and pull this up on the screen all at once. Why might this arguably not be the best design, even though it's correct? There's another term of art we can toss here, like something smells kind of funky about this code. This is an actual term of art. Like there's code smell here. Like something smells a little off. Why? What do you think? Yeah, there's the same output again and again. I mean, I manually typed it, but honestly, I might as well have just copied and pasted most of my original code to do it again and again for the two capital letters. So if line 10 and 14 are the same, and line 18 and 22 are the same, and then the rest of these if and else ifs are almost the same, like there's some code smell there. Like it's not well designed. Why? Because if I want to change things now, just like last week in Scratch, I might have to change my code in multiple places, or copy paste is never a good thing. And God forbid I want to add support for yes and no as full words. It's really going to get long. So how can we solve this? Well, it turns out we can combine some of these thoughts. So let me try to improve the yeses first. It turns out if I delete that clause, I can actually OR things together. In Scratch, there's a couple puzzle pieces, if you didn't discover them, that literally have the word OR and the word AND on them, which allow you to combine Boolean expressions so that either this or this is true, or this and this is true. In C, you can't just say the word OR. You instead use two vertical bars. And vertical bars together mean or, logically. And so I can say C equals quote unquote capital Y, agreed. And now I can get rid of this code down here. And let me go ahead and say vertical bar twice C equals quote unquote N in all caps. And now my program's like, roughly a third smaller, which is good. There's less redundancy. And if I reopen my terminal window, rerun make of agree, /agree, now I can type little y or big Y, and same thing for lowercase and uppercase n. Any questions then on this syntax, whereby now you can combine thoughts and just kind of tighten things up? And there'll be other such tricks too. Yeah? A really good question. Is there not a function to just ignore the case? Short answer, there is, and we'll see how to do that in actually just about a week's time. And in other languages, there's even more ways to just canonicalize the user's input, throwing away any space characters they might have accidentally hit, forcing everything to lowercase. In C, it's going to be a little more work on our part to do that. But in fact, as early as next week, we'll see how we can do that. But for now, we're comparing, indeed, just these literal values. Other questions?
So we're assuming the user's going to put in what they're supposed to. How do you handle if they were to put in a number?
Really good question. So we are assuming with this program and all of my last ones that the human's cooperating. When I asked for their name, they typed in David and not 1, 2, 3. Or in this case, they typed in a single character and not a full word. So this is one of the features often of using a library. So for instance, if I run agree again and I say something like sure, enter, it rejects it altogether. Why? Because SURE is a string of characters. It's not a single character. Now, I could just say something like X, which is neither Y nor N, of course, but it tolerates that because it's a single character. But built into CS50's library is some built-in rejections of inputs that's not expected. So if you use getInt and the user types in not the number 1 or 2, but cat, C-A-T, it will just prompt them again. And this is where, too, if you were to do this manually in C, you end up writing this much code just to check for all of these errors. That's why we use these training wheels for a few weeks, just to make the code more robust. But in a few weeks' time, we'll take the library away, and you'll see and understand how it's indeed doing all that. All right, so how about this? Let's now transition to something a little more Scratch-like literally by creating, how about another program here called meow, so meow.c. We won't have any audio capabilities for this one. We'll just rely on print. And suppose that I wanted to write a program in C that just simulates like a cat meowing. So I don't need any user input just yet, so I'm just going to use standard io.h. I'm going to do my usual int main void up here. And then I'm just going to go ahead and do printf meow \n. And let's have this cat meow 3 times like last week. So I'm going to do meow, meow, meow. Notice as an aside, whenever you highlight the lines, you'll see little dots appear. This is just a visual cue to you to let you figure out how many spaces you've indented. VS Code, like a lot of editors, will automatically indent your code for you. I've not been hitting the spacebar 4 times every time. I've not even been hitting tab. However, in C, the convention is indeed to indent lines, where appropriate, by 4 spaces. So not 3, not 5. And these dots help you see things so that they just line up as a matter of good style. All right, so this program, I'm just going to stipulate right now, is indeed going to work. Make meow, which is kind of cute. And now meow, there, 3 times. Correct. It's meowing 3 times. But of course, this is not well designed. It wasn't well designed in Scratch last week. Why? What should I be doing differently? Yeah. Yeah. It's a perfect opportunity for a loop. Why? Because if you wanted to change maybe the capitalization of these words, or you wanted to change the sound to like woof for a dog or something, like you'd have to change it 1, 2, 3 places. And that's just kind of stupid, right? In code, you should ideally change things in one place. So how might I do that? Well, we could introduce a loop, yes, but we're going to need another building block as well that we had in Scratch, namely those things called variables. So recall that a variable, like in algebra, x, y, z, whatever, can store a value for you. And a variable in Scratch might have looked like this. You use this orange puzzle piece to set a variable of any name, not just x, y, or z, but you could call it something more descriptive like counter, and you can set it equal to some value. In C, the way to do this is similar to some of the syntax we've seen thus far. You start by saying the name of the variable you want, a single equal sign, and then the value you want to initialize it to. Copying, therefore, from right to left. Why? Because the equal sign denotes, again, assignment from right to left. This isn't enough, though. You might have the intuition already. What's missing, probably, from this line of code just to create a variable? So we need int to make sure the computer knows that this is indeed an int. And then lastly, semicolon as well. And that now completes the thought. So a little more annoying than Scratch, but we're starting to see patterns here. So not every piece of syntax will be new. All right, if you wanted to increment the counter by 1, Scratch uses the verb change, and they mean add the value to counter. So if I want to increment an existing variable called counter, this syntax is a little more interesting. It turns out the code looks like this, which almost seems like a paradox, like how can counter equal counter plus 1? Like that's not how math works. But again, a single equal sign is assignment from right to left. So this is saying take whatever the value of counter is, add 1 to it, and copy that value from right to left into counter itself. You still need the semicolon, but I claim you do not need to mention the keyword int when updating an existing variable. So only when you create a variable in C do you use the word string or the word int or any of the others we'll eventually see. Only when creating it or initializing it for the first time. Thereafter, if you want to change it, it just exists. It's the word you gave it. The computer's smart enough to at least remember what type it is. So this line is now complete. Turns out in code, as we'll see, it's pretty common to want to add things together, increment things by 1. So there's actually different syntax for the same idea. The term of art here is syntactic sugar. Like there's often in code many ways to do the same thing, even though at the end of the day they do exactly the same functionality. So for instance, if after a few days of CS50 you find this a little tedious to keep typing in some program, you can simplify it to just this. This is the syntactic sugar. You can use plus equals and only mention the variable name once on the left, and it just knows that that means the previous thing. It's just slightly more succinct. This, too, is such a common thing to add 1 to a value. And it doesn't have to be 1, but in this case it is. But if it is indeed 1, you can further tighten the code up to just do this, counter plus plus. So anytime in C you see plus plus, it means literally adding 1 to that particular variable. There's other ways to do this in the other direction. If you want to subtract 1 from a variable, you can use any of the previous syntax using a minus sign instead of plus, or you can more succinctly do counter minus minus. This is the way a typical C programmer would do this. All right, so if we have now variables, let's go and solve the meowing with loops. So in Scratch, we saw loops like this. This, of course, had the cat meow 3 times. How do we do this in C? Now, this is where things get a little more involved code-wise, but if you understand each and every line, it will follow logically what's going on. So here I claim is one way to implement a loop that iterates 3 times in C. And this is kind of ridiculous, right? Like we went from 2 super simple puzzle pieces like this to, my God, like it's 1, 2, 3, 4, 5, 6 lines of code, all of which are pretty involved. So like that escalated quickly. But what's each line doing? And we'll see other ways to do this more simply. So we're initializing a variable called counter to 3, just like before. Why? Well, what does it mean to loop or to repeat something 3 times? Well, it's kind of like doing something 3 times and then do it, and then count down, and then do it, and then count down, and then do it until you're all out of counts. So this is declaring a variable called counter, setting it equal to 3. Then I'm inducing a loop in C, which is similar in spirit to repeat 3, but you have to do more of the math yourself. So I'm asking the question in parentheses, while counter is greater than 0. What do I want to do? Well, per the indentation inside the curly braces, I want to meow 1 time. And then to be clear, what's this last line of code doing? If counter starts off at 3, this makes it 2 by subtracting 1 from it. Then what happens? By nature of a loop, just like in Scratch, it kind of knows to go back and forth, even though there's a nice pretty arrow in Scratch and there isn't here. C knows to do this again and again and again, constantly asking this question and then updating this value at the end. So if I highlight just a few of these steps, the variable starts off at 3. And actually, let me simplify 2. I claimed earlier that when using single variables, people very often just call it I for int or C for char or S for string, unless you have multiple variables. So let me tighten the code up. And this already makes it look a little more tolerable. Let me actually tighten it up further and one more step. So now this is about as tight, as succinct as you can make this code at the moment. So what's actually going to happen here? Well, the first line of code executes, and that initializes I to 3. Then we check the condition. While I is greater than 0. Is I greater than 0? Well, per my 3 fingers, obviously. So we print out meow on the screen. Then we subtract 1 from I, at which point now we have 2 as the value of I. Then the code goes back to the condition. And notice the condition there is in parentheses. That's another Boolean expression. So loops can use Boolean expressions, just like conditionals use Boolean expressions to make decisions. The loop, though, is deciding not whether to do this thing or that, but whether to do the same thing again and again and again. And as it ticks through the code one line after the other, it's ultimately going to get down to 1 and then 0 and then stop. So put another way, came with some props here. So suppose this ball here is your variable, and you initialize it to 3 with like 3 stress balls. You can do something 3 times, right? If I want to give out 3 stress balls, here's your chance for free stress balls without having to answer any questions. OK, there we go. So here we go. Subtracting 1 from my variable. I'm left with 2. Oh, my God. All right. Don't tell Sanders. Oh, I'm sorry. Oh, OK. That ended poorly. Apologies. All right, but now the educational point, though, is that my variable has been decremented further to just have. I'm not throwing that far again. I can't do this Here we go. All right, here we go. And one final subtraction, and now our variable is left empty. So we have 3 stress balls there, and that's all a variable is, right? It's some kind of storage. It's actually, of course, implemented in the computer's memory, but metaphorically, it's really just like a bowl with some values, and every time you add, or in this case subtract, you're just changing the value of that variable. And then the code, meanwhile, of course, in parentheses, is just checking, is the bowl empty? Is the bowl empty? Is the bowl empty? AKA, is I greater than 0 or not? Any questions on how we've implemented loops in this way? And I owe you a stress ball after class. Questions on loops? All right, so it turns out this is kind of ugly. And like this really starts to take the fun out of programming when you have to like write out this sequence of steps. So it turns out there's other ways to do this. But first, let's see logically how else you might express this, because it's a little weird that we keep using 0. So the one other way to do this would be to invert the logic. You could absolutely start with your variable, call it I, equal to 1. And then you could ask the question, is I less than or equal to 3? And notice a bit of new syntax here. On your typical keyboard, there is no less than or equal sign or greater than or equal sign like you would write in math class with one over the other. And so in C, you use 2 characters, less than followed by an equal sign, or if appropriate, greater than followed by an equal sign. And that logically captures that idea. So notice that I'm kind of changing my questions. I'm initializing I to 1, and then I'm going to increment it ultimately to 2, and then 3. But because I'm doing less than or equal to, it's still going to go from 1 to 3. So that works too. We could similarly do this yet another way. We could initialize I to 0, and then we could say, well, I is less than 3 and keep incrementing it. And I showed this last form is actually the most canonical. Like it might be the most human-like to think in terms of 1 to 3. It might be the most stress ball-like to think in terms of 3 to 0, counting down. But typically, the go-to syntax for most programmers, once you get comfortable counting from 0, is to always start counting from 0 and count up to less than the value you're counting up to. So it would be incorrect Y to change this to less than or equal to 3 here. What would happen if I changed the less than to less than or equal to? Yeah, it'll meow a fourth time, in fact, total, right? Because you'll start at 0, then 1, then 2, then 3. And less than or equal to 3, sorry, 3 will give you the 4th time. So we do want it indeed to be just a single less than. All right, so now that we have those options, let me just give you one other. And this one takes a little more getting used to as well, but it's probably the more common way to write this. Let me go ahead and propose that we implement this as follows. Let me go back to my code here. Let me go into my several printfs, getting rid of all but one of them ultimately. And let's implement this in code. So let's do int I gets 0. How about then while I is less than 3. Then let's go ahead and say printf, quote unquote, meow, mellow, meow, \n. And then we have to do I minus minus or plus plus? So plus plus, because we're starting at 0 and going up 2, but not through 3. So let me go ahead now and make meow after clearing my terminal, /meow. And it's still just as correct, but it's a little more, it's a little better designed. Why? Because now if I want to change it from 3 to 30 times, for instance, I can change it there. I can recompile my code. I can do /meow and done. I don't have to copy and paste it 27 more times to get that effect. And I can even change what the word is by changing it in just one location. But it turns out there's other ways to do this too. And let me propose that we introduce you to what's called a for loop as well. So if you want to repeat something 3 times, you can absolutely take the while loop approach that we just saw. Or you can do this. And this one's takes a little more getting used to, but it kind of consolidates into one line all of the same logic. So notice we have the keyword for here. And for is just a preposition in this case that generally implies here comes a loop. Inside of parentheses here is not just a Boolean expression. And this is where things get a little weird. There's 3 things. To the left of the semicolon, in the middle of the 2 semicolons, and to the right of the semicolon. This is really the only other context we'll see semicolons, and it's weird. Normally it's been at the end of the line. Now it's 2 of them in the middle of the line, but this is the way humans decided years ago to do it. So what is this doing? Almost the same thing. It is going to initialize a variable called I to 0. It's going to then check if it's less than 3. It's then going to do whatever in the curly braces, and it's lastly going to increment I and repeat. So just highlighting those in turn, at first, I is initialized to 0, just like before. Then this condition is checked. This is a Boolean expression. Yes or no, true or false will be its answer. And if I is less than 3, which it should be once it starts at 0, well, then we're going to go ahead and print out meow. Then I is going to get incremented. So it starts at 0. It goes now to 1. At that point, the Boolean expression is checked again. So you don't keep changing I back to 0. That first step happens only once. But now you repeat through those 3 other highlights. I check if I is less than 3. It is. So I print out meow. It then increments I. I check if I, now 2, is less than 3. It is. I print out meow. I gets incremented. I now check. Is I less than 3? No, it's not, because 3 is not less than 3. And so the whole thing stops. And whatever code is below this curly brace, if any, starts executing instead. Just like in Scratch, you break out of the loop and the puzzle pieces being hugged. Questions then about this alternative syntax for loops, aka a for loop. Sorry, say again? Yeah, can I explain again why it doesn't reset to 0? Honestly, just because. Like, this was the syntax they chose. This first part before the first semicolon is only executed once, just because. That's how it's designed. Everything else cycles again and again. And this is just an alternative syntax to using the slightly more lines of code. It was like 6 lines of code using the while loop. Logically, it's the same thing. Programmers, once they get more comfortable, tend to prefer this because it just expresses all your same thoughts more succinctly. That's all. Yeah. OK, so let's just work this into my meow example. Let me go back to the code here. And notice, indeed, if I highlight all these lines, I think we can tighten this up. Let me get rid of all of those and instead do for int I equals 0. And I'm saying equals. Most programmers would say gets. So int I gets 0 means assignment. The word get. Now I'm going to do I is less than 3, I plus plus. Now in here, I'm going to do my printf, quote unquote, meow backslash n. And so it's indeed a little tighter. I mean, 2 of the lines are just curly braces. There's really only 2 juicy lines of code now. Let me go ahead and do make meow dot slash meow. And again, we're back in business with 3 of them printing only. All right, there's one last structure we should explore just because it's sometimes useful. This was a forever block. And this would be a little weird in Scratch to just say meow forever, at least without waiting. But there is indeed a forever block in Scratch, which means do the following forever. And I proposed, I think verbally last week, at least one example where this is useful. Meowing forever, a little annoying. But can you think of common cases where you might want to write code or use a program that loops forever? Yeah. Yeah, playing music, like a Spotify playlist, just repeating again and again would be some kind of loop. Checking for collisions in Scratch. So seeing if something's bouncing off the wall or another sprite. Yeah. Checking for input. So yeah, get string is essentially just waiting there forever for me to type in some input until I do. Checking the time and actually maintaining like human time, like a wall clock behind you. Was that the same? OK, checking the time. And one more. Detecting a key press, too, like in Scratch, just waiting for some kind of event to happen, just like on a phone or a browser. And so there's so many examples where you might want to do something forever, just so you've seen the corresponding C building block. It's a little weird, but this is probably the most canonical way to do it in C. If you want to print meow forever, which would be a little crazy because it would literally print and take over your computer, printing forever meow, you would generally do it like this. Why? Well, a while loop expects in parentheses a Boolean expression. And a Boolean expression is, again, a yes-no, a true-false question. But if you want the answer to that question always to be yes, or really always to be true, turns out in C, in a lot of languages, we'll then just say true. Because true, T-R-U-E, is never going to change magically to false. I mean, it's just a special word in the programming language. So by saying while true, it just means do the following forever. Another common paradigm before true and false became commonplace would be to do this instead. Change while one. You might see in online examples and texts and the like. While one is really the same thing. Any value that is 0 is generally interpreted as false by a computer. Any value that is 1 or any other non-zero value is generally interpreted as true. And so this too would have the same effect, saying while true or while 1. Generally speaking, while true is perhaps a little clearer these days. Now, meowing forever is not a good thing, but suppose I did that by intent or by accident. Well, let's try this. So here I'll go into my code. I'm going to get rid of my for loop and change my while loop to how about true. And in this case here, well, we'll keep it. Let's do this. Make meow, enter, and you'll see this. Use of undeclared identifier true. This is actually hinting at my mention that the old way was 0 and 1. Nowadays, you could say true or false. But true and false are themselves special words that you have to include. And it turns out if you want to use special Boolean values like this, there's another header file we haven't seen called standard bool that essentially creates true and false as keywords. Alternatively, CS50 includes that same file, so it's more common in CS50 to see it like this. Now, if I clear my terminal window and do make meow and then /meow and hit enter, well, unfortunately, this isn't the best thing to do infinitely when you're in the cloud using a browser. This is indeed browser, just full screened here. This means I'm sending millions of meows over the internet to my computer here. So this will happen to you at some point. Probably not with meow, but you'll lose control over your terminal window. Why? Because you screwed up and like you have an infinite loop. You didn't really intend it, or maybe you did. You were curious to see what happens. What do? Like when does the meowing stop? What recourse do we have here? All right, well, Control-C will be your friend. Sometimes you have to hit it a bunch in a cloud environment, but Control-C for cancel will interrupt a program that's running. And I promise that almost all of you will at some point accidentally introduce an infinite loop because your math is slightly off. When in doubt, click in the terminal window and hit Control-C, sometimes multiple times, and that will indeed cancel whatever is happening there. In this case, I might have intended it, but sometimes it's not, in fact, intended. All right, so we've been taking for granted this whole graphical user interface for some time. And indeed, the commands that I'm typing and the buttons that I'm clicking. And let me just give you a better sense of what it is we are using underneath the hood this whole time, namely an operating system called Linux. So I keep alluding verbally, of course, to Macs and PCs, because almost all of us are running Mac OS or Windows on our desktops or laptops nowadays. But there's lots of other operating systems out there. And one of the most popular one is called Linux. And Linux is very often used on servers nowadays, companies that host email, companies that host websites or apps more generally. Certain computer scientists or computer science students often like to brag that they run Linux just because that's a thing. But it is really just an alternative to Mac OS or Windows that provides you with both a GUI, if you want it, but also and especially a command line environment. Now, fun fact, Windows and Mac OS do have terminal windows or the equivalent thereof. And eventually, you might use it on your own Mac or PC to solve some problem. But Linux is really known for, along with other operating systems, its command line environment, which again I distinguished earlier from GUI as a command line interface or CLI. And that refers really to the terminal window. So if I go back to VS Code here, and let me, in fact, go ahead and close my tab and focus entirely on the terminal window. This terminal window is really just your command line interface to your very own server in the cloud. The term of art here is you each will have your own container in the cloud, which is like your own computer running somewhere on the internet with your own username and password to which you have access, and your own hard drive, if you will, your own home folder that has all of your files for the class, and it's only accessible to you unless you enable live sharing thereof. So when you're typing commands here, it looks like you're typing them, of course, on your own Mac or PC, but they're actually being sent over the browser to some server in the cloud where you are controlling really your own account therein. So it turns out that there are other commands that are worth knowing. And we'll give you just a few of these today. And over the coming weeks, we'll have opportunities to play with others as well. But these are kind of some of the basics. And they're all incredibly succinct. Because indeed, for things you're typing at the command line, humans generally have not wanted to type out long commands. So a lot of these are abbreviations here. Now, perhaps the most common one I'll start with first is ls, a lowercase l and a lowercase s. That stands for, succinctly, list. So if I go to my terminal window now, where up until now I've only typed code, which is a VS Code thing for creating and opening files, and make, which triggers the compilation of my code, what if I now type ls? This will list all of the files in my current folder, my hard drive in the cloud, if you will. So if I hit enter, you'll see a whole bunch of results. Now, they're color-coded too. The white ones here end in .c. Those are the source code files I've written during class today. Agree.c, compare.c, hello.c, and meow.c. And you can perhaps guess the green ones here that just by convention have an asterisk on the end to denote that they're special represent what? What are the 4 others? Yeah. Yeah. The machine code. So those are my actual programs that are identically named minus the .c extension. And the asterisk means that they're executable. That is, in the world of Mac OS or Windows, you would double click. But in the world of a command line environment, that means you do // and then the name without the asterisk to execute or run the code therein. So if I open up my File Explorer, and I'm hitting Command B on my computer here just as a keyboard shortcut, you'll see the exact same thing. So ls is the command line interface for listing the files in your account. But here, because I'm using VS Code or any program like it, I also get a graphical user interface as well. So it's just 2 different places to be. You're welcome to use whatever you're comfortable with, but over time, will you naturally get more comfortable and capable with the terminal window alone? Well, what else is on this list here? Well, during the break, I saw that at least one of you, for instance, had created a file called hello instead of hello.c. So you were in a situation where you did this accidentally and hit enter, and then you went ahead and typed in all of your code like this, and then down in your terminal window, you were trying to do make hello, enter. And this now didn't actually do anything. Like I'm trying to run the command. I got permission denied, as at least one of you did. Now, why is that? Well, let's just do a quick check. If I do ls, I see now hello, but hello has no asterisk next to it, which means it's not executable. That's my code. Why? Well, notice the top of my tab confirms, oh, I screwed up. I didn't name my file hello.c, which it just has to be. So what do? Well, you could very hackishly like copy this, create a new file, paste it in, or no. Like we know how to rename things now here, because that's one of our options. Let me do this. Let me do mv for move, hello, and then hello.c, and hit enter. You'll see the tab closes because hello no longer exists. But if I now type ls, you'll see, there is hello.c. And if I open that file now, there's all of my same code. And now if I do make hello, now I do get an executable file wherein the world is restored. So mv is just a command not just for renaming, but it also turns out eventually for moving files as well. You can also create directories or folders. So for instance, if I go into VS Code again, and suppose I hover over here and click not on the plus file icon, but plus folder, I can create a folder called, for instance, like pset1 for problem set 1 in the class. And you'll see now that it's empty because all of my other files are in the default folder of my account. But I could also go in there like this, and I could click on File, and now I can create a new file called like mario.c, which is one of the first problems, for instance. But you'll notice now that mario.c is inside of the pset1 folder. So if I zoom out and I type ls at my terminal window, I won't see mario.c anywhere. But I do see a pset1 folder. And it's in light blue followed by a /, which you don't have to type. It just indicates that's a folder. Now, I can visually at top left obviously see pset1 contains mario.c. But if I try to do something like make Mario here, no rule to make target Mario, like it just doesn't seem to exist. And that's because you're in the wrong directory. So in a command line interface, it's not quite as simple as just clicking on a folder and voila, it opens. You have to change into the directory or folder, and cd is going to be the command there. So if I want to actually change into that directory, I can do cd space pset1, enter, and now you'll see my prompt changes. And this is just a common convention, but it's not the only one out there. Now I still have a $, which indicates where I can type commands. But before it, I see a reminder constantly what folder I'm in. And we put that there deliberately, like a lot of Linux users do, just to remind themselves where they are. Because unlike Mac OS or Windows, where you have a nice big window telling you where you are, at the command line, you kind of need to be reminded textually. But now if I type ls and hit enter, what should I see? Yeah, Mario.c. And now if I want to open it, if I want to actually compile it, I can run make Mario in this directory once I actually type out all of the code. Rest assured that in problem sets and labs will almost always, certainly in the first weeks of the class, give you exactly the commands to type. Odds are, because it's new to many of you, you will accidentally type the wrong commands. No big deal. Just remember that you have different ways to solve these problems. You've got like the graphical file explorer, which should feel a little more familiar. But in time, you'll start to know and honestly probably prefer commands like these. So cd for change directory, cp for copy a file, ls for list, mkdir to make a directory, create a new folder at the command line instead of with the button, mv for move or rename, rm for remove. So be careful with that one. rmdir, remove directory. And there's dozens, hundreds of other commands. You won't need many of them, but we'll start to scratch the surface all the more over time. But ultimately, this command line interface is going to be a more powerful mechanism, a more capable mechanism, and ultimately a more efficient mechanism for writing code, running commands, solving problems, analyzing data more generally, even though, no, there's going to be some growing pains early on, just because it's probably so new for many of you. So with that said, we have some problems still to solve, but we promised cookies today. So let's go ahead and take a 10-minute break. Cookies are now served in the transept, and we'll be back here in 10. All right, we are back. And up until now, each of the code examples in C we've done have been kind of designed to show one specific topic. But we thought we'd try to take a step back and solve a more general problem and give you a sense of when, given a problem set, for instance, or just a programming problem more generally, like where you even begin and how you go about approaching it when it's not obvious what the point of the exercise is. So one of my favorite games from yesteryear is this one here, Super Mario Brothers, that has come in so many different forms since. But in this original two-dimensional side-scroller game, there was a lot of artwork like this. So for instance, up here in the sky were 4 question marks. And we'll find that in C and a lot of programming languages initially, it's a lot easier, a lot more accessible to focus really on black and white type interactive programs textually as opposed to full-fledged graphics and the like, but more on the more graphical acoustic type of programs before long. But for now, let me go over and propose that we try to just implement in ASCII art. ASCII, again, being the code that maps numbers to letters, at least for English, into a textual version of these 4 question marks in the sky. So for this, let me go over to VS Code. I'll create my own version of Mario.c that will be different from the one you're challenged with in problem set 1. Indeed, in problem set 1, you'll be challenged to build a little something like this, albeit with hashtags for ASCII art instead of graphics. And in Mario.c, I want to just solve this simple problem first. So it's all involving output. So I'll do include standard.io.h so I can use printf. I'll do my int main void, more on why we keep doing that in future weeks. And I'm just going to do something simple initially like 1, 2, 3, 4 \n. This is about the simplest way I can implement 4 question marks in the sky like these here using pure text like this. So let me go ahead and do make Mario. /Mario, and voila, we have those 4 question marks. But we've seen, of course, that there are better ways to do this. And if you wanted to generalize this to be 5 question marks, 6, 60 different question marks, you know, loop was always the answer for not repeating ourselves. So maybe I should rewrite this a little bit more flexibly and say something like this. For int I gets 0, I less than 4, I plus plus, and then inside of the for loop, now I can just do a single question mark. But I don't think what I've just done is correct. Anyone spot the aesthetic bug already? Yeah, why is this wrong? If I want to print the same thing, yeah. Yeah, so I don't think I want a \n after every question mark, because the goal is, again, this like row of question marks in the sky. So if I now recompile this, make Mario, /Mario, OK, it's almost there, but now I have that regression to where the $sign's not on its own line. So I think I need a new line, but I don't think I want it here, because that was not going to end well. Where do I want it instead? Any instinct? Yeah. Yeah, so outside the for loop. So indeed, I can just go below line 8 and above line 9, creating a new one. And now it's totally fine to just print a new line like that. You don't have to print anything else with it. It's indeed a character unto itself. So let's do make Mario one last time, /Mario. OK, so now we're back in business there. Well, what if we wanted to do some other scene from Mario, such as this one here, where there's a lot of vertical obstacles like these bricks here? If I wanted to print out now a column of 3 bricks, and I'll use hashtags for these instead of anything graphical, well, I think we're almost there, right? Like, I think I can now, it's almost maybe a little easier. I can go back here, change the question mark to something that looks more like a brick, like this hash symbol. And I think now I do want the new line character, because when I now do make Mario /Mario, OK, there's my wall of 4. Oh, but wait, I didn't want 4. I wanted to be consistent just with this particular scene here, so I just want 3. So I can still change it in one place. And here again is that paradigm. Even whether you're using 4 or 3, if you get into the habit of starting counting from 0, you go on up to, but not through the value you want to count up to. So that's why I'm using less than instead of less than or equals to there. So this would be the common paradigm, though you could certainly count it like we saw earlier in different ways. But what if things escalate one level further? And when you're in the underground version of Super Mario Brothers, there's a lot of these underground obstructions, including like grids of bricks like this. And let me conjecture that if you slice this up, it's roughly a 3 by 3 grid of bricks that all interlock prettily to give us just one big, large brick like this. So if I want to print out a 3 by 3 grid, now things are getting a little more interesting, because up until now, I've printed either one row horizontally or one column vertically, but we haven't really seen any code where I'm sort of printing or living in 2 different dimensions like the game would imply. But let me propose that we could do this. Let me go ahead and say, all right, suppose I want to print a 3 by 3 grid of bricks. It's really that I want to print, what, 3 rows of bricks. Like a grid is 3 rows. So if I take the high level idea and reduce it to something a little simpler, how do I do that? Well, let me get rid of the printf for a moment, as I did. And let me just stipulate that this for loop, even though it doesn't do anything useful yet, will do something how many times, just by design? All right, 3 times. All right, this for loop is good to go. It will do something 3 times by just using I to do the counting. All right, well, if I want to print out now a row of 3 bricks all on the same line, that's pretty similar to what we did earlier when I just wanted to print out 4 question marks in the sky. So we've kind of seen a solution there, and I dare say we can compose one into the other. So if I want to print out a row of bricks, I could just do this. For int I gets 0, I less than 3, I plus plus, and then inside of this inner loop, if you will, let me print out a single brick like this. And then I don't like where this is going yet, but I think I've taken 2 ideas and I've combined them. But what might be problematic about lines 5 and 7 at the moment? What might be bad here? Yeah, and back? Yeah, I'm using the same integer I, which I feel like could get me into trouble, right? If I'm sort of trying to count 3 things here, but then I'm hijacking this variable and using it inside of the loop, like I feel like I should avoid this collision of names. And so what's a good alternative to I? Well, a programmer, if nesting loops in this way, would pretty commonly go with J. You could certainly change this to be like rows and columns if you want more descriptive variables, but I and J is pretty canonical. So I'm going to go ahead and do this, J++ instead of I++ everywhere. And let me try compiling this. So make Mario, enter, /Mario. OK, so a couple of things are wrong here. This is not a 3 by 3 grid. But if you count these things, how many did I indeed print at least? You can probably just guess logically. Yeah, there's 9 hashes there. Unfortunately, they're all on the same line instead of on 3 different lines. So where logically can I fix this? I'm definitely printing all the bricks. They're just not on the right levels. Yeah? Yeah, so put a new line after the first loop, this inner loop, if you will, the nested loop, if you will. So let me go ahead and print out just a \n here. And what's this doing? Well, I think that's going to solve it by just moving the cursor to the next line after you've done 1 row. So let me go ahead and do make Mario, enter, Mario, and now we're in business. So it's a very simplistic version of this same graphic, but I'm leveraging two different ideas now, the same idea twice rather now. I'm using one loop to kind of control my cursor going row by row by row, but then within that loop, I'm doing left to right, dot, 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 with printing out each of these individual bricks like this. Now, there's a little sloppiness here still. Like if I want this to always be a square, just because that's what it looks like in the game, well, I could change it to be a 4 by 4 square by doing this, or a 5 by 5 grid, whoops, by doing this. Why is this perhaps not the best design, to just keep changing the numbers when I want to change the size? Where could this go awry? Yeah. Yeah, if it's always going to be a square and height is going to be the same as width, I'm just inviting trouble here, right? Eventually, I'm going to screw up. I'm going to change one but not the other. Then it's going to come out to be a rectangle instead of a proper square. So I should probably solve this a little differently. So let me do that. At the top of my main function here, let me go ahead and give myself a variable called maybe n for the number of bricks I want horizontally and vertically. And I'll just initialize that to 3 initially. And instead of putting 3 here, I'll literally just use n. But I'll do it in both places so that now, henceforth, if I ever want to change this and change it to 4 or 5 or anything else, like I'm all done. Like it's better designed because there's a lower probability of mistakes. But I could technically still screw up somehow. I could technically accidentally write a line of code like n++, or, I could just change the value of that variable even though I don't want it to ever change. And maybe it's because I'm a bad programmer. I copy-pasted wrong. I'm working with someone who doesn't know what n represents. I can defend myself and my code against human error like that by going up here to line 5. And instead of just declaring a simple variable like we did in Scratch, I can further harden my code, so to speak, by declaring it to be a constant using the keyword const. Now, this is just a feature of C and some other languages to protect you against yourself by proactively saying n is a constant. Specifically the number 5 or previously the number 3, you cannot accidentally write code elsewhere that changes it. The computer will throw an error and catch that error. So it's just a way of programming a little more defensively. Some languages have this, some languages don't. But in general, it's a good practice. It makes your code better designed because it just is less vulnerable to mistakes by you, colleagues, or anyone else using the code. So let me change this back to 3 just to be our default. But now I'm using n in both places. And if I do make Mario, ./Mario, we're back to where we originally started. But the code's a little more better designed. And let me note this too. All this time, I've been mentioning that there's correctness is important, design is important. There was also this matter of style. I've been very deliberately writing pretty code, if you will, not just the syntax highlighting, which is automatic, but notice that I keep indenting everything nicely. Anytime I have curly braces, like on lines 4 and 14, everything is indented one level. When I have additional curly braces on lines 7 and 13, everything is nicely indented as well. Technically speaking, the computer does not care about that kind of white space, so to speak. And you could really make a mess of things like this because you have a strange sense of style or just because you're being a little sloppy. But this code is actually still correct. If I recompile it, let me open up my terminal window, make Mario. No errors, ./Mario, it works perfectly fine. But you can imagine just how annoying this now is to read, like certainly for a TA, but certainly for you the next day, certainly for a colleague who has to read your code. This is just bad style. Like it still works, and it's well designed in that like you're writing code defensively, you're using a constant, but my God, the style is atrocious. Now, you'll often find that there's tools that can help you format your code for you in a manner consistent with the course's or a company's style, but this is the kind of muscle memory you'll want to develop over time too. Take VS Code suggestions as it's outputting lines of code for you because it's trying to format your code in a readable way. And oh my God, if and when you do have bugs in your code and things aren't even indented properly, there's no way you, the human, are going to be able to wrap your mind around what's happening and where. Like you're just making the problem harder for yourself. So do get into this habit too of manifesting good style as well. All right, well, let me propose that we don't only want a 3 by 3 grid. We want this to be a little more dynamic. So suppose we moved away from a constant to just using an integer called n. And let's ask the user for the size of this grid as by prompting them with getInt as we've done before. And I'll store it in n here. And then I can go ahead and more dynamically run make Mario to compile it. Whoops. Oh, I screwed up accidentally. What is it suggesting I do, albeit cryptically? Yeah, I forgot to include the CS50 header file up top, and that's why it doesn't know that getInt is in fact valid. So that's an easy fix. I'm just going to go up here and include cs50.h. Now I'm going to clear my terminal and rerun make Mario. Now we're good. /Mario. And now notice I'm prompted for size. So if I type in 3, it's the same as before. If I type in 10, it's even bigger. But it happens all now automatically. But there are some things that we're not detecting. For instance, suppose I type in cat. Well, that's handled by the getInt function, as I claimed earlier. That's one of the features of using a library. You don't have to deal with erroneous input. But we only designed a function called getInt to get you an integer. We don't know if you want it to be positive, negative, 0, or some combination thereof. And it's kind of weird to allow the user to type in like -1 for the size of the grid, or -3 for the size of the grid. And indeed, your code does nothing. So at least it's not crashing. But that's kind of stupid, right? Like, it'd be nice to force the user, if they want a grid, to give us a positive value. So how could we do this? Well, I could go up here, and I could say something like if n is less than 1, so if it's 0 or negative, which I don't want, what could I do? Well, I could say, well, prompt the user again for the size. And now notice, I'm not declaring n again, because once it exists, you don't have to mention the data type again. We said that earlier. But this is kind of stupid. Why? Because now when you've given the user a second chance, OK, now maybe I'll do, all right, if this version of n is less than 1, well, let's just go and prompt the user a third time. I mean, you can kind of see where this is stupidly going. Like, this can't be the right solution, to keep typing recursively the same thing again and again. Like, where would it stop? You'd have to give them a finite number of chances, or just make a mess of your code. So what would be intuitively a better solution here? Yeah, so some kind of loop. We've seen a while loop. We've seen a for loop. So maybe one of those. So let me try this. Let me delete this messiness and just go back to the first question. And let me do this. So while n is less than 1, so while the number is not what we want, let's just prompt the user in a loop this time for the size again. Now here too, this is better, because it's only 2 requests for information. But clearly, lines 6 and 9 are pretty much identical, other than the int. And if I went in and changed the size, if I add this, if I change the wording here, change it to a different language, like I have to change it in 2 places. That's bad. Copy, paste, bad. So what might be better? Well, it turns out there's another paradigm in C that you can use that gets around this problem, this duplication of code. It would be much nicer if I just write this code once. And I can do that using a third type of loop called a do-while loop. So it turns out in C, you can do this. If you want to get the value of a variable, like n, first just to create the variable without an initial value. So int n semicolon means we don't know what value it has, yes, but that's OK. We're going to add a value to it eventually. Then I'm going to say this, do, literally. I'm going to open my curly braces. And what do I want to do? I want to assign to n the return value of getInt, prompting the user for size. Well, when do you want to do that? I want to do that while n is less than 1. And this code now achieves the exact same goal, but by never repeating myself. Why? Well, notice on these lines of code now, I'm literally saying, on line 6, give me a variable called n of type integer. It doesn't have a value initially, but that's fine. You can do that. Line 7 says, do the following. What do you want to do? GetInt, prompting the user with the word size, and just store that value in n. But because C code runs top to bottom, left to right, now it's reasonable on line 11 to ask that question, OK, is the current value of n, which it definitely got on line 8, less than 1? And if the user didn't cooperate, they typed in 0 or -1 or -3, what's going to happen? It's going to go back up here and repeat, 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 everything in the do-while loop. So a do-while loop in C, which is not something some other languages have, like Python, if you know it, does not have a do-while loop. This is perhaps the cleanest way to achieve this, even though it's a little weird that you have to declare your variable, create your variable up top, and then check it down below. But otherwise, it's similar to a while loop. It just flips the order in which you're asking the question. Any questions on this construct? And do-while in general is super useful when you want to get input from the user and make sure it meets certain requirements. All right, so now that we have this building block after that interlude, how can I go about cleaning up this code? And then let's conclude by taking a look at things that our code can't do or can't do very well or correctly. Let me propose that in a final version of Mario, let me just add what are called now some comments. So it turns out in code in C, you can define what are called comments, which are just notes to self. Some of you discovered these in Scratch. There's little yellow sticky notes you can use to add citations or explanations. In C, there's a couple of ways to write comments. And in general, comments are notes for yourself, for your TA, for your colleague, as to what your code is doing and why or how. It's a little explanatory note in English or whatever your human language might be. So for instance, what I might do here in my implementation of this version of Mario, I might first ask myself a question like, I might first make a note to self like this on a new line above this first block of code, get size of grid. It's just an explanatory remark in any terse English that generally explains the next 6 or so lines, the next chunk or block of code, if you will. It would be a little excessive to comment every single line. At some point, the programmer should know what individual lines of code do. But it's nice to be able to kind of glance at this comment on line 6 that starts with 2 slashes. And it gets grayed out because of syntax highlighting. It's not logic. It's just a note to self. It generally gives me a little cheat sheet as to what the following lines of code should be doing and or why. And then down here, well, there's a second block of code that's a bunch of lines. But together, this just what? Prints grid of bricks. And so it's another comment to myself that just makes it a little more understandable what these 20 some odd lines of code are doing by adding some English explanations thereof. But now that I have these, wouldn't it be nice if I could kind of abstract these pieces of functionality away, this getting of the size and this printing of the grid? In other words, suppose that you didn't know where to begin with this problem. And the problem at hand were literally implement a program that prints a grid of bricks of some variable size, 3 or 4 or 5 or whatever the human types in. If you have really no idea where to start, comments are actually a good way of getting started, because comments can be an approximation of what we called last week pseudocode. Pseudocode is terse English that kind of gets your point across, like for the phone book searching like last time. So if you didn't really know where to begin, you could do something like this. I could, for instance, just say get size of grid as my first step, and then print grid of bricks as my second step. And that's it for my program thus far. This is now implemented in pseudocode. I have some massive placeholders there, like I still have work to be done, but at least I have a high-level solution to the problem in comments. And now I can even go this far. I could say, well, let's suppose that there's just a function already that exists called getSize. I could do something like this. I could do int n equals getSize. And now I just have to assume for the moment that some abstraction called getSize exists. It doesn't. This does not come with the CS50 library. But I could invent it, I bet. How else might I proceed? Well, let's just assume for the moment that there's also a function called printGrid that just prints a grid of that size n. So here, too, is an abstraction. These puzzle pieces don't exist. These functions don't yet exist. But in C, just like in Scratch, I can create my own functions. How do I do that? Well, let me go down later in the file. And by convention, you generally want to leave main at the top of your code. Why? Because it's the main function, and it's just where the human eye is going to look to see what some file of code does. And let me do this. I want to create a function of my own called getSize, whose purpose in life is to get the size that the user wants. I want this function to return an integer. And the syntax for doing that is to write, similar to a variable, the data type that this function returns. I don't need this function to take any inputs. And so I'm going to use a new keyword that we've actually been using thus far, more on it another time, just called void, which just means this getSize function does not take any inputs. It does have an output. It outputs an int. And this is just the weird order in which you write it. You write the output format, the name of the function, and then the inputs, if any, inside of parentheses. And now I can implement getSize. But I've already implemented getSize, or at least now at this point in the story, I at least know concretely what to do. And I could figure out eventually, with some trial and error perhaps, all right, if I declare a variable and I do the following, n equals getInt, prompting the user for size, and I keep doing that while n is less than 1, once that block of code is done, here is a new keyword in C where you can return that value n. So I keep referring to these values that some functions return as return values. In C, there's literally a keyword called return that will hand back to any function that uses that function the value in question. So in a nutshell, between lines 15 and 21 now, here is some code identical to our solution earlier that gets a value n from the user that is positive. It's 1 or 2 or higher. It's not 0 or it's not less than 1. And as soon as we've got that value, we hand it back as a return value. Notice how I'm using this function on line 7. Just like with getInt, just like with getString, I'm calling the function, nothing in the parentheses in this case, but then I'm using the assignment operator to copy whatever its return value is into my variable n. And so now I have a function that didn't used to exist called getSize that gets me a positive integer, no matter what. And now for the grid, how do I do this? How do I invent a function called printGrid that takes a single argument, a number, and prints a grid of that size? Well, let's go down here. I'm going to write the name of this function, printGrid. This function just needs to print. It has a side effect, as we keep saying. So I'm just going to say it has no return value. It's just void. It doesn't have an output per se. It's just an aesthetic side effect. But it does take in an argument. An argument is an input. And the syntax for this in C is to name the type of the input it takes and the name of the variable. And I could call this anything I want. I'll call it size. I could call it n. And it's OK to use the same variable in different functions, but I'll call it size just to be distinct. And then in this function, I'm just going to copy from memory the same code as before. For int I gets 0, I less than size instead of 3, I plus plus. Inside of this, for int j gets 0, j is less than size, j plus plus. And inside of that, print out with printf a single hash, print out after that loop a single new line, and that's it. Now, I did this fast, admittedly, but it's the same code that I wrote earlier. But now, just like I did with Scratch, let me just arbitrarily hit Enter a bunch of times to like move the code out of sight, out of mind. Now I have abstractions. I have puzzle pieces that now exist called getSize and printGrid, syntax for which takes some getting used to, but they now just exist. Except I do need to do one thing. Because C is a little naive, if I try to do make Mario now and hit Enter, implicit declaration of function getSize is invalid. And we've seen that before when I hadn't included a file. Right? When I hadn't included CS50 library, getInt didn't work. But that's not the issue here, because this is not from a library. I just invented this. C kind of takes you literally. And if you define these functions at the bottom of your file, they don't exist on line 7 or 10. So I could do this. I could, all right, fine. Well, let me just kind of highlight all of this, cut to my clipboard, and paste it up here. This would solve the problem. I could just move all of those functions at the top of my file. That's kind of annoying, because now main is like at the bottom of the file. It's going to take longer to find it. It's just, that's not a clean solution. So let me put it back where it was at the bottom. And let me do this. This is the only time in CS50 and really in C programming where copy paste is reasonable. If you copy and paste the first line of code from each function and then end it with a semicolon, you can tease the compiler by giving it just enough of a hint at the top of the file that, OK, these functions don't exist till down later, but here's a hint that they will exist. This is how you can convince the compiler to trust you. So those other functions can still be lower in the file, below main. But now when I do make Mario, oh, damn it. Oh, I said print instead of printf. That's my bad. Printf. So if I do make Mario /Mario, now I can type in 3, and we're back in business. Now, this was a very heavy-handed way and long way to get to a much more complicated solution. But this solution, in some sense, is better designed. Why? Because now, especially without the comments, I mean, look how short my code is. My main function is literally 2 lines of code. Why? Well, I kind of factored out the juicy stuff into its own functions. And now, especially if I'm working with colleagues or others, you could imagine splitting up large programs into smaller parts, having different people implement different parts, so long as you all agree in advance on what those inputs and those outputs actually are. All right, so let's now consider what computers can do well and not so well. C indeed supports a whole bunch of operators mathematically, via which we can do addition and subtraction, multiplication, division, and even calculate the remainder when you divide one number by another. In fact, why don't we go ahead and use these in a very simple program and make our very own calculator. So let me go over here to VS Code. Let me go ahead and create a new file called calculator.c. And in this file, let's go ahead and first include a couple of now familiar header files, cs50.h as well as standardio.h. Let's go ahead then and declare main with int main void. And then inside of main, let's do something relatively simple. Let's declare an int and call it x and set it equal to whatever the return value is of getInt, prompting the user for a value for x. Let's then give ourselves a second variable. We'll call it, say, y. Set that equal to the return value of another call to getInt, prompting the user this time for that value y. And then let's very simply go ahead at the very end and just print out, say, the sum of x plus y, a super simple calculator. So I'll use printf, quote unquote, %i for integer, \n to give me the new line. Then I'm going to go ahead and do x plus y to indeed print out the sum. Let me go down to my terminal window now. Let me do make calculator in order to compile the code. No error messages, so that's good. Let me do /calculator, and let's do something like 2 plus 2, which of course should equal 4, and it does. But it turns out that sometimes there are going to be limitations that we bump up against. And let me get a little more ambitious here. Let me clear my terminal window, and let me go ahead and rerun calculator again. And this time, let's type in 2 billion for x, and let's type in the same for y. And of course, now the answer of 2 billion plus 2 billion should, of course, be 4 billion. And yet it's not. So curiously, we see, of all things, a negative number here, which suggests that somehow the plus operator doesn't quite work as well as we might like. Now, why might this actually be? Well, it turns out that inside of your computer is, of course, memory, or RAM, random access memory. And depending on the size of your computer and the type of computer, it might very well look a little something like this. A little circuit board with these black little modules on it that actually contain all of the bytes of your computer's memory. Unfortunately, you and I only have a finite amount of this memory inside of our computers, which means no matter how high we want to count, there's ultimately going to be a limitation on how we can count, because we only have a finite amount of memory. We don't have an infinite number of zeros and ones to play with. We have to actually be bounded ultimately. So what's the implication of this? Well, it turns out that computers typically use as many as 32 bits, zeros or ones, to represent something like an integer, or in C, an int. So for instance, the smallest number we could represent using 32 ints, of course, using 32 bits, of course, would be 0. 32 zeros like this here. And the biggest number we could represent is by changing all of those zeros to ones, which in this case will ideally give us a number that equals roughly 4 billion in total. It's actually 4,294,967,295 maximally if you set all 32 of those bits to ones and then do out the actual math. The catch, though, is that we humans and computers in general also sometimes want to and need to be able to represent negative numbers. So if you want to represent negative numbers as well as positive numbers in 0, you can't really just start counting at 0 and go all the way up to roughly 4 billion. You got to kind of split the difference and maybe allocate half of those patterns of zeros and ones to negative numbers and the other half roughly to positive numbers. So in fact, in practice, when you're using even as many as 32 bits, the highest most computers could count, certainly in a program like this in C using an int, would be roughly 2 billion. That is 2,147,483,647. But the flip side of that is that we could also now, using different patterns of bits, represent negative numbers as low as -2 billion, give or take. But the implication then, of course, is that if we only have a finite number of bits and can only count so high, at some point we're going to run out of bits, so to speak. In other words, we encounter what's generally known as integer overflow, where you want to use more bits than you have available, and as a result, you sort of overflow the available space. What does this mean, in fact, in real terms? Well, let's suppose that you only have 3 bits, but I'm going to gray out a 4th bit just to convey where we'd like to put an additional bit ultimately. If this, of course, is 0, per week 0's discussion, this is 1, 2, 3, 4, 5, 6, 7. Now, ideally in binary, if you want to add one more to this value 7, you're going to have to carry the 1 mathematically, and that would ideally give you 1, 0, 0, 0. But if you don't have 4 bits and your computer's only sophisticated enough to have 3 bits, not even 32, but 3, the implication is that you're effectively representing not 1, 0, 0, 0, but rather 0, 0, 0. There's just no room to store that 4th bit that that I've grayed out here, which is to say that your integer might overflow, and as soon as you get to 7, the next number, once you add 1, is actually going to be 0. Or worse, as we've seen here in my code, a negative value instead. So what could we do to perhaps address this kind of concern? Well, C does not have just integers or ints. It also has longs, which as the name suggests, are just longer integers, which means they have more bits available to them. So let me go back into my code here. I'll clear the terminal window. And let me go ahead and change my integers to literally long here, long here. I'm going to have to change my function in CS50's library to be not getInt, but getLong. And that's indeed another function we provide in the library. Let me change this getInt to getLong as well. I'll keep my variable names the same, but I do need to make one other change. It turns out that printf also supports other format codes. So not just %i for integers or %s for strings, but also, for instance, %li for a long integer, as well as %f for floating point values with decimals. So with that said, let's go ahead and change my printf line to be not %i, but %li. Now let me go ahead and do make calculator again, enter. No apparent errors now. /calculator, and 2 plus 2 still equals 4 as before. But now if I do calculator again, and let's do 2 billion again, as well as 2 billion for y, previously, we overflowed the size of an integer and got some weird negative number because the pattern was misinterpreted, if you will, as a negative number instead. But a long, instead of using 32 bits, conventionally uses 64 bits, which means we have more than enough spare bits to go when we add 2 billion plus 2 billion. And now, in fact, we get the correct answer of 4 billion, which does fit inside of the size of a long. Now, a long can count up quite high. And in fact, it can count as high as this, 9 quintillion. And so that will give us quite a bit more runway. But of course, it too is ultimately going to be finite. So if you have numbers that need to go bigger than that, you might still very well have a problem. Now, there's another problem that we might run into as well, and we can see it in the context of even this simple calculator. Computers also suffer from, potentially, what's called truncation, where especially when you're doing math involving floating point values, that is, numbers with decimals, you might accidentally, unknowingly, truncate the value, that is, lose everything after the decimal point. So in fact, let me go back to VS Code here. I'll clear my terminal window, and let's still use longs, but let's go ahead and use division instead of addition here. So let me change this plus to a divide operator. Let me go ahead and recompile the code down here with make calculator. Let me go ahead and run /calculator, and let me go ahead and do something like 1 for x and 3 for y, and we'll see that, well, wait a minute, 1 divided by 3, I learned, should be 1/3, but in a floating point value, that should be 0.333333, maybe with a little line over it in grade school, but really an infinite number of 3s. And yet we seem to have lost even one of those 3s after the decimal point, because the answer is coming back here as just 0. So why might that be? Well, if I know that two integers, when divided one by the other, is supposed to give me a fraction, a floating point value with a decimal point, I can't continue to use integers, or even in this case longs, which do not have support for decimal points. So let me go ahead and change this format code here from %li to %f, which is, again, going to represent a floating point value instead of a long integer or even an integer. And let me go ahead further and define maybe a third variable, z, as a float itself. So I'll give myself a variable z equals x divided by y. And now, rather than print x divided by y, let's just go ahead and print z. So now I'm operating in a world of floating point values, because I know proactively that a long or an int divided by another such value, if it's meant to have a fraction, needs to be stored in a floating point value, something with a decimal point. Well, let me go down to my terminal window here and rerun make of calculator. Seems to work OK. /calculator, and let's do 1 divided by 3 again. And still here, we see all zeros. So we do at least see a decimal point. So we've made some progress thanks to the %f and the float. But it seems that we've already truncated the value 1 divided by 3. So how do we actually get around this issue? Well, if you, the programmer, know that you're dealing in a world that's going to give you floating point values with decimal points, you might very well need to use what's called a feature known as typecasting. That is, convert one data type to another by explicitly telling the compiler that you want to do so. Now, how do I do this? Well, let's go back to my code here. And if the issue fundamentally is that C is still treating x and y as integers, or technically longs with no decimal point, and dividing one by the other therefore has no room, so to speak, for any numbers after a decimal point, why don't I proactively do this? Let me, using a slightly new syntax with parentheses, specify that I want to convert x proactively from a long to a float. Let me specify proactively that I want to convert y from a long to a float as well. And now let me go ahead and trust that in z should be the result of dividing not a long by a long or an int by an int, but rather a float by a float. Let me clear my terminal window, run make calculator again. Seems to work OK. /calculator, and now 1, 3, and hopefully now we actually see that my code has outputted 0.333333. And I think if we kept showing more numbers after the decimal point, we'd theoretically see as many of those 3s as we want. But there is still one more catch. And especially when we're manipulating numbers in this way in a computer using a finite amount of memory, another challenge we might run up against, besides integer overflow, besides truncation, is this known as floating point imprecision. Just as we can't represent as big of an integer as we want using int or long alone, because there is going to be an upper bound, there's similarly going to be a boundary on just how precise our numbers can be. And indeed, let's go back to VS Code here. I'll clear my terminal window yet again. And this time, let me use some slightly unwieldy syntax to specify that I don't want to see the default number of numbers after the decimal point, which %f gives us automatically. Let's go ahead and show me 20 decimal point numbers after the decimal point. And the weird syntax for this is to do not %f, but %20 to indicate to C that I want to see 20 digits, not the default after now the decimal point. Let me rerun make calculator. Let me do /calculator again, and let's do 1, let's do 3. And now this is even weirder, right? From grade school, you presumably learned that 1 divided by 3 is, of course, 1/3, but that should be 0.33333 infinitely many times, or on paper with a little line over it. But the computer is just doing some weird approximation here. It's a whole bunch of 3s and then 4326744079590. Well, what's really happening under the hood? Well, again, is this issue of floating point imprecision. If you only have a finite number of bits, and in turn a finite amount of memory, the computer can really only be so precise intuitively. Equivalently, the computer has decided on some way of representing floating point values, but the catch is, per grade school math, there's an infinite number of numbers out there and an infinite number of floating point values, because you can keep adding more and more digits if you want. So the computer, given the way it's implementing these floating point values, is essentially giving us the closest approximation that it can. Now, how can we go about improving the situation? Well, there is one alternative. Instead of using float, I can use something called a double, which, as the name suggests, uses twice as many bits as a float. So instead of 32 typically, it will use 64. And that's just like the difference between a long and an int, which gave us more bits. But in this case, this will be used for more precision. Let's go ahead and cast x to a double. Let's cast y to a double. And now let's go ahead and, using the same format code, %.20f is still OK for doubles. Let me do make calculator. Let me do /calculator. And now let me do 1 divided by 3. And we still have some of that imprecision. And we'd see even more of it if we looked at more than just 20 digits. But now we have more 3s after the decimal point. So it's at least more precise. But it's not perfect, but it's at least more precise. So these kinds of issues then are going to be necessary to keep in mind anytime you do something numerically, scientifically, at least with a language like C, where you're going to bump up against these real world limitations of hardware and in turn language. Now later in the semester, we'll transition to a language called Python, and that's actually going to solve at least one of these problems for us, but just automatically giving us more bits, so to speak, as we need them, at least for integers. But even the issue of floating point imprecision is going to remain. Now, just how real world are these issues? Well, back in the year 1999, we got a taste of this when the world realized, in the years leading up to that date, that it might not have been the best idea to implement computers and software therein by storing years using just 2 digits. Like, instead of storing 1999 to represent the year 1999, a lot of computers, for reasons of space and cost, were in the habit of kind of cutting a corner and just using 2 digits to keep track of the year. The problem problem with that is that if systems were not updated by the year 1999 to support the year 2000, 2001, and so forth, is that just like before with integer overflow, some computers might add 1 to the year in their memory, 99. It should be the year 2000, but if they're only using 2 digits to represent years, they might mistake the year, as some systems may very well have, for the year 1900 instead, taking literally a big step backwards, if you will. Now, you'd like to think that kind of issue is behind us, especially as we understand all the more about the limitations of code and computing. But we're actually going to run up against this very same type of issue again in just a few years. On January 19th in the year 2038, we will have run out of bits in most computers right now to keep track of time. It turns out years ago, humans decided to use a 32-bit integer to keep track of how many seconds had elapsed over time. They chose a somewhat arbitrary date in the past, January 1st, 1970, and they just started counting seconds from there on out. And so if a computer stores some number of seconds, that tells the computer how many seconds have passed since that particular date, January 1st, 1970. Unfortunately, using a 32-bit integer, as we've seen, you can only count so high, at which point you overflow the size of that variable. And so potentially, if we don't get ahead of this as humans, as a society, as computer scientists, on the date January 19th, 2038, that bit might flip over, thereby overflowing the size of those integers, bringing us back computationally to December 13th, 1901. So this is to say now with all of this computational ability in code comes a responsibility to actually write correct code. Next week we'll peel back some of these layers, but for now this was week 1, and best of luck on problem set 1. This is CS50, and this is week 2, wherein we're going to take a look at a lower level at how things work. And indeed, among the goals of the course is in this bottom-up understanding, so that in a couple of weeks' time, even a few years' time, when you encounter some new technology, you'll be able to think back, hopefully, on some of this week's and this course's basic building blocks and primitives, and really just deduce how tomorrow's technologies work. But along the way, it's going to be a little hard, perhaps, to see the forest for the trees, so to speak. And so the goal at the end of the day still is going to be problem solving. And so we thought we'd begin today with a look at some of the problems we'll talk about or solve this coming week. And for that, we have some brave volunteers who have already come up. If we could turn on some dramatic lighting and meet today's volunteers. So on my left here we have...
Hi, my name is Alex. I'm a first year at the college, and I'm from Chapel Hill, North Carolina.
Welcome to Alex. And to Alex's right...
I'm Sarah. I'm from Toronto, Canada, and I'm also a first-year student at the college.
Wonderful. Well, welcome to both Alex and Sarah. So one of the problems you'll perhaps solve this week for problem set 2 is to analyze the reading level of a body of text, whether someone reads at a first grade level, second grade level, third grade level, all the way up to 12 or 13 or beyond. But you've perhaps never quite thought about, certainly in terms of code, like how you would analyze some text, some book, and figure out what reading level is it at. And yet surely our teachers growing up kind of knew or had an intuitive sense of this. So let's consider some sample text. For instance, Alex, what have you been reading lately?
1 fish, 2 fish, red fish, blue fish.
Wonderful. So given that, what grade level would you say Alex is currently reading at? Feel free to just shout it out. First. So indeed, you'll see this week, if you run your code on Alex's text, it actually turns out he reads below a first grade reading level. But why might that be? What might your intuition be for why we've accused Alex of reading at this level? Feel free to shout out. Yeah, so very few syllables, short words, short sentences. And so there's some heuristics, perhaps, we can infer from that short text that probably means that it's best for younger children. Now, Sarah, by contrast, what have you been reading?
Mr. and Miss Dursley of number 4, Privet Drive, were proud to say that they were perfectly normal. Thank you very much. They were the last people you'd expect to be involved in anything strange or mysterious because they just didn't hold with much nonsense.
All right, now, irrespective of what grade you were in when you might have read that text, what grade level does Sarah seem to be reading at? So 8th grade, 2nd grade. OK, so hearing a bit of everything, so that, at least according to code, would actually be 7th grade. And what might the intuition there be? Why is that a higher grade level, even though we might disagree exactly which grade it is? Yeah, so complicated sentences, longer sentences. So indeed, a lot more words were being spoken by Sarah because there was so much more there on the page. So we'll translate these ideas this coming week in problem set 2, if you tackle this one, to code so that you can ultimately infer things of these quantitatively. But to do so, we're going to have to understand text. So let's first thank our volunteers, and then we'll dive in to that lower level. Stress balls. You can keep those, yeah. All right, so besides that, let's consider one other body of text perhaps that you might see this week, which is namely a little something like this. What I have here on the screen is what we'll start calling today ciphertext. It's the result of encrypting some piece of information. And encryption, or more generally the art and science of cryptography, is all around us. It's what you're using on the web, on your phones, with your banks, and anything that tries to keep data secure is using encryption. But there's going to be different levels of encryption, strong encryption, weak encryption, and what you see here on the screen isn't all that strong, but we'll see later today how we might decrypt this and actually reveal what the plain text is that corresponds to that ciphertext. But in order to do so, we have to start taking off some training wheels, so to speak. And believe it or not, even though your time with C this past week, for the first time probably, might have been rather in the weeds and much more complicated seemingly than C, it turns out that along the way we have been providing and will continue to provide certain training wheels. For instance, the CS50 library is one of them, and even some of the explanations we give of topics for now in these early weeks will be somewhat simplified, abstracted away, if you will. But the goal ultimately is for you to understand each and every one of those details so that after CS50 you really can stand on your own and understand and wrap your mind around any future technologies as well. So let's consider first the very first program with which we began last week, which was this one. So Hello World in C. At the end of the day, it was really the printf function that was doing the interesting part of the work, but there was a lot of technical stuff above and below it. The curly braces, the parentheses, words like void and include, and then of course the angled brackets and more. But at the end of the day, we needed to convert that source code in C to machine code, the zeros and ones in binary that the computer understood. And to do that, of course, we compiled the code. We ran make, and then we were able to actually run that code there. So let me actually go over here to VS Code and really quickly recreate that hello.c, pretty much by transcribing the same. So I might have here include standard io.h, int main void. And then in here, I had quite simply hello, comma, world with my backslash end quotes and more. Now, last time to compile this, I indeed ran make hello, followed by enter. Hopefully, you see no errors, and that's a good thing. And if you do /hello, you see, in fact, the results of that program. But it turns out that make is not actually a compiler, as I alluded to last week. It's a program that clearly makes your program, but it itself just automates the process of using an actual compiler. And there's lots of different compilers out there. And the one that it's actually using underneath the hood is a little something called Clang for C language. And Clang is a pretty popular compiler nowadays. There's another one that's been around for ages called GCC. But these are just specific names for types of compilers that different people, different companies, different groups have actually created. But if you use, in week 1, a compiler yourself manually, you have to understand a little more about what's going on, because it's even more cryptic than with just make alone. So in fact, let me go back to my terminal window here. Let me go ahead and clear the screen a little bit and just run really the raw compiler command. So what make is automating for me, let me actually do this manually for just a moment. So if I want to compile hello.c into an executable program I can run, I can do this. Clang space hello.c and then enter. And now there's no output, which is a good thing. In this case, no errors. But notice this. If I go ahead and type ls, it turns out there's a file that's been created suddenly in my current folder, weirdly called a.out. That stands for assembler output. And long story short, that's actually the default name of a program that's created when you just run Clang by itself. Now, that's a pretty bad name for a program because it doesn't describe what it does. So better would be here to perhaps do, well, instead of a.out, which, yes, still prints hello.world, but isn't really a clearly named program, it'd be nice to name this hello. So what could I do? I could do like we learned last week. Well, I could rename a.out to hello by using Linux's mv command. So I'm going to move a.out to become hello. But that, too, seems kind of tedious. Now I have 3 steps, like write my code, compile my code, and then rename it before I can even run it. Like, we can do better than that. And so it turns out that certain commands like Clang support what we're going to start today calling command line arguments. A command line argument, unlike an argument to a function, is just an additional word or key phrase that you type after a command at your prompt in your terminal window that just modifies the behavior of that command. It configures it a little more specifically. So what you're seeing here on the screen is a summary of a better command with which to run Clang, so that now I can specify the output of this command per this -o. So what do I mean by that? Well, let me go ahead and clear my terminal window again and more explicitly type Clang -o hello.c and then enter. Nothing, again, appears to happen, but that's a good thing when you see no errors. And now the program I just created is indeed called hello. So it achieves really the same exact effect as make did, but what I don't have to do with make is type and remember something as long as this command. And this, too, is a bit of a white lie. It turns out we have pre-configured VS Code in the cloud for you to also use some other features of Clang that would be even more tedious for you to write yourselves. And so really, this is why we distill this as ultimately just running make. So let me pause here to see first if there's any questions on what I've done by taking my very first program in C and just now compiling it first with make, but then starting over and now manually compiling it with Clang, with what we'll call command line arguments, -o space hello, and then the name of the file. Yeah. Yeah, so a.out is a historical name. It refers to assembler output. More on that soon. And it's just the default file name that you get automatically if you just run the compiler on any file, so that you have just a standard name for it. But it's not a very well-named program. Instead of running Microsoft Word on your Mac or PC, it would be like double-clicking on a.out. So instead, with these command line arguments, you can customize the output of Clang and call it hello or anything you want. Other questions on what I've done here with Clang itself, the compiler? Yeah. So -o, and you would only know this from reading the manual, taking a class, means output. So -o means change Clang's output to be a file called hello instead of the default, which is a.out. And this, too, is, again, a detail you would have to look it up on a web page, read the manual, hear someone like me tell you about it. And in fact, there's even more than these options. But we'll just scratch the surface here. All right, so if we now know this, what more is actually happening underneath the hood? Well, let's take a closer look at not just this version of my code, but my slightly more complicated version last week, which looked a little something like this, wherein I added in some dynamic input from the user. So I could say not hello world to everyone, but hello David, or hello to whoever actually runs this program. So in fact, let me go ahead and change my code here in VS Code just to match that same code from last week. So no new code yet. I'm just going to, in a moment, compile it in a slightly different way. So I did last week string, I think answer equals get string, quote unquote, what's your name, just like in Scratch. And then down here, instead of doing world, I initially wrote answer, but that didn't go well. What did I ultimately do instead to print out hello David or hello so-and-so? Yeah. Sorry, a little louder? Yeah, so %s, the so-called format code that printf just knows how to deal with. And I had to add one other thing, someone else. Besides %f, yeah. The name of the variable that I want to plug into that placeholder %s. And in this case, it's answer. Now, let me make one refinement, only because now we're in week 2, and we're going to start writing more lines of code. Even though Scratch called the return value of the ask puzzle piece answer always, in C, we have full control over what our variables are called. And now it's probably good not to just generically always call my variable answer if I'm using getString. Let's call it what it is. So this is now just a matter of style, if you will. Let me change the variable to be named, just so that it's a little clearer to me, to you, to a TF or TA, exactly what that variable represents, instead of more generically answer. All right, so that said, let me go down to my terminal window. And last week, again, I ran make to compile this exact same program. Now, though, let me go ahead and just use Clang. So Clang -o, I'll still call this version hello, space hello.c. So exact same command as before. The only thing that's different is I've added a couple of more lines of code to get the user's input. Let me hit enter. And now, darn it, our first error. So output from Clang and make is not a good thing. And here we're seeing something particularly cryptic. So something in function main, undefined reference to getString, and then linker command failed with exit code 1. So there's actually a lot of jargon in there that we'll tease apart today. But my hint is that clearly my problem's in main, although that's not surprising because there's nothing else going on here. GetString is an issue, and the issue is that it's an undefined reference. And yet, notice, I was pretty good. I added the CS50 header file, and I said last week that that's enough to teach the compiler that functions exist. But the problem is that even though this does, in fact, teach Clang that getString exists, it is not sufficient information for Clang to go find on the hard drive of the computer the zeros and ones that actually implement getString itself. So in other words, this include line per last week is a little bit of a hint. It's a teaser to Clang that you're about to see and use this function somewhere. But if you actually want to use the zeros and ones that CS50 wrote some time ago and bake those into your program so your program actually knows how to get input from the user, well, then I'm going to have to go ahead and run a slightly different command. So let me do this. Let me clear my terminal window just to get rid of that distraction. And let me propose now that we run this command instead. Almost the same as before, Clang -o, space hello, then hello.c, but with one additional command line argument at the end. And this is a -l, not a number 1, so -l CS50 with no space in between those two. Now, the L is going to result in all of those zeros and ones that actually were written by CS50 being linked into your code, your few lines of code or mine here. But that's the second step that the compiler requires in order to know how to actually execute and rather compile your code and CS50's. And CS50 is not the only one that does this. If you use any third-party library in C that doesn't come with the language, you would do -l such and such, where however they've named their own library. But you don't have to do it for built-in things like we've been using thus far. All right, so let me go ahead and try this. I'll go back to VS Code here, and let me go ahead now and run Clang -o, hello, then hello.c, and now instead of just hitting enter, -l CS50 with no space between the L and the CS50, enter. Now nothing bad happens, and now I can do /hello. What's your name? I'll type in David, enter, and now we see hello, David. Now, honestly, this is where we're really getting into the weeds. And now this is really just adding nuisance to the process of compiling and running your code. And so the reality is, even though this is indeed what is happening, this is why we used last week, and we're going to continue using this week onward, make, because it just automates that whole process for you. But it's ideal to understand what's going wrong, because any of the error messages you saw for problem set 1, any of the error messages you see for the next few weeks, probably aren't coming from make. They're coming from Clang underneath the hood, because make is just automating the process. But with make, you literally just write make and then the name of the program. You don't have to worry about any of those command line arguments. Questions then on compiling with -L, CS50, or anything else? Yeah? Sorry, what is the benefit of? What is the benefit of using Clang manually? None really. In fact, all make is doing is saving us some keystrokes. If you prefer, though, and you just like to be more in control, you can totally run Clang manually if you remember the various command line arguments. Yeah? Exactly. Why did I have to explain, that is, provide a hint to CS50 with the cs50.h header file, but I didn't have to do that with standardio.h? Just because. Standardio.h comes with C, just like a few other libraries come with C that we'll start seeing today. CS50, though, is not built into C everywhere, and so you do have to explicitly add that one there. Yeah? A command line argument is a word or phrase that you type at the command line, aka your terminal, in order to influence the behavior of a program. Yeah, it changes the defaults, right? In our GUI world, graphical user interface, you and I would probably click some boxes. We would select some menu options to configure a program to behave in the same way. At a command line interface, you have to just say everything all at once, and that's why we have command line arguments. Yeah? No, make is not just for CS50. It's used globally in any project really nowadays using C, C++, even other languages as well. In fact, most every command you see in this class, unless it has 50 at the end of it, is globally used. Only those suffixed with 50 are indeed course specific. And even those will gradually take training wheels off of so that you know exactly what those commands are doing as well. All right, so what is it that we've just done? Everything we've just done, of course, I keep calling compiling. But let's just go down one rabbit hole so that you understand that when you compile code, there's actually a whole bunch of steps happening. And this is going to enable a lot of features, like companies can write code and then convert it to run it on Macs and PCs alike, or phones or the like. So it's not just a matter of converting source code to machine code. There's actually 4 steps involved in what you and I, as of last week, know as compiling. And these aren't terms that you'll have to keep in mind constantly, because again, we're going to abstract a lot of this away. But just so we've gone down the rabbit hole once, let's consider each of these 4 steps that have been happening for you for a week automatically. The first of which is called pre-processing. So what does this mean? Well, let's consider that same program as before. Notice that 2 of the lines of code start with a hash mark. That is a special symbol in C, and it's a so-called preprocessor directive. You don't need to memorize terms like that, but it just means that it's a little different from every other line. And anything with a hash symbol here should be preprocessed. That is, analyzed initially before anything else happens. So let's consider these 2 lines up top. What exactly is happening? Well, it turns out with these 2 lines, you have 2 header files, of course, cs50.h and standardio.h. Where are those files? Because they've never been in VS Code for you, seemingly. If you type ls, if you open up the File Explorer in the GUI, you have never seen probably cs50.h or standardio.h. They just work. But that's because there's a folder somewhere on the hard drive that you're using on your Mac or PC or somewhere in the cloud, as in our case. And inside of this folder, traditionally called /user/include. And user is deliberately misspelled. It's just slightly more succinct, although it's a little weird why we dropped that one letter. But user/include is just a folder on the server that contains cs50.h, standardio.h, and a bunch of other things as well. So in fact, if you type in VS Code in your terminal window, when you're using code spaces in the cloud and type ls space /user/include, you can see all of the files in that folder. But we've pre-installed all of that stuff for you. So let's consider what's actually in those files here. Where if I highlight these 2 lines up top that start with #include, well, I kind of hinted last week that what's in that first file is a hint as to what functions CS50 wrote for you. So you can kind of think of these include lines as being temporary placeholders for what's going to become like a global find and replace. That is, the first thing Clang is going to do, it's pre-process this file. It's going to look for any line that starts with hash include, and if it sees that, it's going to essentially go into that file, like cs50.h, and then just copy and paste the contents of that file magically there for you. You don't see it visually on the screen, but it's happening behind the scenes. And so really, what's happening with this first line is that somewhere in cs50.h is the declaration of getString, like we talked last week, and it probably looks a little something like this. And we didn't spend much time on this yet this past week, but we will in time more. Notice that this is how a function is declared. That is, it is decreed to exist. The name of the function, of course, is getString. Inside of the parentheses are its arguments. In this case, there's one argument to getString, I claim today, but you've known this implicitly, and it's a prompt. It's the prompt that the human sees when you use getString. What is that prompt? Well, it's a string of text, like quote unquote, what's your name, or anything else that I asked last week. Meanwhile, getString, as we know from last week, has a return value. It returns something to you, and that too is a string. So again, this is also called a functions prototype. It's the thing toward the end of last week that I just copied and pasted from the bottom of my file to the top, just so that it was like this teaser for Clang as to what would exist later. So you can think then of these include lines as just kind of combining all of those function declarations in some separate file called cs50.h so that you yourself don't have to type them every time you use the library. Or worse, so that you yourself don't have to copy and paste those lines. This is what Clang is doing for you in its first step of pre-processing. Second and last in this example, what happens when Clang pre-processes this second include line? Well, the only other function we care about in this story is printf, of course, which comes with C. So essentially, you can think of printf's prototype or declaration as just being this. Printf is the name of the function. It takes a string that you want to format, like hello, comma, world, or hello, comma, %s. And then with dot, 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 this actually has technical meaning. It means, of course, that you can plug in 0 variables, 1 variable, 2, or 10. So dot, dot, dot means some number of variables. Now, we haven't talked about this yet, and we won't really in general. Printf actually returns a value, a number that is an integer, but more on that perhaps another time. It's generally not something the programmer tends to look at. But that's all we mean by pre-processing, so that at the end of this process, even though there's more lines of code in cs50.h and standard.io.h, what's really just happening is that Clang, in pre-processing the file, copies and pastes the contents of those files into your code so that now your code knows about everything. getString, printf, and anything else. Any questions then on that first step, pre-processing? Yes? Good question. When you include a file, does it only include what you need, or does it include everything? Think of it as including everything. So if it's a big file, that's a lot of code at the very top. And that's why, if you think back to all of the zeros and ones I showed a little bit ago, as well as last week, there's a lot of zeros and ones that end up on the screen as a result of just writing hello world. A lot of those zeros and ones are perhaps coming from code that you didn't actually necessarily need. But some of it is perhaps there. But there are ways to optimize that as well. All right, so step 2 of compiling is confusingly called compiling. It's just this is the term that most everyone uses to describe the whole process instead of just this one step. But once a program has been pre-processed behind the scenes by the compiler for you, it looks now a little something like this. And I've put dot, dot, dots just to imply that, yes, to your question, there's more stuff above it, there's more stuff below it. It's just not interesting right now for us. So now we have just C code. There's no more preprocessor directives. At this point, all of the hash symbols and those lines of code have been preprocessed and converted to something else. And so now, and this is where things get a little spooky looking, here now is what happens when Clang or any compiler literally compiles code like this. It converts it from this in C to this in assembly code. So this is among the scarier languages. I myself don't really have fond memories. This is not a language that many people program in. If you take a subsequent class in computer science, in systems, a higher level class, you might actually learn this or some variant thereof. But there's at least a few people out there that need to know this stuff, because this is closer to what the computers themselves nowadays understand. Like the Intel CPUs or the AMD CPUs, the brains of today's computers and phones, understand stuff that looks more like this and less like C. Now, it's completely esoteric, but let me just highlight a few phrases. There's some stuff that's a little familiar. There is mention of main at the top there in yellow. There is mention of getString toward the bottom. There is mention of printf down below. So this is just another programming language called assembly language that decades ago humans, myself included in school, did write code in. And absolutely, some people still write this code, especially since you can write very, very efficient code. But it's a lot more arcane. It's a lot less user-friendly. So you'll see in yellow now, these are the so-called instructions that a computer's brain or CPU understands. Pushing values around, moving them, subtracting values, calling functions, and move, move, move. So really, the low-level operations that computers understand tend to be arithmetic operations, subtraction, addition, and the like, moving things in and out of memory. It's just a lot more tedious for folks like us to write code like this. This is why you and I tend to write stuff like this. And ideally still, people like you and I tend to drag and drop puzzle pieces that sort of abstract all of that away further. But for now, this is again called assembly language. It is what happens when the compiler literally compiles your code. But of course, this still not zeros and ones. So we got 2 steps to go. So when a compiler proceeds to step 3, this is where things get converted to machine code. And when a compiler assembles your code for you, it converts what we just saw on the screen here to actual zeros and ones, the so-called machine code that your phone or your computer understands. But it's worth noting that these are not necessarily all of the zeros and ones of your program. Yes, they are the zeros and ones that correspond to your hello program or printf and getString and the like. But notice that here we need one final step. In those zeros and ones are only your lines of code. But what about CS50's lines of code that we wrote to implement getString? What about the lines of code that humans wrote decades ago to implement printf? Those are somewhere on this hard drive, like on my Mac, my PC, or somewhere in the cloud. But we need to combine all of those zeros and ones together and link my code with CS50's code with standard IO's code all together. And so what happens in the last step ultimately is that if we have my code here in yellow, and then the code that CS50 wrote, and the code that the authors of C itself wrote, what really is happening is that somewhere we have not only hello.c, which obviously I wrote and wrote with us live here. There's also, let's assume, somewhere on the computer a CS50.c file that coincidentally I and CS50 staff wrote years ago. And also somewhere on the computer there's another file. Let me oversimplify by just calling it standardIO.c. In practice, it's probably specifically called printf.c. But there's somewhere these 2 other files. And so this last step called linking takes my zeros and ones from the code I just wrote, namely this code on the screen here. It then grabs the zeros and ones that CS50 wrote, and it grabs the zeros and ones that the authors of C wrote in order to implement the standard IO library. And lastly, voila, links them all together. And this is the same blob of zeros and ones that we saw earlier. It's just now the result of pre-processing your code, compiling your code, assembling your code, linking your code. And my God, at this point, like if there were any fun in programming for you yet, we've just taken it all away. We just call this whole process compiling. Why? Because now that we know those steps exist and smart people solve that problem for us, you and I can kind of operate at this level of abstraction and just assume that compiling converts source code to machine code. Questions, though, on any of these intermediate steps? Yeah?
For linking, like, are they like different parts, like for example, Studio and CS50, your own parts, are they stored in different places? Like what these kind of use, like it's all
A good question. So where are all of these zeros and ones stored? Because you and I, we've been using a browser. At code.cs50.io, of course, is this web-based user interface. But again, recall from last week, even though you're using a web browser to access VS Code, that web-based version of VS Code is connected to an actual server somewhere in the cloud. And on that server, you have your own account and your own files and really your own hard drive virtually in the cloud. Think of it a little like Dropbox or Box or Google Drive or OneDrive or something like that. So you have a hard drive somewhere out there that we've provisioned for you. And it's on that hard drive that we have your code that you just wrote or I just wrote, cs50.c, standardio.c, and all of the other code that implements the math functions and everything else that C supports. Good question. Yeah?
So say the CS50 library, the line counting included, is that you can save that thing by going to the cs50.c and copy pasting all the library?
Good question. That hash includes cs50.h line at the top of my code. If I just replace that with the contents of cs50.c, would that work? Short answer, yes, that would work. You could copy all of the code there. However, there's some order of operations that might come into play. And so it's probably not quite as simple as copy paste. But conceptually, yes, that's what's happening. Now, with that said, in cs50.h are only the prototypes of the functions, the hints as to how the functions look, what their return type is, what their name is, and what their arguments are. It's in the .c file that actual code tends to be written. And this is a little confusing now because you and I have only written code in .c files. But in the next few weeks, you'll actually start writing some of your own .h files as well, just like CS50, just like standardio. But in essence, that line of code just makes it easier to use and reuse code that's already been written. And that's the whole point of a library. I say that a little louder. Yes. Does linking happen when you compile your code? Yes. When you run make, as we have been doing the past week now, all 4 of these steps are happening. Preprocessing converts the hash include lines to something else. Compiling technically converts it to assembly code, which the Mac, the PC, the server more closely understands. Assembly converts that language to binary, machine code that this computer actually understands. And then linking combines everything together. And in fact, if you think back a few minutes ago to when I did this -l CS50, the reason I had to add that and the reason my code did not compile at first was because I forgot to tell Clang to link in CS50's zeros and ones per that last step. I don't need to do -l standard IO because it comes with C. So that would just be tedious for everyone in the world. But CS50 does not come with C, so we link that in. And to be clear, too, we won't always use CS50's library. That'll be yet another pair of training wheels we take off in the coming weeks. But for now, it makes a few things simpler. Yeah? Short answer, yes. So what do the zeros and ones, the machine code, translate to? Yes, there is a one-to-one relationship between the machine code and the assembly code. Assembly code, it's not really English, but at least it's symbols I recognize. It's not zeros and ones. Machine code, of course, is just zeros and ones. So back in the day, before C existed, people were programming only in assembly code. Before assembly code existed, people were coding in zeros and ones. And you can imagine just how painful that was. And so each of these languages makes life for us sort of easier and easier. In a few weeks, we'll transition to Python, which will in turn make C even simpler, or coding in general simpler to do too. All right, so with that said, what now can we, what could go wrong with this? Well, it turns out that besides compiling, technically speaking, there's decompiling. And we've not done this, and we won't do this, but it's worth considering for just a moment. If you were to not compile your code, but decompile it, as the word suggests, this just means reversing the process, converting it, ideally, from machine code, zeros and ones, maybe back to C. Now, this would be cool, perhaps, if all you have is a program, you can convert it and see the actual source code. What might a downside be if anyone on the internet is able to decompile code on their machine? Yeah. OK, so it's easier to find bugs in the code to exploit. So it might be easier to hack into the software by finding mistakes you and I made, because literally they're staring at you in code, whereas the zeros and ones make it way less obvious. Other downsides of what I call decompiling? Yeah?
If stuff is copyrighted or people don't want people to know how they did it.
Yeah. Yeah, if your code, your work is your intellectual property, copyrighted or otherwise, that's kind of obnoxious that someone can just like run a command and boom, they can see the original code that you wrote. Now, it turns out it's not quite as simple as that. And so even though, yes, you could take a program like Hello or even Microsoft Word and convert it from zeros and ones back to some form of source code, be it in C or Java or Python or something else, whatever it was originally written in, odds are it's going to be an utter mess to look at. Why? Because things like variable names are not retained in the zeros and ones typically. Function names might not be retained in the zeros and ones. The code is, the logic is, but the computer doesn't care what pretty variables you chose and how nicely named your functions were. It just needs to know them as zeros and ones. Moreover, if you think about last week, we introduced things like loops in C. And besides for loops, there's what other kind of loop, for instance? So a while loop. And even though they look different and you have to write different code, they achieve exactly the same functionality, which is to say when you compile a for loop or you compile a while loop, if they logically do the same thing, they might end up looking identical as zeros and ones. And so therefore, it's not necessarily predictable that you'll get back the original code. Why? Because the zeros and ones might not know, so to speak, whether it was a for loop or a while loop. So maybe decompiling will show you one or the other. And honestly, decompiling, while possible, and it's one way of reverse engineering someone's product, odds are if you're good enough to start reading code that's been decompiled and reading through the messiness of it, odds are you have the talent probably to just write that same program from scratch yourself. Now, that's an overstatement perhaps, but it's not quite as easy or threatening as you might first think. So in general, once code is compiled, it's pretty challenging, time-consuming, costly to reverse engineer it, much like it would be in the real world, right? Like all of us have some kind of phone probably nowadays in our pocket. There's nothing stopping you from opening it up somehow, poking around, recreating what's there. That's a huge amount of effort, most likely. And at that point, maybe you should just invent the phone instead of trying to reverse engineer it. So same kind of idea in the physical world. Any questions then on compiling or even decompiling in these forms? All right, so odds are at this point, not only I, but you have made mistakes. And you've written buggy code. A bug in a code is just a mistake, a logical error or otherwise, where the code just does not behave correctly as you intend. And up until now, odds are your debugging techniques have been to maybe look back at what I did in class, maybe ask a question online or in person. But ultimately, it'd be nice if you had some tools of your own with which to debug code. And this, honestly, is a lifelong skill. You're not going to emerge from CS50, and even 20 years from now, you're not going to be writing, if you're writing code at all, correct code all of the time. Like all of us on the staff continue to write bugs. Hopefully, they get a little more sophisticated and not sort of like, oops, I missed a semicolon. But even those kinds of mistakes we make too. But there's tools out there and techniques that can make your life easier when it comes to solving those problems. Now, the term bug has actually been around for decades, but a fun story to tell is that the first documented actual bug was actually somehow connected to Harvard. In fact, this is the logbook relating to the Harvard Mark II computer from 1947, whereby if you read the notes here, and if I zoom in, this was an actual moth discovered inside of this big mainframe computer that was causing some kind of problems. And the engineers at the time actually thought it was funny that, wow, physical bug actually explains the issue. And it's been forever taped to this sheet of paper, which I believe now is on display in the Smithsonian. With that said, this is just representative of a logical bug. And that story is actually that story was often retold by a famous mathematician, then computer scientist, really, Dr. Grace Hopper, who actually worked not only on the Harvard Mark II computer, but its predecessor, the Harvard Mark I. And if you ever spent time yet in the engineering building across the river here, you can actually see much of this computer, which is along the wall when you first walk into the science and engineering complex. And indeed, as you've probably heard growing up, this is a mainframe computer. Like this is what Macs and PCs, so to speak, looked like back in the day, with very physical things that essentially implemented the zeros and ones that you and I take for granted now being miniaturized in our laptops and phones. So there's a piece of history there. If you visit campus, that side of campus sometime, do take a look. But let's consider then how we solve not, of course, physical bugs, but logical bugs. And let's consider something like this from last week, whereby we were trying very simply to print like this column of 3 bricks using hashtags of sorts. So let me go over here in just a moment to VS Code. And I'm going to go ahead and open a program I wrote in advance. And I'm bringing it to class because there's a bug in it. And I'd like to figure out how to solve this bug. So let me open up buggy0.c, which is version 0 of my code. And let's just take a quick peek at what's here. It's pretty short. It includes only standard io.h. It uses printf. It uses a for loop. And the goal, quite simply, is to print out that column of 3 bricks. Now, it's short enough that some of you, if you're getting comfy already with C, you might already see the logical bug. It's not a syntax error. Like, it will compile and run. But there's a bug there. And suppose that I'm very new to C. I'm very uncomfortable with C. It's 2 a.m. and I just can't see the bug. What are my recourses here for actually finding a mistake like this? Well, first, let's look at the symptom. Let me go down to my terminal window. I'm going to use make buggy0. Because again, the file is called buggy0.c. I'm not going to use clang. In fact, I'm never really going to use clang manually here and out. I'm just going to use make because it makes our lives easier. It does compile, no errors, so it's not syntax. It's not something silly like a missing semicolon. But when I run /buggy0, I of course see 1, 2, 3, 4. And this, of course, does not match the 1, 2, 3 bricks that I actually intended for that column. And yet, I'm starting counting at 0 as I usually do. I've got 3. I'm going up to 3. So where is my logical error? If it hasn't obviously jumped out at you already, well, how can I solve this? Well, first and foremost, perhaps the best technique for solving bugs, at least early on, is just use printf. Like thus far, we've used printf to say hello and other things on the screen. But printf is just a function for printing anything. And there's no reason you can't temporarily use printf to like print out the contents of variables, what's going on inside of your program, just to figure out where your mistake is. And then you can delete that line of code later. It doesn't have to stay there forever. So let me do this. Instead of just printing out in VS Code the hash symbol, let me do a little safety check here and print out the value of I. So let me go ahead and say something like I is. Now, I want to say I is this. But of course, this is not how I print out the value of I. If I want to print out the value of I, what should I put here? So %i for integer instead of %s for string. So there's still placeholders, but we use %s for integers. And now if I want to print out I just need the comma as the second argument and then I. All right, let me go ahead and back to to my terminal window. Let me recompile the program because I've changed it. That still works fine. /buggy0. And now let me increase the size of my terminal window here. You just see some diagnostic information, if you will. Like this is not the goal. This is not what you should be submitting for this homework problem we're at 1. But it is helping us diagnostically know that, OK, when I is 0, here's a hash. When I is 1, here's a hash. When I is 2, here's a hash. When I is 3, here's a hash. Well, wait a minute. That's 1, 2, 3, 4. So clearly, I'm printing it 1 too many times. So let me look back at the code here by shrinking my terminal window. And let me just ask the group, where is, in fact, the mistake? Or what equivalently would be the solution? Yeah, in the middle. Yeah, instead of less than or equal to, use just less than. So you got to kind of pick a lane here. Like if you're going to start counting from 0, you generally use less than and go up to, but not through the value. Or if you prefer, like in the human world, counting from 1 on up, you can use less than or equal to, but you have to be consistent. And in general, as a programmer, just always start counting from 0 if you're doing something canonical like this. But the solution is indeed just to change this by changing the less than or equal to less than. If I compile this program with make buggy0 and then do .buggy0 again, and let me increase the size of my terminal window, now you see, OK, almost the same output, but indeed I starts at 0 and goes up 2, but not through 3. All right, so printf, in short, can be your first diagnostic tool. Instead of just staring at the screen or raising your hand, use printf to see literally what's going on inside of your program by just printing out things of interest. And then once you've solved the problem, you can go back into your code, as I'll do here, by shrinking my terminal window. I'll delete the printf line, and now I'm ready to share this program with the world or submit it as homework or the like. It's just meant there to be temporary. Any questions on printf as a debugging tool? No? All right. Well, that only gets us so far. And honestly, as your programs grow and grow and grow, it's going to actually get really annoying to start going in and adding printfs, then removing them and figuring out if you've got multiple printfs, well, which one printed what. Like, it just gets messy eventually to rely on printf alone. So being computer scientists have written software to make it easier to debug code. That software is what we would generally call a debugger, which would be the second tool of the trade that you can use to actually solve problems in your code. Now, in the world of VS Code, there's actually a debugger built in. So the graphical user interface you're about to see in VS Code isn't specific to CS50. It actually comes with VS Code, and it supports C and C++ and Java and Python and lots of other languages too. But it's admittedly a little complicated to just start using the debugger. You have to like create a configuration file and do like some annoying steps that just get in the way of solving real problems. So we have automated the process for you of just starting the debugger. And thereafter, it's sort of industry standard how you use it, but we save you the headache of having to create those configuration files. So suppose I want to do this. Suppose I want to try to debug this program step by step using special software. Well, how can I do that? Well, let me propose that if I revert this back to the original version, where I was less than or equal to 3, I'm pretty sure that I was printing too many hashes. So I'm going to do this. And you might have done this accidentally or never at all. But notice if you hover over the gutter, so to speak, in VS Code, the part of it all the way to the left of the editor, you see this sort of grayed out red dot. If you click there, it becomes a brighter red dot. And this represents what we're going to call a breakpoint. And this is just a visual indicator that you've put like a stop sign equivalent there. And you're telling the debugger in a moment, stop running my code there. Why? Because I prefer to step through my code at sort of a human speed and not as computer speed, where it runs all at once. So I've set my breakpoint, which is step 1. And then step 2 is quite simply this. Instead of running the program itself, run a command called debug50, and then /buggy0. And now this will start your program, but inside of the debugger, which is a special program that smart people wrote that will empower you to now step through your code line by line again, at your own comfort pace. I'm going to hit Enter. Some stuff's going to happen on the screen. Whoops. Notice this is a common mistake that I made accidentally here. Looks like I've changed my code. I did, because I went in and changed the less than or equal to sign. So let me go ahead and rerun make buggy0, Enter. Good. Now let me rerun debug50, Enter. And now some stuff just happened on the screen. And it takes a moment to get started. But once it's started, you'll see this. You'll still see your code, but you'll see this yellow highlight, which you've probably not seen before. And notice that it's specifically highlighting the same line that I set a breakpoint on. Why? That just means the program has the debugger has executed all of these lines except for line 7. It has broken not in a bad way, but it has paused execution on line 7, so it hasn't yet printed any hashes. And you can see that. No hashes in the terminal window yet. It's paused execution. But what's interesting with the debugger is the stuff over here on the left-hand side. In the debugger here, you'll see under variables all of your so-called local variables. And we haven't really made a distinction between local and something called global. But for now, local variables just means all of the variables that exist in your function. So I currently has a value of 0. OK, and that makes sense. So now how do I step through my code and see what it's doing? Well, at the top of the screen here, you'll see some playback icons, kind of like a video player, but they have special meaning. This first one will just play the rest of your program all the way to the end. So you only click that if you've sort of solved a problem and you just want to run it to completion like before. But the next 3, or next 2 really, are really the juiciest. The second one here, if you hover over it eventually, you'll see that it's called step over. Step over means that the debugger will run this currently highlighted line of code, but it's not going to dive into it. So if it's a function like printf, it's not going to start stepping through printf line by line. Why? Because I can pretty much assume printf written decades ago is correct. Problem's probably with me. But this next line, if I did really want to step into the printf code to figure out how it works or find some problem in it all these years later, you can step into printf, and then the screen would change, and you'd see each of the lines for printf line by line, at least if you have the source code for printf installed. All right, I'm going to use the first one, step over, and watch as the yellow highlight moves, and watch as in the terminal window there's a hash symbol. Here we go. There's one hash. Now notice line 5 is highlighted. That means it has paused on line 5. Line 5 has not yet been executed. So what does that mean? The value of I, per the top left-hand corner, is still 0. But as soon as I click step over again, watch what happens at the top left, where I is a variable on the screen. Now I, and it flashed briefly, has a value of 1. And now if I step over again, watch the terminal window. There's my second hash. Now let me click step over on the for loop. Watch the variable at top left. Now 1 goes to 2. Now let me click it again. Third hash. And here's where the logical error is perhaps revealed. Let me go ahead and step over the loop. Now I is 3. Wait a minute. I'm still going to print out a hash. Well, there it is. There's the fourth hash. And at this point, hopefully the light bulb proverbially has gone off. I realize, oh, I screwed up. I can either stop the program altogether with the red square, or I can just let it run all the way to the end, which just terminates everything. At this point, I just want to get back into my code and start fixing things. And you can close, for instance, as I will here, the File Explorer just to hide the panel that opened. So that's debug 50, but it's not a CS50 thing. That just starts the debugger for you, which is something you'd find in most any programming environment nowadays. Questions on debugging? Questions? Yeah? Good question. Where does it tell you where it went wrong? So sadly, it does not tell you any of that. The onus is still on you, the human, to use this tool productively to walk through your code at a saner pace. But your brain is the one that still needs to solve it. And I don't doubt down the line, with artificial intelligence and more, programs like this will get all the more helpful and start answering questions like that for us. And there are other tools we'll introduce you this semester that are even more powerful than this. But for now, it's just a tool really to slow things down and not have to change your code. The fact that I had that panel on the left that just showed me eyes changing value is just an alternative to printf. And I can step through it a little more slowly. Other questions on debugging? No? Let me show you one final example with this debugger here. And this one, too, I wrote in advance. Let me close buggy0.c. And let me open up buggy1.c, my second version thereof. Let me close my terminal window for a second and give you a quick tour of this program, which similarly has a mistake. Now, at the top of this program, some familiar includes cs50.h and standardio.h. This is not something we've seen before. It's specific to this example, a function called getNegativeInt. Takes no arguments, and it returns an integer. What does it do? It literally gets a negative integer, ideally from the user. Fun fact, though, it doesn't correctly. That's the bug. GetNegativeInt is broken at the moment. So what does main do? Well, main just calls this function, passing in nothing in parentheses, no inputs, and it stores the return value in I. And then it just prints out I on the screen. So honestly, just by eyeballing this, I feel comfortable enough with programming in C. I think main is correct. Let me just stipulate main is correct. But there is going to be a bug down here. Now, what's the bug down here? Well, let me look at getNegativeInt's implementation. Notice this first line, 12, is identical to the prototype up here. The prototype is sort of stupidly required up here because C reads things top to bottom, left to right. The compiler technically does. So if you reference getNegativeInt here, but you don't implement it until down here, and you haven't told C in advance that it will exist, again, you get the error we saw last week. All right, so how does getNegativeInt work? We declare a variable called n. We've got a do-while loop that does what? It uses getInt, which comes with the CS50 library per last week. It prompts the user for negative integer, quote unquote, and stores the value in n. I then do all of this while n is less than 0. Right? Remember we used a do-while loop last week to make sure the human cooperates and doesn't give us the wrong type of value, be it positive or negative or something else. And then we return n. And there's some subtleties. Anyone recall or have an intuition for why I've declared n on line 14 instead of on line 17? This is a C-specific thing. Exactly. There's this notion of scope in C, and we'll continue to see this over time, whereby a variable only exists inside of the most recent curly braces that you've opened. So if I've declared n here on line 14, I can use it anywhere between lines 13 and 21, because those are the nearest curly braces. If by contrast, as you note, if I instead said this, int n equals getInt and so forth, and didn't have the current line 14, well, n would exist inside of these curly braces, but not here, which is too late, and definitely not here. So you just have to declare it first and then use and reuse it as such. Now, let me just show you how I can debug this, but let me show you the symptoms first. Let me open my terminal window. Let me run make buggy1. Compiles OK, so it's not something silly like a semicolon, /buggy1, and I'm asked for a negative integer. All right, let me give it -1. Enter. Well, the main function is supposed to print out what I typed, but it clearly didn't. It's prompting me again. All right, so maybe it'll like -2. No, maybe -3. 50? OK, so it's definitely broken, right? It kind of seems logically to be doing the opposite. Now, you can perhaps see why this is happening already. These are deliberately simple programs for demonstration's sake. But let's do this. Let me go ahead and set a breakpoint in main, even though I'm pretty sure main is correct. But it just helps me start my thought process. Start with main and then take it from there. Let me run now debug50 /buggy1, enter. And let's see, with that breakpoint now, the GUI is going to reconfigure itself. It's going to pause on line 8, because that's the first interesting line inside of main. So I could have just put the breakpoint on line 8 too. It's smart enough to know that if I set it on 6, you really mean line 8, because that's the first actual line of code. And watch now what happens. If I step over this line, notice that I, which at the moment seems to have a default value of 0, more on that another time. But if I click step over, like before, I'm prompted for a negative integer. Let me type -1, enter. And now notice there's no additional yellow highlight. Why? Where am I currently stuck logically? Yeah, just logically, I must be in that do while loop. And even if you don't understand it, like that's the only explanation. If you keep getting prompted, surely there's a loop going on. There's only one loop in my code, so there's probably a problem there. So OK, I can't just set a breakpoint in main and then wait for this to work. So let me just let me stop this with the red square. And let me think, all right, instead of, I can still set my breakpoint in main, but let me rerun the debugger instead. And this time, not step over that line of code. Let me step into that line of code. So watch what happens now. Instead of clicking the second icon here, let me click the third, whose name is indeed step into. And watch as the yellow highlight does not move to line 9. It dives into line 8. The function on line 8, thereby bringing me whoosh down to line 17. It's kind of going down into that next function. Now, it didn't bother pausing on line 12 or 13 or 14, because there's nothing intellectually interesting there happening yet. The juicy part really starts, it would seem, in line 17. So now notice, n is my variable at the top left. If I click, I don't want to click step into now, though. What would go wrong if I click on step into? Or what would it do that I don't think I want to do? Yeah. Yeah, it would step into getInt, but I'd like to think that the staff's version of getInt is correct, and that's not our problem today. So I want to step over it. And watch now at top left that nothing happens yet to the value of n until I go to the terminal window now and type in something like -1. Now notice it jumps to line 19, which is the next interesting line. Top left, n indeed is -1. And here's where I can now pause as a human and think, all right, so while n is less than 0. All right, n per the top left corner is -1. So all right, while -1 is less than 0, well, obviously that's true mathematically. So what's going to happen? It's a do while loop. So when I click on step over again, it's going to go to this line, because it's at the end of the inside of that loop. And now here, it's looping through again and again. All right, let me do this once more. I'm going to step over. All right, I'm going to type in -2, and it's the exact same thing. Now is my chance on the yellow line. OK, wait a minute. -2 is obviously less than 0. Let me try this one more time. Click it once here. And now, all right, let me give it 50. And now, OK, while 50 is less than 0, that's not true. So the loop is over, because it's not going to do it while 50 is less than 0. That's not true. So now watch, when I click step over once more, it then finishes the loop. Even though there's nothing more to do, it's now about to return n. It jumps back up to main, where I left off on line 9. It now prints in my terminal window the number 50. And hopefully at this point, to your question earlier, my human brain has realized, oh, I'm an idiot. Like, I flipped my sign there. So let me stop this. I probably want to do something like this. If the goal is to get a negative integer, I probably want to say, while n is, for instance, greater than or equal to 0 would work. So while n is greater than or equal to 0, keep doing this. And that's the logic I wanted to express. So the debugger just saves me from staring at the screen, raising a hand, sort of asking someone else. At least in this case, it allows me to go through it at a healthier pace. Questions now on debug 50, which should be your new friend, even if it's not your first instinct after printf. Any questions on debug 50? No? All right. Well, there's one last technique we can equip you with here. And that is, in addition to printf and a debugger, no joke, a rubber duck is actually a reasonably recommended solution to finding bugs in your code. To your question earlier, the duck2 is not going to solve the problem for you. But if you've wondered why this little guy has been here for so long, there's this technique. It has its own Wikipedia article called rubber duck debugging. The idea of which is that if you're home in your dorm room wrestling with some bug in your code, printf didn't quite reveal the source to you, debugger isn't really helping, honestly, maybe it would help to just sound out what problem you're having. Similar to going to office hours, talking to a TA or a professor, just walking through your problems, because in sort of talking to the duck about, the fact that you're doing this while n is less than 0, and then if it is, oh, wait a minute, I'm an idiot. Not just for talking to the rubber duck, you realize hopefully in expressing yourself literally verbally, you probably will hear with non-zero probability like some illogic in your statement. And just by sounding things out, you'll realize like, oh, that's my problem. And so, frankly, if you have roommates, you can also use a roommate for this. But the rubber duck is just sort of a go-to when your roommates have no interest in your, C problem set, talking something through that as such. And this is an invaluable technique. I admittedly tend not to do it so much with a rubber duck, but ideally with colleagues, human colleagues. But just talking through things often will help you just realize, oh, I said something illogical. Now I can go back to the code. So don't solve problems by staring at your screen endlessly for minutes, for hours. At that point, it's time for a break, time to walk away, time to talk to the duck if you've already exhausted some of those other tools. As an aside, on your way out today at the end of class, we have clearly plenty of rubber ducks for you. It's become a thing over the years, at least among some, to bring the duck with them when they travel and send us photos. Here, for instance, is CS50's Rubber Duck Debugger, aka DDB for Duck Debugger, which is a pun on a geekier program called GDB, the GNU Debugger, which is an actual piece of software for debugging. This is CS50's debugger in the hills of Puerto Rico, also here on the sea. He made its way to San Francisco here. Also down by Fisherman's Wharf by the sea lions, if familiar. Here at Stanford, where there's a William Gates Computer Science building for computer science. Down the road in SF at Google. And this is the Trevi Fountain in Rome. And lastly, the Colosseum. So we'll be curious to see in the coming years where your duck2 travels. So that then was quite a bit. Why don't we go ahead here and take a short 5-minute break. No snacks yet. You're welcome to get up or sit down. We'll return in about 5. All right. So we are back. And if the goal ultimately today is to have a better understanding of things like strings so that we can solve problems with text, let's consider some simpler types of data first, how we might represent those, and then see if that doesn't lead us to a discovery as to like how strings in just today's modern software is using things like that. So when we talked on week 0 about representation of data, we had different ways of doing it in terms of binary and decimal and unary even. When we started talking about the same last week in code, we started talking about data types instead. And these data types were a way of telling the computer, like, do you want an integer? Do you want a character? Do you want a floating point value, like a real number, or even a string, as we've seen? But it turns out that computers, of course, only have finite amounts of resources. Your computer only has a fixed amount of memory or RAM, and that actually has very real-world implications. So for instance, here are some of the data types we've seen thus far. And it turns out that each of these in C has a specific number of bits allocated to it. Now, admittedly, this can vary by system. It's not so much the case nowadays, but for many years, for decades, computers were getting better and better. The earliest computers might have used fewer bits for some of these data types. More modern computers might use more bits. So the numbers you're about to see are pretty much where we are present day. So when it comes to these data types, a bool, which is true or false, somewhat curiously uses a whole byte, even though that's way overkill. Because for a bool, true or false, you of course only need 1 bit. But it turns out, even though it's wasteful to use 8 bits or 1 byte just to represent true or false, it's just easier for computers. So a bool tends to be 1 byte. An int, which we've been using a lot, uses 4 bytes typically, or 32 bits. And if I do some quick math from week 0, with 32 bits, you have 4 billion possible values, roughly. But if you want to represent positive and negative, that means you can represent represent roughly -2 billion all the way up to +2 billion. So that's the range typically with ints. If that's too few numbers for you, turns out there's things called longs, and longs use 64 bits, which allow you to have like a quintillion number of possibilities, which is a lot, certainly a lot more than 4 billion. So sometimes you might use a long, but even that's finite. And so, as we discussed at the end of last week, bad things can happen if you make certain assumptions as to data because of things like integer overflow or the like, where things wrap around. Then there's a float, which is a real number, something with a decimal point. By convention, it's 4 bytes or 32 bits, which gives you, in short, only a specific amount of precision. It doesn't necessarily dictate how many numbers to the left or to the right. In the aggregate, ultimately, you have, though, 4 billion possible permutations still. If you need more precision for scientific, for medical, for financial applications, you might use 8 bytes, aka a double, which just gives you more digits of precision. They eventually get imprecise per the example we looked at last week, but it at least gets you further down the line. As an aside, in really, really important applications in finance, in medicine, in military operations and the like, where you really can't have rounding errors, long story short, humans have developed libraries in C and other languages that use more even than 8 bytes. So there are solutions to these problems, but they're always finite. You have to pick an upper bound. Then there's char, which we saw briefly last week when I asked the user for y or n for yes or no. And then there's string, which I'm going to propose as a question mark, because a string totally depends. Like hi, h, I, exclamation point would seem to be 3 bytes. D-A-V-I-D would seem to be 5. So strings clearly are variable based on what you or the human type in. So we'll see what this means, though, in just a bit. This, though, is the thing inside of your Mac, your PC, your phone. Might not look exactly like this, but this is a memory module for a modern computer. And let's go ahead and use this really as just representative of the finite amount of memory that any computer indeed has. Let's zoom in on one of these little black chips on the circuit board here. Zoom in, and let me propose that this rectangle really represents some number of bytes. Like tucked inside of this little black circuit on the board is maybe, I don't know, a gigabyte, a billion bytes, maybe it's 100 bytes, some number of bytes. It totally depends on the computer and how much you paid for the stick of memory. But if there's a finite number of bytes physically implemented somehow digitally inside of this hardware, well, then it stands to reason that we could number those bytes. We can just arbitrarily decide that the top left corner is byte number 1, or really byte number 0. The one next to it is number 1, then number 2, number 3, dot, 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 number 2 billion, or whatever it is, however big this memory is. So if you use a variable in a C program that's only 1 byte, like a char, it might literally be stored in that top left-hand corner of the memory. Like in practice, you don't care where physically it is, but really, the artist's rendition would be this. A char might use one of those single bytes somewhere in the computer's memory. If you use an int, which is 4 bytes, it would give you 4 bytes, contiguous, that is left to right, top to bottom, but all 32 bits would be next to each other. So the computer knows that those indeed all belong to the same int. If you need a long, or a double for that matter, then you might use a full 8 bytes in this case. And you just keep using and using this memory kind of like a canvas, you know, almost in Photoshop or a spreadsheet, where you can just move pixels or you can move data around. That's really what your computer's memory is, a canvas for storing information in units of bytes or 8 bits. Now, we don't need to keep looking at these circuit boards. We can abstract it away, as we often do. And let's go ahead and zoom in on this grid just to consider some very specific variables. So let me zoom in, and now I see fewer but larger boxes on the screen, each of which, again, represents a byte. And now let me propose that we play with some actual code. So here in C, albeit without a full program, are 3 ints, score 1, score 2, score 3. I have coincidentally given myself two scores at around 72 and 73, and then a pretty low score at 33. Of course, last week or 2 weeks ago, this would have been high, but now we're dealing with actual integers. So these are 3 so-so scores on my quizzes or tests or the like. So let me go to VS Code here, and let's make a program called scores.c. So I'm going to write code scores.c. That's going to give me my new file. And let me go ahead and implement something like this. Include standard.io.h, int main void, and then inside of here, let me do int score 1 will be 72, int score 2 will be 73, and int score 3 will be 33. And then let me just do something like write a program to average my 3 test scores together, something like that. So let me do printf, quote unquote, my average is, and I'm going to go ahead and do, say, %i, \n, and now let me plug in the results. And this is kind of grade school math now. How do I compute the average of 3 values? Well, just like on paper, I can do score 1 plus score 2 plus score 3 in parentheses, because of order of operations, divided by 3, since there's 3 total scores. All right, so I think this checks out. And indeed, you can use parentheses and operators like plus in your code like this in C. Let me go ahead now and do make scores. No syntax errors, so that's good. Nothing missing there. And now let me do /scores and see what my test average is. All right, you know, it's not great, but I think I still passed. And indeed, my average here is 59. Is it precisely 59, though? Well, let's see. Let's actually, instead of using an int, how about we go ahead and use something like a floating point value here. And let me go ahead and do this. So let me recompile my code, make scores. All right, I've got an issue. Let me zoom in on my terminal window. We've not seen this one necessarily before, but error on line 9. Format specifies type double, which is a lot of precision, but the argument has type int. So what does this mean? Well, it's showing me with these green squigglies that something's bad between the %f and this thing over here. Well, on the left, I'm implying a float, or a double for that matter. On the right, though, what data type are score 1, score 2, score 3? All right, so they're ints. So Clang does not like this. The compiler just doesn't like that I'm using ints on the right, but I want floats on the left. So there's going to be different ways of solving this. One way would be to just ignore the problem like I originally did and just go back to %i. Or, as an aside, %d is often an alternative to %i for a decimal number, but we use %i because it sounds like int. So %i is fine here too. But I don't want to just avoid the problem. I want to actually display a floating point value. So how can I fix this? Well, it turns out I can solve this in a few different ways. The simplest is just to make sure that at least one number on the right is a floating point value, like 3.0 instead of just 3. Now, I think Clang will be happier. Let me do make scores, enter. And indeed, it's OK. Why? As soon as you have at least one more precise data type on the right, it just treats everything at that point as floating point value so that the math works out. So /scores, enter. And now, there we go, right? You know, some of us might really want that third of a point. Our average was not 59. It's 59 1/3, as in this case here. All right, so we've solved that there. As an aside, though, there's one other technique to show here. If you didn't want to change it to 3.0, because that's a little weird, because there were literally 3 scores. It's not like that needs to have a decimal point. You could also explicitly convert the 3 to a float by saying in parentheses float. This is what's called typecasting. And this will just convert the thing right after it to that data type, if it's possible. So if I do this again, make scores, no errors now, /scores, and I get, in fact, the same result. There's a bit of a rounding issue here, but we know the rounding relates to the imprecision from last week. For now, let me just be happy with my 59.3 something. I'll take that for now. But this is, you know, is close to a good enough correct answer for me now. But how do I think about now what's going on inside of the computer's memory? Well, let's consider. Here's that same grid of memory. Each box represents a byte. Where are score 1, score 2, and score 3 in my memory? Well, score 1, let me just propose, is at the top left, but it's taking up 4 boxes for 4 bytes. Score 2 probably ends up right next to it in memory, though this isn't always going to be the case, but I've chosen simple examples. 73 is next to it, also taking up 4 bytes. And then lastly, 33 is in score 3 down there underneath. Now, if we really look at the computer's memory, look at it with some kind of microscope or the like, there's actually 32 bits, 32 bits, 32 bits in each of those 4 groups of 4 bytes representing those values. But again, for today's purposes onwards, we don't really need to think again and again in binary. It's just indeed these decimal numbers being stored there. But I claim now this isn't the best design. Even if you had never programmed before CS50, what you're looking at here on the screen as an excerpt, in what sense is this perhaps bad design, even though it's a correct way of storing 3 test scores? What's kind of bad here? Yeah? Yeah, always do exactly what you did. Extrapolate to 4 scores, 5 scores, 50 scores. This can't be that well designed because now you're going to have 4 lines of code, 5 lines of code, 50 lines of code that are almost identical, except for this like arbitrary number that we're updating at the end of the variable. So indeed, there's probably going to be a better way, even though, at least in C, we haven't yet seen that technique. But the solution today onward is going to be something called an array. An array is a way of storing your data back to back to back in the computer's memory in such a way that you can access each individual member easily. Put another way, with an array, you can instead do something like this. Instead of saying int score 1, int score 2, int score 3, giving each a value, you can first tell the computer, please give me a variable called scores, plural, though you can call it anything you want, of size 3, each of which will be an integer. That is to say, this is how you declare an array in C that will have enough room to store 3 integers. Put another way, this is the technical way of telling the computer, please give me 12 bytes in total. 3 times 4 each for an int, so give me 12 bytes in total. And what the computer will do is guarantee that they're back to back to back in the computer's memory. And that'll be useful in just a moment. So let me go ahead and do something useful with this. Let me store 3 actual scores. Here's how I could now store those same numeric scores in this array. Syntax is a little different, but there's one variable called scores. But if you want to go to its first location, starting today, you use square brackets and go to location 0 first, which because things in C are 0 indexed, so to speak, you start counting at 0. The first int is at bracket 0. Second int is at bracket 1. Third int is at bracket 2. So it's not 1, 2, 3. It's literally 0, 1, 2. And this is not something you have control over. You must start at 0. So these lines now create an array of size 3, and then insert 1, 2, 3 values into that array. But the upside now is that you only have one name of the variable to remember. It's just called scores. Yes, you need to go into the array to get individual values. You need to index into it using those square brackets, but at least you don't have this hackish approach of declaring a separate variable for each and every one of these values. So let me go back to scores.c here, and let me propose that I do this. Let me just kind of use that same idea to do the following. Let me get rid of these 3 separate integers. Let me give myself an int scores array of size 3, and then scores bracket 0 will, as before, be 72. Scores bracket 1 will be 73. And scores bracket 2 will be 33. And let me get rid of the little dot there. All right, so now if I go ahead and run this again with make scores, enter. What did I do wrong here? I think I got a little too ahead of myself. Let me increase my terminal window. Let's focus on line 10 here first. Error, use of undeclared identifier score 1. What did I do here that was dumb? Yeah. Right, so I didn't declare score 1. I've got old code, right? So I just kind of honestly got ahead of myself here, not even intentionally. So let me go ahead and shrink my terminal window again. I need to finish my thought here. So let me clear my terminal, and let me change this now to be scores bracket 0 plus scores bracket 1 plus scores bracket 2. So it's a little more verbose because I've got these square brackets, so to speak. But I think now my code is consistent. So let me make scores now. It now compiles. /scores gives me indeed the same rough average with those same values. All right, so let me go ahead and maybe enhance this a little bit. It's a little silly to have to write a special program just to check your average of 3 test scores, like 72, 73, 33. Why don't I actually make the program dynamic and ask the human for that average, for those scores? So instead, let me do this. How about we get rid of the 72 and change this to getInt, and I'll just prompt the user for a score. Let me get rid of the 33 and change 73 and get this to be getInt, score, quote unquote. And then lastly, get rid of the 33 and replace it with getInt, quote unquote, score. GetInt is a CS50 thing for now, so I need to include cs50.h as always. But I think now it's sort of a better program because now I can compile it once, I can even share it with my friends, and now any of us can average 3 scores on some class's test. They don't need to know the code or rewrite the code just to type in their scores. So make scores, worked, /scores. Now I can type anything I want. Maybe it's a 72, 73, 33. Still get the same answer. Or maybe I'm having a better semester, 100, 100, maybe 99. And now we get still a pretty high score there. But now it's dynamic. Now you don't need the source code. You don't need to recompile the program. It's just going to work again and again. But this too, let me propose that this code is correct if I want to get 3 scores from the user. But these highlighted lines now, 6 through 9, are they well designed, would you say? Yeah. Yeah, right? We can use a loop is the spoiler here. Why? I mean, my God, it's like the same code again and again and again. The only thing that's changing is the number. And it should have kind of had some code smell again, because if I keep typing the same thing again and again, like that's clearly an opportunity to better design something. So let me do this. Let me go ahead and still create my array of size 3. But let me use our old friend, the for loop, for int I equals 0, I less than 3, I plus plus, and then in here, let me do scores bracket. We haven't seen this before, but any intuition? Scores bracket I, because that will use whatever I is, be it 0 or 1 or 2 in iteration, and then I can get an int asking the user for score without having to repeat myself again and again. So hopefully, if I didn't make any typos, make scores. All good. /scores, 72, 73, 33, and we're back in business. But the code is arguably now better designed because now I haven't actually hard-coded the scores, and I haven't actually copied and pasted any of that code. Well, if we consider now what's going on inside of the computer's memory, it's pretty much the same in terms of the values. But instead of the variables being literally score 1, score 2, score 3, there's just one variable. It's an array called scores, but you can index into its 3 locations by using scores bracket 0 to get the first, scores bracket 1 to get the second, scores bracket 2 to get the third. But this is key. The memory is contiguous. It's only the screen is only so large, so it wraps around. But physically, digitally, the memory is contiguous, top to bottom, left to right. And that's important. Why? Because the brackets indicate 0, 1, 2, that each of these integers is just one integer away from the next. It can't be randomly down here all of a sudden. It's got to be back to back to back. All right, now equipped with that paradigm, what more could we actually do here? Well, it turns out it's worth knowing that it's possible in code to even pass arrays around as arguments. And let me just whip this program up somewhat quickly just so you've seen it before long. But let me go ahead and do this. Let me propose that I create a function that does this averaging for me. So I'm going to create a function called average that returns a float. And the arguments this thing is going to take, let's see, it's going to be the array. So it turns out if you want to take in an array of numbers, you can call it anything you want. This is how you tell C that a function takes not an integer, but an array of integers. And you don't have to call it array. I'm doing that just for the sake of discussion. It can be called x. It can be numbers. It can be anything else. I'm just calling it array to be super explicit as to what it is there. Now, how do I change my code down here? What I think I'm going to do for the moment is just this. I'm going to get rid of this code here where I manually computed the average. And let me just call the average function here by passing in the whole array of scores. So this is just an example of abstraction. Like now I have a function called average. I don't care. I don't have to remember how it works once I implement it. And it just kind of tightens up my main code a little bit. But I do still have to implement this. So later in my file, let me repeat myself before. The only time it's OK in C to repeat yourself again and again by typing out again average and then int array open bracket. But now not a semicolon. Now I have to implement this thing. And I can implement this in a bunch of different ways. But I don't know, in advance, I can't just do this. I can't just do array bracket 0 plus array bracket 1 plus array bracket 2, unless this program's only ever going to work on 3 numbers. So, let me go ahead and do this. Let me first propose that there's a poor design here. In my main function, what value have I repeated twice? Among the highlighted lines, what jumps out at you as twice? Yeah, the length of the array is just 3. Now, it's not a huge deal that I type the number 3 on line 8, on line 9. But this is exactly the kind of like shortcut that's going to get you in trouble eventually. Why? Because eventually you or someone else is going to go in, make the array bigger or smaller. And you're not going to realize that magically that same number is in 2 places. And indeed, this is what a programmer would often call a magic number. A magic number is one that just kind of appears magically. And you're on the honor system to change it here if you change it here. And then you change it over here. Like, that's not going to end well if the onus is on the programmer to remember where they hard-coded, that is, wrote out 3 explicitly. So anytime you reuse a value like this, you know what? We should probably do what we did last week. which was to declare a variable, perhaps at the very top of my program, so it's super obvious what it is, called maybe n, and set that equal to 3. Better yet, what did I do last week to make sure that I can't screw up and accidentally change that value? Yeah, constant. And the keyword there was just const for short. And now I have a global variable, global in the sense that I can access it anywhere, that is called n. It's an int, and it's always going to be 3. And now I can improve my main function a little bit by just changing the 3's to n. So now if a colleague realized, oh, wait a minute, there's 4 tests this year, you change n to 4, recompile the code, and it just works everywhere else. Except in my average function. Let me change it back to 3, just for consistency. This is not going to fly now to just sum up things like this, for instance, and then return this divided by 3. Why will this not work now, as I've defined it? Yeah. OK, I might be returning an integer value when I intend to return a float per this, but I think I'm OK because I used that little trick where I made sure that at least one of the numbers in my arithmetic expression is, in fact, a floating point value. And just by adding the point 0, make sure that everything gets treated as a float. So I think that's OK. Oh, sorry, a little louder? Exactly. So left hand's not talking to the right hand here, in that my current implementation of average is still assuming that there's only going to be 3 tests or whatever. But wait a minute, I just went through the trouble of modifying this to be n generically. And if I change this to 4, I'm not going to be happy perhaps with my average, because now I'm going to ignore one of my test scores altogether. So let me change this back to 3. And unfortunately, if it's a variable now n, and therefore I have literally a variable number of scores, how do I take the average of a variable number of things? I mean, what's my building block there? Yeah? Yeah, why don't I use a loop that goes through the array and adds things up as you go? I mean, kind of like grade school. As you take the average on your calculator or paper pencil, you just keep adding the numbers together, and then you divide at the end by the total number of things. So how can I do this? Well, let me change my implementation of average to first declare a variable called sum or whatever, set it equal to 0. So this is like me on my piece of paper getting ready to count, or my calculator, of course, when you turn it on, typically defaults to 0. And now let me do for int I equals 0. I is less than a nope, I didn't do that. N, I is less than n, I plus plus. And now in here, let me go ahead and add to the current sum whatever is in the array's location I. And then down here, I think I can just return sum divided by nope, not 3.0, n. Perhaps here? And actually, I think I'm going to get, let's make sure it's a float. Let's use the typecasting trick, just to make sure I don't accidentally shortchange someone and throw away everything after the decimal point. So it just escalated quickly, right? Like average just got a lot more involved. It's not just a single one line of code, but now it's dynamic. I initialize a variable called sum to 0. In this loop, I go through and just keep adding to sum, which is initially 0, whatever's in array bracket I, or specifically array bracket 0, array bracket 1, array bracket 2. That gives me a total sum that I return divided by the total number of things. Now, this I can tighten slightly. Recall that this is syntactic sugar for just adding things. I can't use plus plus, because that only literally adds 1. But I can use here plus equals. Questions on this implementation here? Really, the only takeaway, or the most important takeaway, is that this is the syntax for how you tell a function that it expects a whole array, not a single variable like an int or the like. You literally use square brackets, but you don't specify the length inside there. Yeah? What about the variable at the top? Good question. What do I have it defined as at the top? This variable n, it must be an integer if you're going to use it inside of an array's square brackets here. So this line 10, notice, no longer says 3, it says n. And so whatever n is, 3 or 4 or something else, that's how many integers I will get in that array. And it must be, by definition of an array, an integer that goes in those square brackets. And here's a common source of confusion. When you create the array, that is, declare it, you use square brackets like this, where you put the total number of elements you want. When you subsequently use the array, like I'm doing here, you don't mention int again, just like you don't mention int again and again once a variable exists. You use the square brackets still, but you don't use n. You use 0 or 1 or 2, or generically here, I. So when C was designed, they sometimes used the same syntax for two different ideas or contexts. Yeah? Good question. Do I have to include line 6? Short answer, yes, because of the reason we ran into last week. C, or Clang really, reads your code top to bottom, left to right. And so if the compiler sees some mention of this function average on line 16, but you haven't told the compiler that average exists, you're going to get an error on the screen. So the conventional way to do that is you just copy paste the first line of code from the function. It's so-called prototype or declaration. Yeah? Really good question and a perfect segue. Is there a library you can use if you don't know the size of the array? No. And so if any of you have programmed in Java or Python or other languages, you can actually just ask the array, like, how big is it? In C, you and I, the programmers, have to remember it. And so short answer, no. There's no function that will just automatically do this for us. And in fact, let me make a more subtle claim that it's fine to use global variables like this if they're really for configuration options. Why? It's just convenient to put them at the very top of the file because everyone, you, your colleagues, your TAs, are going to see them at the top of the code. But you really shouldn't be using them everywhere throughout your code. It'd be better if the average function itself were independent of that special variable. So by that I mean this. You know what I should really do if I really want to be well designed? I should pass in the length of the array to the average function. I should give the average function a second argument. I'll call it length, for instance, but I could call it anything I want. And so rather than putting n all the way down here at the bottom of my file, let me just dynamically say length instead. And this is a subtlety, and no need to get too tripped up over this. But this now is just an example of how the same function can take not one but two arguments. But indeed in C, you must remember yourself what the length of an array is. You can't just ask the array via some syntax like you can, those of you who've programmed before in Java or Python. Yeah? Good question. Would it be better designed to write a function that computes the size? Short answer, can't do that in C. As soon as you pass an array into a function in C, you cannot figure out its size if it's a generic array like that of integers. There are special cases that you can do that, but in general, no. It's just not possible in C. And if that's some frustration, honestly, this is why more modern languages add that feature. Why? Because it was really annoying, as I'm alluding here, to not having that information. Now, just to make sure I didn't screw up anywhere, let me compile this final version of scores. Suspense, all good, /scores, 72, 73, 33, and we're still back in business. So this version's more complicated, and as always, we'll have this version on the course's website for reference. But the point really is that arrays not only can be used as containers to store multiple values, 3 or more in this case, you can also even pass them around as arguments. As such. All right, now besides that, let's simplify for just a moment and consider now the world of chars. If we've just got single bytes, where does this lead us, and how does this get us ultimately to strings to solve problems like readability and cryptography and the like? Well, here, for instance, are 3 lines of code out of context that simply store 3 chars. And you can already see where this is going. Having 3 variables called C1, C2, C3 is clearly going to end up being bad design because of all the silly redundancy here. But notice I'm using single quotes like last week because these are single chars. What does this look like in the computer's memory? Well, it looks a little something like this. If we clear out the old memory, C1, C2, C3 probably will end up here. Maybe not literally in the top left-hand corner. This is just an artist's rendition. But C1, C2, C3 will probably end up like that. Now, what's really there? It's really those same 3 numbers, 72, 73, 33. But how many bits does a byte have? Just 8. So if we were to look at the binary representation of these characters, it would only be 8 bits each. That's enough to store small numbers like 72, 73, 33. We're not dealing with Unicode and emoji and the like, but the point is the same. You don't have to use 4 bytes to store these numbers. You can use a different data type like chars, and underneath the hood, it's indeed going to use just single bytes for each. But this is sort of like this isn't really how we implement strings, right? When you wanted to say hi last week or this, we used double quotes, and we wrote all of the things together and used one variable, not 3, right? When I typed in David, I didn't have a variable for D, A, V, I, D. I had one variable called name that stored the whole thing. So in C, we keep talking about these things called strings. We'll see eventually that strings are not necessarily what they seem to be. But for now, the key thing about strings is that they're variable length, so to speak, right? They might be 3 characters, hi, or 5 characters, David, or anything smaller or larger. So how do we go about implementing strings if all we have at the end of the day is my memory? Well, here is an example of just creating declaring and defining a string called s. S because it's just a simple string, and quote unquote hi in double quotes. What does this look like in the computer's memory? Well, let's clear it again. And here now, because it's technically stored in one variable s, here is how I might draw it as an artist. It's 3 bytes in total, hi exclamation point, but there's no C1, C2, C3. It's just the whole thing is s. But it turns out that a string, fun fact, is really just what underneath the hood? Kind of leading up to this. What is a string if this is how it's laid out in memory? Literally, it's just an array of characters. And we didn't have to know about arrays last week to use strings. This is where, again, the training wheels are starting to come off. But a string is just an array of characters. Hi exclamation point, for instance. So technically, an array, or a string called s, is really a variable called s that allows you to get at the first character with s bracket 0 if you want. S bracket 1, s bracket 2. You can literally get individual characters just by treating s as though it's an array, which it really is underneath the hood in this case. But there's a catch. How do you know where strings end? In the past, when I drew some integers on the screen, I claim they always take up 4 bytes. If I had drawn a long, it always takes up 8 bytes. If I had drawn a character, it always takes up 1 byte. But how many bytes does a string take up? Yeah, I mean, that's kind of the right answer. In this case, 3, it would seem. But if it's David, that's a good 5 characters. But where do we put the number 3? Where do you put the number 5? Right? This is literally all that's into your computer. This is all our building blocks in front of us. So where does the 3 go? Where does the 5 go? Well, it turns out you can solve this in a couple of different ways. But the way humans decided to implement strings years ago is indeed an array. But they added 1 extra byte at the end of every such string array just to make clear with a so-called sentinel value that the string ends here. Why? So that if you have 2 strings in the computer's memory, like hi and bye, you know where the barrier is between like the exclamation point of one and the letter B in the next, right? You need some kind of delimiter. And so what really is underneath the hood is this. When you store a string in memory, when you type in a string as the user, if you type in 3 characters, it's going to use 3 plus 1 equals 4 bytes in total. If you type in David, it's going to use 5 plus 1 equals 6 bytes in total. Why? Because C automatically adds this special 0 at the end of the string. I've drawn it with \0 because this is how you represent 0 as a char, as a character. But this is literally just 0, as we'll soon see. So anytime there's a string in memory, it always takes up 1 more byte than you yourself as the programmer or human typed in. In fact, if we convert this again, just for discussion's sake, to those integers, what's literally stored in the computer's memory is going to be 72, 73, 33, and now a 0. And the computer, because of C and how it was invented, it's just smart enough to know that when you print out a string, it prints out every character until it sees a 0, and then it just stops printing. In particular, printf knows how this works, and this is why printf knows when to stop printing. Decimal numbers are not that enlightening. We'll generally write the characters like this. And again, \0 is just special symbology, like it's what the programmer types to make clear that you're not saying hi 0, you're saying hi, and then it's a special 0. Specifically, it is 8 0 bits that indicate that it's the end of the string. Technically, that \0, if you want to be fancy, it's called null, N-U-L. And it turns out you've seen this before, though we didn't call it out. Here's that same ASCII chart from the past couple of weeks. If I highlight this, what is decimal number 0 mapping to? NUL, which is just programmer speak for the special null character. All 0 bits, that means the string ends here. This all happens automatically for you. You do not need to create these null characters or these zeros. Any questions then on this implementation thus far? Any questions here? No? Well, let me do this. Let me go back to VS Code in a second, and let's actually corroborate this with some code. Let me go ahead and create a small program called hi.c. And how about we do this? Let me include standardio.h. Let me include, let me type out int main void as always. And now let me do something simple and kind of bad, but char c1 equals quote unquote h in single quotes. Char c2 equals quote unquote I in single quotes. And lastly, char c3 equals exclamation point in single quotes. And now let me just print this out. I can't use %s because that is not a string. That's literally 3 chars because that's the design decision I made. But I could do this. %c, 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 which we haven't seen before, but %s is string, %i is int, %c is indeed char. So let me put a \n at the end for cleanliness, and now do c1, c2, c3. So this is like a char-based version of printing strings. So let me make hi, and then let me do /hi, and it looks like I used printf with %s. But I did things very manually by printing out each individual character. What's cool now, though, is that once you know that characters are just numbers and strings are just characters, you can kind of poke around. Let me change all 3 placeholders to %i instead. And this is totally fine, too. Let me rerun this. Make hi, actually, let me make one change just so we can see this. Let me add spaces just for aesthetic's sake. Let me do make hi, /hi, enter, and voila. Like now you can actually see the numbers that I claimed back in week 0 were in fact happening underneath the hood. Well, this is not how you would make strings. It'd be incredibly tedious to have 3 variables for 3-letter words, 5 variables for 5-letter words. We've been using, of course, strings since last week, so let's do that instead. String s equals quote unquote double quotes hi. For this, no, because of these training wheels, I need to include the CS50 library, but we'll come back to that in the coming weeks. But for now, I'm going to go ahead and create a string s called quote unquote hi. And now I'm going to change this to be my familiar %s, and now just print out s itself. This, of course, is the same thing as last week. /hi gives me the exact same thing. But now we're dealing, of course, with strings. But how can we see a little beyond that? Well, how about this? Let's poke around further with today's primitives. Even though s is a string, I could technically print out its first character with %c by doing s bracket 0. I could technically print out its second character with %c by doing s bracket 1. I could print out its third character with %c and printing out s bracket 2. So again, this just derives logically from my understanding now of that strings are arrays, as you note. Let me do make hi, /hi, and no visual change, but I'm just kind of now tinkering around. And in fact, if you're really curious, let me do this. Let me change these back to I, back to I, and let me add a 4th one, because if I'm really curious now, let's see what's at s bracket 3. This is the 4th byte, and even though the string itself is hi, I think we can corroborate this whole null thing. Make hi, /hi, enter, and there it is. You could have done this last week if you really wanted to geek out on strings, but like for now, it's just revealing what's going on underneath the hood. Questions then on what these strings are? Yeah? Why do we need the bracket? Why do you not need brackets? Good question. Why do I not need brackets on line 6? Because s is a string. We'll see in a couple of weeks that s is essentially implemented underneath the hood, indeed, as an array, but that happens automatically for you. You can treat s as just a variable name without square brackets. You will use square brackets when you have arrays of ints, or you manually create arrays of chars or doubles or floats or anything else. But strings are special. Why? I mean, every program you write seems to use strings, text in some form. We're humans. We like text, not just numbers and such. So this is just treated a little specially in C and many other languages as well. Other questions on this here? No, let's add then one other string to the mix. So instead of just saying hi, why don't we consider a version of the program that says both hi and bye? And I claim now that that \0, that null character, is going to be ever more important now if we've got two strings in memory so that C knows how to distinguish one from the other. So let me go ahead and just get rid of these two lines for the moment. Let me recreate string s equals, quote unquote, double quotes, hi. Let me give myself another one. And because I'm just playing around, I'll choose very short variable names. String t equals, quote unquote, bye, exclamation point. And then let me just print them both out. Let me go ahead and print out %s \n, comma s, and then printf %s \n, and then t. So very simple demonstration of just these two variables, make hi, /hi, and of course it prints out two lines, one after the other. What's actually going on underneath the hood? Well, let's go back to the computer's memory. Hi, I think, is going to be, I claim, pretty much the same. So s, I'll claim, is in the top left, followed by the \0. And that's important now because bye probably is going to end up there. And visually it wraps just by nature of how I've drawn this grid of bytes, but it's contiguous. B, Y, E, exclamation point, null, aka \0. This is now helpful to printf because now printf knows where one begins and ends by way of that special null character. But we can poke around now too. What else can I do here? How about this? How about I go into my code here, back to VS Code, and let me go ahead and say something like, well, if I've got two of these strings, let's put them in an array. Let's kind of do this sort of arrays in arrays, sort of Inception style here. So string words, bracket 2. So give me an array of two strings is what I'm saying here in code, even though we've not done it with strings yet. We only did it with ints. And now let me do this. The first word, aka words bracket 0, will equal, as before, hi. And now words bracket 1 will equal, quote unquote, bye. Bytes. So bye. And now I've done the exact same thing. But again, I'm just avoiding having s, t, q, r, and like all these different variables in my code. I just now am treating them as one single array of strings. How do I change my code down here? Well, if I want to print the first word, I do words bracket 0. And if I want to print the second word, I do words bracket 1. This is not a useful exercise at the moment because I'm just making my code more complicated. But again, it allows us to poke around and see what's going on because there's that hi and bye. But watch this. If I really want to be cool, I can do this. Let's print out %c, 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 \n. And then here, %c, 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 %c. So 4 of those. And now, here's where things get interesting. Words is an array of strings. But again, if I may, what's a string? An array of characters. So just use the same logic. If words is an array of strings, you get at the first string with words bracket 0. How do you get at the first character in the first string? Bracket 0. Words bracket 0, bracket 1. And lastly, words bracket 0, bracket 2. And now down here, words bracket 1, but the first character is there. Words bracket 1, the second character is here. Words bracket 1, the third character's here. Whoops. Third character's here, and words bracket 1, the fourth character is here. Like, this is not how people program. This is only for demonstration's sake. My God, it's so tedious and verbose already. But if I make hi now, /hi, now I'm like manually reinventing %s if I forgot it existed using %c alone. But you can indeed manipulate arrays in this way. But because strings are arrays of characters, you can manipulate strings in this way too. Any question now on this syntax? Any questions here? No? All right. Well, let's go ahead and propose that we solve a couple of other problems we might not have as before. But first, a quick visual of what's been going on underneath the hood here. If here again is where we left off on the screen, hi and bye back to back, here is really how I just treated these things. S bracket 0, 1, 2, 3, and then T 0, 1, 2, 3, 4. But really, once I put them in an array, the picture becomes this. Words bracket 0 is the whole hi. Words bracket 1 is the whole bye. But if I really get into the weeds and start indexing into individual characters in those strings, all I'm using is new syntax in order to represent these same values here. Questions then on these representations before we forge ahead? No? Yeah. Does the new line character, say that once more? Really good question. Does the new line character take up any space? It does when, so far as printf is concerned, but I'm not storing the \n in my strings. Printf is being manually handed that thing instead. All right, so let's go ahead then and consider how we might solve some problems that have arisen now with these strings as follows here. Let's do this. Let me go back to VS Code here, and let me go ahead and open up a new file called, how about length.c. And let's consider for a moment how I might actually figure out what the length of a string is, which is distinct from the length of an array. I claimed earlier you cannot figure out dynamically what the length of an array is, but I can figure out the length of a string specifically because of this implementation detail of that null character. So let me go ahead and do this. Let me include cs50.h in this second program here. Let me include standardio.h as before. And let me do this. Int main void. And in the first thing I'll do is just get a string from the user. I'll ask the user, as always, for their name. So I'll call getString and say, what's your name, question mark, as always. And then down here, if I want to figure out the length of this string and print the length out on the screen, well, I can kind of do this similar in spirit to the average, where I'm accumulating something. Let me go ahead and initialize n to 0. Let me give myself it's not a for loop because I don't know in advance how long it is. But what if I do this? While the value at name bracket n does not equal single quote \0. Crazy syntax at the moment, but it's just the culmination of these various building blocks. Let me just finish the thought here. N++. And then down here, let's just print out with printf and %i that value of n. So I claim this is going to show me the length of any string I type in, whether it's hi or bye or David or anything else. I initialize a variable to 0. And that's good because that's where you start counting in general. While name bracket 0 does not equal \0. What is this saying? Well, if name is the string the user typed in, and name is just an array, as you noted, then name bracket 0 is going to be the first character. And I'm asking the question, well, does the first character not equal \0? And if I type in David, D, it's not. So I keep going, and I add 1 to n. Then I'm going to check name bracket 1. Well, if I typed in David, name bracket 1 is going to be A. A does not equal \0, and so it's going to go again. And again, and again. But 5 steps in total later, it's going to get to the byte after DAVID, realize, wait a minute, that is a \n. The loop finishes, and I print out the total length. Arrays in general do not have this null character. However, strings do. Again, strings are special versus all of the other data types we've talked about thus far. But how could I, for instance, do this differently? Well, let's actually factor this out as a function, as I've commonly done. But rather than implement it myself, you know what? It turns out what's nice about strings being so common, there are many other people who have solved these problems before. And in fact, there's a whole string library in C. It is used by way of a header file called string.h. And what string.h is a library of string-related functions. In fact, you can see in CS50's manual pages for C, the string.h functions, at least those that we recommend as most useful. And in particular, if you poke around there, you'll see that there's a function called strlen. Means string length. It was named very succinctly just because it's a little easier to type than string length. But strlen tells you the length of a string. So how might I use this in my code here? Well, it turns out I can simplify this quite a bit. Let me get rid of my loop, get rid of my counting manually, and do something like this. Int n equals strlen of the human's name. And now I'll just use printf as before with %i \n. And output the value of n. But there's a bug at the moment. What have I forgotten to do? Yeah, I have to include the header file at the top of the screen. So at the top of the code. So let me also include string.h at the top of my file so that C knows that in fact strlen exists. Let me go ahead and make length as before /length. Or actually really for the first time, what's your name? DAVID. And hopefully I'm going to see, in fact, 5. By contrast, if I run it again and type in hi exclamation point, now I see 3. So Stirling is just one of the functions in that library, and there's so many more. In fact, yet another library that might be useful moving forward is this one, ctype, which relates to C data types and lots of functions therein that can be useful. For instance, if you review its documentation in the manual pages online, you'll see that there are functions via which we can solve problems like this. Let me go ahead and propose here. Let me see. Let's do example here involving how about checking if something is uppercase or lowercase and converting it to uppercase only. Let me go back to VS Code and code a program called uppercase.c. In this file, I'm going to start by including now, as always, cs50.h. I'm going to include standardio.h. And I'm going to add one other to the mix, which is string.h now too. So I can access the length of things as needed. Int main void comes next. And then within my main function, I'm going to go ahead and declare a string called s. I'm going to call getString as before. And I'm going to go ahead and just ask the user for a string called before. I want to do a before and after. Whatever the user types in is before, but I want to force everything to uppercase thereafter. Let me now, in this loop here, do this. Let me printf, quote unquote, after, just so we can see this on the screen. And let me do for int I gets 0. I is less than Stirling of s, I plus plus. What am I about to do? I'm about to iterate over every character in the string from left to right, from 0 on up to, but not through the length of s. And how do I check if something is lowercase so that I can actually force it to uppercase? Well, it turns out I could do this literally. If the character in s at location I is greater than or equal to capital A, ampersand ampersand, which means and instead of or, which we saw in the past, s bracket I is less than or equal to little z, that means logically in English that this is indeed lowercase. How do I now convert it to uppercase, this character? Well, I could just literally print out the same character, but that would not be the answer here, because that's not changing the value. But what could I do instead? Well, let me actually pull up here real fast the ASCII chart as before, and let's see if we can't glean some insight. If I pull up the same ASCII chart, and suppose the human has typed in a lowercase a, that's 97. What letter, I want to convert it to uppercase A, so what number do I want to convert the 97 to per week 0? So 65, we keep coming back to that one. What if the user types in lowercase b? I want to change the 98 value to 66 and so forth. And any quick math, how far apart are those? So it's always 32. Like uppercase to lowercase is always, wonderfully, good design, 32 away, one from the other. So what does this mean? Well, I think we saw earlier that underneath the hood, a char is just a number. You can certainly do arithmetic on it. And here again, if you understand these lower level primitives, what if I do this? Whatever s bracket I is, if I know on line 13 that it's lowercase, do I want to add or subtract 32? So I want to subtract because I want to go from like 97 to 65 or 98 to 66. So indeed, if you do some quick math, that gives you 32. So it suffices to just treat chars as numbers, subtract the 32, and printing it with %c, I think will just convert lowercase to uppercase. If you now fast forward to like the real world, Microsoft Word or Google Docs, if you've ever chosen the menu option that forces things to uppercase or lowercase on occasion, literally that's what Microsoft and Google have done. They iterate over every character in the document, check if it's lowercase, and if so, they subtract 32 from it and show you the new value. What if, though, it is not a lowercase letter? I think I can keep it easy and just print out the current letter unchanged if my goal is to simply force things to all uppercase, and that letter then would be s bracket I. So let me go ahead now and make uppercase. Hopefully no errors. /uppercase. And I'll now type in David with an uppercase D, but lowercase everything else. But now the after version is David. An aesthetic bug. Notice here I forgot to include, just for prettiness' sake, a \n at the end. No problem. I'll add that. Let me fix my mistake. Make uppercase. /uppercase enter. DAVID enter. And voila. And I deliberately added another space after the after just so that they would line up pretty, even though before and after have different numbers of letters. Questions then on this implementation of forcing something to uppercase, which in and of itself is not all that enlightening, but is representative now of how you can leverage these low-level primitives? Question? No? All right. Well, this honestly is tedious. My God, like does Microsoft, Google, everyone, you have to literally write out this code just to do something simple? Well, no. That's again why we have things like libraries. And increasingly now for problem sets, projects, and beyond, well, you just use libraries more often off the shelf so as to solve problems that surely other people have had before you. So how can I now use this library, ctype.h? Well, let me go back into my code. Let me include this among my header files here. I tend, just so I can skim things easily, I tend to alphabetize my headers, but that's not strictly necessary. But it allows me at a glance to realize, did I or did I not include something I need? Now let me go ahead and do this. It turns out if you read the documentation for the ctype library, there's a function wonderfully called if is lower that takes in a character as its argument, essentially, so s bracket I. And if that returns true, a Boolean value, if you will, well, I'm going to force it to lowercase. But I don't have to do this math anymore. Turns out in the ctype library, there's also a function called toUpper that takes a character as input, like s bracket I, and it just does the math for you so that you can abstract away the 32 thing and just know that someone else has solved that problem for you. Otherwise, I can leave my code unchanged down below because I'm not changing anything else. So if I do make uppercase now, and then /uppercase, DAVID with just a capital D, and now it still works. But if you read the documentation further, it turns out that toUpper is smart. If you pass in a character to toUpper that's lowercase, it obviously converts it to uppercase by doing that math. But if you pass in a character to toUpper that's already uppercase, the documentation you would see tells you that it leaves it unchanged. So I can tighten all of this up. I can get rid of the whole else. I can get rid of the whole if, and arguably now implement a program that's just as correct, but better designed. Why? Fewer lines of code, easier to read, lower probability of mistakes. Assuming the library is correct, it just makes it easier and faster for me now to write code. So if I now do one last time, make uppercase, enter, /uppercase, and type in my name, still working. But now notice we've whittled this down to far fewer lines of code, albeit using now this additional library. Questions then on how we did this? Well, even though this code, I dare say, is correct, it's not necessarily well designed just yet. In fact, there's one line of code, one function call in this current implementation that's more inefficient than it needs to be. And allow me to draw our attention to this here, line 10, wherein we're calling Sterling. But we're calling it inside of this for loop, specifically inside of the condition. And why might that not necessarily be the best idea? Well, is the length of the string s changing ever? I mean, certainly not within the span of this loop. And so here we are within our for loop on line 10, 11, 12, and 13, asking on every iteration that same question. What's the length of s? What's the length of s? What's the length of s? And in turn, we're calling Sterling every time, even though we're getting back the same answer. So I dare say a better solution here would be to maybe figure out the length of s earlier on in my code and maybe declare a variable, or perhaps do something that's syntactically a little more elegant. And in fact, a very common design in a loop like this would be to declare not just one variable like I, but to actually declare a second variable called n, for instance, where n is just some number. Set n equal to the length of s, but thereafter, inside of this condition, instead of calling Sterling of s again and again and again, what might I now do? I could instead just compare I against n itself, because n now will only be calculated once when it's initialized, just as I is initialized to 0. And thereafter, we're going to be comparing I, which is changing, against n, which will not be. So it's going to be marginally more efficient by design. Now, with that said, a good compiler could also recognize that there was this optimization possibility and maybe do it for us. But for now, best to get into the habit, best to develop the muscle memory for making those better design decisions yourselves. Questions then on how we did this? No? All right, a few final building blocks for the day. So we started by talking about those command line arguments that Clang uses, whereby anything after the command that you type at a prompt, be it make or clang or even CD in Linux, any word thereafter or something cryptic like -o is a command line argument. It's an input to the command. It's different from a function argument because a function argument, of course, is an input to a function. But it's the same idea. It's just different syntax after the $sign at the prompt. Well, it turns out that command line arguments are something you can now use in your own programs by accessing words after the prompt. And let me propose that we invent this as follows. Let me propose that we switch back to VS Code here. And I'll open a new file here called greet.c. So in greet.c is going to be a program that very simply greets the user. Had we written this last week, we would have done this. Include cs50.h, and then include standardIO.h, and then int main void. And then we might do something simple like string name equals get string, quote unquote, what's your name question mark. And then we would have printed out, as always, hello, comma, %s, and then plugging in that name. So this is the same program we've implemented many times just to make sure it works. Although, nope, that's not quite the same program. Semicolon's in the wrong place. This now is the same program. So make greet /greet, and I'll type in my own name, hello, David. So we're back there. Now, what's arguably a little annoying about this program, if I type in something else like Carter, enter, you know, I have to run the program, wait for the prompt, type in my name, hit enter. And that's fine. But imagine if every program worked like this, like make. Suppose you could only type make. Then you wait for a prompt. Then you type the name of the program you want to make. Then you hit enter. Or worse, in Linux, when you have to change directories, as you might have for problem set 1, what if you had to type cd, enter? Now type the name of the folder you want to change into, enter. I mean, it just slows life down. And so it just gets annoying quickly. So command line arguments just let you express your whole thought all at once. So how can I do this? Well, if I want to express the notion of command line arguments in my code, I could do something like this. I could, for the very first time, go up and get rid of this void, which as of today means this program takes no command line arguments. And I can change it to exactly this. Int argc string argv with brackets. Now, it's cryptic, admittedly, and let me zoom in. But I think we can perhaps infer now what's going on. If main now does not have void as its input, which means it takes no arguments, surely the spoiler here is that now main will take command line arguments somehow. Any guesses as to what argv is or will be? What might this represent? It's an array of strings, right, by way of the syntax. Yeah? Exactly. It will be all of the characters, or really all of the words that you type at the prompt. Argc as an int, any guess? Argument count is what it generally stands for, though technically you could call these things anything. But this is the convention. Because I claimed earlier that arrays don't keep track of their own length, if you want to know how many words the human typed at the prompt after your program's name, you have to be told not just the array of the words, but the length of that array. The strings you can figure out the length of using strlen, but you can't figure out the length of the array of strings, the collection of words that the human typed in. So how can I now use this? Well, let me go ahead and do this. Let me go ahead and change this program now just to be printf, quote unquote, hello, comma, %s \n, then argv bracket 1. So this is not the best version of my code yet, but it's my first. Make greet, and now let me do /greet David all at once. Enter. Hello, David. Now let me run it again. /greet Carter. Enter. Hello, Carter. You know, it's a marginal improvement, but I don't have to wait for getString to prompt me to hit enter. It's just speeding things up, you know, twice as fast. One less command to type in. But I deliberately did bracket 1. But what's the beginning of argv? It would be bracket 0. Well, what's that? This is sometimes useful, though for now it's not. Suppose I recompile my code and run this program now, greet David. Anyone want to guess what's in argv0? Say again? Greet. Enter. Hello /greet. So if you want, sort of Inception style, your program to figure out what its own name is, or at least how it was executed at the command line, at the terminal, you can look at argv0. In general, probably not that useful. Probably better to start looking at bracket 1, which was the first word after the program name. And if there were more, I could do this. How about argv bracket 2? Let me add in a second %s. Let me recompile greet. Let me do /greet David Malan, enter. And that too now works, taking in 2 words at the prompt. If I really want to be smart at this now, I could do something like this, though. How about if the count of arguments, aka argc, equals 2, then assume that the human typed in only their first name, and do printf hello, comma, %s, \n, and then argv bracket 1. Else, if the human did not provide exactly 2 arguments, the name of the program and their own name, let's just print out a default value, lest they forgot their name or they typed in 2 names or 3 names. Let's just do hello, comma, world as a default, and we'll just ignore what the human typed in. If I recompile this, make greet, I can do /greet and David again, enter. Oops. Sorry, what am I missing? Yeah, so newbie mistake. Else. All right, make greet again, /greet David, enter. There's my hello David. But if I omit my name, I just get the generic, like a default value. And if I get a little curious and I type in both names, then I get ignored too. Why? Because I just haven't built in support for argc of 3. I could do anything I want, but now we have access to these kinds of building blocks. All right, what else might I do here? Well, it turns out there might be some final features for us to now execute. Notice, though, that in C, despite what you might see in books or online tutorials, nowadays, the 2 official formats for defining a main function are either this, which we've been using now for 2+ weeks, or now this, whereby you change the void to int argc, and then for now, string argv, and then empty brackets. And we'll see that this too is a simplification, some training wheels, if you will. But for now, those are the 2 forms. Even though you will see in online tutorials and even books, some people use main in different ways. These are the 2 now to keep in mind. And I'll note that these command line arguments are kind of all over the place. Didn't probably expect to see this word on the screen here. And what does it mean? Well, it turns out that for decades, there's actually this program that comes with Linux systems in particular called cowsay. Why? Probably because someone had too much free time once and decided to write a program that creates ASCII art out of a cow saying something textually on the screen. But you use cowsay, just for fun, by way of command line arguments. So for instance, let me propose that I go back to VS Code here. Not because I want to write any code, but I just want to use my terminal window. And let me maximize my terminal window here. And let me go ahead and type in something like, how about cowsay space moo. So cowsay is not a program I wrote. It's been around for decades, but we installed it in VS Code for you in the cloud. It takes at least 1 command line argument. What do you want the cow to say? I can say cowsay moo and hit enter. And voila, there's my ASCII art of a cow saying moo on the screen. It can say multiple words. So I can say hello world, enter. And now it says hello world. So this is just an example of a silly program that uses command line arguments, but it takes others too. Just like Clang used this convention of hyphens to change the output of the program, dash something is just a super common convention with command line arguments when you want a very terse notation for some option, like output. In cowsay, I read the documentation, and it turns out there's a -f command line argument that allows you to change the appearance of the cow, if you will. So if I do cowsay -f duck, and then some other word like quack, it's no longer a cow. That command line argument turns it into a tiny, adorable duck instead. And then lastly, just for fun, because I spent way too much time playing with command line arguments, cowsay-f dragon, and then how about like rar, enter. You can even get this on the screen here. So this too is just an example of what you can do with these command line arguments now that we have this building block. And there's one final thing we can now do with code. There's one last feature today that we'll introduce before we now connect all of these dots to readability and encryption by talking lastly about something called exit status. It turns out that whenever your main function exits, it returns a secret integer that you can figure out as the programmer or an advanced user what it was. And these exit codes, exit statuses, are typically used to indicate errors. So for instance, over the past couple of years, if you've used Zoom and you ever got some kind of error, you might have seen a screen like this. It's usually not that helpful. Maybe tells you to click report problem or contact support. But very often in our human world on Macs, PCs, and phones, you see cryptic error codes, like literally numbers that probably only Zoom knows, or Microsoft, or Google, or whatever company wrote the software you're using. But that number corresponds to a specific error that some human somewhere knows might very well happen. These are used similarly, although under a different name that we'll talk about later in the term, on the web as well. Have you ever seen this, maybe not character, but number? So 404 means what? So error, yes, but really not found. So why? I mean, this is the most arcane thing, and we'll talk in a few weeks about like what this and other numbers mean. But numbers are all around us in technology, and they very often mean something to the technical people who wrote the software, less so to humans like you and me. Why so many of us recognize 404 is kind of weird, that like that's been around long enough that we all know it, but it really is just a special number that represents an error of some sort. So it turns out the last thing we'll reveal today about what we've been taking for granted for 2 weeks is what the int is in main. We've seen just a moment ago that the thing in the parentheses, which up until now has been void, which means no command line arguments, now int argc string argv brackets just means yes, command line arguments. And we've seen how to access them. So the last piece of the puzzle, honestly, of all the cryptic syntax the past 2 weeks, is just what int means. Int is always there for main, and it indicates that main will always return an integer, even though you and I have never done so explicitly. Usually, main returns 0 by default. But it would be weird if you saw an error message saying 0. So 0 is just hidden. You would never see it on the screen. But it's happening automatically by way of how C is designed. So let me write one final program here. I'll call it, for instance, status.c to show you these exit statuses. Code of status.c. And then up here, let me do something simple like include cs50.h, then include standardio.h, and then int main. Let's use a command line argument. Int argc string argv. So that's copy paste. But now let's do this. If argc does not equal 2, why don't we do something like this? Let's not just default to hello world like last time. Let's yell at the user. So let's say something like printf missing command line argument, so that they know they screwed up and they need to run the program again correctly. Else, let's go ahead and say print out, as before, hello, comma, %s, and then plug in argv bracket 1, so the human's name from the prompt. Now at this point, let me go ahead and run status, /status, and I'll type nothing first. I get yelled at. This time I'll type it again, /status David, and it works properly. But now let me show you a somewhat secret cryptic command. You can type this at your prompt, and it's just a coincidence that there's another $. Echo $? Totally arcane, but it allows you to see what exit status your program has ended with. So let me run this again the wrong way. /status. OK, I get the error message. What was secretly returned? I can't see it. There's obviously no error screen. But by typing echo $? I can see that, oh, my program automatically, by default, returns 0. However, if I run it again correctly, /status David, enter, this is the correct version. But if I run echo $status again, it's still entered with 0. And long story short, this is just a missed opportunity. When something goes wrong, why don't I return a value other than 0? 0 by default means success, and it's always there automatically. But you can control this. I can go into my code here and return 1. Else, if something works fine, I can return 0 by default. And honestly, if I omit the return 0, again, 0 automatically is returned. So let me go ahead and, though, be explicit, just so I know what's going on. Make status again, /status. And let's do this correctly with David. Enter. Hello, David. Echo echo $? 0. So all is well. But now if I do /status and nothing, or multiple things, but not just David, enter, I get the error message. But now if I do echo $? Voila, There now is the 1. So what does this now mean? This is, in the graphical world, we would just show something like this on the screen, which is a little more informative to the user. But even in the Linux world, where you don't have a GUI necessarily, even for the programs we've written, you can check these exit statuses. And in fact, more comfortable, more advanced programmers, when they write code that calls programs, be it cow say or anything else, you can in code check what the exit status is of a program and then decide, did my program work or did it not? And now let's connect the final dots before we adjourn for some fruit snacks. Cryptography, namely one of the applications this week via which you'll be able to send, if you will, secret messages, and better yet, decrypt secret messages. This will be in addition to perhaps analyzing the readability of text using heuristics, like we identified at the start of class 2. So cryptography is just the art, the science of encrypting information, scrambling information, so that if you have a secret message to send in so-called plain text, you can run it through some algorithm and turn it into what's called ciphertext, thereby encrypting it. And only someone who knows what algorithm you've used and what input you've used to the algorithm, theoretically, can decrypt that process and convert it back to the original message. So if we use our mental model from last week, here is a problem. Here is an input and output. The goal, I claim here, is to take some plain text, like the message you want to send. Think back to grade school. If you ever passed a note to a friend or to your crush saying, I love you, it's a little awkward if the teacher or someone else intercepts the paper and in English it just says, I love you, or whatever it is. It'd be nice if you had at least encrypted it in some way. But the other person needs to know what algorithm you used and what inputs you used to that algorithm, so that ultimately they can decode the so-called ciphertext, which is the output. So what goes inside of the box today? Well, an algorithm, as it relates to cryptography, is called a cipher. And a cipher is a fancy name for an algorithm that encrypts text, from plain text to ciphertext. The catch is, there needs to be not just the algorithm, there needs to be an input to it. And so, for instance, you might draw the picture like this for the first time today. And we've seen this in code. You can give multiple inputs or arguments to functions. So in this black box, can you imagine passing in the message you want to send and then some secret? So for instance, suppose that the simplest thing I could think of as a kid was, instead of sending the letter A, why don't I write the letter B? Instead of the letter B, why don't I write the letter C? So I can kind of shift the English alphabet by one space. So A becomes B, B becomes C, dot, 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 Z becomes A. You can wrap around at the end. And let's assume no punctuation in this part of the story. So that's a very simple algorithm. Add a value to each letter and send the value as the ciphertext. And now the teacher, the classmate, they have to know that you use not only this rotational algorithm, also known as a Caesar cipher, they also need to know what number you use. Did you add 1 to every letter, 2 to every letter, 25 to every letter? Now, if they're super smart and probably not the young age in this story, they could also just try all possibilities. And that would be an attack on the algorithm. This is not a sophisticated algorithm. But it's enough to send a message in class. So if the two inputs now are hi as the plain text message, and 1 as the so-called key, the secret number that only you and the other person know, you might be able to encrypt a message from one way to the other. And so in this case, for instance, hi would become IJ, exclamation point. In this version of the algorithm, we're not going to bother with numbers or punctuation. We'll only operate on A through Z, be it uppercase or lowercase. So now if you were to receive a slip of paper in class with IJ on it, you know, you, the recipient, would know what it is so long as you know that the sender used 1, because you just reverse the algorithm and you subtract 1 instead. The teacher, you know, they probably don't know what this means and they're not going to spend time hacking the message, so it just looks scrambled to them. And that's what we get from encryption. Someone who intercepts it, be it in class or in the real world, on the internet or anywhere else, can't actually figure out, ideally, what it is you have sent. The opposite, of course, is indeed called decryption, but the process is the same. We now pass in -1. And so how about this? Why don't we end with a demonstration here? UYJTXBTDT50. There's a bit of a tell there. If we pass that in and do -1, well, how do we get out the plain text originally? Well, if this is the ciphertext and we subtract 1 from each letter, I think U becomes T, I becomes H, J becomes I, T becomes S, X becomes W, B becomes A, T becomes S, D becomes C, T becomes S. And this was indeed CS50. Have a duck on your way out and some snacks in the lobby. right, this is CS50, and this is week 3 already, wherein we'll take a look back actually at week 0, where we first began. And in week 0, recall that everything was very intuitive in a sense. We talked not just about representation of information, but algorithms. And we talked about tearing a phone book again and again, and that somehow got us to a better solution. But today we'll try to start formalizing some of those ideas and capturing some of those same ideas, not in pseudocode just yet, but in actual code as well. But we'll also consider the efficiency of those algorithms, like just how well designed our algorithms actually are. And if you recall, when we did the phone book example, wherein I first had an algorithm searching 1 page at a time, and then second went 2 pages at a time, and then third started tearing the thing in half, recall that we, with a wave of the hand, kind of analyzed it as follows. We proposed that if the x-axis here is the size of the problem, like number of pages in a phone book, and the y-axis is the time required to solve the problem in seconds, minutes, page tears, whatever your unit of measure is, recall that the first algorithm was this straight line, such that if you had n pages in the phone book, it might have this slope of n, and there's this one-to-one relationship between pages and tears. 2 pages at a time, of course, was twice as fast, but still really the same shape. The yellow line here indicating that, yeah, it's n over 2, maybe plus 1 if you have to double back, as we discussed, but it's really still fundamentally the same algorithm, 1 or 2 pages at a time. But the third algorithm, recall, was this one here in green, where we called it logarithmic in terms of how fast or how slow it was. And indeed, the implication of this algorithm was that we could even double the size of the phone book, and no big deal, 1 additional page tear, and we take yet another 1,000-page byte out of the phone book. So today, we'll revisit some of these ideas, formalize them a bit, but also translate some of them ultimately to code. And all of that now is possible because we have this lower level understanding, perhaps, of like what's actually inside of your computer. This, of course, is your computer's RAM, or memory. And recall that if we kind of start to abstract this away, your computer's memory is really just a grid of bytes. In fact, we don't have to look at the hardware anymore. And we looked at a grid of bytes like this, whereby each of these bytes could be used to store a char, an int, a long, or even an entire string at that. But let's focus perhaps just on a subset of this, because last week, of course, we emphasized really arrays, storing things in arrays. And that allowed us to start storing entire strings, sequences of characters, and even arrays of integers if we wanted to have multiple ones and not just multiple variables as well. But the catch is that if you look inside of an array in the computer's memory, and for instance, suppose these integers here are stored, it's pretty easy for us humans to glance at this and immediately find the number 50. You sort of have this bird's eye view from where you're seated of everything on the screen, and so it's pretty obvious how you get to the number 50. But in the world of computers, of course, it turns out that this is hardware, and computers, for today's purposes, can only do one thing at a time. They can't just take it all in and find instantly some number like 50. So perhaps a decent metaphor is to consider the array of memory inside of your computer really as a sequence of closed doors. And if the computer wants to find some value in an array, it has to do the digital equivalent of opening each of these doors one at a time. Now, how can code do that? Well, of course, we introduced indices or indexes last week, whereby we, by convention, call the first element of an array location 0, the second location 1, the third location 2, and so forth, so-called 0 indexed. And this allowed us to now bridge this conceptual world of like what's going on in memory with actual code, because now we had this square bracket syntax via which we could go searching for something if we so choose. And it turns out if I now paint these red instead of yellow, it would seem that we actually have a pretty good physical metaphor here standing in place for what would be a computer's array of memory if, for instance, you're storing some 7 numbers like that. And so today we begin with a look of a specific type of algorithm. That is for searching. Like searching is all over the place. All of us have probably gone to google.com or some equivalent like already multiple times per day. And getting back answers fast is what companies like Google are really good at. So how are they doing that? How are they storing information in computers' memory? Well, let's consider what this really is. It's really just a problem, as it was back in week 0. The input, though, to the problem for now might be this array of 7 lockers. So that's the input to the problem, inside of which is a number. And maybe for simplicity now, we just want a yes, no, a true, false answer, a bool, that is to say, of whether or not some number, like 50, is in that array. It's not quite as fancy as Google. That doesn't just tell you, yes, we have search results. It actually gives you the search results. But for now, we'll keep it simple and just output as part of this problem, yes or no, true or false. We have found the number we're looking for given an input like that array. But it turns out inside of this black box that we keep coming back to, there's all sorts of possible algorithms. And we talked about this at a high level conceptually in week 0 with the phone book. But today, let's consider it a little more concretely by way of a game that some of you might have grown up with, namely Monopoly. And so behind these doors, it turns out, will be hidden some denominations of Monopoly money. But for this, we now have 2 volunteers, if you'd like to greet the world.
Hi, I'm Jackson.
Hi, my name is Stephanie.
And do you want to say a little something about yourselves, years, house, dorm?
I'm a first year living in Matthews.
Nice.
And I'm a first year in Canada.
Nice. Well, welcome to our 2 volunteers. So why don't we do this? Would one of you like to volunteer the other to go first?
I'll go.
OK. All right, so Stephanie's up first, and behind one of these doors here, we've hidden the Monopoly Money 50. And so we'd like you to find the 50. We'll tell you nothing more about the lockers, but we would like you to execute a certain algorithm. And in fact, I'm going to give you some pseudocode for this, and I'm going to give you the name for it. It's called linear search. And as the name implies, you're pretty much going to end up walking in sort of a straight line. But how are you going to do this? Well, let me propose that in a moment, your first step will be to think kind of like a loop for each door from left to right. What do we want you to do on each iteration? Well, if 50 is behind that door, then we want to go ahead and have you return true and sort of hold up the 50 proudly, if you will, for the group. Otherwise, if you get through that whole loop and you haven't found the number 50, you can just throw up your hands in disappointment. False. You've not found the number 50. So to be clear, step 1 is going to be for each door from left to right. How would you like to begin? Oh, and then, yep, there we go. Yep. Oh. And if you'd like to at least tell, good acting here. What have you found instead?
It's not 50, but 20.
Oh, OK. So step 1 was a fail. So let's move on to step 2. Inside of this loop, what are you going to do next?
I'm going to move to the next door.
OK.
Almost.
Oh, OK, almost, sort of. A 500 instead. Next locker.
I would rather take. No.
OK, we're not telling the audience?
That was a 10.
OK. So keep going. This is step 3 now.
Oh, man.
5, OK. A few more lockers to check.
A little sad, guys.
All right, second to last step.
This one,
no.
Kind of close.
All right. And finally, the last step. Clearly, you've been perhaps set up here.
Let's go.
All right. So the number 50. And Stephanie, if I may, let me ask you a question here. So on the screen, this is the pseudocode you just executed. Suppose, though, I had done what many of us have gotten to the habit of doing when you have a if condition. You often have an else branch as well. Suppose that I had done this now. And I'm marking it in red to be clear this is wrong. But what would have been bad about this code using an if and an else, might you say? Any instincts?
Then you would end up like canceling the code before you found the 50.
Yeah, exactly.
And we'd just be eternally sad.
Indeed, when Stephanie had opened the first locker, she had found 20. 20, of course, is not 50. She would have decreed false, but of course, she hadn't checked all of the rest of the lockers. So that would seem to be a key detail that with this implementation of the pseudocode, we actually do go through as we did and only return false, not even with an else, but just at the end of the loop, such that we only reach that line if we don't return truer earlier than that. Well, let's go ahead and do this. Let me take the mic from you if you'd like to take a seat next to Jackson. Jackson, in just a moment, we'll have you come up. Carter, if you don't mind reorganizing the lockers for us. But in the meantime, let me point out how we might now translate that same idea to code. Pretty high level, pretty English-oriented with that pseudocode. But really now, as of last week, we have syntax via which Stephanie and soon Jackson could treat this locker, this set of lockers, as really indeed an array using bracket notation. So we can now get a little closer in our pseudocode to actual code. And the way a computer scientist, for instance, would translate fairly high high-level English, pseudocode like this, to something that's a little closer to C, or any language that supports arrays, would be a little more cryptically like this. But you'll see more of this syntax in the coming days. For I from 0 to n minus 1. This is still pseudocode, but that's kind of like the English-like way of expressing what we've come to know as a for loop. If 50 is behind doors bracket I, so I'm assuming for the sake of discussion that doors now is the name of my variable, this array of 7 doors, but then the rest of the logic, the rest of the pseudocode really is the same way. And so you'll find in time that programmers, computer scientists more generally, when you start expressing ideas, algorithms to someone else, instead of maybe operating at this level here, you now have in your vocabulary really a new syntax that you can be a little more specific, not getting so into the weeds of writing actual C code, but at least now doing something that's a little closer to manipulating an array like this. So Jackson, would you like to stand on up? All right. Yes, yes, support for Jackson here too. Nice. And here now, I'm going to allow you an assumption that Stephanie did not have. Stephanie clearly was really doing her best, searching from left to right, using linear searches, we'll now call it. But they were pretty much in random order, right? There was a 20 over there was a 1 over there, and then a 50. So we deliberately jumbled things up and did not sort the numbers for her. But Carter kindly has just come up to give you a leg up, Jackson, by sorting the numbers in advance. And we'd like you this time, much like in week 0, to do something again and again, but this time using what we'll now call binary search. It's exactly the same algorithm conceptually as we did in week 0, but if we translate it to the context of this array, we might say something like this. The first step for Jackson might be to ask the question. If 50 is behind the middle door, where presumably he's done some mental math to figure out what the middle is, then he's going to just return true. And hopefully we'll get lucky and 50 will be right there. Of course, there's 2 other possibilities at least, which would be what? 50 is with respect to these doors? Yeah, so to the left or to the right, alternatively. So if 50 is less than the middle door, then presumably Jackson's going to want to go left. Else, if 50 is greater than the middle door, he's going to want to go right, much like I did physically last week with the phone book, dividing and conquering left to right. But there's actually a 4th case. Let's put it on the board first. What else might happen here that Jackson should consider? Yeah. It's not there. So let me actually go back and amend my pseudocode here and just say, Jackson, if we don't hand you any doors at all, or eventually, as he's dividing and conquering, if he's left with no more doors, we have to handle that situation so that the behavior is defined. All right. So with that said, Jackson, do you want to go ahead and find us the number 50 and walk us through verbally what you're doing and finding?
All right. So it looks like this one is the middle door. So I'm going to open it. But it's 20, not 50.
Oh.
Sad.
OK. What's going through your head now?
So now I'm looking, because 50 is higher than 20, I want to look to the right.
Good.
And look for the new middle door, which would be here.
Nice.
And it's 100. Oh. Sad. But 50 is less than 100. So now we know to look left, which would be here. And ta-da!
Nice. Very well done this time around, too. So thank you first to our volunteers here. And in fact, since you're a fan of Monopoly, as we're so informed, we have the Cambridge edition of Monopoly with all your Harvard favorites. Here you go.
Right. Thank you so much.
Thank you to our volunteers for finding us 50. So that was more popular than we expected. So here we can translate this one more time into something a little closer to code. And again, still pseudocode, but here now might be another formulation of exactly what Jackson just did, just using the nomenclature now of arrays, where you can be a little more precise with your instructions and still leave it to someone else to translate this finally to code. But here we have same question at the beginning. If no doors left, return false. If 50 is behind doors bracket middle. So I'm assuming here, because this is pseudocode, that somewhere I've done the mental math or the actual math to figure out what the index of middle is. For instance, if these are 7 doors in an array, this would be location 0, 1, 2, 3, 4, 5, 6. So somehow I've taken the total number of doors, 7, divided by 2 to find the middle. That's 3.5. We have to deal with rounding, but suffice it to say there's a well-defined formula for finding the middle index given the total number of lockers, divide by 2, and then round accordingly. So that's presumably what Jackson did just by counting or in his head to find us door number 3. Not the third door, the fourth door, but door bracket 3. So this is just saying if 50 is behind doors bracket middle, return true. That was not the case. He found a $20 bill instead. Else, if 50 is less than the doors bracket middle, go ahead, and now it gets interesting. Search doors 0 through doors middle minus 1. So it's getting a little more into the weeds now, but if middle is 3, this one here, well, we want to now have Jackson search if 50 had been, if the number had been less, we want to start at bracket 0 and go up through this one. When we deliberately subtract 1, because what's the point of looking in the same locker again? We might as well do 0 through middle minus 1. Else if 50 is greater than doors bracket middle, which it was, what did we then do? Jackson intuitively searched for doors middle plus 1 through doors n minus 1. And honestly, it gets a little annoying having the pluses and the minuses here, but just think of what it means. This is the middle door. And Jackson then did proceed to search through doors middle plus 1, because there's no point in searching this one again. And then the last element in any array of size n, where n is just our go-to number for the size, is always going to be n minus 1. It's not going to be n. It's going to be n minus 1 because we always start counting arrays at 0. So here then we have a translation into pseudocode that's a little closer to C of this exact same idea. And here we come full circle to week 0. Like in week 0 is pretty intuitive to imagine dividing and conquering a problem like this. But if you now think back to actually your iPhone, your Android phone, or the like, when you're doing autocomplete and searching the list, it's possible, if you don't have many friends or family or colleagues in the phone, you know what? Linear search, just checking every name for the person you're searching for, might be perfectly fine. But odds are your phone's being smarter than that, especially if you start to have dozens, hundreds, thousands of people in your contacts over the years. What would be better than linear search? Well, perhaps binary search. But there's an assumption, a requirement, which is what? Why was Jackson ultimately able to find the 50 in just like 3 steps instead of a full 7, like Stephanie? Because the array was sorted. And so this is sort of a teaser for what we'll have to come back to later today. Well, you know, how much effort did it take someone like Carter? How much effort does it take your phone to sort all of those names and numbers in advance? Because maybe it's not actually worth the amount of time. Now, someone like Google probably somehow keeps the database of web pages sorted. You can imagine it being super slow if when you type in cats or something else into google.com, if they searched linearly over their entire data set. Ideally, they're doing something a little smarter than that. So we'll formalize now exactly this kind of analysis. And it's not going to be so much mathy as it still will be intuitive. But we'll introduce you to some jargon, some terminology that most any programmer or computer scientist might use when analyzing their own algorithms. Let's formalize now what this kind of analysis is. So right now I claim binary search better than linear search. But how much better and why exactly? Well, it all comes back to this kind of graph. So this, recall, is how we analyzed the phone book back in week 0. And recall that indeed we had these formulas, rough formulas that describe the running time of those 3 algorithms. 1 page at a time, 2 pages at a time, and then tearing the thing again and again in half. And precisely, if you counted up the number of pages I was touching or the number of pages I was tearing, it's fair to say that the first algorithm, in the worst case, might have taken n total pages. It didn't, because I was searching for John Harvard at the time, which is somewhat early in the alphabet. But if I were searching for someone with the last name of Z, I would have had to keep going and going, in the worst case, through all n pages. Not as bad for the second algorithm, and that's why we do n divided by 2. And even that's a bit of a white lie, right? It's probably n divided by 2 plus 1 in case I have to double back. But again, I'm sort of doing this more generally to capture the essence of these things. And then we really got into the weeds with like log base 2 of n for that third and final algorithm. And at the time, we claimed anytime you're dividing something in half, odds are there's going to be some kind of logarithm involved. And we'll see that today. But today, we're going to actually start using computer science terminology. And we're going to sort of formalize this imprecision, if you will. We are not going to care generally about exactly how many steps some algorithm takes, because that's not going to be that enlightening, especially if maybe you have a faster computer tomorrow than you did today. It wouldn't really be fair to compare numbers too precisely. We really kind of want to, with a wave of the hand, just get a sense of roughly how slow or how fast an algorithm is. So the notation here is deliberate. That is literally a capital O, often italicized, referred to as big O. And so the first algorithm is in big O of n. The second algorithm is in big O of n divided by 2. The third algorithm is in big O of log base 2 of n. But even that is kind of unnecessary detail. When using big O notation, you really don't care about, we'll see, the smaller ordered terms, right? We're not going to care about the divided by 2. Because you know what? The shape of these algorithms is almost the same. And really, the idea, the algorithm itself is sort of fundamentally the same. OK, instead of 1 page at a time, I'm doing 2. But if you throw millions of pages, billions of pages at me, those algorithms are really going to kind of perform the same as n gets really large, goes off toward infinity. And the same is true for logarithms. Even if you're a little rusty, it turns out that whether you do the math with log base 2, log base 3, log base 10, you can just multiply one by the other to really get the same formula. So this is only to say a computer scientist would generally say that the first 2 algorithms are on the order of n steps. The third algorithm is on the order of log n steps. And we don't really care precisely what we mean beyond that. And this big O notation, as we'll see, and actually let me zoom out. If you can imagine suddenly making the x-axis much longer, so more pages on the screen at once, it is indeed going to be the shapes of these curves that matter. Because imagine in your mind's eye, as you zoom out, zoom out, zoom out, zoom out, and as n gets much, much, much bigger on the x-axis, the red and the yellow line are essentially going to look the same once n is sufficiently large. But the green line is never going to look the same. It's going to be a fundamentally different shape. And so that's the intuition of big O, to get a sense of these rates of performance like this. So here then is big O. Here is perhaps a cheat sheet of like the common formulas that a computer scientist, certainly in an introductory context, might use when analyzing algorithms. And let's consider for a moment which of our first 2 algorithms, linear search and binary search, fall into these categories. So I've ordered them from sort of slowest to fastest. So order of n squared. It's not something we've actually seen yet, but it tends to be slow because it's quadratic. You're doing n times n. That's got to add up to a lot of steps. Better today is going to be n log n. Even better is going to be n. Even better than that is log n. And best is so-called order of 1, like 1 step, or maybe 2 steps, maybe even 1,000 steps, but a fixed, finite number of steps that never changes no matter how big n is. So given this chart, just to be clear, linear search, let's consider the worst case. In the worst case, how many steps did it take someone like Stephanie to find the solution to the problem, assuming not 7 doors, but n doors? Yeah. So on the order of n. And in this case, it's exactly n. But you know what? You know, maybe it's arguably 2n, right? Because it took Stephanie a couple of steps. Like she had to lift the latch. She had to open the door. Maybe it's 3 steps. She had to show the money. So now it's 3n, 2n. But there, we don't really care about that level of precision. We really just care about the fundamental number of operations. So we'll say yes on the order of n. So that might be an upper bound, we'll call this, for linear search. And how about binary search? In Jackson's case, or in general, me in week 0, if there's n doors, how many steps did it take Jackson or me using binary search? In this case, it was literally 3, but that's not a formula. Yeah, so it's on the order of log n. And indeed, if there's 7 doors, well, that's almost 8 if you just do a little bit of rounding. And indeed, if you take log base 2 of 8, OK, so that does actually give us 3. So the math actually checks out. And if you're not comfy with logarithms, no big deal. Just think about it intuitively. Logarithm of base 2 is just dividing something again and again. So on this chart, when we consider big O, which to be clear allows you to describe the order of an algorithm's running time, like the magnitude of it, but it also describes more specifically an upper bound. So in the worst case, for instance, these are pretty good measures of how good, or rather of how bad, linear search and binary search might be. Why? Well, suppose you're searching a 1,000-page phone book and the person's name starts with Z. The algorithm's still going to be on the order of n steps. Why? Because it might take you as many as all n steps to find it. Now, that's not necessarily going to be the case in practice. If I use big O as an upper bound, well, it would be nice if there's sort of a corresponding lower bound, especially if you want to consider not just worst cases, but maybe best cases. So what might we use here? Well, so this is a capital Greek omega symbol. So omega is the symbol that a computer scientist uses generally to describe a lower bound on an algorithm, often in the context of best case, though not necessarily. So a lower bound means how few steps might an algorithm take. And here too, same formulas, and we'll fill in these blanks over time. Some algorithms might always take a minimum of n squared steps, or on the order of n steps. Some might only take n log n, or log n, or 1. So something like linear search. When Stephanie started with linear search, she didn't get lucky this time on stage, but what if she had and the first door she opened were 50? How might you then describe the lower bound on linear search in this so-called best case using this list of possible answers? Yeah. Yeah, so omega of 1. So in the best case, the lower bound on how many steps it might take linear search to find something might just be 1 step. Why? Because maybe Stephanie had gotten lucky and we had pre-filled these lockers with the numbers in some other order such that she might have opened the first locker and voila, the number 50 could have been there. So a lower bound arguably could indeed be omega of 1 for linear search. And how about now for Jackson? He used binary search, so he dived right into the middle of the problem. But what would be a lower bound on binary search using this logic? Yeah. Yeah, so again, omega of 1. Why? Because maybe he just gets lucky. And indeed, right in the middle of the lockers could have been the number 50. It wasn't. And so more germane in Jackson's actual practice would have been the big O discussion. But big O and omega, upper bound and lower bound, just allow a computer scientist to kind of wrestle with what could happen maybe in the worst case, what can happen in the best case, and you can even get even more precise, like the average case or the like. And this is indeed what engineers might do at a whiteboard in a company, in a university, when designing an algorithm and trying to make arguments as to like why their algorithm is better than someone else's by way of these kinds of analyses. And just so you've seen it, it turns out that if some algorithm happens to have an identical upper bound and lower bound, you can actually use a capital Greek theta as well. And this is the last of the Greek symbols today. But a Greek theta indicates a coincidence of both upper bound and lower bound. That is, they are one and the same. That was not the case for our discussion a second ago of linear search, not the case for binary search, but you could use the same kinds of formulas if it turns out that your upper bound and lower bound are the same. So for instance, if I were to count everyone, like literally in this room, 1, 2, 3, 4, 5, 6, and so forth, you could actually say that counting in that way is in theta of n, right? Because in the best case, it's going to take me n points at the people in the audience. In the worst case, it's going to take me n. It's always going to take me n steps if I want to count everyone in the room. You can't really do better than that unless you skip people. So that would be an example off the cuff of something where theta is instead germane. Are any questions now on big O, on omega, or theta, which are now just more formal tools in the toolkit for talking about the design of our algorithms? Any questions? No? Seeing none? Yeah, oh, is this yes? No? OK, so we're good. So let's go ahead and translate this perhaps to some actual code. Let me go over to VS Code here, and let's see if we can't now translate some of these ideas to some actual code, not so much using new syntax yet. We're going to still operate in this world of arrays like last week. So let me go ahead and create a program called search.c by executing code space search.c in my terminal. And then up here, let's go ahead and include our usual. So include cs50.h so I can get some input. Include standardio.h so I can print some output. We'll do int main void, which the meaning of which we did start to tease apart last week. The fact that it's void again today just means no command line arguments. And let me go ahead and do this. Let me go ahead and declare, just for discussion's sake, a static array, like an array that never changes. And the syntax for this is going to be give me an array called numbers using the square bracket notation, and I'm going to immediately initialize it to 20, 500, 10, 5, 100, 1, and 50, reminiscent of those same denominations as before. So this is a slightly new syntax that we've perhaps not seen. And the curly braces here, which are different from for loops and while loops and functions, just tell the compiler, please give me an array of whatever size this is containing those numbers left to right. I could alternatively use last week's syntax of saying something like this. Let's see, 1, 2, 3, 4, 5, 6, 7 denominations. I could alternatively do this. And then I could say numbers bracket 0 equals 20, numbers bracket 1 equals 500. And I could do this 5 more times. That's just a little tedious. If you know the numbers in advance, you don't have to tell the compiler how many there are. You can just let it figure it out that your numbers will be 20, 500, 10, 5, 100, 1, and 50. So this is how you statically define an array. All right, let me just go ahead and ask the user now for a number. We'll call it n by using getInt and prompting them for a number. So nothing new there. And now let me go ahead and implement linear search. And the pseudocode we had for this before used some array-like notation. Let me go ahead then and start similarly. For int I, and you almost always start counting at I by convention, so that's perhaps a good starting point. I'm going to do this so long as I is less than 7. Not the best design to hard code the 7, but this is just for demonstration's sake for now, because I know how many numbers I put in there. And then I'm going to do I++. So now I have the beginnings of a loop that will just allow me to iterate over the entire array. And let me ask this. If the current number at location I equals n, which is the number the human typed in, then let's go ahead and do something simple like printf, quote unquote, found, \n. And then, per our discussion last week, to indicate that this is successful, I'm going to return 0 if I found it. And if I don't find it, I'm just going to go down here and by default say not found, \n. And just for convention, just for good measure, per convention, I'll return 1, or really any value other than 0. 0, recall, means success, and any other integer tends to mean error of some sort, irrespective of the number I'm looking for. So just to revisit, the only thing that's new here is the syntax for creating an array of 7 numbers, these numbers. And then after that, we have really highlighted here an implementation of linear search. I mean, this is the C version, I dare say, of what Stephanie did on the board, whereas now the array is called numbers instead of doors. But I think it's pretty much the same. Let me go ahead and open my terminal window and run make search. Seems to compile OK, /search. And let's go ahead and search for a number. We'll start with what we did before, 50. And it's found. Let's go ahead and run it again, /search. Let's search for maybe 20 at the beginning. That one, too, is found. Let's run it one more time, searching for like 1,000, which is not among the denominations. And that one, indeed, is not found. So we've taken an idea from week 0, now formalized in week 3, and just translated it now to code. Questions on this implementation of linear search? Linear search. Nothing. Oh. So successful so far today. OK, so let's see if we can't maybe make this a little more interesting and see if we can't trip over a detail that's going to be important in C. Instead of doing numbers, let me go ahead and do this. We'll stay on theme with Monopoly. And I went down the rabbit hole of reading the Wikipedia article on Monopoly and the original pieces or tokens that came with Monopoly. And it turns out we can represent those with strings. So I'm going to create an array called strings, plural, of whatever size I defined here. And the very first Monopoly pieces back in the day were a battleship that you could play with, a boot, a cannon, an iron, a thimble, and a top hat, some of which you might know from the game nowadays. Turns out they've been changing these, had no idea, over the years. So here is now an array of strings. Let me go ahead and prompt the user now, not for an integer anymore. I want to now search for one of these strings, still using linear search. So let me create a string s, set it equal to getString, prompt the user for a string to search for. And then I think my code here is almost the same, except for one detail. I now have an array called strings. I now have a variable called s. But it turns out, for reasons we'll explore in more detail next week, this line of code is not going to work. And it turns out the reason has to do with what we discussed last week of like what a string really is. And what is a string again? A string is an array. And it turns out, though, that equals equals is not going to generously compare all of the characters in an array for you just because you use equal equals. It turns out it's not going to compare every letter. And so thankfully, there is in the string library that we introduced last week a solution to this problem. The reason for the problem we'll explore in more detail next week. But for now, just know that when you want to compare strings in C, especially if you've come into the class knowing a bit of Java or Python or some other language, you cannot use equals equals. Even though you could in Scratch, you cannot in C. So what I have to actually do here is this. I have to ask the question, does the return value of a function called strCompare or strcomp equal 0 when passed in the current string and that user input? So if you read the documentation for this function called strCompare, you'll see that it takes two strings as input, first one and second one. It then, someone decades ago wrote the code that probably uses a for loop or a while loop to compare every character in each of those strings. And it turns out it returns 0 if they are in fact equal. Turns out, too, it will return a positive number or a negative number in other situations. Any intuition for why it might actually be useful to have a function that allows you to check if two strings are equal? If they're not equal, what else might be interesting to know when comparing two strings? Or if certain values are? OK, possibly. Maybe you want to know just how similar they are. And that's indeed an algorithm unto itself. But strCompare is a little simpler than that. Exactly. If you're trying to like alphabetize a whole list of strings, just like your phone probably is for your contacts or address book, it turns out that strCompare will actually return a positive number or a negative number or a 0 based on whether maybe it comes alphabetically first or later or in fact equal. So that can be a useful thing. And that's just a teaser for a lower level explanation that we'll see next week. So now let me cross my fingers and see if I got this right. Let me go ahead and do make search. Did compile, OK, albeit slowly, /search. And let's search for something like the thimble. And we see that that's indeed found. Otherwise, let's search for something that I know isn't there, like a race car, which was there when I grew up. But, segmentation fault, core dumped. And actually, some of you have tripped over this error before. Anyone want to admit seeing this? So yeah, not something we've talked about. And honestly, not something I intended just now. But that, too, we'll see next week. Any intuition for why my program just broke? I didn't really change the logic. It's still linear search. Let me hide the terminal so you can see all of the code at once. The only thing I did was switched from integers to strings, and I switched to strCompare here. But segmentation fault happened. And the teaser is that that somehow relates to the computer's memory. Yeah? Yeah, and this is subtle, but spot on. So 1, 2, 3, 4, 5, 6 elements total in this array versus the 7 numbers of monopoly denominations that we had earlier. And this is where, see, sort of case in point, this came back to bite me. The fact that I hard-coded this value as opposed to maybe separating it out as a constant or declaring it higher up kind of bit me here, because now I'm iterating over an array of size 6. But clearly, I'm going one step too far, because I'm literally going to iterate 7 times, not 6. So it's as though I'm looking at memory that's over here. And indeed, next week, we'll focus on memory. And that's just a bad thing. So odds are, not even seeing your code from this past week, if any of you have had segmentation faults, odds are you touched memory that you shouldn't have. You maybe looped too many times. You might have used a negative number to get into your array. In general, you touched memory that you shouldn't have. And you touched a segment of memory that you shouldn't have. The fix, though, at least in my case, is simple. Just don't do that. So let me go ahead and recompile this. Make search, /search. And I'll search again for race car. Enter. And now it does not crash, but it does tell me it's not found. So subtle, but something you might yourself have tripped over already. Questions then on what I just did, intentionally or otherwise? Yeah, in front.
One thing is, the program still works if you don't do return 0, return 1. So what is the purpose of doing that?
A really good question. So the program will still work even if I don't return 0 or return 1. In fact, let me go ahead and do that and just hide my terminal window for a second. Let's get rid of the return here. Let's get rid of the return here. However, watch what happens here. Let me go ahead and recompile this, make search. Let me scroll up in my code here. Let me go ahead and do /search. And let me go ahead and search for the first thing in the list, battleship. So I know that this should be found. I hit enter. Huh, interesting. So it's saying found, not found. But do you see why logically in this case? Exactly. So the loop is still running. So there's a couple of solutions to this. I could, for instance, somehow break out of the code here, but that's going to still result in line 18 executing. I could then instead just return here. I don't strictly need to return 1 down at the bottom, but I made this claim last week that it tends to be helpful as your programs get more sophisticated to at least signify, just like a real-world programmer, error codes when something goes wrong. So returning 0 in main is the easiest way to signify my code is done. I'm ready to exit successfully. That's it. But down here, I could absolutely still return 0 because it's not a huge deal. It's not really an error that deserves annoying the user with some kind of pop-up that something went wrong. But return 1 is just a lower level way of signaling, it didn't really find what I was looking for. And remember from last week, you can see this as follows. If I recompile this again, now that I've reverted those changes, so make search, and if I do /search and search for battleship, which is indeed found, recall I can execute this magical command echo $? Which you're not going to often execute, but it shows you what main returned. If I run search again and search for race car, which is not found, I see not found, but I can also run this command again and see that, oh, it returned 1. So now if you fast forward a few months, a few years, when you're actually writing code in a company or for larger projects, you might want to be automating software. You might not want the human to necessarily be running it manually. You might want code to be automated by some nightly process or something like that. Using these exit codes, can a program determine yes or no that other code succeeded or failed? Other questions on linear search in this way? No? All right, well, let's translate this to one other feature of C here by incorporating these two ideas now into one other program. So I'm going to create a phone book in C by doing code space phonebook.c. And let's combine some of these ideas and implement this notion of like searching a phone book for an actual name and getting back a number. So I'm going to go ahead and quickly include some of the same things, cs50.h so we can get input, standard.io.h so we can print output, and I'm going to preemptively include string.h in case we need that one as well. Int main void, no need for command line arguments today. And let me give myself now an array of names for this phone book. So string names equals, and then in curly braces, how about Carter will be one person in the phone book, and David, myself, will be the other. So we'll keep it short so we don't have to type too many names. But this is a phone book with 2 people thus far. Suppose now we want to also store Carter's phone number in mine. So it's not just saying found or not found. It's literally looking up our phone numbers like a proper phone book. Well, at the moment, there's really no way to do this. I could do something hackish, like I could put a number like 617-495-1000 after Carter. I could maybe do something like 949-468-2750 after me. But now you're kind of doing the whole apples and oranges thing, right? Like now it's not strings. It's a string int. All right, so maybe I could just make all of these strings. But now it's just a conceptual mixing of apples and oranges. Like, yes, that's an array of 4 strings, but now you're on the honor system to know that the first string is a name, the second string is a number, the third string is, like, you can do it, but it's a bit of a hack, so to speak. So what might be cleaner than this? Instead of combining our phone numbers into the same array as our names, what else might we do that's perhaps a little better? Say a little louder. A 2D array, possibly something we could do. I'm going to keep it even simpler now because we haven't used those by name, even though that is, we saw last week, technically what argv is. What else could I do if I want to store names and numbers? Yeah. Yeah, let me go with this suggestion. Just it's a little simpler. Rather than complicate things in literally different dimensions, let me go ahead and do string. Well, I could do int numbers, but you know what? So that we can support punctuation like dashes or even parentheses or country codes, I'm going to do this instead. I'm going to do string numbers so that I can represent Carter's number as quote unquote +1 for the US, 617, 495, 1000, complete with hyphens, as is US convention. And then for mine, I'll go ahead and do +1, 949, how about 468, 2750. Semicolon. And now down below, let's actually enable the user to search this phone book, just like in week 0 we did. String name equals getString, and let's ask the user for a name, presumably David or Carter or someone else. And now let's re-implement linear search. So for int I gets 0, I is less than 2, and do as I say, not as I do. I think we should beware this hard coding, but we'll keep it simple for now. I++, and then in this for loop, I think we have all of the ingredients to solve this. So if the return value of stir compare of all of the names, bracket I, comparing against the name that the human typed in, if all of that equals 0, that is, all of the characters in those two strings are equal, then I think we can go ahead and say found, just like last time. But you know what? Let's actually print Carter's or my phone number. So found %s, and we'll plug in numbers, bracket I. And then just for consistency, I'll return 0 here. And down here, how about I'll say something like printf not found, just to be clear. And then I'll return 1 as well. So just to recap, here's all of the code. It's almost the same as before, except now it's useful. I'm not just saying found or not found. I found a number in Monopoly, or I found a piece in Monopoly. I'm looking up in one array one of the strings, and then I'm printing from the other array the answer. So let me go ahead here and run the compiler, make phone book, enter. OK, that's promising. No errors. /phonebook now. And let's search for instance, Carter. Enter. All right, so we found Carter's number. All right, let me do that again. Phone book. Let's search for David. All right, we seem to have found David's number. All right, let's do it one last time. Phone book. Enter. And now we'll search for like John Harvard. Enter. Not found. All right, so I dare say, albeit with minimal testing, this code is correct. Would anyone now like to critique the design? Does something rub you the wrong way, perhaps, about this approach here? And as always, think about how, if the program maybe gets longer, more complicated, how decisions like this might unfold. Yeah? OK, so if I is less than 2, so technically, if I change the number of people in this phone book, I'm going to have to update I. And we've already seen that I get myself into trouble. So that's bad design. Good. Yeah, so again, I'm sort of trusting myself not to screw up. If I add John or anyone else to the first array, but I forget to add their number to the second array, you know, eventually things are going to drift and be inconsistent, and then the code will be incorrect at that point. So sort of a poor design setting me up for future failure, if you will. Other thoughts? Yeah. Yeah, really good. We're assuming the same order. From left to right, the names go, and from left to right, the numbers go. But that's kind of just the honor system. Like, there's literally nothing in code preventing me from reversing the order for whatever reason, or maybe sorting the names. Like, they're sorted now, and maybe that's deliberate, but maybe it's not. So this honor system here, too, is just not good, right? I could put a comment in here to remind myself to, note to self, always update arrays the same way, but like that's something's going to happen eventually, especially when we have not 2, but 3, but 30, 300 names and numbers. It would be nice to keep all of the related data together. And so in fact, the one new feature of C we'll introduce today is one that actually allows us to implement our very own data structures. You can think of arrays as a very lightweight data structure in that it allows you to cluster related data back to back to back to back. And this is how strings are implemented. They are a data structure effectively implemented with an array. But with C and with other languages, it turns out you can invent your own data types, whether they're one-dimensional, two-dimensional even, or beyond. And with C, can you specifically create your own types that have their own names. So for instance, wouldn't it have been nice if C came with not just char and int and float and long and others? Wouldn't it be nice if C came with a data type called person And ideally, a person would have a name and a number. Now, that's a little naive and unrealistic. Like, why would they define a person to have just those two fields? Certainly, people could have disagreed what a person is, so they leave it to us. Like, the authors of C gave us all of these primitives, ints and floats and strings and so forth. But it's up to us now to use those in a more interesting way so that we can create an array of person variables, if you will, inside of an array called people, just to pluralize it here. So how are we going to do this? Well, for now, let's just stipulate that a person in the world will have a name and a number. That we could argue all day long what else a person should have, and that's fine. You can invent your own person eventually. At the moment, I'm using just two variables to define a person's name and number. But wouldn't it be nice to encapsulate, that is, combine these two data types into a new and improved data type called person? And the syntax for that is going to be this. So it's a bit of a mouthful, but you can perhaps infer what some of this is doing here. So it turns out C has a keyword called typedef. As the name kind of suggests, this allows you to define your own type. Struct is an indication that it's a structure. It's like a structure that has multiple values inside of it that you are trying to define. And then at the very bottom here, outside of the curly braces, is the name of the type that you want to create. So you don't have discretion over using typedef or struct in this particular case, but you can name the thing whatever you want, and you can put anything in the structure that you want as well. And as soon as this semicolon is executed at the bottom of the code, every line thereafter can now have access to a person data type, whether as a single variable or as an entire array. So if I want to build on this then, let me go ahead and do this. Let me go back to my C code here, and I'm going to go ahead and change just a couple of things. Let's go ahead and do this. I'm going to go ahead and first get rid of those two hard-coded arrays. And let me go ahead and at the top of my file, invent this type. So typedef struct. Inside of it will be a string name and then a string number. And then the name of this structure will be person. And best practice would have me define it at the very top of my file so that any of my functions, in fact, could use it, even though I just have main in this case. Now, if I wanted, I could do this, like person p1 and person p2. But we know from last week, like that already is bad design. If you want to have multiple instances of the same type of variable, we should probably use what instead? An array. So let me not even go down that road. Let me instead just do this. Person will be the type of the array, but I'm going to call it, I could call it persons, but in English we typically say people. So I'll call the array people, and I want 2 people to exist in this array, though I could certainly change that number to be anything I want. How now do you put a name inside of a person and then put the number inside of that same person? Well, slightly new syntax today. I'm going to go ahead and say this. People bracket 0 just gives me the first person in the array. That's not new. But if you want to go inside of that person in memory, you use a dot, and then you just specify the name of the attribute therein. So if I want to set the first person's name to Carter, I just use that so-called dot notation. And then if I want to set Carter's number using dot notation, I would do this, +1 617 495 1000. And then if I want to do the same for myself, I would now do people bracket 1 dot name equals quote unquote David. And then people bracket 1 still dot number equals quote unquote +1 949 468 2750. And now, at the bottom of my file, I think my logic can pretty much stay the same. I can still, on this line here, prompt the user for the name of the person they want to look up. For now, even though I admit it's not the best design, I'm just doing this for demonstration's sake, I'm going to leave the 2 there, because I know I have 2 people. But down here, this is going to have to change. I don't want to compare names bracket I anymore. What do I want to type here as the first argument to stir compare? What do I want to do here? Yeah. So people I dot name. Yeah, so I want to go into the people array at the ith location, because that's what my loop is doing. It's updating I again and again. And then look at name. And that's good. I think now I need to change this too. What do I want to print if the person is found? Someone else? What do I want to print here if I found the person's name? Yeah. Say a little louder. Perfect. So people bracket I dot number, if indeed I want to print the corresponding number to this person. And then I think the rest of my code can stay the same. So let me go ahead and rerun make phone book to recompile this version. So far, so good. /phone book. Let's go ahead and type in Carter's name, found. All right, let's go ahead and run it again. David's name, found. Let's go ahead and run it one more time. So type in John Harvard, for instance. Not found in this case. So fundamentally, the code isn't all that different. Linear search is still behaving the same way. And I admit this is kind of ugly looking. Like we've kind of made a 2-line solution like 5 lines of code now. But if we fast forward a week or two, when we start saving information to files, we'll introduce you to files like CSV files, comma separated values, or spreadsheet files, which you've surely opened on your Mac or PC at some point in the past. Suffice it to say, we'll soon learn techniques for storing information like names and numbers in files. And at that point, we're not going to do any of this hackish sort of hard coding of the number 2 and manually typing my name and Carter's name and number into our program. We'll read the information dynamically from a file. And in a few weeks, we'll read it dynamically from a database instead. But this is, for now, just syntactically how we can create an array of size 2 containing 1 person each. We can update the name and number of the first person, update the name and the number of the second person, and then later search across those names and print out the corresponding numbers. And in this sense, this is a better design. Why? Because my person data type encapsulates now everything that it means to be a person, at least in this narrow world. And if I want to add something to the notion of a person, for instance, I could go up to my typedef and tomorrow add an address to every person and start reading that in as well. And now it's not the honor system. It's not a names array, a numbers array, an addresses array, and everything else you might imagine related to a person. It's all encapsulated, which is a term of art, inside of the same type. Reminiscent, if some of you have programmed before, of something called object-oriented programming, but we're not there yet. C is not that. Questions on this use of struct or this new syntax? The dot operator being really the juicy part here. Any questions? Yeah? On what line number? 16. So yes, so syntactically, we introduced the square brackets last week. So doing people bracket 0 just means go to the first person in the array. That was like when Stephanie literally opened this door. That's doors bracket 0. But this is, of course, people bracket 0 instead. Today, the dot is a new piece of syntax. It means go inside of that person in memory and look at the name therein and set it equal to Carter and do the same for number. So that's all. It's like open the locker door, go inside of it, and check or set the name and the number. Yeah? Attributes is fine. Good question. In the struct, can you set default values? Short answer, no. And this is where C becomes less featureful than more modern languages like Python and Java and others, where you can, in fact, do that. So when we transition to Python in a few weeks' time, we'll see how we can start solving problems like that. But for now, it's up to you to initialize name and number to something. Yeah? Really good question. How can we adjust or critique the design of what I'm doing? This is one of the few situations where I would say hypocritically, do as I say, not as I do. I am using pretty ugly lines like this just to introduce the syntax. But my claim pedagogically today is that eventually when we start storing names and numbers or other things in files or in databases, you won't have this redundancy. You'll have 1 line of code or 2 lines of code that read the information from the file or database and then fill the entire array with that data. For now, I'm just doing it manually so as to keep our focus only on the new syntax. But that's it. So forgive the bad design by design today. Other questions on this? All right. That's been a lot already. Why don't we go ahead and take our 10-minute break with snacks first? We have some delightful brownies in the lobby. All right. We are back, and up until now, it clearly seems to be a good thing if your data is sorted, because you can use binary search. You know a little something more about the data. But it turns out that sorting in and of itself is kind of a problem to solve too. And you might think, well, if sorting is going to be pretty fast, we absolutely should do it before we start searching, because that'll just speed up all of our searches. But if sorting is slow, that kind of invites the question, well, should we bother sorting our data if we're only going to search the data maybe once, maybe twice? And so here is going to be potentially a trade-off. So let's consider what it means really to sort data. In our case, it's just going to be simple and use numbers, but it might, in the case of the Googles of the world, be actual web pages or persons or the like. So here is our typical picture for sorting input, for solving any problem. Input at left and output at right. The input to our sort problem is going to be some unsorted set of values, and the output ideally will be the same set of values sorted. And if we do this concretely, let's suppose that we want to go about sorting this list of numbers: 7, 2, 5, 4, 1, 6, 0, 3. So it's all of the numbers from 0 to 7, but they're somehow jumbled up randomly. That's going to be the input to the problem, and the goal is now to sort those so that you indeed get out 0, 1, 2, 3, 4, 5, 6, 7 instead. So it turns out there's lots of different ways we can actually sort numbers like these here. And in fact, just to complement our search example earlier, could we perhaps quickly get some 8 volunteers to come up if you're comfortable appearing on the internet? If you want to do 1, OK, 2, 3, 4, 5, 6, 7, 8. How about? All right, come on down. All right. Come on over here, and I'll give you each a number. And if you want to start to organize yourselves in the same order you see the numbers on the board. OK. So look up on the overhead and organize yourselves from left to right in that same order. And let's have the first of you perfect. If you want to come right over here, how about right in line with this? Sure. All right, and a few more numbers. All right, number 2. 6, and perfect. Just the right number. All right. No. Uh-oh. All right, there we go. Number 3. All right, so let's just do a quick check. We have 7, 2, 5, 4, 1, 6, 0, 3. Very good so far. Do you want to just scooch a little this way just to make a little more room? All right, and let's consider now who we have here on stage. You want to each say a quick hello to the audience?
Hi, my name is Ryan. I'm a first year from Pennypacker.
Hi, my name's Itzel. I'm a first year at Strauss.
Hi, my name is Lucy, and I'm a first year from Greeno.
Hi, my name is Shiloh. I'm a first year in Wigglesworth.
Hi, my name is Jack, and I'm a first year in Strauss.
Hi, my name is Catherine. I'm a first year in Strauss.
Hi, my name is Michael, and I'm a first year at Pennypacker.
Hi, my name is Muhammad. I'm a first year in Matthews.
Nice. Welcome aboard. All right, so let's consider now how we might go about sorting our kind volunteers here. The goal being to get them into order from smallest to largest, so that presumably then we can use something smarter than just linear search. We could actually use binary search, assuming that they are already then sorted. So let me propose that we first consider an algorithm that actually has a name called selection sort. And selection sort is going to be one that literally has me, or really you as the programmer, selecting the smallest element again and again, and then putting them into the appropriate place. So let me go ahead and start this here, starting with the number 7. At the moment, 7 is the smallest number I found, so I'm going to make mental note of that with a mental variable, if you will. I'm going to move on now. Oh, number 2 is obviously smaller, so I'm just going to update my mental reminder that 2 is now the smallest, effectively forgetting for now number 7. 5, not smaller. 4, not smaller. 1, smaller, and I'm going to make mental note of that. 6, not smaller. 0, even smaller. I'll make mental note of that, having forgotten now everything else. And now number 3 is not smaller. So what's your name again? Michael. So Michael is number 0. He belongs, of course, way down there, but unfortunately you are Ryan. Ryan is in the way, so what should we do? How should we start to sort this list? Where should number 0 go? Yeah, okay. Do you want to say it louder? Yeah, so let's just go ahead and swap. So if you want to go ahead and 0, go on where 7 is. We need to make room for number 7. It would kind of be cheating if maybe everyone kind of politely stepped over to the side. Why? Because if we imagine all of our volunteers here to be an array, like that's a crazy amount of work to have every element in the array shift to the left just to make room. So we're going to keep it simple and just evict whoever's there. Now maybe we get lucky and number 7 is actually closer to its destination. Maybe we get unlucky and it goes farther away, but we've at least solved one problem. If we had n problems at first, now we have n minus 1 because number 0 is indeed in the right place. So if I continue to act this out, let me go ahead and say 2. OK, currently the smallest. 5, no. 4, no. 1, currently the smallest. I'll make mental note. 6, 7, 3. And now let me pause. 1 is obviously the now smallest element. So did I need to keep going? Well, it turns out, at least as I've defined selection sort, I do need to keep going because I only claim that I'm using one variable in my mind to remember the then smallest element. I'm not smart enough, like us humans, to remember, oh, wait a minute, 1 is definitely the smallest now. I don't have that whole recollection. So I just am keeping track of the now smallest. So number 1, your name was?
Jack.
Jack. Where should Jack go? Probably there. And what's your name? Itzel? OK, so Jack and Itzel, if you want to swap places, we've now solved 2 of the n total problems. And now we'll do it a little faster if each of you want to sort of start to swap as I find the right person. So 5, smallest. 4 is smaller. 2 is smaller. Got to keep checking. OK, 2 was smaller. All right, now I'm going to go back to the beginning. All right, 4 is small. 5 is not. 6 is not. 7 is, 3 is small. Where do you want to go? OK, good. I'm going to go back here. And I can be a little smart. I don't have to go all the way to the end because I know these folks are already sorted. So I can at least optimize slightly. So now 5 is small, 6 is small, 7 is 4, 4 is smaller if you want to go in place there. And now here things get interesting. I can optimize by not looking at these folks anymore because they're obviously problem solved. But now 5 is small, 6 is not, 7 is not. OK, 5, you can stay where you are. Now a human in the room is obviously going to question why I'm wasting any more time. But with selection sort, as I've defined it thus far, I still have to now check 6 is smallest, not 7. And now my final step, OK, they're all in place. So here, too, is this dichotomy between what we all have is this bird's eye view of the whole problem where it's obvious where everyone needs to go. But a computer implementing this with an array really has to be more methodical. And we're actually saving a step here. If we were really doing this, none of these numbers would be visible. All 8 of our volunteers would be inside of a locked door, and only then could we see them one at a time. But we're focusing now just on the sorting aspect. So let me just, before we do one other demonstration here, propose that what I really just did here in pseudocode was something like this. For I from 0 to n minus 1, keeping in mind that 0 is always the left of the array, n minus 1 is always the right end of the array. For I from 0 to n minus 1, I found the smallest number between numbers bracket I and numbers bracket n minus 1. And that's the very geeky way of expressing this optimization. I'm always starting from numbers bracket I, wherever I am, and then everything else to the right. And that's what was allowing me to ignore the already sorted volunteers. If, though, my last line says swap smallest number with numbers I think that implements what our humans were doing by physically walking to another spot. All right, so that then would be what we'll call selection sort. Let's go ahead and take a second approach here using an algorithm that I'm going to call bubble sort. But to do this, we need you all to reset to your original locations. We have a little cheat sheet on the board if you'd like to go back to this position here. And let me take a fundamentally different approach because I'm not really liking selection sort as is because it's kind of a lot of walking back and forth. And a lot of walking suggests like a lot of steps again and again. So what might I do instead? Well, bubble sort is going to have me focus a little more intuitively on just smaller problems. And let's see if this gets me somewhere else. So if I just look at this list without looking at everyone else, 7 and 2. This is obviously a problem. Why? Because you're out of order. So let's just solve one tiny problem first. So 7 and 2, why don't you swap? I know 2 is in a better place now because she's definitely lower, less than 7. So I think I can now move on. 7 and 5, problem. So let's solve that. 7 and 4, problem. Let's solve that. 7 and 1, let's solve that. 7 and 6, let's solve that. 7 and 0, solve that. 7 and 3, solve that. OK, done. Sorted, right? All right, obviously not if you just glance at these numbers here, but we have fundamentally taken a bite out of the problem. 7 is indeed in the right place, so we maximally have n minus 1 other problems to solve. So how do I do this? I think I can just repeat the same logic. Let me go over here. 2 and 5, good. 5 and 4, no. 5 and 1, no. 5 and 6, yes. 6 and 0, no. 6 and 3, no. So now we've solved 2 of the problems. And what's nice about bubble sort, at least as a glance, it's nice and simple, it's nice and local, and you just keep incrementally solving more and more problems. So let's go ahead and do this again, and we can do it faster. 2 and 4 we know are good. 4 and 1, 4 and 5, 5 and 0, 5 and 3, 5 and 6, 6 and 7. Good. So we go back. 2 and 1. Now another problem solved. 2 and 4. 4 and 0, 4 and 3, 4 and 5, 5 and 6, 6 and 7. And so notice, too, as per its name, the largest elements have bubbled their way up to the top. And that's what seems to be happening just as we're fixing some remaining problems. So almost done. 1 and 2, 2 and 0, 2 and 3, 3 and 4, 4 and 5, 5 and 6, 6 and 7. Almost done. Obviously, to us humans, it looks done. How do I know as the computer for sure? What would be the most surefire way for me to now? Oh, it's not done. Sorry. That's a bug. OK, 1 and 0. OK, 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6, 6 and 7. OK, so now it's obviously sorted to the rest of us on stage. How could I confirm as much as code, right? You're doing it with your mind, just glancing at this. How would the computer, the code, know for sure that this list is now sorted? Yeah. Let's do it one more time and look, draw what conclusion? Yeah, let's do it one more time, even though it's a little wasteful. But logically, if I go through the whole list, comparing pairs again, again, and again, and I don't do any work that time, now it's obviously logically safe to just stop, because otherwise I'm wasting my time doing the same thing again and again if no one's actually moving. So I'm afraid we don't have Monopoly games for all of you, but we do have 8 stress balls. And a round of applause, if we could, for our volunteers. If you want to put your numbers on the shelf there. So if we consider for a moment, thank you so much. Sure. Thank you. Thanks. Sure. So if we consider now these two algorithms, which one is better? Any intuition for whether selection sort the first is better or worse than bubble sort the second? Any thoughts? Yeah? OK. So bubble sort seems like less work, especially since I was focusing on those localized problems. Other intuition? Selection sort versus bubble sort? Well, let me propose that we try to quantize this so we can actually analyze it in some way. And this is not an exercise we'll do constantly for lots of algorithms, but these are pretty representative of algorithms, so we can wrap our minds around, indeed, the performance or the design of these things. So here is my pseudocode for selection sort, whereby, as per its name, I just iteratively select the next smallest element again and again. So how can we go about analyzing something like this? Well, we could just do it on paper pencil and count up the number of steps that seem to be implied logically by the code. We could literally count the number of steps I was taking again and again, left to right. We could also just count the number of comparisons I was making with each of the persons involved. And I was doing it kind of quickly in selection sort, but every time I was looking at a person trying to decide, do I want to remember that number as smallest, that number, I was comparing two values with an equals equals or less than or greater than sign, at least if we had done this in code. So that tends to be the norm when analyzing algorithms like these, counting the number of comparisons, because it's kind of a global unit of measure we can use to compare different algorithms entirely. So think, too, that in the general case, when we have more than 8 volunteers, more than 7 doors, we can generalize our array in general as this is the first element at bracket 0, and the end of it is always n minus 1. So arrays, or doors in this case, or volunteers are always numerically indexed from 0 on up to n minus 1, if there's n of them in total. So how do we analyze the code of selection sort? Well, how many steps did it take me to find the first smallest element? Or more precisely, how many comparisons did I need to make when I walked left to right to find our first smallest person, which ended up being 0? How many comparisons did I do when walking left to right? If there were 8 people on stage, how many total comparisons did I do? Like if there's 8 people, I compared these folks, then like this person, yeah. Yeah, so 7 total, right? Because if there's 8 people on stage, you can only do 7 comparisons total, because otherwise you'd be comparing one number to itself. So it seems like in the general case, if you've got n numbers that you're trying to sort, finding the smallest element first takes n minus 1 comparisons. Maybe n total steps left to right, but the number of comparisons, which I claim is just a useful unit of measure, is n minus 1. How about finding the next smallest person? How many steps did it take me to find the next smallest number, which ended up being the number 1? Yeah, so just n minus 2. Why? Because I'd already solved one problem. Someone was already in the right position. It would be silly to keep counting them again and again. So I can whittle down my number of comparisons for the next pass to n minus 2. The third pass, to find the third smallest number, would be n minus 3. And then dot, dot, dot. Presumably this story, this formula, ends when you have just one final pair, the people at the end to compare. So if this is looking a little reminiscent of some kind of recurrence from high school or high school math or physics or the like, let me just stipulate that if you actually do out this math and generalize it, that is the same thing as n times n minus 1 divided by 2. And if you're rusty on that, no big deal. Just kind of commit to memory that anytime you add up this kind of series, something plus something slightly smaller plus something slightly smaller, each of which differs by 1, you're going to get this formula, n times n minus 1 over 2. If we, of course, multiply that out, that's really n squared minus n all divided by 2. If we keep multiplying it out, that's n squared divided by 2 minus n over 2. And now we have kind of a vocabulary with which we can talk about the efficiency, the design of this algorithm. But honestly, I don't really care about this level of precision, like n squared divided by 2 minus n divided by 2. As n gets really large, which of these symbols, which of these terms is really going to dominate, become the biggest influencer on the total value of steps? Right, it's the square, right? Like, it's definitely not n divided by 2. That's shaving some time off. But n squared, as n gets big, is going to get really big. If n is 100, then n squared is bigger. If n is 1,000,000, n squared is really bigger. And so at the end of the day, when we're really just talking about sort of a wave of the hand analysis, an upper bound, if you will, let's just say that selection sort, as analyzed here, it's on the order of n squared steps. It's not precisely n squared steps, but you know what? N squared divided by 2, the intuition here might be that, well, it's half of that. N squared is what really matters as n gets really, really large. And that's when you start thinking about and trying to solve the Google problems of the world. When n gets large, that's when you have to be smarter than just sort of naive implementations of any algorithm. So where then does this algorithm fall into this categorization here? Well, n squared, it turns out, is on the order of n squared steps in the worst case, whether it's sorted or not. It turns out, though, lower bound, if we consider this same code, suppose the best case scenario, like our 8 volunteers came up on stage, and just because they already sorted themselves, so 0 through 7, suppose they just happened to be in that state. How many steps would selection sort take to sort an already sorted list of volunteers? Any intuition? Yeah. Would it still be n? So for the first pass, it would still be 7 for the first pass across the humans, because even though, yeah, I'm claiming 0 is here, I don't know that 0 is the smallest until I make my way all the way over there, doing all 7 comparisons. OK, fine. First pass took 7, or more generally, n minus 1 steps. What if I look for the next smallest element, and the humans in this story are already sorted 0 through 7? Well, yes, the number 1's here, and I see them first. But I don't know they're the smallest until I compare against everyone else, get to the end of the list, and realize, oh, well, that was stupid. I already had the smallest person in hand then. And so this pseudocode, this implementation of selection sort, is sort of fixed like this. There's no special case that says, if already sorted, quit early. It's always going to take n squared steps. And so in this case, if we borrow our jargon from earlier, using omega notation, just to be clear, selection sort is also going to be in this incarnation an omega of n squared. Because even in the best case where the list is already sorted, you're going to waste a huge amount of time essentially verifying as much or discovering as much, even though we humans, of course, could see it right away. So selection sort would seem to take both n squared steps in the worst case, n squared steps in the best case. And so you know what? We can use our theta terminology for that. Here would be an algorithm, just like counting earlier, that always takes n squared steps, no matter whether the array is sorted or not from the get-go. All right, so hopefully we can do better. And someone proposed earlier that bubble sort felt like it was using fewer steps. Well, let's consider that next. With bubble sort, we had this pseudocode, I claim, whereby, let's focus on the inside of the code first. Down here, what was I doing? For I from 0 to n minus 2. That's curious. We've never seen n minus 2 before, but I asked this question. If numbers bracket I and numbers bracket I plus 1 are out of order, swap them. So that was when I was pointing at our first 2 volunteers here. I saw that they were out of order, so I swapped them. How come I'm doing that again and again up to n minus 2, though, instead of n minus 1, which we've always used up until now as our rightmost boundary? Any intuition for why I'm doing this from 0 to n minus 2? Yeah. Exactly. Because I'm looking at the ith person per this pseudocode here and the ith plus 1 person, I better make sure I don't go step beyond the boundaries of my array. So if you think of like my left hand when my back was to here, pointing at the current person at the first position, my right hand for this if conditioner is essentially pointing at the person next to them. And you want to iterate with your left hand all through these people, but you don't want your left hand to point at the last person. You want it to point at the second to last person. But we know that the last person is always at n minus 1. So the second to last person just mathematically is at n minus 2. So it's a subtlety, but this is like a seg fault waiting to happen. If you implemented bubble sort using n minus 1, you will. My right hand would go beyond the boundaries of the array. So just bad. All right, so why am I saying this n times? Well, we did it very organically with humans, but each time someone each pass I did through the array, someone bubbled their way up to the end. Number 7, then number 6, then number 5. So if on each pass through the array of volunteers, I was solving at least one problem, it seems like bubble sort can just run n times total to solve all n problems. Because the first pass will get at least one number into place. Second pass, second number into place. You might get lucky and it would do more, but worst case, this feels like enough. Just do this blindly n times, and they'll all line up together. Well, technically, all right, now we're getting into the weeds. Technically, you can just repeat it n minus 1 times, because if you solve all n minus 1 other problems and you're left with 1, like literally that person's where they need to be, just logically. If you've already sorted everything else and you've got just the one left, it's already bubbled up. So how do we analyze this? Well, in bubble sort, we might do something like this. I'm essentially doing n minus 1 things n minus 1 times. Now let me back up to the pseudocode, because this one's a little less obvious. This is where you can actually mathematically infer from your loop how many steps you're taking. So this first line literally says repeat the following n minus 1 times. So that's going to translate very straightforwardly to our mathematical formula. Do something n minus 1 times. This loop, just because I'm using for loop terminology, it's framed a little differently. But if you're iterating from 0 to n minus 2, you're iterating a total of n minus 1 times. And again, the arithmetic's getting a little annoying, but this just means do the following n minus 1 times. So do n minus 1 things n minus 1 times. We can now run out the math as follows. We have the formula n minus 1 times n minus 1. We do our little FOIL method here, n squared minus 1 times n minus 1 times n plus 1. We can combine like terms, n squared minus 2n plus 1. But at this point, when n gets really large, which term are we really going to care about? This is on the order of, yeah, n squared. So at least asymptotically means as n approaches infinity, gets really large, turns out that the upper bound on selection sort and bubble sort are essentially the same. Now, if we really nitpicked and compared the total number of comparisons, they might differ slightly. But as n gets large, honestly, you're barely going to notice the difference, it would seem, between these two algorithms. But what about the lower bound? If the upper bound on bubble sort is also big O of n, what about the lower bound here? Well, with this pseudocode, what would the lower bound be on bubble sort, even in the best case when all of the volunteers are sorted? Any intuition? In this pseudocode. Yeah, in the middle? Good question. Isn't bubble sorts designed such that you wouldn't need to compare numbers that have already bubbled up? That's what's happening here in the middle implicitly. I'm always going from left to right. But remember that even when I screwed up at the end and the last two people were out of order, I do always need to restart at the beginning, because the big numbers are going that way and the small numbers are coming this way. So that is true. There are some slight optimizations that I'm kind of glossing over here. Let me stipulate that it would still end up being on the order of n squared. But that would definitely shave off some actual running time here. But what if the list is already sorted? Our pseudocode at the moment has no allowance for if list is already sorted, quit early. So we're going to blindly do n minus 1 things n minus 1 times unless we modify our pseudocode. As I did verbally earlier, I propose this. Inside of that outer loop, if you make a pass across all of the volunteers and your mental counter has made no swaps, you have to keep track with some kind of variable, well, then you might as well stop. Because if you do a whole pass and make no swaps, why would you waste time doing it again expecting different behavior? So to help visualize these, whereby now bubble sort can be advantageous if the data is already sorted or mostly sorted. Why? Because it does have this short circuit detail. At least if we implement it like that, how can we go about visualizing these things a little more clearly? Well, let me go ahead and do this. Let me pull up here a visualization of exactly these algorithms, thanks to a third-party tool here that's going to help us visualize these sorting algorithms as follows. Small bars represent small numbers. Big bars represent big numbers. And so the idea now is when I hit a button here to get all of the small bars this way, all of the big bars this way. So just like our volunteers, but instead of holding lighted numbers, it's bars representing their magnitude. So let's go ahead and start with, for instance, selection sort. And you'll see in pink is being highlighted the current number that is being selected and then pulled all the way to the left. So this is selection sort. And again, it's selecting the next smallest element. But you can see here all the more visibly that just like my human feet were taking a lot of steps, so is this algorithm touching these elements again and again and again. And this is why the n squared is really a thing. There's got to be some inherent redundancy here. Like, why do we keep looking at the same darn elements again and again? We do, in terms of our pseudocode, need to do so. But it's this redundant comparisons that kind of explains why n squared is indeed the case. So now it's done. Small bars here, big bars there. And I had to just keep talking there to kill time because it's relatively slow. Well, let me re-randomize the array, just so we start with a different order. And now let me click on bubble sort. And you'll see similar idea, but different algorithm. So now the 2 bars in pink are the 2 that are being compared and fixed potentially if they're out of order. And you can see already that the biggest bars are bubbling their way up to the top. But now you can also see like this redundancy, like we keep swooping through the list again and again, just like I kept walking back and forth. And this is n squared. This is not that many bars. What, 10, 20, there's like 40 or something bars, I'm guessing. That's pretty slow already just to sort 40 numbers. And I think it's going to get tedious if I keep talking over this. So let's just assume that this too is relatively slow. Had I gotten lucky and the list were almost sorted already, bubble sort would have been pretty fast. But this was a truly random array, so we did not get lucky. So indeed, the worst case might be what's kicking in here. So I feel like it'll be anticlimactic, like holding in a sneeze if I don't let you see the end of this. So here we go. Nothing interesting is about to happen. Almost done. OK, done. All right, so thank you. Thank you. So still somewhat slow, though. How, though, can we perhaps do a little better fundamentally? So we can do so if we introduce yet another technique. And this one isn't so much a function of code as it is concept. And it's something that you might have seen in the real world, but perhaps not so obviously so. So it turns out in programming, recursion refers to the ability of a function to call itself. In the world of mathematics, if you have a function f, if f appears on both the left side and the right side of a formula, that would be a recursive function in the math world too. Whenever f is defined in terms of itself, or in our case, in programming, anytime a function calls itself, that function is said to be recursive. And this is actually something we've seen already in class, even though we didn't call it as much. So for instance, consider this pseudocode from earlier, whereby this was the pseudocode for searching via binary search. A whole bunch of doors. If no doors are left, return false. That was the additional conditional we added. But then if number behind middle door, return true. And here's the interesting part. If number is less than middle door, search the left half. Else, if number is greater than middle door, search the right half. This pseudocode earlier was itself recursive. Why? Because here is an algorithm for searching. But what's the algorithm telling us? Well, on this line and this line, it's telling us to search something else. So even though it's not explicitly defined in code as having a name, if this is a search algorithm, and yet the search algorithm is using a search algorithm, this pseudocode is recursive. Now, that could quickly get you into trouble if a function just calls itself again and again and again. But why intuitively is it not problematic that this code, this pseudocode, calls itself? Why will the algorithm still stop? Yeah. Exactly. It has some exit condition, like if no doors less. And more importantly, anytime you search the left half, you're searching a smaller version of the problem. Anytime you search the right half, you're searching a smaller version of the problem, literally half the size. So this is why in the phone book, obviously, I couldn't tear the phone book in half infinitely many times, because it was literally getting smaller each time. So recursion is this ability to call yourself, if you will. But what's important is that you do it on a smaller problem, so that eventually you have no more problems to solve, or no more data, no more doors at all. So these two lines here would be the recursive elements here. But if we go back to week 0, we could have used recursion in some other way. So this was our pseudocode for the phone book back in week 0. And recall that we described these yellow lines as really representing a loop, some kind of cycle again and again. But there was a missed opportunity here. What if I had re-implemented this code to do this instead? Instead of saying open to middle of left half of book and then go back to line 3, like literally inducing a loop, or open to middle of right half of book and go back to line 3, inducing another loop, why don't I just recognize that what I'm staring at now is an algorithm for searching a phone book? And if you want to search a smaller phone book, like A through M or N through Z, we'll just use this same algorithm. So I can replace these yellow lines with just this, casually speaking. Search left half of book, search right half of book. This would be implicitly, and now I can shorten the whole thing, a recursive implementation of the phone book pseudocode from week 0. And it's recursive because if this is a search algorithm and you're saying go search something else, that's fine. That's recursive. But because you're searching half of the phone book, it's indeed going to get smaller and smaller. Even in the real world, or the real virtual world, you can see recursive data structures in the wild, or at least in Super Mario Brothers like this. Let me get rid of all of the distractions here and focus on this pyramid, where you have 1 block, then 2, then 3, then 4. Well, this itself is technically recursively defined in the sense that, well, what is a pyramid of height 4? Well, it's really what? How would you describe? A pyramid of height 4 is actually the same thing as a pyramid of height 3 plus 1 additional layer. Well, what's a pyramid of height 3? Well, it's technically a pyramid of height 2 plus 1 additional layer. And so even physical structures can be recursive if you can define them in terms of itself. Now, at some point, you have to say that if the pyramid is of height 1, there's just 1 block. You can't forever say it's defined in terms of a height -1, -2. You would never stop. So you have to kind of have a special case there. But let's go ahead and translate something like this, in fact, to code. Let me go back to VS Code here, and let me implement a program called iteration that refers to a loop iterating. And let me implement a very simple pyramid like that. So let me go ahead and include the CS50 library. I'll include our standard io.h, int main void, no command line arguments today. And let's go ahead and do this. Let's declare a variable called height, ask the human for the height of this pyramid. And then let's go ahead and draw a pyramid of that height. Now, of course, draw does not yet exist, so I'm going to need to invent the draw function. Let me go ahead and define a function that doesn't have a return value. It's just going to have side effects. It's just going to print bricks on the screen, call draw, and it takes in an integer n as its input. And how am I going to implement this? Well, again, I want to print 1 block, then 2, then 3, then 4. That's pretty straightforward, at least once you're comfortable with loops. Let me go back to the code here. Let me go ahead and say for int I gets 0, I is less than n, I plus plus. And that's going to iterate essentially row by row. And on each row, I want to print out 1, then 2, then 3, then 4 bricks. But I'm iterating from 0 to 1 to 2 to 3. So I think that's OK. I can just say something like for int j gets 0, j, let's be clever about this, is less than I, j plus plus. And now let me go ahead and inside of this loop, I think I can get away with just printing out a single hash sign. But then outside of that loop, similar to last week, I'm going to print my new line separately. So a little non-obvious at first, but this outer loop iterates row by row, line by line, if you will. And then the inner loop just makes sure that when I equals 0, let's see. Oh, nope, there's a bug. I need to make sure that it's j is less than I plus 1. So when I is 0 on my first line of output, I'm going to print out 1 brick. When I is 1, I'm going to print out 2 bricks, and so forth. So let me go ahead and run make iteration. All right, and now seems to compile. Implicit declaration of function draw. So I'm making week 1 mistakes again. What? Say again? Yeah, the prototype is missing. I didn't declare it at the top. That's an easy fix, and the only time really it's OK and necessary to copy paste. Let me copy the function's declaration there, end it with a semicolon, so that Clang now knows that draw will exist. Make iteration. Now it works. Thank you. / iteration. We'll type in something like 4, and there we have it. Our pyramid of height 1, 2, 3, 4 that looks pretty similar to this, albeit using hashes. So that's how we would have implemented this like 2 weeks ago in week 1, maybe last week, but just using arrays. But let me propose that we could do something recursively instead. Let me close this version of the code, and let me go back to VS Code and open up recursion.c just to demonstrate something recursively. And I'll do it incorrectly deliberately the first time. So let me include cs50.h. Let me include standardio.h. Let me do int main void. And let me just blindly draw a pyramid initially of height 1. But now in my draw function, let me re-implement it a little differently. So my draw function this time is still going to take a number n, but that's how many hashes it's going to print. So let's do for int I gets 0, I is less than n, I plus plus. Then let's go ahead and print out a single hash mark here. And then after that, let's print out the end of the line, just as before. But now this, of course, is only going to draw a single row. It's going to print out 1 hash or 2 hashes or 3 hashes, but only on 1 line. Let me now incorrectly, but just kind of curiously say, all right, well, if this draws a pyramid of height 1, let's just use ourselves to draw a pyramid of height n plus 1. So the first time I call draw, it will print out 1 hash. Then the second time I call draw, it will print out 2 hashes, then 3, then 4. So we're kind of laying these bricks down from top to bottom. Make recursion. Whoops, I screwed up again. So let's copy the prototype here. Let's put this down over here, semicolon. Let's do this again. Make recursion. All right, all good. / recursion. And now let me increase the size of my terminal window just so you can see more of the output. And here we have. OK, bad, but thank you. So we have an infinitely tall pyramid, and it's just flying across the screen, which is why it looks kind of like a mess. But I printed out a pyramid of height 1, and then 2, and then 3, and then 4. And unfortunately, what am I lacking? Any sort of quit condition, any kind of condition that says, wait a minute, when it's too tall, stop altogether. So this is an infinite loop, but it's not a loop. It's a recursive call. And actually, doing this in general is very bad. We'll see next week that if you call a function too many times, you can actually trigger yet another of those segmentation faults, because you're using too much memory, essentially. But for now, I haven't triggered that yet. Control-C is your friend to cancel. And as an aside, if you're playing along at home or play with this code later, I actually cheated here. We have a special Clang configuration feature that prevents you from calling a function like that and creating a problem. I overrode it just for demonstration's sake. But odds are at home you wouldn't be able to compile this code yourself. But let me do a proper version recursively of this code as follows. Let me go back into the code here. Let me go ahead and not just blindly start drawing 1, then 2, then 3 layers of bricks. Let me prompt the human as before for the height of the pyramid they want using our getInt function. And now let me call draw of height again. So now I'm going back to the loop-like version. But instead of using a loop now, this is where recursion gets rather elegant, if you will. Let me go ahead and execute and code the draw function as follows. Per your definition, if a pyramid of height 4 is really just a pyramid of height 3 plus another row, well, let's take that literally. Let me go back to my code. And if you want to draw a pyramid of height 4, well, go right ahead and draw a pyramid of height 3 first, or more generally, n minus 1. But what's the second step? Well, once you've drawn a pyramid of height 3, draw an extra row. So I at least have to bite off that part of the problem myself. So let me just do for int I gets 0, I is less than n, I plus plus, and let me, the programmer of this function, print out my hashes, and then at the very bottom, print out a new line so the cursor moves to the next line. But this is kind of elegant now, I dare say, in that draw is recursive, because I'm literally translating from English to C code this idea that a pyramid of height 4 is really just a pyramid of height 3. So I do that first. And I'm sort of trusting that this will work. Then I just have to lay one more layer of bricks, 4 of them. So if n is 4, this is just a simple for loop a la week 1 that will print out an additional layer. But this, of course, is going to be problematic eventually. Why? It's not done yet, this program. How many times will draw call itself in this model? Infinitely many times. Why? Yeah, there's no equivalent of quit. Like if you've printed enough already, then quit. Well, how do we capture that? Well, I don't think we want this to go negative, right? It would make no sense to draw a negative height pyramid. So I think we can just pluck off as the programmer an easy case, an easy answer, a so-called base case. And I'm just going to do this. At the top of my draw function, let me just say if n is less than, or heck, less than or equal to 0, that's it. Go ahead and just return. There's nothing more to do. And that simple condition, technically known as a base case, will ensure that the code doesn't run forever. Why? Well, suppose that draw is called with an argument of 4. 4 is, of course, not less than 0, so we don't return. But we do draw a pyramid of height 3. And here's where things get a little mentally tricky. You don't move on to line 20 until draw has been called. So when draw is called with an argument of 3, it's as though you're executing from the top of this function again. 3 is not less than 0, so what do? You draw 2. OK, how do you draw 2? Well, 2 is not less than 0, so you don't return. So you draw 1. Gotta be careful here. Draw 1, and now we go ahead back to the beginning. How do you draw 1? Well, 1 is not less than 0, so you don't return. You draw height 0. How do you draw height 0? Wait a minute. 0 is less than or equal to 0, and you return. And so it's kind of like this mental stack, this to-do list. You keep postponing executing these lower lines of code because you keep restarting the draw function until finally one of those function calls says there's nothing to do, return. And now the whole thing starts to unravel, if you will, and you pick back up where you left off. And this is perhaps the best scenario. We won't do it in class, but if you'd like to wrestle through this on your own, using debug 50 to keep stepping into each of those lines logically, you'll see exactly what's actually happening. So let me go to my terminal and do make recursion, which is now this correct version of the code, /recursion. Let's type in a height of 4, and voila, now we have that same pyramid, not using iteration per se, though admittedly we're using iteration to print the additional layer. We're now using draw recursively to print all of the smaller pyramids that need come before it. No, question is, can you only use recursion with a void function? No, not at all. In fact, it's very common to have a return value, like an integer or something else, so that you can actually do something constructively with that actual value. Other questions on this? Say a little louder. When is line 21 getting executed? So if you continue to unwrap, let me scroll down a bit more so you can see the top of the code. So line 21 will be executed once line 19 is done executing itself. Now, in the story I told, we kept calling draw again. But as soon as one of those function calls, where n equals 0, returns immediately, then we don't keep drawing again and again. So now if you kind of think of the process as reversing, then you continue to line 21. Then line 21 again. Then line 21 again. And as the sort of logic unravels. And next week, we'll actually paint a picture of what's actually happening in the computer's memory. But for now, it's very similar to the pseudocode for the phone book. You're just searching again and again. But you're waiting until the very end to get back the final result. Google now, whom I keep mentioning by coincidence today, is full of programmers, of course. Here's a fun exercise. Let me go back to a browser. I'm going to go ahead and search for recursion because I want to learn a little something about recursion. Here is kind of an internet meme or joke. If I zoom in here, the engineers at Google are kind of funny. See why? Ah, there we go. Yes? Yes, this is recursion. And there's going to be so many memes you'll come across now where recursion, like if you've ever pointed a camera at the TV that's showing the camera and you sort of see yourself or the image again and again, that's really recursion. And in that case, it only stops once you hit the base case of a single pixel. But this is a very funny joke in some circles when it comes to recursion and Google. So how can we actually use Google, or rather, how can we actually use recursion constructively? Well, let me propose that we actually introduce a third and final algorithm for sorting that hopefully does better than the two sorts thus far. We've done selection sort and bubble sort. Bubble sort we liked a little better, at least insofar as in the best case where the list is already sorted. Bubble sort's at least smarter, and it will actually terminate early, giving us a better lower bound in terms of our omega notation. But it turns out that recursion, and this is not necessarily a feature of recursion, but something we can now leverage. It turns out using recursion, we can take a fundamentally different approach to sorting a whole bunch of numbers in such a way that we can do far fewer comparisons and ideally speed up our final results. So here is the pseudocode for what we're about to see for something called merge sort. And it really is this terse. Sort the left half of numbers. Sort the right half of numbers. Merge the sorted halves. Right? This is almost sort of nonsensical because if you're asked for an algorithm to sort and you respond with, well, sort the left half, sort the right half. Like that's being sort of difficult because, well, I'm asking for a sorting algorithm. You're just telling me to sort the left half and the right half. But implicit in that last line, merging, is a pretty powerful feature of this sort. Now, we do need another base case at the top. So let me add this. If we find ourselves with a list, an array of size 1, well, that array is obviously sorted. If there's only one element in it, there's no work to be done. So that's going to be our base case, but allowing us now in just these, 6 lines of pseudocode to actually sort some elements. But let's focus first on just a subset of this. Let's consider for a moment what it means to merge sorted halves. So Carter has wonderfully come up to volunteer here just to help us reset these numbers. Suppose that in the middle of the story we're about to tell, we have two sorted halves. I've already sorted the left half of these numbers, and indeed 2, 4, 5, 7 is sorted from smallest to largest. And the right half appears to be already sorted. 0, 1, 3, 6, already sorted. So in my pseudocode, we're already done sorting the left half and the right half somehow, but we'll see how in a moment. Well, how do I go about merging these two halves? Well, because they're sorted already, and you want to merge them in order, I think we can flip down. We can hide all but the first numbers in each of these sublists. So here we have a half that starts with 2. And I don't really care what the other numbers are because they're clearly larger than 2. I can focus only on 2. And 0, 2. 0 also. We know that 0 is the smallest there. So let's just ignore the numbers that Carter kindly flipped down. So how do I merge these two lists into a new sorted larger list? Well, I compare the 2 on my left with the 0 on my right. Obviously, which comes first? The 0. So let me put this down here. And Carter, if you want to give us the next element. Now I have two sorted halves, but I've already plucked 1 off. So now I compare the 2 against the 1. 1 obviously comes next. So I'm going to take out the 1 and put it in place here. Now I'm going to compare the two halves again. 2 and 3, which do I merge first? Obviously the 2 comes next. And now notice, each time I do this, my hands are theoretically making forward progress. I'm not doubling back like I kept doing with selection sort or bubble sort, back and forth, back and forth. My fingers are constantly advancing forward, and that's going to be a key detail. So I compare 4 and 3. 3 obviously. I compare 4 and 6. 4 obviously. I compare 5 and 6, 5 obviously. And then I compare 7 and 6, 6 of course. And then lastly, we have just one element left. And even though I'm kind of moving awkwardly as a human, my hands technically were only moving to the right. I was never looping back, doing something again and again. And that's perhaps the intuition and just enough room for the 7. So that then is how you would merge two sorted halves. We started with left half sorted, right half sorted, and merging is just like what you would do as a human. And Carter just flipped the numbers down, so our focus was only on the smallest elements in each. Any questions before we forge ahead with what it means then to be merged in this way? So now, here is an original list. We deliberately put it at the top because there's one detail of merge sort that's key. Merge sort is technically going to use a little more space. And so whereas previously, we just kept moving our humans around and swapping people and making sure they stayed ultimately in the original positions, with merge sort, pretends that here's our original array of memory. I'm going to need at least one other array of memory. And I'm going to cheat, and I'm going to use even more memory. But technically, I could actually go back and forth between one array and a secondary array. But it is going to take me more space. So how do I go about implementing merge sort on this code? Well, let's consider this. Here's an array of size 8. If only one number quit, obviously not applicable. So let's focus on the juicy part there. Sort the left half of the numbers. All right, how do I sort the left half of the numbers? I'm going to just nudge them over just to be clear which is the left half. Here is now a sub list of size 4. How do I sort the left half? Well, do I have an algorithm for sorting? Yeah, what do I do? Here's a list of size 4. How do I sort it? What's step 1? Sort the left half. So I now sort of conceptually in my mind take this sublist of size 4, and I sort it by first sorting the left half, focusing now on the 7 and 2. All right, here's a list of size 2. How do I sort a list of size 2? Sorry? I think we just keep following our instructions. Sort the left half. All right, here is a list of size 1. How do I sort a list of size 1? I'm done. Like, it's done. So I leave this alone. What was the next step in the story? I've just sorted the left half of the left half of the left half. What comes next? I sort the right half of the left half of the left half. And I'm done, because it's just a list of size 1. What comes after this? Merge. So this is where it gets a little trippy, because you have to remember where we're pausing the story to do things recursively again and again. But if I've just sorted the left half and I've just sorted the right half, now I merge them together. This is a super short list, so we don't need Carter's help here as before. But I think the first number I take here is the 2. And then the second number I take, because it's the only option, is the 7. But what's nice now is that notice the left half of the left half is indeed sorted, because I trivially sorted the left half of it and the right half of it, but then merging is really where the magic happens. All right, again, if you rewind now in your mind, if I've just sorted the left half of the left half, what happens next? Sort the right half of the left half. So again, you kind of rewind in time. So how do I do this? I've got a list of size 2. I sort the left half, just the 5, done. Sort the right half, 4, done. Now the interesting part, I merge the left half and the right half of the right half of the left half. So what do? 4 comes down here, 5 comes down here. And now, notice what I have. Left half is sorted, right half is sorted. If you rewind in time, where is my next step? 3? Merge the 2 halves. And so this is what Carter helped me do before. Let's focus only on the smallest elements just so there's less distraction. I compare the 2 and the 4. 2 comes first, so let's obviously put that here. Now I compare the new beginning of this list and the old beginning of this list. 4 obviously comes next. And now I compare the 7 against the 5. 5 obviously comes next. And now lastly, I'm left with one number. So now I'm down to the 7. So even if you've kind of lost track of some of the nuances here, if you just kind of take a step back, we have the original right half here still untouched. But the left half of the original input is now indeed sorted, all by way of doing sorting left half, right half, right half, but with those merges in between. All right, so if we've just sorted the left half, we rewind all the way to the beginning. What do I now do? All right, so sort the right half. So sort the right half. How do I sort a list of size 4? Well, I first sort the left half, the 1 and the 6. How do I sort a list of size 2? You sort the left half. Just the number 1. Obviously, there's no work to be done. Done. Sorting the left half. 6. Done. Sorting the right half. Now, what do? I merge the left half here with the right half here. And that one's pretty straightforward. Now what do? I've just merged. So now I've just sorted the left half of the right half. So now I sort the right half of the right half. So I consider the 0, done. I consider the 3, done. I now merge these two together. 0, of course, comes first. Then comes the 3. And now I'm at the point of the story where I've sorted the left half of the right half and the right half of the right half. So step 3 is merge. And I'll do it again like we did with Carter. All right, 1 and 0. Obviously, the 0 comes first. Now compare the 1 and the 3. Obviously, the 1 comes first. Compare the 6 and the 3. Obviously, the 3. And then lastly, the 6th. So now where are we? We've taken the left half of the whole thing and sorted it. We then took the right half of the whole thing and sorted it. So now we're at lastly, step 3 for the last time. What do? Merge. And so just to be consistent, let me push these down. And let's compare left hand to right hand, noticing that they only make forward progress, none of this back and forth comparisons. 2 and 0, of course, the 0. So we'll put that in place. 2 and 1, of course, the 1. So we put that in place. 2 and 3, we merge in, of course, the 2 in this case. 4 and 3, we now merge in the 3 in this case. 4 and 6, we now merge, of course, the 4 in place. And now we compare 5 and 6. We keep the 5. Bug. OK, well, pretend that the 5 is on. Oh, this is why. All right, so now we compare the 7 and the 6. 6th is gone. And lastly, 7 is the last one in place. And even though I grant that of all the algorithms, this is probably the hardest one to stay on top of, especially when I'm doing it as a voiceover, realize that what we've just done is only those 3 steps recursively. We started with a list of size 8. We sorted the left half. We sorted the right half. And then we merged the 2 together. But if you go down each of those rabbit holes, so to speak, sorting the left half involves sorting the left half of the left half and the right half of the left half, and so forth. But this germ of an idea of really dividing and conquering the problem, not such that you're having the problem and only dealing with one half. Clearly, we're sorting one half and the other half and merging them together ultimately. It does still lead us to the same solution. And if we visualize the remnants of this now, if I depict this as follows, where on the screen here, you see where the numbers originally started in the top row from left to right. Essentially, even though this is in a different order, I divided that list of size 8 ultimately into 8 lists of size 1. And that's where the base case kicked in and just said, OK, we're done sorting that. And after that, logically, I merged 2 lists of size 1 into many lists of size 2. And those lists of size 2 into lists of size 4. And finally, the lists of size 4 into one big list sorted of size 8. And so I put forth this picture with the little line indicators here because how many times did I divide in half? Or really double, double, double. So exponent is the opposite. Oh, spoiler. How many times did I divide? So 3 concretely. But if there's 8 elements total and there's n more generally, it really is a matter of dividing and conquering log n times. You start this, and you can divide 1, 2, 3 times, log n times. Or conversely, you can start here and exponentially double, double, double 3 times, which is log n. But on every row, every shelf, literally, I made a fuss about pointing my hands only from the left to the right, constantly advancing them, such that every time I did those merges, I touched every element once and only once. There was none of this back and forth on stage. So if I'm doing something log n times, or if I'm doing rather n things log n times, what would be our big O formula perhaps? N things log n times? Yeah, so n log n. The order of n log n is indeed how we would describe the running time of merge sort. And so of all of the sorts thus far, we've seen that merge sort here actually is n log n, which is strictly better than n squared, which is where both selection sort and bubble sort landed. But it's also slower than linear search, for instance. But you would rather expect that. If you have to do a lot of work up front sorting some elements versus just searching them, you're going to have to put in more effort. And so the question of whether or not you should just search something blindly with linear search and not bother sorting it really boils down to, can you afford to spend this amount of time? And if you're the Googles of the world, odds are you don't want to be searching their database linearly every time. Why? Because you can sort it once and then benefit millions, billions of people subsequently using something like binary search, or frankly, in practice, something even fancier and faster than binary search. But there's always going to be this trade-off. You can achieve binary search only if the elements are sorted. How much does it cost you to sort them? Well, maybe n squared if you use some of the earlier algorithms. But it turns out n log n is pretty fast as well. So at the end of the day, these running times involve trade-offs. And indeed, in merge sort 2, I should note that the lower bound on merge sort is also going to be omega of n log n. As such, we can describe it in terms of our theta notation, saying that merge sort is indeed in theta of n log n. So generally speaking, probably better to use something like merge sort or some other algorithm that's in n log n. In practice, most programmers are not implementing these sorting algorithms themselves. Odds are they're using a library off the shelf that themselves have made the decision as to which of these algorithms to do. But generally speaking, and we're seeing now this for the first time, if you want to improve time, like use less time, write faster code, you've got to pay a price. And that might be your human time, just takes you more time to code up something more sophisticated, more difficult to implement, or you need to spend something like space. And as these shelves suggest, that too is one of the key details of merge sort. You can't just have the elements swapping in place. You need at least an auxiliary array so that when you do the merging, you have a place to put them. And this is excessive, this amount of memory. I could have just gone back and forth between top shelf and bottom shelf, but it's a little more interesting to go top down. But you do need more space. Back in the day, decades ago, space was really expensive. And so you know what? It might have been better to not use merge sort, use bubble sort or selection sort even, or some other algorithm altogether. Nowadays, space is relatively cheap, and so these are more acceptable trade-offs. But it totally depends on the application. The very last thing we thought we'd do is show you an actual comparison of some of these sorting algorithms. It's about 60 seconds long, and it will compare for you selection sort, bubble sort, and merge sort in parallel, simultaneously, with some fun sorting music, showing you ultimately what it really means to be an O of n squared, or better yet, big O of n log n. Selection on the top, bubble on the bottom, merge in the middle. That's it for CS50. We'll see you next time. right, this is CS50, and this is week 4. And if you think back a few weeks ago already, in week 0, we started talking about like what images are. And we talked about representation of images as this grid of pixels, and each pixel has like some pattern of bits that defines its color. Well, it turns out today we'll take a deeper look underneath the hood at how things like images and so much more is actually implemented using just these zeros and ones, and how now, as a programmer, you can actually harness that, for better or for worse, to better understand and better manipulate what's going on inside of a computer's memory using a language like C. In fact, even this bowl of stress balls that we keep happening is just a photograph, of course. But if you think back to week 0, if you sort of enhance this image, like they do in the movies, it actually doesn't work out the way you would think from Hollywood. As I continue to zoom in and zoom in and zoom in on a screen like this, you'll see that, yes, it gets bigger, but if it gets too big, what do you start to notice? The so-called pixelation. And indeed, you can see the individual dots. So next time you watch some show or movie on TV that has this sort of notion of enhancing, there's actually a finite limit there. You can only enhance so far as there's actually information there. But once you zoom into a certain level like this, like that's all that's there. You're not going to see the glint of the suspect in some crime drama in their eye just because you've enhanced the image. There's only a finite amount of information actually there. But we'll see today, too, that by understanding what's going on inside of a computer's memory, we can start to represent and even create and code more interesting things. So for instance, here is a bitmap, if you will, which is a term of art. A bitmap is a type of image. And it's a map of bits in the sense that you have this coordinate system of top, down, left, right, at least in this artist representation here. And suppose that maybe we all decide as the world that 1 shall represent the color white and 0 shall represent the color black. What might this map of bits, this bitmap, actually be? Can you see through it? Yeah. It is indeed a smiley face. So an amazing eye. If I actually turn all of the ones to white just to visualize this, you'll see indeed this is what was embedded there. But of course, on our computer monitors and phones, we have this grid of squares, this grid of pixels. So indeed, if you were to actually see on your screen a smiley face, like a black and white one at that, what's probably going on underneath the hood is just some pattern of zeros and ones and maybe single bits, 1-bit color, if you will, where 1 here represents white and 0 represents black. So if you kind of like this thing, it turns out you can do pretty beautiful, pretty interesting, pretty artistically inclined things. If you go to this URL at your leisure, cs50.ly/art, it'll actually redirect you to a Google spreadsheet that we've made in advance. And we've kind of shrunk the rows and columns to resemble a grid of pixels, tiny little squares, all of which are white by default, not unlike this easel here that we have a couple of volunteers working away at. In fact, would you guys like to come forward for a moment and say a quick hello before we come back to you?
Hello, my name is Daniel. I'm from Chicago.
Welcome to Daniel. And?
Hi, everyone. I'm Adam, and I'm from Trinidad and Tobago.
Nice. Well, welcome to you both. Thank you. You'll see that in their hands are actually a whole bunch of pixels, Post-it notes that we've handed them in advance. So if you don't mind, we'll come back to you in a couple of minutes and see what they've created, if you will, on this grid of white paper, much like you could create on this Google spreadsheet. In fact, feel free to send us your creations, if so inclined, via the URL you'll get at cs50.ly/art. Now, let's come back to week 0, where we define some of the building blocks for images. We talked about RGB, which is just red, green, blue. And it's just one of the systems, a popular system via which you can represent any color of the rainbow using some combination of red and green and blue. And if any of you are artistically inclined or have used Photoshop or similar programs, you might typically have some means of selecting a color via some grid like this. But down here, notice there's explicit mentions of the types of color systems in use, RGB. And in fact, here you see 0, 0, 0. And up here under new, you see the color black. And that implies that if you have no red, no green, no blue, well, that indeed would represent, by convention, the color black. By contrast, if we play around with Photoshop or any similar program, if you have a lot of red, a lot of green, and a lot of blue, for instance, 255, 255, 255, like really crank it up to the max value you can represent with 8 bits per week 0, well, then it turns out you get the color white here. And we can play with these numbers endlessly. For instance, if we use 255 of red, but 0 green and 0 blue, not surprisingly, the square at the top of the screen becomes, of course, red entirely, because it's all red and no green, no blue. If we change it instead to 255 for green, but 0 for red and blue, of course, we get green. And then lastly, if we crank up the blue, but leave red and green as 0, we, of course, get blue. But all this while, down here highlighted, is something that maybe some of you have seen before, like some combination of numbers and letters. If any of you have made personal web pages or used programs like Photoshop, you might have used these so-called color codes. So indeed, the world has this convention whereby using 6 digits, or sometimes 3, you can represent a little more succinctly some amount of red, green, blue. And you'll see here, maybe by inference, that if RGB is 0, 0, 255 respectively, perhaps where we're going with this is that 0, 0, 0, 0, FF is just an alternative way of expressing the exact same idea. No red, no green, and a lot of blue. But why is that? And in fact, we'll come full circle here to introducing something that we could have done in week 0, but it doesn't really solve a problem then. But today, as we focus more on images and on memory itself, turns out understanding these patterns is pretty useful. So back in week 0, we talked, of course, about binary. And binary, by implying 2, only gives you 2 digits, 0 and 1. You and I, as humans, almost always use the decimal system in normal conversation, dec meaning 10. So we have 0 through 9 instead. If a human like us wants to count up as high as 10 or 11 or 12, we don't have a digit per se for 10, 11, and 12. We start reusing digits. So it's 1, 0, 1, 1, 1, 2, and so forth. But in other systems, not binary, not decimal, but systems called hexadecimal, hex implying 16, there are actually more digits than these, which might come as a surprise. It's not pairs of digits, like in decimal, single digits. And frankly, it doesn't really matter what the digits are, because at the end of the day, these are just symbols that you and I immediately associate with some notion of math, but just strokes on the screen that represent some actual value. So it turns out that by convention, when you want more than 10 digits, 0 through 9, you start using letters of the English alphabet, A, B, C, D, E, and F. And you can represent them in lowercase. It's case insensitive, so it doesn't really matter. You might see it in uppercase or lowercase. But this is how you can count beyond 9, not using decimal, but using indeed something called hexadecimal. If we get really technical, this is also known as base 16. And it's the same idea as week 0, where instead of using base 2 for binary, base 10 for decimal, use 16 as the base for hexadecimal. And so if we run through just some simple examples here, in the world of hexadecimal, your columns are just powers of 16. 16 to the 0, 16 to the 1, 16 to the 2, and so forth. But in the world of hex, we usually, at least thus far, and today, we'll see just pairs of digits like this. So here, for instance, is the 1s column and the 16s column, if we multiply that out. So if you wanted to represent the number you and I know in the real world as 0, in hexadecimal, it would just be 0, 0. If you want to represent the number 1, it would be 0, 1. And from there, we get 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, 0, 7, 0, 8, 0, 9. Now things get potentially interesting. In decimal, it would obviously become 10. But in hexadecimal, it just becomes 0a and then 0b. Which is to say, if I rewind, after 9 comes in hexadecimal. If I pronounce it in decimal, this is how you'd represent 10. This is how you'd represent 11, 12, 13, 14. And then lastly, in hexadecimal, the 16th value is f, which is just always going to represent 15. So how do we connect this to some of the past math? Well, once you get to 0f in hexadecimal, if f is the highest you can count, just like in decimal, 9 is the highest you can count, what comes next? If this is 15, I claim, how do I represent 16 in hexadecimal? With what pattern of symbols? What pattern of symbols for hexadecimal? Yeah. So 1, 0, not 10, even though you might read it like that as a typical human, but 1, 0. Because why? Well, even if this is completely new to you, the whole column system, the places are exactly the same intuitively. So you need a 1 in the 16's place and a 0 in the 1's place. And we won't count all the way up to 255, but if we count a little higher, this would be 1, 0, aka 16 in decimal. This would be 1, 1, aka 17 in decimal. And then 18, 19, 20, and so forth, ... And we can count all the way up to FF. Because if F is the biggest digit in hexadecimal, FF is indeed as high as we can count. And if each F represents 15, well, let's just do the math like in week 0. So 16 times F plus 1 times F is how all of us learn to do math in grade school, even though not in hexadecimal. That's, of course, 16 times 15 plus 1 times 15. Multiply that out, you get 240 plus 15. And ergo, you can count as high as 255 using 2 hexadecimal digits. Now, this is not the kind of thing where like this is going to be an interesting exercise mentally to ever convert in your head. Generally, you'll get used to the fact that after 9 comes A, and the biggest digit is F, and you'll just start to see patterns like this in the worlds of Photoshop, web pages in a few weeks, and beyond. But like, why is hexadecimal useful? Like, why are we complicating the world and adding on top of decimal something else? Well, it turns out that a single decimal digit, like F, the biggest one, for instance, is 15. And here, let me just propose a bit of mental math. How many bits do you need to represent the number 15 in binary? If you've got the 1's place, 2's place, 4's, and so forth, how many bits total? So fewer than 5 to count as high as 15, I think, but close. Someone else? Seeing a hand? Yeah. So 4 bits, I think, suffice, because if you want to count as high as F, that is to say 15, I think if you have 4 bits, you can do that. Because if over here is the 1's place from week 0 for binary, this is the 2's place, this is the 4's place, this is the 8's place, do out some quick math. So 8 plus 4 is 12, plus 2 is 14, plus 1 is 15. So it turns out that by convenience, hexadecimal digits can just be represented consistently with 4 bits, or fewer, but 4. And 4, of course, is half of 8. And 8 is like everywhere. Like 8 bits is a byte, which is, again, just a convention we've seen. And so the reason that you see hexadecimal in the world of Photoshop and eventually web pages is it actually just maps really nicely to expressing binary numbers more succinctly with a fixed number of digits. So for instance, anytime you see 1111, 1111 in the world as binary, you know what? That's a little tedious to both say and write. You can represent more succinctly any group of 4 1 bits more succinctly in hexadecimal as just F. So 1111, 1111 in binary more succinctly and more commonly now in the world of Photoshop, memory, images, and the like is represented more succinctly as FF. And that's why, because it just maps really nicely to 4 bits. And so we can be a little more succinct. So any questions on hexadecimal, which is just another way of representing information, but using the same grade school approach? Yeah. Good question. If you represent 15 with F, it would use 4 bits. So base systems are really just a way for us humans on paper or on screens to represent information. If F represents the decimal number 15, the computer underneath the hood has to use 4 bits to represent it. So 1 hexadecimal digit, by convention, always implies 4 bits underneath the hood. So therefore, if you have 2 hexadecimal digits, like 00, that means 8 0 bits underneath the hood, like for red or for green. If you see FF, now we know that's 4 1 bits and another 4 1 bits. And if we do out the math, that's 255. That's why in Photoshop, 0000FF means no red, no green, and 255 of blue. And it's just way more succinct than writing out like, what, 8 plus 8 plus 8, 24 zeros and ones. And it's just cleaner than even using decimal when you're using units of 8, which, again, computers just use everywhere. So it's just another system. It's not one you need to dwell on very much. But again, it's fundamentally no different from binary or decimal. We're just using a slightly different base. No? All right, well, we had this blank canvas here. And I think, are you two perhaps ready to reveal for the world what you've created? Do you want to go ahead and I'll swivel it around for you. All right, here we go. Big reveal. And today's pixel art. A round of applause if we could. Very nicely done. Well, thank you both. If you want to come up after and tear this off and bring it home, you're welcome to. And keep the Post-it notes too. Well, thank you to our volunteers there. Let's now translate this to really more technical world where we're going to see and consider it more often. Because in fact, sometimes when you've had error messages over the past few weeks from Clang, the compiler, you might have even seen evidence of hexadecimal. We didn't call it out. It wasn't useful to know at the time. But it turns out a lot of programs and a lot of code uses hexadecimal for those reasons of more succinct representation. So for instance, where else might we see it? Well, here's that picture we keep pulling up of our computer's memory. And each of these squares in this grid represents a byte, sort of top left to bottom right in the computer's memory. But again, just an artist's representation. A few weeks ago, I claimed that each of these bytes can be numbered, of course. Like this is byte 0 at top left, then byte 1, then byte 2, then byte 2 billion if you have 2 gigabytes of memory. And so we could just number them like this, 0 through 15 on up. 16, 17, 18, and so forth. But per the reasons earlier, it's just more common in computer systems and in software to actually use hexadecimal just to describe the locations of, the addresses of things in memory. So instead, a typical programmer or computer scientist would call these first 16 bytes 0 through F, just because, but that's because it's a predictable number of bits. So if we keep going beyond that, you would get not 10, not 11, not 12, but in hexadecimal, 10, 11, 12, and so forth, all the way down on the screen to 1F. And if I shrunk this down or had a bigger monitor, we would see eventually 255 bytes later from the start, 255 as well. But there's a potential problem here with using hexadecimal in this way. There's an ambiguity. Can anyone imagine what can go wrong if we use hex to just simply describe locations in memory like this? Yeah. Yeah, 10 might also be 10. And, maybe if you're, really thorough, OK, wait a minute, it can't be 10 because here's F over here. So it's obviously not decimal. But why create potential confusion, especially when you're collaborating, building something with someone? We want to avoid that ambiguity. And so the convention humans decided on years ago is that if you want to make clear that a number is in hexadecimal, just by convention, you prefix all of the digits with 0x. The x is not like another character. It's not like a 17th character. It's just a human convention of putting 0x to imply here comes hexadecimal. And now it's unambiguous. So now we see 0x10 obviously is not 10 as we know it in decimal, but rather it's the number that comes after a single f. So it's really the number in decimal 16. So 0x, anytime you see it, that's just a visual cue that what is ahead is actually hexadecimal. So let's now start playing around with this information. So here's a super simple line of code from week 1 where I'm just declaring a variable n, and I'm defining it to be the value 50. And this is out of context. We probably need a main function and all of that. But let's just rewind to week 1 where we actually saw code like this and do something useful with a line of code like this. So let me go over here to VS Code. And in VS Code, I'll create a program called, how about addresses, since the goal of this, the goal here is to just play around ultimately with a variable like n. And let me go ahead and do this. I'll include, how about standard io.h. I'll do int main void, so no command line arguments for now. Int n gets 50. And now so that we can do something mildly useful with it, let's just go use printf and print out with %i and then a new line, whatever that value of n is. So this is not going to be interesting per se. It's just week 1 stuff where I'm defining a variable and printing it out to the screen. So let me go down to my terminal window and do make addresses. No errors, so that's good. I'll do /addresses, and of course I should see the number 50 here. Now what's going on underneath the hood? Let's translate now code to really what's going on underneath the hood of the computer. So if this is our grid of memory, I don't necessarily know as the programmer, and I definitely don't care as the programmer where exactly it's ending up in memory. That's the whole point of using code. Let the computer figure this out. But at least conceptually, I know that by declaring a line of code like that, the number 50 ends up somewhere in the computer's memory, and it's assigned the name n, a symbol n, via which I, the programmer, can refer to it. And I very deliberately used 4 of these squares. For what reason? What might be the reason for using 4 squares specifically? Yeah. Yeah, so an integer is 4 bytes. At least most of the time on modern systems, an integer is 4 bytes. On an older computer, it might just use 1 or maybe even 2 bytes. But here, by convention, we're almost always going to see 4 bytes. I don't know if it's going to end up here. It might end up over here. But for now, who cares? I just know that the computer can store the information in this way underneath the hood. So let's now introduce another feature of C that we haven't had occasion to use just yet that's going to allow us to start poking around the computer's memory, for better or for worse. And this is one of those situations where you're about to learn, acquire a skill, a power that can actually come back to bite you. Because once you know how to start poking around a computer's memory, you can do very powerful things. And next week, we'll see what you can build in a computer's memory. But you can also screw up pretty easily and cause more of those segmentation faults that a few of you have already suffered. So with that said, let's just stipulate that, you know what, I don't care necessarily where the 50 is in memory, but I know it exists at some address in memory. And just so I have an easy address to pronounce, let's just suppose it lives at 0x123. So that's the address in memory in hexadecimal by convention, and that just happens to be where it ends up when I write that line of code. But it turns out C has some other operators we can use. When we've seen the asterisk before, the star, and we've used it for multiplication. But today we're going to use it for something more powerful. And we're also going to introduce an ampersand, which allows us to do something as well. The ampersand operator is going to allow us to get the address of a piece of data in memory. Like by literally putting ampersand before the name of a variable, C will tell you what address that variable lives at. Maybe it's 0x123, maybe it's 0x456, who knows, but that will give you back the answer. The star does the opposite. It sort of means go there. So using the star, otherwise known as the dereference operator, I can actually go to a specific address if I want. And we'll see what this means in code. So how can I leverage this in some mildly interesting way to start poking around, but eventually we'll use this primitive to build more interesting things. So let me go back to, say, VS Code here, and let me go ahead and do this. I'll clear my terminal to start fresh, and I'll introduce another format code for printf, %p. And for now, just take on faith that it is %p because, but %p is going to allow me to print the address of a variable if I additionally tell C, get the address of n. So I'm changing %i to %p, and that's just something you have to do when printing addresses for now. But I need to change an ampersand in front of the variable name, so I don't print n, the number 50. I print out something like 0x123. And it's not going to be as simple as that. We'll see on the screen, though, where it actually ended up in my code space's memory. So here we go. Down in my terminal, make addresses again to recompile. And now /addresses should reveal not the value of 50, but the address of 50. And there it is. It's pretty long. It's not quite as simple and pretty as 0x123, but there's the 0x, meaning here's a hexadecimal address, and it's 7f, fc, c784a04c. Suffice it to say, your code space, and even your Macs and PCs nowadays have a lot of memory. That's why, in part, this address is so big, not as small as the thing on my slide. So this, at the moment, isn't that useful yet, but it introduces us to a concept that we'll now call pointers. And pointers are admittedly one of the more challenging aspects of C. And if in future life you tell friends that, oh, I took a class called CS50 and we learned C, like you'll probably get kind of a look at people like, why did you learn C? Or like, oh, C was hard. And it's largely because of this topic, which isn't to say that it's that hard to wrap your mind around, but it's definitely very different. And it's not a feature that you can harness in higher level languages that we'll see in class 2, like Python and Java and the like. C is about as close to the computer's hardware, so to speak, that you can get before things get actually scary. The so-called assembly language we saw in week 2 when I had to link and compile and assemble and all of that, like that gets really low level. And you really have to be an expert with the computer's CPU or brain to understand that. But with C, you can actually poke around the computer's memory and do powerful things with that. But again, with great power comes responsibility. It's very easy to break programs by misusing memory or just having a bug that touches memory in some way that you don't intend. So pointers, at the end of the day, are pretty much what we just saw. A pointer is really just a variable that contains the address of some value. A pointer is a variable that contains the address of some value, or more simply, it's fine to think of it as an address. A pointer is an address of something in the computer's memory. Now, what might we do to actualize this? Well, here's 2 lines of code. It turns out, by using our 2 new operators today, I can declare an int, call it n, and assign it a value like 50, just like before. If I want to store the address of n in a variable and not just print it immediately via printf, I can declare a variable, for instance, called p, but I could call it anything I want, like any variable. But because it's an address, it's not int p. It has to be int star p, so to speak. And the star here on the left-hand side of the equal sign is just a clue to C that means p is going to be a pointer. That is, p is going to be the address of what? The address of an integer. Now, technically, it's still an integer itself, right? Because an address is just a number, whether it's 123 or 0x123. So this is really just a semantic difference. So int star p just means that this variable doesn't contain any old number, like 50. It specifically contains a number that is the address of something else. So how can I now use this? Well, let me go back to VS Code, and let me propose that we add a line of code like that. So instead of just directly printing out that value, let's go ahead and define a second variable called p that's of type int star p, set it equal to ampersand n, and then this time, let's not just print out ampersand n, let's actually print out the value of p. So the only two new things here, if I zoom in, are I've used not only the ampersand on the right to get the address of n, I'm now using the star on the left to tell C that p is still a variable as always, but it's a pointer. It is the address of some other value like this. And I'm still going to print it with the same format code, %p, so that doesn't change. So let me go ahead and zoom out and do make addresses and /addresses. And there it is, exactly the same thing. Now, in and of itself, not that useful yet, but the fact that you can now access the addresses of things in memory means that we'll be able to build things and construct things and link things together by knowing where they live, so to speak. So any questions on this technique thus far? Yeah? A good question. On line 6, must it be star, p, and ampersand? And in this case, yes, because what am I doing? On the left, and I'll get rid of the equal sign for now, this would give me a variable called p that's not an integer per se, but that's the address of an integer. But without the equal sign, I'm not storing anything in that variable. So by adding the equal sign and then ampersand n, I am explicitly figuring out with ampersand what the address of n is, which already exists per line 5, and tucking it away in this new variable called p. Other questions? Yeah. Good question. Every time I run the program, it uses up a different piece of memory. Short answer, yes. Computers, though, long story short, also have something called virtual memory. So if you run it again and again, you might actually see the same addresses on the same Mac or PC or cloud-based server. But we'll see in a bit where, at a high level, it's laid out. But it will always exist at some address. Good question. Yeah. Correct. Ampersand n is the address of n, and int star p is a pointer called p. And honestly, in an ideal world, if C were made today and not decades ago when humans were first creating languages, ideally, we would just have a data type called pointer. And then this would be a little less complicated because it would literally be what it says. The humans who invented C didn't do this, but this is the idea. So pointer is not a legitimate word in the code. It is a term of art in English, but this is really just the idea. But the way you express pointer as a data type is a little more cryptic as int star p here. But notice, in line 7, when I print out p, I don't use a star, I don't use an ampersand. Why? I literally just want to print the value of p. And we've been doing that since week 1. If you want to print a variable, just describe the variable by its name. No special syntax. Any other questions on this thus far? What's the advantage of using pointers? With pointers, we'll see today some applications of them. Really, the idea is going to come to fruition next week when we're going to create what are called data structures in memory, where we can build not just, for instance, one-dimensional data structures like an array. We'll see next week we can actually create the equivalent of two-dimensional data structures or even three-dimensional data structures by using these addresses and sort of linking things together. And we'll see the beginnings of that this week. But for now, focus, at least for now, on just really the syntax and what these building blocks can do for us. Does the p pointer have to be point to an integer? Short answer, no. And we'll come back to this. For now, for the sake of discussion, we're only dealing with integers, like the number 50. You mentioned strings or characters. Absolutely. We're about to go there soon. So you can use the address of anything you want in the computer's memory. So in fact, let's translate this now to just the same picture, just to help you wrap your minds around what these two lines of code really fundamentally are doing. So if I come back to my grid of memory here, let's plop the number 50 in the variable n at the bottom right, like it was before. So this is that first line of code as before. But with the new second line of code, as soon as I create p, what do? Well, first, remember that n lives somewhere in the computer's memory. Usually I don't care precisely where it is, but for the sake of discussion, let's suppose it's at 0x123, which is easier to say than where it actually ended up. And now what is p? Well, p is just another variable, and variables live in memory too. So let me just hypothesize that p lives up here. And it turns out that p, once you assign it, the value of ampersand n means that C will take a look at the variable n, realize, oh, it lives at 0x123, and what goes in the value of p is literally 0x123. So again, it's still an integer, which is confusing, but it's technically an integer being used as an address. And now just a prompt here. Notice that this pointer is pretty darn big. It's like 8 squares. What's the implication of that? Because I did that deliberately. How big must a pointer apparently be in most modern systems, would you say? OK, good. Computers today are very big. You have gigabytes of RAM in your computer. You therefore need big pointers to be able to point at memory that's conceptually pretty far away. So to be clear, how many bytes does a pointer apparently take up? Well, it seems to take up 8 in total. Integers by convention nowadays are usually 4. Pointers, though, nowadays are typically 8 in this case. So I'm drawing it in a manner consistent with the reality, even though at the end of the day, it's not really that interesting what values are in here. In fact, let's emerge from these weeds. I don't really care what else is going on in my computer's memory at the moment, because I've only got those 2 lines of juicy code defining n and defining p. So let's hide all of the other squares. And honestly, I mean it when I say that programmers need to know that a variable exists somewhere in memory and needs to be able to get that address using like the ampersand. But you're never going to printf like I did the actual address. Like it's not generally interesting unless you're debugging your code. But you're not going to like start typing out crazy OX numbers in your code to move things around. You just need to know that the computer can figure out where things are. So frankly, by that logic, who cares that it's OX123, right? Tomorrow it could be OX456 or something else. So one of the ways to think of a pointer is literally as a variable that points at something else. And indeed, in this case, p, yeah, technically it has an address, and yeah, technically it's OX123 in the story. But honestly, who cares? I just need to know that using p, I can get to the value n. And so what are these addresses? And in fact, if Carter wouldn't mind joining me up here for a moment, what are these addresses? Well, just like in our human world, we have mailboxes, even though you might not check it very frequently nowadays. But to get physical mail, every home, every business has a unique address. The Science and Engineering Complex is 150 Western Avenue, Austin, Massachusetts, 02134 USA. And theoretically, that uniquely identifies that building in the world. Well, here we have 2 mailboxes. Over here, we have a value n that happens to live, I'll claim, at address OX123. And then over here, I claim there's another address called by name p. I don't actually care where it is, even though it definitely exists somewhere in the computer's memory. But if this is p, which is a variable, and that's n, another variable, ideally, this mailbox would be twice as big because of the number of bytes using, but Home Depot only had identical size mailboxes. But here is p, one variable. There is n, another variable. If I open up this mailbox, what should I find inside of it based on our story thus far? Like what value will I pull out dramatically in just a moment? Yeah, I think OX123. Now, using this, you can kind of think of this as like X marks the spot, no pun intended, where I can now like walk around the computer's memory and find my way to that location by sort of following the treasure map. Or if I want to more dramatically, thanks to our little Yale foam finger here, you can think of it more abstractly as p is just pointing at n. OK, that's not going over well. So let's switch over to the Harvard one. So p is pointing. So p is pointing at n, and so it turns out we will be able to write code now that will do the equivalent of me walking over to n. But for now, Carter, if you want to reveal what's in the mailbox, we should see, indeed, the number 50. So that's really all that's, oh, I feel Carter's waiting for applause. So like really, well, nicely done. Thank you. So that's just like a physical metaphor of what's going on here. In one variable, we have an address, and that variable by convention is called a pointer. In the other variable, per week 1, we just have a value like n. And you can, yes, follow the map and walk yourself to that particular address. And we'll see how to do that in code. But what's really interesting is this abstraction, that pointers literally, or really, I guess, figuratively, point at some other value in memory. All right, questions then on pointers in this form. Can pointers point to each other? So yes, there's things called double pointers. We're not going to see them anytime soon, but using star star, you can express an address of an address. But we won't see that just yet. Other questions on pointers? Yeah, in front. Are arrays, so to summarize, are arrays then pointers? So short answer, there's a relationship, and we'll come back to that in a little bit. But arrays are technically different from pointers, but we're going to be able to blur the lines a little bit by using one like the other. But let me come back to that in just a bit of time. All right, so if we have now this mental model, if you will, of like what a pointer is in memory, I think we can start to peel back a layer of simplification that we've been assuming for the past few weeks since week 1. So a string, recall, is a sequence of characters. And so if you want to create a string that says hi in all caps and an exclamation point, we do string s equals quote unquote hi. And we can hard code it like this, or we could use getString. But for now, just assume that I hard coded it into my code to always say hi in all caps with an exclamation point. Well, what does that look like in the computer's memory? Well, let's stop looking at the entire memory. Let's just focus on really what's going on. Once you create a string called s and store in it hi, you know that a couple of things are happening. H and I and the exclamation point are ending up in the computer's memory. We know from week 2 that this thing, the so-called null character, NUL, aka \0, is also being added for you. And it's somewhere in memory. At the moment, I don't really care where. I drew it at the bottom right. Yes, it has an address. But for now, it just ends up somewhere. And in fact, here's a little visual cue as to how this happens. In C, anytime you use double quotes to give you a string, you can imagine that the double quotes are like a clue to not only store hi exclamation point, but also put the null character there for you. And this is in contrast to what? Chars, if you want individual characters, what syntax did we use instead? So single quotes. Single quotes do not add magically a \0. They literally just store one character. So again, strings have always been a little special. You get an extra byte for free so that you know where the string ends, and functions like strCompare can then find their way there. So in memory, it might indeed look a little like this. And if we assume that there's going to be somewhere in memory, these things are going to be somewhere in memory, we can address them per week 2 by way of the name of the variable. So if s is the name of the variable, s bracket 0 is how you would refer to the first letter, s bracket 1, s bracket 2. And if you really want, s bracket 3 would get you at the null character at the very end. But what is s? So technically, in this line of code here, not only is the computer giving you memory for hi exclamation point \0, it turns out that s itself must take up some amount of space, right? Because s is the variable. And every time we've talked about variables thus far, I've given you a rectangle on the screen in which to store its value. So let's assume, for the sake of discussion, that the h is at 0x123, and I is at 0x124, exclamation points at 0x125, and the null character is at 0x126. Well, what then is s? Well, s is just going to be some other variable, and I'll draw it somewhat abstractly without all of the other boxes up here. And I'll claim that the name of this variable is s. But it turns out, what is s really? How do strings really work? Well, s is a variable and has been since week 1. But when you define it, what the computer is doing for you automatically is when it knows you want to store hi exclamation point, it puts that somewhere in memory. The computer then figures out for you what's the address of the very first character. And it stores that address, and only that address, in the variable you created on the left-hand side of the equal sign. And that's enough. Like, to represent a string with 3 letters of the alphabet or punctuation, you don't need 3 variables. You just need 1. You just need to know the beginning of the string. Why? Why is it sufficient for a variable to only store the first byte's address and not all of the byte's addresses? Exactly. Because of the design of strings, per week 2, we always null terminate them. So it suffices to only remember the first byte's address, because from there you can sort of follow the breadcrumbs, byte after byte after byte. And until you see the new line, the null character, you know that all of those characters are apparently part of the same string. So this is what's been going on in the computer's memory all since week 1. And in fact, if we abstract this away, you can really think of s as being just this. Really a pointer to that chunk of memory. So in fact, what do we have here? Well, in the left, to recap on the code here, on the left-hand side, string, that's what ensures that we'll actually be able to store a string in a variable called s. We're going to have on the right-hand side, though, the actual value. So let me switch back to VS Code here, and let me change my code to no longer involve integers alone. So I'm going to add the CS50 library, just so that I can use some shortcuts in there, cs50.h. And then in my main function, I'm going to go ahead and do this. String s equals, quote unquote, hi in all caps, exclamation point. And then I'm going to go ahead and print out, using %s as always, \n, the value of s. So this program at the moment, not interesting at all. It's just week 1 stuff again. /addresses indeed prints out hi. But it turns out that now that I know this, What's really been going on underneath the hood all this time? Well, here's that same line of code that defines the variable called s. And it turns out, anyone want to guess what string is actually a synonym for? String, it turns out, is kind of a white lie we've been telling since week 1. There is no such thing as string as a keyword in C. It's technically a CS50 thing, yeah? It's a pointer to a character. So really, all this time, we've kind of been lying to you. There is no string, quote unquote. It's actually char star. And if I may dramatically, here go the training wheels. Like, OK, that didn't land very well. So what have we been doing? Well, it turns out that string is a much easier way conceptually to think about what a string of characters is. Like, my God, if we had to start in week 1 by having you type char star, like, yeah, you might get past it. But like, this is just way too much ugly syntax, not intellectually interesting at all. So we abstracted away what a char star was in the first week of C by telling you it's actually called string. Now, string is a term of art. Like C programmers are in any language will use the word string to mean a sequence of characters. But in C, it's not technically a word unto itself. It's rather a synonym that we ourselves created in some form. So in fact, how did we do this? Well, think back to just last week. Last week, I proposed that it'd be really nice if we had a person data type, which the creators of C did not think of decades ago. But that's OK. We can define it ourselves. What did we do here? Well, we're using syntax like this. Recall that we defined a person to be what? To be this structure. This structure, using the new keyword last week, struct, means that a person is just a name and a number. And it could have been other things. We just kept it simple. But how did I associate person with that structure? Well, we claimed that it was this value here, typedef, which, as you might expect, defines a data type. So what did we do as CS50 back in week 1 without telling you? Well, we could have done something like this. Like int itself is a little cryptic, and maybe we should have, to keep things even simpler, said, hey, everyone, turns out you can define integers in C. And if you wanted to do this, well, if you want to create the keyword integer as a data type, you can just typedef it to int. So typedef creates the word on the far right, integer, and creates a synonym for it, in this case called int. So what did we do in week 1 without telling you? We have a line of code like this in the CS50 library that associates quote unquote string with, more cryptically, char star. And this is why in week 1 onward, anytime you use the CS50 library, you can write the word string as though it's a real C data type. And that's just because we wanted to have this abstraction, these training wheels on for the first weeks, so we don't have to get in the weeds of all this crazy memory stuff. We can sort of talk about strings at a higher level. But that's all they are. Strings are the address of the first character in that sequence of characters. Questions now on any of these details? Yeah? Good question. What about the strings library, which we have used? Unrelated. So it does not define the word string. Everything in there actually relates to char stars. And so in fact, if you've used the CS50 manual, which is just our user-friendly version of the actual manual pages for the official language C, you'll see throughout that now, if you start poking around or turning off less comfortable mode, you'll actually see that we've changed any mentions of char star in the official documentation for these first weeks to just string, to simplify it. But underneath the hood, C does not know the word string per se as a keyword, but it's absolutely a concept that like every program in the world knows about. And in fact, in other languages, in Python, for instance, there will actually be a proper string, although it's not going to be called string. It's going to be called str, S-T-R for short. Questions on these strings here? Well, let me propose there's one other feature of this syntax that we can now leverage as follows. Let me propose that if we go back to the previous version of my code here, wherein, let me switch back to VS Code in just a moment. I'm going to rewind in VS Code to the integer version of my code from before. And most recently, it looked like this. Before, when we were using integers only and not, in fact, strings at all. Let me propose that there's this other feature of C that we can use that actually allows us to go to an address. So at the moment, let me just rewind and do make addresses to remind you what this program did when it was using integers alone. And there's that address. Why? Because on line 7, notice, I'm printing out the value of p, which is a pointer. So of course, it's going to look like an address. But let me zoom out now and make one change. Instead of printing out p, how can I use today's second new operator, not the ampersand, but the star, to actually go to that address? Well, what I can actually do on this line of code is this. If I want to print out the actual integer 50 that's in that variable, or equivalently at that address, I can go to p here and not print p literally, because that's just an address. I can now say star p. And star p means go there. More technically, dereference p. That is, follow the treasure map to the actual address and do what Carter did, open the mailbox and print whatever was in the mailbox, which recall was the actual number 50. So let me try this. Let me recompile the code. So make addresses. OK, let me clear my terminal window. /addresses. This time, I shouldn't see the OX anything. I should see just the number 50 in this case. And here, too, is kind of a unfortunate design decision. Certainly pedagogically, I would say in C. If I zoom in on this code, star is unfortunately being used in 2 different ways. In an ideal world, they would have used 3 different symbols to make this more semantically clear. But this is what we're stuck with. So in line 6, when you declare a pointer, that is a variable that stores an address, you put the type of variable that you want to point at, then a star, just because, and then the name of the variable. And then on the right-hand side, you actually get the address of whatever using ampersand. But when you want to go to an address, you want to dereference a pointer, you don't use int again. And we've never done that, right? Once you declare a variable, you never again mention the data type. But in the world of pointers now, if you want to not print out p, but go to whatever address p is storing, you use star p here. So a good visual indicator would be when you declare a pointer, that is, make it exist in your program, you have to declare the data type with the star. But when you use a pointer, you just use the star. In an ideal world, this would be a completely different symbol. But again, this is what we have. Questions now on that syntax? Yeah? Why can't we just do the ampersand here, are you saying? It was still a little quiet. So strictly speaking, we do not need line 6. So this is really for pedagogical sake that I am defining a separate variable p and then printing it out. At this point, though, I'm just kind of going in circles, if you will, because more simple would have been what I would have done in week 1, which would be get rid of p altogether, get rid of p here, and just print out n, right? But today, we're just giving you this new building block, this new syntax via which you can figure out the address of something and then reverse the process later and actually go to it as well. Other questions on what we've done here with these pointers? All right, well, let's context switch back to the string now and see what more we can do with this here. In the case of our strings here, let me refine this to zoom out. Let me delete the integer related code here. Let me do string s equals quote unquote hi in all caps. Let me go ahead and for the moment include cs50.h at the top so that indeed I can use the keyword s, or string rather. And let me go ahead now and do something more than I did last time. Last time I did printf of %s\n, and then I printed out s. And again, I'll recompile this just for clarity. Make addresses, /addresses, that just prints out hi. So that's, again, week 1 stuff. But now that we have this other bit of syntax, we can do some interesting things too. So for instance, suppose I want to print out not s itself, but what if I want to print out the address of s? Like at what memory location is s? Well, I can change my %s to %p, which now we know p is for pointer. So %p means print out the value of a pointer. That is an address. And here, I can actually print out s itself. But why that is, we'll see in a moment. Let me do this. Here go the training wheels. String does not technically exist, but it does if I'm using the CS50 library. But if I get rid of the CS50 library, as I'm metaphorically doing by taking off the training wheels, I can't use the word string anymore. And in fact, let me make this mistake deliberately, as you might have accidentally in past weeks. Here's the error message I get if I forget the CS50 library. Use of undeclared identifier string. Did you mean standard in? It's trying to be helpful, but it's not, because I didn't mean standard in. So indeed, this is confirmation that C does not know the word string exists, at least as a keyword. Exists as a concept, but not a keyword. So I could fix this by adding back the CS50 library, but that's kind of a step backwards educationally as instead of a step forward. What could I do instead to fix this now if the training wheels are now off? Yeah. Exactly. Replace string, quote unquote, with char star instead. So I'm going to go ahead and change this to char. Technically, you can put the literal star here, the asterisk, or you can put it there, or you can put it here. By convention is to do what I'd done from the beginning, put the star next to the name of the variable as opposed to anywhere else. Let me go ahead now and Or, sorry, I meant to add the spaces there. You could do this too, but this would be the most normal convention. So now let's do this. Make addresses. Compile's OK now. / addresses, what should I see? Hi or something else? Feel free to just call it out. So still hi, you say? Someone else? A memory location. All right, so it could be one of the two options, right? Either I'm going to see the string or I'm going to see a memory address, though I do in fact see a memory address, and this one's quite different from the integer one. But does anyone now want to explain why you were correct? Why am I seeing the address down here and not hi? It's subtle, yeah. Exactly, because I left my %p there, which means, hey, printf, show me a pointer. But this is where printf is smart and has been smart since week 0. Humans who invented printf decades ago wrote code that notices that, OK, %s means to treat the following value, not as just an address per se that gets printed literally, but print it, as with the mailbox demo, as sort of a treasure map that leads you to the address of a character. So simply by changing one character, %p to %s, and if I now do make addresses again and / addresses, this now is identical to week 1, but hopefully makes sense because %s is just a clue to printf that means go to this address in s, we'll print out every character there and thereafter until you see what? The null character, and then stop printing anything more. And this is why hi has printed since week 1. Today we can see the address %p, but this combination of having access to addresses and the null terminator is all the information printf needs to actually do something more useful by printing the actual strings. Any questions now on this approach to %s? Yeah, in back. Oh, so why is it traditionally being used in this way? Honestly, the word string has been around for decades. It's not a keyword you should be able to type in C unless you're using a library like CS50s. And so %s just means string. So even though it doesn't exist as a keyword, %s connotes string. And humans decades ago, like today, just kind of know what that means. So they could have chosen any letter of the alphabet, but S sort of makes the most sense. All right, well, let's, in back. Other question? Good question. Before, let me zoom in. I did not use a star before the S. Why? Well, it's subtle here, but printf was invented years ago to know, given an address, like in the variable s, printf knows to go there. So if we looked at the source code that some human wrote years ago for C, we would likely see the actual asterisk that you're referring to. Printf is taking on the responsibility for going to S. If you were to do star S here instead, an asterisk and an S, that would now be literally a character. Because if I say star s, that means go to the address in s, and all you're going to find there is a single character. What printf wants to know is not what is the character there, what is the address of that character. Why? Because printf needs to walk through the rest of those characters looking for the final null character. And in fact, let me see with a bit more syntax if we can highlight this a bit more. Let me do this. In addition to printing s, let's try out our syntax in another way. Let me print out with %s. How about not s here, but let's print out some addresses. %s, \n, close quote, and then let's print out, how about this? The first character in the string s would be called s bracket 0. But how do I get the address of the first character in s? Well, I could technically just use today's new primitive. I can just add an ampersand. That always gives me the address of some value. So when I end this thought and clear my terminal window and run make addresses, still compiles. When I run addresses in just a moment, any guesses as to what I will see line by line? This will print out two things. And you don't have to remember what the actual number was. But at a high level, what will be printed now? The same thing twice. Why? Well, when I run this, what I'm printing here, and let me zoom in at the bottom, I indeed see two really long addresses, but they're in fact the same. Why? Well, that's because, again, if s is the address of a character, as implied now by either the CS50 word string or the actual phrase char star, well, then s is just an address. By contrast, per week 2, s bracket 0 is a char. always has been a char, a specific char. But if you want the address of that char, you just add the ampersand. Well, it turns out that strings, per the definition we keep emphasizing, is just the address of the first character in a string. So of course, if you do this, you're going to see the exact same thing. And if I do this a bit more, generally you don't want to copy paste, but this is just for visualization's sake. Let me print out all of the characters. So another, and let me change this to print out the address of bracket 1, bracket 2, and bracket 3. So all 4 characters, HI, exclamation point, and the null character. Notice I'm using %p for all of them. So if I now do make addresses and /addresses, now notice, and this is kind of cool, the first 2 are indeed still the same. But what's noteworthy about the other values on the screen? Yeah, they're consecutive. Each of these is just 1 byte away. Even if you're not good at hex yet and there's a crazy number of digits here, who cares? They're all the same except for the last ones. 4, 4, and then 5, 6, 7. And this confirms what I've been claiming for weeks, is that in an array, all of the characters are back to back to back, contiguous, 1 byte away. So with just this ampersand, with just this star, like, it's actually a pretty cool tool in the toolkit to have, because you can start to poke around what's actually going on inside of the computer's memory. And in fact, if we do this, I can introduce one other cool trick here, if you will. Let me propose that we can actually now do arithmetic on pointers. And you don't have to. You'll see a simpler way to do this. But now that you have perhaps this underlying understanding of where things are in memory, and it's just addresses, we can actually do something kind of neat. We can do something like this. Let me go back to how about the string version of this with hi. And let me do this instead. Let me clean this up a bit, get rid of some of these lines of code, and let me do this. Let me print out %c, %c, %c. Let me get rid of all these ampersands. We're going to roll back to like week 2 stuff. Just to be clear, when I compile and run this version of the program, and I'll zoom in, what should get printed on the screen? This is just week 2 stuff now. No pointers per se. Yeah? Just HI exclamation point, 1 per line, because I have all of these \n. So let me do that. Let me go down here, make addresses, enter. OK, pretty good, /addresses, and indeed HI exclamation point. But now, if you're getting a little more comfortable, and it's fine if you're not yet today, but over the coming week or weeks, as you get a little more comfortable with the equivalence of addresses with our definition in the past of arrays and strings and all of this, you can start to play around. And I can do this instead. If I want to print out the first character in the string, I could do, like week 2, s_0. Like, that will always work, and you can keep using that. That's not a CS50 thing. It's just a convenience in C. But I could technically print out not s, because s is an address, but what would be the syntax I could use to say print out the character at s? Any instinct? How can I say go to the address in s? It's one of 2 possible answers today. So of our two new operators today, we have the ampersand and the star. Which one will lead us to what is at an address? So the star. So in fact, if I want to print out what is at address 0 at the address s, I can just do *s. And if you really want to get fancy, how do you print out the second character that's immediately to the right of it, so to speak? Well, you can go to with the dereference operator. And do you want to answer this one? s+1. Ergo pointer arithmetic. Like, you can do math, simple addition, subtraction, whatever, on pointers if you want. And you can do this here too. So star, if you want to pluck this one off too, how do I print out the last character, the third? s+2. Right? Because if you know and understand that, like, a string is just a sequence of characters, every character is just a byte, and these bytes are back to back to back, you can just go wherever you want in the computer's memory. And here, I can do make addresses again, /addresses, and voila, we now have hi exclamation point. So we haven't printed out anything new, but again, just by using these 2 new operators, the ampersand and the star, you can figure out the address of something, and you can go to the address of something. OK, question in back. Indeed, it ends up being the exact same. And so I might have used this term before, the ampersand technique, the square bracket technique, where you do s_0, s_1, s_2. That's actually what we would really call syntactic sugar. Like, it works, and you can use it. You should use it. It's nice and simple. But the square bracket notation underneath the hood is essentially being converted to this, which this is not fun, right? Like, this is when you want to show off to your friends, like, you know how to do cool stuff in code. But this is not as readable as just s_0 and 1 and 2. But but that's all that's happening underneath the hood. And so again, this is why in CS50 we spend time on some of these lower level building blocks, because if you assume that indeed your computer's memory is just this grid of bytes, and you have now the code ability in code to get an address and go to an address, you can start doing anything you want. And you can poke around a computer's memory at any location. And herein lies the danger. Like, I'm kind of on the honor system right now that if my string is high, exclamation point, it's kind of up to me to go to the first byte, the second, and the third. But I could get kind of crazy now. And if I want to see what's going on in the computer's memory, I mean, there's nothing stopping me from doing like s plus 50. And let's see what's there. So make addresses, /addresses, high, and then, OK, nothing, it seems. Well, how about 5,000 bytes away? Let's just poke around what's inside of the computer's memory. So make addresses again. Make addresses, /addresses, enter. OK, still nothing there. Let's try 50,000. All right, make addresses. /addresses. OK, there we see it. So you've probably done this, some of you, by accident, because you probably went too far to the left or to the right in an array, touching memory that you shouldn't. Suffice it to say, I should not go blindly touching 50,000 bytes away, because who knows what's there. And indeed, in your computer, when a program is running, the computer segments it into different segments of memory. And if you get a little too greedy and you touch another segment of memory that technically was not allocated to you by Mac OS or Windows or Linux or the operating system, bad things happen and you get a segmentation fault. And that means it's a bug in your code. So you can now do this. And this means hackers, too, can do things like this. If they can somehow inject code into your C program, maybe they can poke around the computer's memory. And indeed, this is kind of the technique whereby maybe a really sophisticated hacker can jump to this memory, this memory, this memory, looking for something like your password or your financial information or anything that's in the program but at some other address. There's nothing stopping an adversary, at least right now, from poking around, if they can execute code on your computer, from doing this kind of thing. So therein again is the power of C, but also the danger. And you'll absolutely suffer more seg faults in the coming days. But ultimately, the goal is going to be to help you solve them ultimately and fix things. But for now, I think that was quite a bit. So let me propose that we go ahead and take our longer break here, maybe 10 minutes, and have ourselves some whoopie pies in the transept. We'll be back in 10. All right, so we're back. And to recap where we left off, you now have this new capability in code to do pointer arithmetic, like treat addresses as numbers, which they really are in hexadecimal or otherwise, and like add them together and kind of poke around a computer's memory. And it was asked during break, actually, how we might further harness this in the context of strings. So I didn't change the code we wrote just before break. Recall that we last broke the program by checking out bytes 50,000 bytes away. But let's not do that, and let's actually try printing out not individual characters like I did per the %C, but why don't we try printing out strings and substrings, if you will. So let me clear my terminal window. Let me change all of these %Cs to %S, 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 and then let me rewind to what we've been doing since week 1 with strings, which is just print them out. For instance, with that first line. And the only difference at the moment is that now I took off the training wheels. I got rid of cs50.h, wherein string is typedef to char star for you. Got rid of that. So now on line 5, I'm declaring s as being a char star, which just means the address of a character. And printf is smart enough to know that the end of a string is wherever that null character is. But now that I can do pointer arithmetic, notice that I could do something like this. If I want to print out s, I just print out s. Suppose I do s plus 1 here and s plus 2 here, again after changing %C to %S. Any intuition around what this code will now print on the screen, line by line? Yeah, thoughts? OK, reasonable conjecture. Maybe the memory address of h, that of I, that of exclamation point. But other thoughts? Yeah, I think it's actually going to do the latter. It's going to print high in the usual way, because honestly, line 5 is this, line 6 is the same as like week 1 stuff, except we took off the training wheel of string and we're calling it char star. But I think line 7 is indeed going to print out I, and line 8 is just going to print out, because it'll be just the exclamation point. Printf will still be smart enough to know where each of those substrings, portions of the string, end by the same logic as always. But let me go ahead and zoom out, run make addresses, enter, compiles OK, /addresses, and now, indeed, This is all a string is. It's a sequence of characters identified by its first byte. If you then start poking around and tell printf to print at what's at the next byte or the next byte, it's going to do its same thing, printing out that character and everything after it up until that null character. So again, even though there's like a lot going on, we've introduced these two new operators, like there's nothing that's happening today that hasn't been happening for weeks, but hopefully through this week, this week's lecture, this week's problem set and beyond, you'll start to realize that now you just have more tools via which to harness those lower level implementation details. So last week too, recall one other implementation detail. I claimed that you could not compare two strings quite as easily as you could compare to integers, for instance. And I told you to use a different function instead that you probably used one or more times with the past problem set. How are you supposed to compare strings, apparently? Yeah, so string compare, strcomp, that additional function that we said, you just have to use it for now. But you might have a little intuition already as to like why we have to use str compare and we can't just use equals equals to compare strings. Like any intuition for this already? Why was str compare necessary last week? Perfect. Equals equals would compare literally the two memory addresses instead of the actual strings character by character. And unless the memory addresses are literally the same, so you compare that exact same memory address, two different strings probably are not going to be considered equal, even if to us humans they indeed look equal. So let's see this. Let me go ahead and close addresses.c. And actually, before I do, one last mention. One of the powerful things about pointer arithmetic, as an aside, is that C, and really the compiler, is smart enough to know how many bytes to keep adding and adding. And by that I mean this. Right now we got lucky because a string is a sequence of characters. And by definition, every character is a single byte. You can poke around and do s plus 1 to get the next byte, s plus 2 to get the third byte. However, if we weren't dealing with strings, suppose we were dealing with integers that were in an array back to back to back. If you wanted to get at the next integer, you could still do plus 1 or plus 2 to get at the next or the next integer. You would not start to get into the weeds of doing plus 4 and then plus 8. You don't have to know or care how big the data types are in the computer. C and the compiler will figure that out for you based on the data type in question. So keep that in mind if ever doing this on a different data type than chars. All right, so let me go ahead and open up a file that I wrote in advance most of. And let me hide my terminal window and show you this. So here's a program called compare.c, whose purpose in life is to compare two strings. I'm back to using the CS50 library because at least for now and probably a couple more weeks, it is so much easier to get input from the user using CS50's function, getInt. But we'll conclude today by taking off those training wheels as well so you can see how you can actually get user input with nothing CS50 specific. So lines 6 and 7. Pretty boring, week 1 stuff. Get an int called I, get an int called j, and store them in two variables, I and j respectively. If I equals j, print out the same, else print out that they're different. Let me just stipulate for time's sake, I'm pretty sure this code is correct. This will get two integers from the human. It will compare them and tell me correctly if they're the same or different. And I'll prove as much by running make compare /compare, and I'll type in 50 for I, 50 for j, and they're the same. And now I'll do how about 50 and say 13, and those are different. So let me just stipulate this code is indeed correct. Would have worked in week 1, also works now in week 4. But let me now change it to compare not two integers, but as I hinted, maybe two strings instead. So let me go ahead and change this line of code to maybe be string s equals get string, asking the user for s. Then let's change this second line here to be string t, just to keep the variable name short for now. And t is a good choice after s for something like this. Get string, prompt the human for t. And then let's change our I and j here to do the wrong thing. Per the intuition earlier, if s equals t, then print out the same, else print out that they're different. Now, if I want, I could take off at least some of the training wheels. I could change this to char star. I could change this to char star. Either's fine. I still need the CS50 library, though, because I'm using get string, because it's actually hard, as we'll see today, to get strings manually without using a library. But I'll keep it using string just for now with the library. All right, make compare again. /compare, and now let me go ahead and type in, for instance, hi, exclamation point, enter, and hi, exclamation point, enter, and they're different. All right, they're obviously not visually, but they are underneath the hood. And you probably do have the intuition for this already, whereby what's going on underneath the hood is that we're comparing accidentally the two memory addresses. So in fact, let's go there. Let's consider the memory. And let me zoom out now so I can just have more bytes to play with. So the squares are a little smaller than before, just so we can fit more in them. And let me propose that when I declare S on what was line 6 a moment ago, it ends up somewhere in memory, like the top left-hand corner of my picture, for discussion's sake. And when I execute that same line of code and getString is called, and I type in high exclamation point, we know from week 1 that getString puts it somewhere in the computer's memory, and I'll propose that it's in like the bottom left-hand corner of the screen here. What happens after that? Well, I know, even though I don't generally care, that HI exclamation point in the null character exists at some address, like 0x123, 124, 125, 126, for discussion's sake. And what's in S? Same as before break, 0x123. So that's all that's happening again on line 6, which is pretty much the same as when we were getting an S earlier. But notice now with line 7, when I get a second variable called t and I call getString again, and by coincidence, as the human, I type the same thing. Well, what happens here? T gets its own chunk of memory, maybe at the top right. That second version of high gets somewhere else in memory. You know, the computer could be smart and notice that it's the same, but C doesn't generally do that for you. It just plops it somewhere else in memory. And maybe it's at address 0x456, 457, 458, 459, or wherever. But you can perhaps see where this is going already. T now, of course, contains the address of that first byte. And so in my code on line 9, when I compare S and T for equality, suffice it to say they are not equal. Because of the way the strings are laid out in the computer's memory, it indeed looks the same values are there. But if we abstract away further, you can really see that S and T are not the same themselves. And so how did we fix this? Or really, how did we avoid this last week without spilling the beans and going down this rabbit hole of explaining like why you have to use stir compare? Well, if I go back to my code here, let's do it now the right way. Let me go ahead and include a line of code that says string compare of S, comma T, both as inputs. And then, if you recall, what does stir compare return when two strings are equal? There's 3 possible return values. So 0. So 1 is for if it comes alphabetically or ASCII-betically first or second. But for now, I just want 0. If I want to use stir compare, I do need string.h. So string.h does exist. That's not a CS50 thing. There's no keyword string as a data type. That's a CS50 thing. But string.h does exist. So I think now, with that change on line 10, if I do make compare and /compare, and then run again, type again, high exclamation point, high exclamation point, I think now they're the same. And just as a second check, high in all caps, maybe high in lowercase, those are in fact different. Why? Well, stir compare, which was written by some other human decades ago, is just smart enough to know that it should go to S and go to T, start comparing them left to right, stopping once it hits one or both null characters, and return 0 only if everything in S and in T are exactly the same. Are any questions then on this here? Any questions on why we're using stir compare? All right, if no, yeah, in the middle. Yeah, so why is it not the case with integers? So it turns out it's not the case with integers, with floats, with bools, with doubles, with longs. Like literally every other data type works correctly. Strings, though, are special. They're useful enough in programming and have been for decades that the authors of printf and the authors of stir compare and bunches of other functions, Stirling for that matter, just kind of treat strings special because they're just useful, right? We humans interact using language, be it English or anything else, and so it's just useful to have into the language C just sort of first-class support for this notion of strings of human text. So the short answer is just because. Like it just is necessary. Strings are different. They're implemented with this address and the null character. Everything else, though, is just a value. But a string, again, is a white lie. It's an address. It's not a thing unto itself. Good question. Yeah, in front. Oh, really good question. So in my code here, in VS Code, what if I do this? Instead of stir compare, and instead of if S equals T, what if I start playing around using star S and star t. Really interesting case to consider. Let's go back to our sort of deductive logic here. So star, the asterisk operator today, means go there. So when I've typed in hi once and then hi again, both uppercase, for instance, what is at the address s literally? Someone else. What is at the address s? Yeah. So not quite. At the address. Not what is the address. What is at the address 0x123? H. And what is at the address 0x456? H also. And so here, you're kind of cheating. Like you're comparing the first character of both strings, but not every other one. Now, you could be really pedantic. And here, again, this is not like a good use of code. But you could do this. If that, and how about this craziness? So star s plus 1 equals star t plus 1. And you could do this for every character manually, but that's why stir compare exists. It does all of this for you. But that's why, and that's the intuition. So I would encourage you to, anytime there's something kind of weird going on, I realize we might be straining credibility now. We haven't told you that many white lies. And so most everything that we've seen thus far can explain pretty much all of the behavior up until now, from week 1 onward in C. So let me revert this back to the right way. If stir compare of s and t equals 0, this now is the right version of the code. And now here is again where you can play. So let me do this. Let me clear my terminal window just to tidy things up. Let me get rid of all of this comparison stuff. And let's just see what's going on. As you are welcome to in your own code, let's print out, for instance, as we might have in week 1, the value of s itself in a new line, comma s, and then let's just print out t just to make sure it compiles and I'm not doing anything wrong. But this is not going to be that interesting. And frankly, I don't need string.h anymore because I'm not using stir compare. So make addresses, /addresses. There's my, oh, sorry, that's fun. OK, not %t, %s here too. Ignore that. Let's do this again. Make address, oh, and that's the wrong program. OK, let's do make compare. /compare, and let's type in hi again, and now we just see the two strings. I'm not comparing. But now we can kind of play around, right? Instead of printing out %s, which prints the string, how do I print the address in s? I just need to make a slight change. If I want to see not what's at s, but I want to see s, the address. Yeah. Perfect. So change %s in both places here to %p. So now printf will treat it literally as an address. It's not going to do any fanciness with a loop from left to right looking for the null character. It's just going to print out s and t. So let me clear my terminal, run make compare. Whoops. Let's do make compare, /compare, enter, type in hi again, and now you see, oh, so this is interesting. It's not quite as straightforward as the other values, which were 1 byte away. They're almost the same, but this one ends in B0. This one ends in F0. So they're indeed separated by some number of bytes. Not just one, but a few, because these strings are indeed longer. All right, so once you've seen this here, how can we now maybe leverage this to solve other problems? Well, let me propose that we do this. Let me zoom out here. Let me close compare. And let me open up another program I wrote part of in advance called copy.c. So copy.c, in theory, makes a copy of a string. How? On line 8, I'm using the same thing as before, get string, storing it in a string or char star, and asking the user for it. Then I'm not asking get string again. I'm just making a copy, super simply, with line 10 here, string t equals s. Now, intuitively, I think that's how I would copy a variable, right? That's how we've copied variables every week thus far in C. But something's going to go wrong. In line 12, in English, does someone want to explain what you think line 12 does? Don't worry about finding any bugs or mistakes. But what does line 12 seem to be doing using toUpper, which is thanks to the C-type library, which I've included the header file for? Yeah. Yeah, right? It's kind of like ugly syntax, but this would seem to be capitalizing the first letter of T specifically and just changing it. So we have T bracket 0 here because we want to save the change, and we're passing to toUpper the first character here. So this is how we did uppercase in the past, and now I print out S and T respectively using %s. So this feels like it should work. I copied S and stored it in T on line 10, and then I change T and only T on line 12. But you can perhaps, if you're comfy thus far, see where this is going if I do make copy /copy, and let me type in lowercase hi, exclamation point this time, just once. So I'm going to hit enter, and watch what we see for the value of s and t. The new value of s and t at the end of my program seems to be what? It seems to be the same. Hi is capitalized both times. So what's the intuition then for this? Why did this just happen? Yeah, and back. Yeah, I assigned s and t the same memory address. So it did copy s into t, but C takes this very literally. What is s? It's an address. What is t? It's a copy of that address. If you want to copy the whole string like a normal human would expect, hey, you or someone has to do a lot more work. You have to go to that address, copy this character, this one, this one, this one, and copy it to a new location in memory. That does not happen automatically here for you in C. It does in some other languages. Those of you who've programmed in certain higher level languages, this just works as you would hope, and that's one of the benefits of Python and other languages that we'll soon see. But for now, it literally takes at face value what this is. Copy the address into this address. And I'll make that more clear by getting rid of the string keyword, which again is just a type def. This is technically an address here. This is technically an address here. So what's being copied is the value of that address, not all of the characters that might very well follow it. So I should make one note too here. I'm going to start getting more in the habit of trying to avoid segmentation faults because things could go wrong here. For instance, on line 12 previously, I was kind of blindly, naively, dangerously assuming that there will be at least one character in S or T. That might not be the case. If the user just hits enter, there's no characters to uppercase. And so this is reckless of me and could theoretically create a seg fault. So I should probably start to be smarter and say something like this. If the length of T is greater than 0, OK, now it's safe to actually capitalize the first letter. And that will decrease the probability now of those segmentation faults by just not making any assumptions about what the human does. Almost always, your programs will crash when you've made a mistake, yes, but the user gives you an input that you yourself did not expect. So what does this all look like in memory? Well, let's go back to the big grid, this time focusing on the copying of values. And let's do this. Here's S, as in this new program, just declared to be a char star. Here is where my lowercase hi maybe ended up in the computer's memory. That's probably at 0x123, 124, 125, whatever, something like that. And that's, of course, what ends up in S as a value. When I declare t, I do get a second variable called t, just like before. But when I copy S into t, what happens? It's really just literally 0x123. Whatever the value of s is now also the value of t. And so if we abstract this away at a high level, get rid of all of those extra squares, this is what s and t now are. They're indeed copies, but copies of each other, not copies of the underlying characters. And so if you follow those arrows and try to print them both out after capitalizing one or the other, you're going to unfortunately end up capitalizing not just one of them, s, but both of them, S and T, because literally it's the same address. Any questions then on this visualization? Yeah? Good question. Is this pass by reference? We have not seen in detail an example like that. Right now you're copying by value. But references will come into play, and remind me in a bit if I haven't used that term yet. But this is just copying things by, could have ended poorly, value. Other questions? No? All right, so with this in mind, like how do we actually copy things properly? For this, we actually need another building block. So today we give you two functions, one of which is called malloc, one of which is called free. And these are used all of the time by like every piece of software you and I use on our Macs, PCs, and phones, whether it's written in C or some equivalent other language. Malloc is for memory allocation. It's a function that you can use to ask the operating system, Mac OS, Linux, Windows, anything, for some number of bytes. 1 byte, 100 bytes, a gigabyte of memory. You can ask malloc for however much memory you want in advance. It will return to you the address of the first byte of memory that it found free for you. Unlike a string, it is not null terminated. And so the danger with malloc is that it's on the honor system. If you ask it for 1 byte or 10 bytes, you, the programmer, in like a variable, have to remember how many bytes you requested, 1 or 10 or the like. Strings do that for you, not when we're getting now to this low level. Malloc's just going to give you some memory, and it's up to you to manage it. Free does the opposite. When you're done with some chunk of memory, you can free it by passing in that same address and just hand it back to Mac OS, Windows, or Linux and say, I'm done with this. You can let me use this for something else later. As an aside, if your computer has ever like frozen or hung, like the whole thing maybe just spontaneously reboots, yet another reason for a bug like that might be if you write a program with a bug that keeps mallocing, that is asking for more and more and more memory, but you make a mistake and you never free it, well, eventually the computer is going to literally run out of memory and something's going to go wrong, and that's often when computers freeze. Like they're just out of memory. It has the memory there, but the program was trying to use too much of it endlessly. So this too will be a mistake that some of us will surely make in the coming weeks, but hopefully you'll now see the solution. So let me go back to VS Code here, and let me propose that we do the following. I'll hide my terminal window for a moment, and I'm going to introduce another header file up here. And I promise there's not going to be too many more of these, but this one is called standardlib.h for standard library. And in this file are the declarations, the prototypes for malloc and free and a bunch of other stuff as well. It lets me now manage my own memory. So let's focus now on line 11. Line 11 is where I went wrong before, because conceptually I want to copy the whole string, but of course I'm only copying modestly the individual address. So how do I copy the whole darn thing? Well, what I need to do is this. When I declare t to be the address of something in memory, why don't I set t to be the address of a free chunk of memory? So let me ask the operating system, give me this many bytes, tell me what the address is, and I'm going to store that in t initially, just so I know where there's free space for me. So how do I do that? Well, quite simply, I call malloc, and then I pass in the number of bytes that I need. Now, for hi exclamation point, I think I need 3, although wait, no, I really need 4 because of the null character. But I don't think I should be hard coding numbers like this, because who knows what the human's going to type in. So I can actually use strlen of s and then +1. This will ask malloc then for however many bytes corresponds to the number of characters the human typed in, +1 for, again, the null character. So it's just being smart and defensive rather than choosing a number myself. But now all t is a pointer, if you will, to some random chunk of free space. So there's nothing there yet, or there's bits there, but who knows what value they are. They're certainly not identical to what the human typed in. I now have to do this. So how can I copy one string into the other? Well, let me do this. Instead of capitalizing something just yet, let me do this. How about for int I gets 0, I is less than the length of s, and then I ++. So I'm going to iterate for the whole length of the string. And in here, I'm just going to do this. The ith character in t should be identical to the ith character in s. So I'm just literally copying from right to left each and every character in s. And I can trust that there's enough memory in ty because I asked for that many bytes +1. Now, there's technically a bug here. I actually should probably do this. I should do +1 here. Or, if you prefer, I should do less than or equal to the strlen. But I think it's a little clearer to do the +1. Why do I, for the first time, want to go just beyond the boundary of s and copy one more byte? Yeah, I need the null character. Like, I could technically manually add it with some additional line of code, but I might as well just copy it because \0 is \0. So this time, and probably only this time, it's reasonable and correct to go just beyond the boundary of your string. So you copy the null terminating character so that the computer also knows where t ends. And now I think what I can do a little more safely is this. Let me go down here and say t_0 equals 2 upper of t bracket 0. So same line of code as before. If I actually want to be really safe, I should probably do this. So if the strlen of t is greater than 0, so there's at least 1 byte there, OK, now it's safe to blindly capitalize the first character. And I think that now puts me in better shape. So let me try this now. Let me open up my terminal, make copy, /copy. I'm going to type in hi exclamation point in all lowercase, crossing my fingers this time. And now if I zoom in, it indeed capitalized only t and not s in this case. So pictorially, let me switch over here. Here is, as before, the variable s pointing at hi in all lowercase. When I call malloc, though, that gives me a chunk of memory that I'm going to store the address in T of. So if T is some other variable, as it is in my code, and there's some other available chunk of memory, I don't know where it is, but let's assume, as always, it's at 0x456, 457, 458, 459, so 4 bytes total. What is now happening? Well, T is defined as pointing to that, because that's what malloc gives us, the address of the first byte of the free memory. And now with my for loop, I'm just iterating over it, copying the H, then the I, then the exclamation point, and then for good measure, the \0 instead. Questions then on this process here? A really good question. If I omitted in my code the +1 and I didn't do less than or equal to, so that I'm copying the 4th byte, odds are in this program, because it's so short, you wouldn't notice that there's an actual error. But what could happen is when I call printf on T, if there's no null byte there, it might print H, I, exclamation point, some random value, some random value, some random value, some random value, until it gets lucky and there happens to be a 0 byte, a null byte by chance, for instance. So if you don't include the \0 some way, that's going to happen. And I say some way, I could even do this. I could technically just copy the length of the string s, and at the very bottom here, I could do something like T bracket strlen of T. I could do this, but this is just not necessary. Like, I could manually add it at the end of the string. But again, I'd claim that it's just simpler to borrow, that is, copy the one that's already in S, because it's the same thing at the end of the day. Good question. Other questions on this copying correctly now? All right, is there any room for improvement here? Well, let me propose a slight optimization. This is kind of a throwback now to week 1. Turns out that arguably my line 13 here, wherein I have this for loop, now that I'm doing things in loops again and again and using a function like strlen, this is correct. It will iterate from 0 on up to the length of s plus 1. But it's kind of stupid of me to write this for loop in this way. Why? Well, here's my initialization on the left. Here's my condition in the middle. And in general, calling a function inside of your condition is probably not very good design. Like, why? Why is it bad for me to be calling a function like strlen in this condition in the middle of my for loop? Yeah. Yeah, you're just calling it again and again for no reason. Like, the length of s never changes. So, like, why are you wasting everyone's time by calling strlen of s again, 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 just to check this inequality, whether I is less than that value? So it turns out, if you haven't discovered this already, there's a slight optimization we can do here that has nothing to do fundamentally with strings or pointers, just with better design. I can actually define 2 variables at once. I could do this. Let me remove this whole condition. And let me add a comma after I equals 0, set n, or any variable, equal to the strlen of s plus 1, and then after the semicolon, just ask the question while I is less than n. So it's almost the same, but notice now my condition in the very middle of this loop is at least comparing 2 static values. N never changes. Sorry, 1 static value. N never changes. All that changes is I. But I'm not foolishly calling strlen again and again. Why? Well, how does strlen work? Similar in spirit to printf, strlen, given the name of a string, looks at the first character and then starts looking through the entire string, looking for the null character. And we saw this in week 2, counting up how many characters are there. So it's just a waste of time again and again.
Do you have to find n like all the way at the top so that way you can use n again in the output?
Totally. If you wanted to use n multiple times, you could absolutely take it out of the for loop, put it right after s is defined, and reuse n and again and again. Absolutely. But in general, consider this when designing your for loops. Even though modern compilers like Clang can actually fix this problem, this inefficiency for you, good practice would be don't call functions unnecessarily, especially if the answer is always going to be the same. All right, so what else should I perhaps refine here? Well, how about I do one last thing and just comment on what exactly could go wrong here? Well, a couple of things. Well, actually, this is just silly too. Like, surely someone before me in the world has had to copy a string before. Surely there's a function like called strcpy, maybe, like strcompare, like strling. And indeed there is. So let me propose that we actually get rid of this whole for loop, and we actually just call a function called strcpy, no O, just strcpy, and pass in the destination, which is t first, and then the source that you want to copy into the destination, and that takes the place entirely of that whole loop. So again, I demonstrated the loop first just to be very pedantic about it, but that's wasting time. You're wasting time writing lines of code you don't need to. Strcpy is what you can use here instead. And so this has now always existed. And what more can I do? Well, as one final point, it turns out that there's actually things that can go wrong in this code, even besides the string being too short. Like if the human just hits enter and there are no characters, I don't want to blindly capitalize the first character that doesn't exist. That's why I added that if condition. But there's other things that can go wrong, and we introduced those to you today. It turns out that functions like getString and functions like malloc return potentially a special value. And wonderfully confusingly, it's also called null, but with two L's. All right, so left hand and right hand weren't talking so well like decades ago. NUL is a \0. It's a single character, as it always has been for a couple of weeks now. NULL is technically a pointer. It's an address, but it's address 0. It's like the top left-hand corner, if you will, of your computer's memory that just nothing is ever supposed to go in by convention. So null is a synonym for 0, but it's specifically an address. Now, why is this useful? Well, suppose that in my code here, something goes wrong with getString. Suppose you're being a little crazy and you type in way too long of a string. It's not just hi, but it's like an entire essay of text, and there's not enough memory in the computer. How does getString signal to the programmer, whoa, like that's way too big of a string. I can't fit it in memory. Well, we never told you this, but all of this time, it turns out that getString will return this special value called null if something goes wrong. So to be really careful now, you should do something like this. If s equals literally null, then you better exit the program entirely and return like 1 or 2 or 3 to signify that something went wrong. Don't go any further. Similarly with malloc. It's possible if you ask for way too much memory, that could fail, especially if you're asking now for double the memory after the human types something in. So if t equals null, then you know what? Let's also return 1 or some other value to just get out before something crashes or freezes on the human as well. So honestly, I tend not to do this always in class because the code just gets so bloated and complicated. But you absolutely, in practice, need to start doing this. Otherwise, you will be responsible for the freezes and the crashes and the reboots that users in the real world might actually encounter otherwise. Of course, if we get to the bottom of this program now, I should probably return 0 explicitly or implicitly to just signify that everything is successful. But there's one other thing I haven't done. We introduced malloc, but what did I claim also existed? So free. I'm also being a little reckless now. Here I am not practicing what I'm preaching. I'm asking the computer for memory via getString. I'm asking the computer for more memory via malloc, and I'm never technically handing it back. So really what I should be doing at the very bottom of my program too is freeing the memory I've asked for. So henceforth, it is a rule, a law, if you will, in C. Whenever you allocate memory with malloc, or certain other functions as well, you, the programmer, must free it when you're all done with it. Now, this is a bit of an overstatement because technically when programs quit, they'll free the memory automatically. So you're not going to break someone's Mac or PC because you necessarily have this bug. But for programs that are running all the time, like someone keeps a Chrome, their browser open, Microsoft Word or the like, bad things will happen if over time you never call free and the program keeps running. So always get into this habit here. You do not need to free memory that comes from getString because the CS50 library automatically frees it for you. But you, anytime you use malloc henceforth, as you did or I did here, you must free that by just passing in the same address you got back. Questions now on malloc and free? Questions? Yeah? A really good question. So free so what does free do? So free just lets the computer know that you are done with that chunk of memory, which means that if you have another line of code elsewhere, that same memory might be reused. and can be used again and again. And that's going to be necessary, certainly for any long-running program. You can't ask for memory constantly. You'll eventually run out. So you need to free it in this way. Other languages, as an aside, Python, yet another motivation in a couple of weeks for it is going to be Python and certain other languages manage all this headache for you. But in C, the goal here is to really harness these capabilities ourselves. All right, so it turns out like almost everyone in the room, myself included, you're going to screw up when it comes to anything memory related if you haven't already. Seg faults are in your future, but hopefully there's tools via which you can detect these things and fix them proactively and not just use printf or debug 50 or rubber duck. We actually have another tool we can equip you with now that'll help you find some mistakes. So let me do this. Let me close copy.c. Let me open a program I wrote in advance called memory.c that doesn't do anything really interesting, but it's going to have 2 bugs in it. Notice that I've included standard.io.h, as always. I've also included standard.lib.h, which is necessary now for anything related to malloc and or free and the like. Line 6. It's a little weird what I've done here, but this is like the manual way of asking for enough memory for an array. In week 2, how do we ask for memory for an array? You very simply say int x3, and that gives you an array called x of size 3. But if you do it manually now using malloc, what you have to do is use syntax like this. You call malloc, you ask for 3 things, times however big an int is. Now we know it's 4, so you could literally write 12 here, but this is more generic. So 3 times the size of an integer will give you 12 dynamically. And what does malloc return? The address of the first byte you get back. What do I want to put that? Well, I want to put it in a variable. Now, the variable can't just be int x, because that's a number. It's not an address per se. If I want to store this address in a variable, I could call it x, I could call it p. But int star x just means that x is now the address of a chunk of memory. Specifically, a chunk of memory that's big enough, not for 1, but for 3 ints in total. All right, now I'm just sort of naively putting our old friends 72, 73, and 33 at the first, second, and third locations in memory. But perhaps based on week 2 or week 4, I'm clearly screwing up here in a couple of ways. Someone want to identify at least one bug. What did I do wrong? Yeah, like this is now, amateur stuff. Like I should be 0 indexing, not 1 indexing. So this has got to be 0, 1, 2 ultimately. And other bugs that are maybe more week 4 specific? Other bugs. It's more subtle, yeah. I'm not freeing the memory, right? So I'm not practicing what I'm preaching by freeing this memory. Now, suppose these are non-obvious. And honestly, after like an hour or 2 of this, like this shouldn't be obvious yet. It will be over time. How could I find these bugs with software as opposed to just staring at the thing or asking someone for help? Well, let me propose this. Let me first go ahead and run make memory to compile the program. And it seems to look fine. There's no syntax errors, at least. /memory, notice, seems to work fine too. Now, this program doesn't do anything interesting. There's no printf or anything like that. But it didn't crash. There's no segmentation fault. But that doesn't mean there aren't bugs latent in the software. And this is true, sadly, of all of today's software, like Chrome and Microsoft Word and other programs surely have memory-related bugs that people at Google and Microsoft haven't yet found. But there are tools, at least to find the most obvious of those bugs. And we're going to introduce you now to a program called Valgrind. So Valgrind, it's a fairly fancy program, but we'll use it for very simple ways. We'll look at your code and find memory errors as it's executing and try to help you understand where they are. So let me go back to VS Code here. Memory seems to be fine. I feel like, OK, I'm going to submit this homework. All is good. No error messages. That's no longer the case. Now you need to poke a little more at your code to see if maybe there's still some bug there. So let me do this. Valgrind. And then space /memory. So just like debug 50, you run it on a program you already compiled. Valgrind, I'm going to run it on a program I already compiled. Let me zoom in on my terminal window so we can see more at once, and enter. All right, the output is crazy cryptic for no good reason. There's lots of numbers and equal signs. It's a lot of clutter, but there is some juicy information here. And let me start from the top down. Invalid write of size 4. So write means to change a value. Read means to access a value. And this is, again, esoteric like a lot of our error messages are. But it looks like after a block of size 12 alloc'd, and then there's these weird hex notation, there's some mention of malloc. But honestly, the juicy part here is memory.c, line 6. That's probably my fault. So let's look at line 6 per that output. Let me shrink the terminal window. Look at line 6. OK, 12 is now germane, right? If you did the mental math of the size of an int times 3, 12 is somehow involved here. but line 6 is now happening next here. That's where the memory came from. What is this? Let me zoom back in. Where is there invalid right of size 4? Like, what's perhaps going wrong here? Invalid right of size 4. What does that mean? It's like a very technical way of explaining. The bug is actually one line later on line 7, as we already identified. Yeah. Indeed, and I misspoke a moment ago. The bug actually arises here with line 9. So after the allocation of memory, I'm somehow writing 4 bytes incorrectly. And unfortunately, the onus is kind of on you to sort of think through deductively, like, what could that mean? But I'm clearly touching 4 bytes of memory in these few lines of code that I shouldn't be. And hopefully here, as the light bulb already went off earlier, oh, I'm not 0 indexing. OK, that must mean that x bracket 3, as you note, is just too far past the chunk of memory. So I'm invalidly writing to 4 bytes that I shouldn't be. So again, it's not super obvious. This is not super user-friendly, but at least it does give you a clue as to where that bug is. So the fix there is going to be quite simply to change the 1 to a 0, the 2 to a 1, and the 3 to a 2. That'll fix that, but there's still a second error. And let me look at the cryptic output again. Heap summary, some stuff there. OK, this does not sound good down here. 12 bytes in 1 blocks are definitely lost in loss record 1 of 1. Very arcane output 2, but clearly related to line 6 again, our allocation of memory. Now here too, it's not obvious what the solution is, but memory is lost, aka this is a memory leak. And now the deduction's kind of up to you. What is leaking? Oh, wait, I didn't call free. And so the second solution here is probably to free x at the very end of the program. And if you really want to be pedantic, you should probably check, like I proposed earlier, if x is null, just get out now while you still can, and don't even touch those other lines of code. But if you get to the bottom, return 0. But really, the takeaways are, I fixed my 0 indexing of the array to avoid the invalid right of size 4. And now I'm freeing the memory that I asked for. So there should be no leak lost. All right, let's try this again. Make memory, /memory. No visible errors yet. But let me now increase my terminal window again, do valgrind of /memory, crossing my fingers. And now all heap blocks were freed. No leaks are possible. I don't see any invalid writes. There's still a crazy amount of output, but none of it is erroneous. It's not bad. Now I've fixed my memory bugs. And so now my TA, my TF, they're not going to find them either, because at least Valgrind has proactively done that for me. Questions then on Valgrind? Generally, it's those 2 types of errors you might trip over. There's not too much else in the way of arcane output. Questions then on this? No? All right. Well, what else might be going on? So someone alluded to this earlier. What happens when you, for instance, forget the null terminator? Or you generally start poking around memory that you yourself didn't ask for, or looking at values you didn't put there? Well, let me go ahead and open this. Code of garbage.c, in honor of Oscar the Grouch here of sorts. And here is a simple program. If I hide my terminal window, that just does something kind of arbitrary. I first declare an array called scores. But I made it crazy big, like 1024. Like, that's a lot of integers, but so be it. And then I iterate over those integers, and I print each of those scores out. So I'm using week 2 syntax here. But based on this program, what have I clearly not done that I did do back in week 2? I've allocated the array. I'm printing the array, but. Yeah, I didn't initialize any values for that array. Back in week 2, we didn't do 1024. We did like 3, and I typed in like 3 test scores or something like that. Here, I'm allocating memory, even more than that, just because I really want to be dramatic with what I'm demonstrating. But I'm not initializing those values to anything. And so here it turns out in C, generally, if you do not initialize a variable, or you do not initialize an array with explicit values, there are going to be garbage values there, so to speak. Remnants of that memory having been used before, probably by some other function of yours, some library function, or something else while your program is running. Not a huge deal with a super small program like this, but for anything sizable, memory is going to be used and unused and used and unused. That is mallocked and freed again and again. There's going to be lots of garbage values in the computer's memory by default. So if I open my terminal window here, let me do make garbage. Let me zoom in on my terminal so we can see the output. When I run /garbage, theoretically, I should see 1,024 integers, but none of which have been initialized. Now, I'm going to get lucky with some of them. And it looks like, wow, OK, a lot of them are initialized to 0. And C does, in some contexts, initialize memory for you to 0, at least at the beginning, but not again and again typically. But if I start scrolling backwards in time at this array of size 1024, where did these values come from? So just random positive and negative numbers interspersed among the zeros, well, that's because I'm literally poking around on a random 1,024 bytes of the computer's memory. Who knows what's there? So the lesson here is that garbage values are indeed this like term of art. It means that a variable that you might have defined, that you might have declared, if you don't give it an explicit value, who knows what's going to be there? And the lesson here is just don't do that. Always initialize variables to something, either yourself or prompting the human for it. Questions about garbage values. You'll see them sometimes if you print things you shouldn't or touch arrays beyond their boundaries. All right, so maybe to make this a little visual too, it turns out that a lot of things can go wrong, unfortunately, with pointers, and we've seen some of them. And here's another program that's a little contrived. It's very simple, and it just is about manipulating values. It doesn't do anything useful per se, except demonstrate some of today's concepts. So in main here, let me propose that we declare a pointer called x that's going to store eventually the address of an integer, apparently. Here's another one called y that's going to store the address of an integer as well. Here now, I'm allocating enough memory to fit one integer. Now, technically, it's 4. We know that. But size of int just gives me that answer dynamically. So it will work on all systems. And I'm going to store the address that malloc finds for me in x. Then I go to x and put the number 42 there. All right, y, it's the sort of meaning of life, the universe, and everything here. But star x, again, just means go to that address and put a value there. So y, I don't know, but it's just correct at this point. But what about this line here? Star y equals 13. Unlucky in this case. What's bad about this line here, star y? It's a combination now of today's primitives and that point here. Yeah? Yeah, we didn't ask the computer to allocate any space, so y was not initialized with an equal sign at any point to anything. And so what is inside y, so to speak? Like a garbage value. Maybe it's 0, which isn't bad because at least it's nice and simple, but maybe it's some crazy large positive number, some crazy large negative number. Either way, odds are if I go to this address or that address randomly with star y, bad things are going to happen. And so let me go ahead and propose, well, let's not do that. Let's actually do this instead. Assign y equal to x, and we've done that before. And then I can go to y now and change what was a 42 to a 13. Again, why? This is just for educational sake. But for now, this does not crash, because I only dereference y with star y after actually giving it a value, albeit a duplicate value, similar to our copy example earlier. So our friends at Stanford have put together a wonderful visual. It's about 2 minutes long. Allow me to dramatically dim the lights if we could and play with what happens with memory when you do bad things like this.
Hey, Binky, wake up. It's time for pointer fun. What's that? Learn about pointers. Oh, goody! Well, to get started, I guess we're going to need a couple pointers. Okay, this code allocates 2 pointers which can point to integers. Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything. That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step. Oh, right. I knew that. The pointees are separate. So, how do you allocate a pointee? Okay. Well, this code allocates a new integer pointee, and this part sets x to point to it. Hey, that looks better. So make it do something. Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing. Your magic wand of dereferencing? That's great. This is what the code looks like. I'll just set up the number and... Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y. Okay, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Whoa! Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it. Good point. Yeah, we allocated the pointer y, but we never set it to point to a pointee. Very observant. Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x? Sure, I'll use my magic wand of pointer assignment. Is that going to be a problem like before? No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another. Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over. Okay, here goes. Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13. Yeah, sharing, whatever. So are we going to switch places now? Oh, look, we're out of time. But
our thanks to Professor Nick Parlante of Stanford for spending a huge amount of time doing stop motion animation for that. But hopefully now you have a sense of what too can go wrong when you misuse memory in this way. But at the end of the day, we really only have these 4 new building blocks today, like the star operator, the ampersand operator, malloc, and free. And really with that and the underlying understanding of what your computer is doing underneath the hood, we have this way now to really manipulate things in memory, for better or for worse, and eventually we'll see how we can build things. But we can also now use today's primitives to better explain some things that we've been asking you to take for granted over the past several weeks. So for instance, let me propose that we do a one volunteer up here if we could. Could we get one volunteer who's just, you want to come straight up? Yep, right in the middle. Come on. You'll have to take a left or a right there. All right, so we have 2 empty glasses here and 2 colors of liquid. And we have, let me give you the mic, if you'd like to say hello to the group.
Hello, I'm Moeen. I'm in Thayer and first year.
All right, welcome. Well, welcome here. I'm going to go ahead and fill these 2 glasses with this colored liquid, purple here on my right. Let's fill up a glass here. Yes, don't drink. And now we'll put some orange in here. And what we'd like you to do for the audience, if you don't mind, is swap the 2 values. We've got a purple value and an orange value, and I'd like the purple liquid in this glass and the orange liquid in that glass, please. Oh, OK, good intuition, but for the microphone.
Can I have another glass?
So you can, and just in fact, I brought one here for you. Why are you asking for this, though?
Because if I just pour this into this, then it'll get mixed up.
Right, so obviously we need like a temporary variable, if you will. So here's your temporary variable.
And you want,
okay. Yeah. All right, so pouring the value of the orange glass into this temporary variable, if you will. All right, and now pouring the value of the purple glass into the former orange glass. And now the temporary value goes back into the original purple glass. And now I think we give you a round of applause for having done that very well. Okay. Thank you. All right, so it should go without saying that in the real world, like that's how you do this. And in fact, in code, that's pretty much how you have to do this. Although, ask us sometime for a super fancy way of doing it without a temporary variable. Turns out that is possible using bits. But for now, let's suppose that indeed this demonstrates what is the reality in code. If you want to swap 2 values, you need to have something like a temporary variable. So for instance, on the screen here is the beginning of a function called swap, whose purpose in life is to, as you just did, swap 2 values, call it a and b. So orange and purple, respectively, are now just a and b in integers to keep things simple. Well, here is the corresponding code, if I may, to what you just enacted as a human. You declared a temporary variable called temp in this case, which was like me handing you the empty glass, and you stored the orange liquid in it, aka a. You then changed the value of the formerly orange glass to be equal to the purple by pouring one into the other, and then you did the opposite there. Now at the end of this, you still have a temporary variable that's now empty, so it's temporary in literally that sense. Like you just don't need it anymore, but it was necessary along the way. So I dare say this code is correct logically. Like this will swap 2 values, a and b, thanks to the use of that temporary variable. Unfortunately, though, if I actually do this in practice, let me go over to VS Code here and open a program I wrote in advance called swap.c, which does this as follows. In here, notice I have my prototype for a swap function at the very top. And let me scroll down to the very bottom. There's that exact same code. So I'm the same code for swapping 2 values, a and b, which I'm claiming for now is correct. Now, if I go back up here, what is main going to do for us? Main is really just meant to be a demonstration of the correctness of your algorithm. So here I declare on line 7 and 8 2 variables, x and y, being 1 and 2 arbitrarily, respectively. I then on line 10 just print out what the value of x is and y is, just so I can see it on the screen. I then call the swap function on line 11, and then I literally print the exact same thing again. I print x and y. Hopefully, it'll obviously be the opposite. So I think logically swap is indeed correct. Let me do make swap and then /swap, and I should see x is 1, y is 2, and then hopefully x is 2, y is 1. Enter. But I don't. And it did work in the sense that the code compiled, the code ran. So it's not like some bug in that sense. But because I don't quite understand what's going on underneath the hood, at least as of right now or prior weeks, this code here is indeed buggy in some way. But does anyone have an intuition, perhaps based on today's discussion, as to like why this code, while logically correct, clearly works in reality, apparently does not work in C? Any intuition? Yeah. Perfect. And to summarize, here's that term of art I promised. When you call a function and pass in two arguments, like a and b, you're passing those arguments by value. So copies of those values effectively. And so when swap is actually called here, when you pass in x and y, we call them a and b, but that's just a convention. We could call the parameters anything we want. What a and b are indeed the values of x and y respectively, but copies of the values. So this code here is very successfully in VS Code 2 swapping the values of a and b. But as you note, because I'm passing them in by value, literally 1, literally 2, and not by another term of art, by reference, aka by their addresses, swap has no capability in C to go to those locations, swap the actual locations, just like we did successfully in reality. But I think we really have the syntax already for solving this if we consider that really this is just an issue of scope. And we've talked a bit about scope in the past, whereby scope refers to the context in which a variable lives. And generally, I've claimed that a variable exists between the most recent curly braces. And that's pretty much true for the swap function, because a and b, I now claim again, exist only in the context of these curly braces. They have no effect on main up top, which has different variables, x and y. But we can consider now what's really going on underneath the hood. And here's that same picture of memory as we've seen in the past. If we zoom in and see on these little black chips, this is a bunch of bytes of memory. If I create a grid out of it just to kind of highlight that we can address each of these bytes, throw away the plastic circuit board and focus only on those bytes, what's going on underneath the hood when functions are called in C, which you've been doing for weeks now? Well, this rectangle of memory, if we kind of abstract it away further, is generally broken up into different regions or segments, like I called them earlier, and different things get put in different parts of the computer's memory. And without getting too into the weeds, when you double-click a program on your Mac or PC, or when you do /something on a Linux, you are loading your machine code into the computer's memory from the computer's hard drive. So all the zeros and ones that compose Microsoft Word or Chrome or whatever are loaded into the computer's memory or RAM. And by convention, it's put up top in the so-called machine code area. And that's how the CPU has access to them quickly at that. Below that are what are going to be our globals, so global variables, which we haven't used very much in C, but you can declare them outside of main at the very top of your files. If you have globals, they end up there as well, just FYI. And then there's this big chunk of memory that we saw Valgrind mention indirectly earlier called the heap. And it's kind of like heap, literally, like it's a heap of memory that you can use as you see fit. And the heap is where malloc grabs memory from. So initially, there's nothing in the heap. It's just a big chunk of free space. Anytime you call malloc, malloc kind of carves out from the heap area more and more bytes. And malloc keeps track of essentially which bytes have already been allocated. So initially, it looks empty, but different bytes, squares, if you will, keep getting requested again and again as a program runs, thanks to functions like malloc. And it grows, if you will, conceptually down. So the more and more memory you request from malloc, it starts up here, but then the next chunk you get is down here conceptually. The next chunk is down here, down here. So it kind of fills the available space in the computer's overall memory. But there's this other chunk of memory called the stack. And just like a stack of trays in like Annenberg or a cafeteria kind of grow upward, so does the stack of memory. And it turns out the stack is where functions have variables and have arguments stored temporarily. So whenever you call a function and it has variables inside of it or has arguments there too, this is the chunk of memory in the computer's overall block of memory that are used for functions. But anytime you call malloc, it's memory up here. Right? At the end of the day, they just had to pick a direction, top, bottom, and technically it's an artist rendition. You could circle this thing around any orientation you want, but you're just using a finite amount of memory in this conventional way. Malloc starts here, functions start here. Now you can kind of see where like bad things can happen. And indeed, one of the other reasons computers can crash is if you ask for way too much memory from the heap by calling malloc many, many, many times, or if you call way too many functions, or accidentally, per last week, you recurse infinitely many times, you might have a segmentation fault. And that's because you're using too much stack memory. So this is bound to be a problem eventually. And the onus is on the programmer to just minimize the probability of doing that and really avoid the possibility of doing that by just checking return values, like checking if malloc or getString return null, because you can proactively with conditionals make sure that these two things do not collide by just making sure that you get back non-null values. So let's consider the stack in the context of swap and what's really happening here. And Carter, if you wouldn't mind helping me animate the screen here, when I call the main function of any program, it is allocated a slice of memory called a frame at the bottom of this stack. So if Carter, you want to go ahead and advance here, here's like the first slice of memory that will always be used by main, whether it has command line arguments or local variables. It just ends up here in memory. Suppose now, per our swap.c program, that main calls swap. Well, where does the memory for swap end up? Like right up here. So swap had two arguments, a and b, and it also had a temporary variable. So all of those end up in here in memory. And if you want to go ahead and advance again, Carter, once swap is done executing, whether it just returns because there's no more lines of code or you explicitly return, this memory is just freed up automatically. You don't call free, you don't undo malloc. This just all happens automatically. It has been since week 1. Now, technically, it's still there, even though we've removed it from the picture. And there's your first hint of garbage values, right? Like there's still zeros and ones there, and they're left in the previous configuration. And so the reason you get random values in the memory is because even though we haven't drawn swap here, there was stuff there a moment ago. It's going to be there the next time you use that same memory. Now, let's go ahead and step through this a little more methodically. Main has two variables called x and y, 1 and 2. So let's advance and represent x as 1, y is 2, taking up these two chunks of memory. When we call swap now, swap gets a new slice of memory that then gives us 3 variables, a and b, technically the arguments, and temp. So what happens? Well, because functions automatically pass in values by value, or rather pass in arguments by value, x gets copied into a, y gets copied into b, and then once we start executing the algorithm a la the watered glasses, well, what happens here? So if I execute the first line of code, temp equals a, temp gets a copy of a. What happens next? A equals b. So a takes on a copy of b. And now we do the final swap in the glasses. B equals temp. B gets a copy of temp. Now, we don't have to change temp because it's essentially empty, although there's the garbage value. 1 is always now going to be there until we reuse that memory. The important thing, though, is that a and b have been swapped. But what obviously has not been swapped, as is manifest, is when swap returns, x and y are untouched because copies thereof were passed in. So we need a solution to this problem. And if we advance one more time, if you don't mind, let me step over here, but then call you back in a second. This code here is logically correct. This is what you did, but this is now a detail of C. You can't just swap the things by value because you're only changing it in the scope of the swap function. But I think if we change it to this and add some annoying syntax, we can solve the problem. Just like you can declare variables as storing addresses, you can declare arguments to functions, aka parameters, as taking addresses. This new version of swap means that a shall be the address of an integer. B shall be the address of an integer. And now it gets a little cryptic here. Temp is the same because it's just an integer like it was in week 1. Nothing special about temp. But if you want to get the value at a, you do star a. And that goes to the address, grabs the number 1, presumably. If you want to change the value of a, you go to that address, you follow the treasure map to the other mailbox, and you set it equal to whatever's at the value of b. You go to b as well. Last line, you go to b now and change it to be whatever the temporary variable was, which happened to be the same as a. So that's where the final value gets swapped. But here, there's a lot more like crisscrossing metaphorically across the stage where you're going to all of these different addresses in the swap function to make these changes. So if we advance now to the pictorial version of this, here's the same story as before with main. and x and y are 1 and 2 respectively. When swap gets called now, notice, and I'll do it with arrows here, A is effectively pointing to x, B is effectively pointing to y. If we really get into the weeds, these are actually like addresses, but who cares about the specifics? It's really just the concept here. So now what happens? Int temp gets star A. Star A means start at A and go there. Follow the arrow, if you will, sort of chutes and ladders style. And then that's 1, so we put 1 in temp. All right, star A equals star B. So let's do it from right to left. Star B means follow the arrow. It's 2. And then what do? Follow the arrow. It's now 2 because you copy 1 to the other from right to left. And then lastly, star B gets temp. So start at B, go to B, and now store whatever the value is in temp. So just by having this basic new syntax of like ampersands and stars and so forth, we can actually now go to places and circumvent what is otherwise a feature of C, that these variables are locally scoped, but you can still access things in other functions as well. So thank you so much for helping step through this. So we now have an application of this that explains why now in this version of the C code, this would actually now work. So in fact, let me go back to my swap code here. And let me change the function ever so slightly in VS Code. So let me scroll down, leaving main the same, and let me change swap's prototype to taking in addresses. Let me go to A here, let me go to A here, let me go to B here, and let me go to B here as well. But nothing else changes. This change here in particular is enough of a clue to see that means when you call swap and pass in 2 values, I'm expecting addresses now, not integers. But now that I've made this change, I do need to go up to main and make one change. Does anyone have the intuition for what now needs change in main so that I pass in x and y by reference, that is by address, rather than by value or copy? Oh, yeah, in back? So close. So on the swap line, it's not star that I want in front of the x and the y. It's instead, what's the other one? It's the ampersand. Why? Because if I want to enable swap to go somewhere, just like Carter and I played this game with the mailboxes, I need to inform swap of the address of x and the address of y. And again, per the beginning of today's class, ampersand is the syntax via which we do that. So I add an ampersand here to get the address of x, ampersand here to get the address of y. And now this code lines up with the picture that Carter just helped us walk through. And so when I run make swap here, I have a mistake. Oh, what did I do wrong? Not intentional, but I guess worth pointing out. I screwed up here. It doesn't like ampersand x because of something on line 3, which is way early in the code. What did I screw up? Yeah, in the middle? Yeah, so this is why you should not copy paste, even though it's necessary for things like function prototypes. If I change swap at the bottom, I need to change its prototype. So let me add the star there, or just recopy paste it at the top of the file. Now let me do make swap again. Let me now do /swap, and I should now see x is 1, y is 2, and hopefully x is 2, y is 1, which I now do. So the logic is the same. The algorithm is the same. All the week 0 stuff is the same, except now in week 4, you just have a bit more expressiveness via which you can tell the computer exactly what you want to manipulate and how. Any questions then on this technique here? No? All right. Well, when we fix this, there's still going to be problems. And just so you've seen some terms of art here, this is bad whenever you have 2 arrows pointing at one another. Certainly if you might use and reuse more and more memory. And it turns out there's some terms of art that might suddenly now make sense, especially if you've programmed before. Bad things can happen by this design, but there's really only this kind of design because it's a finite amount of memory. So at some point, bad things are going to happen no matter what if a computer runs out of memory. So it's not that this was a poor decision. It's just sort of a necessary one given finite amounts of memory in a computer. But a heap overflow, so to speak, is when you actually overflow the heap and touch memory that you shouldn't up there. Stack overflow is when you somehow overflow the stack and touch memory that you shouldn't down there. So with that said, these are really just problems that can happen, and they're specific incarnations of what are generally called buffer overflows. A buffer, like in the YouTube sense, is just like a chunk of memory that in the case of YouTube stores like the next few seconds or minutes of video. But generally speaking, a buffer is just a chunk of memory that the computer is using for some purpose, be it the stack, be it the heap, be it an array in the computer. And so buffer overflows are what happens when you just have logical bugs in your code. But with these primitives now in mind, we wanted to conclude with the final revelations. And that's how some functions like these here work. The other thing in the CS50 library, besides the typedef for quote-unquote string, is, of course, all of these functions. And we give you these functions because, honestly, in C, it is hard, it's annoying, it's painful, it's difficult to get user input correctly. It's very easy when you don't know how much the human's going to type to write buggy code when it comes to it. And indeed, it's really hard to store it correctly without accidentally having some kind of buffer overflow. So for instance, let me show you a program here. I'm going to go ahead and write this one from scratch. So let me go ahead and open a file called get.c, wherein I'm going to go ahead and mimic the idea of getting integers manually without the CS50 library. So I'm going to include standard io.h only. I'm going to define main as not taking any command line arguments. And then I'm going to do something like this. Give me a variable x with no value yet. And normally, I would do something like getInt. But let me take that away. No more training wheels for getInt either. So let me just define the int x. Let me then just print out something like a prompt. And I'll just do x colon just to make it obvious to the human what we're waiting for. And now I'm going to use a built-in C function to get user input. I'm going to call a function called scanf, which sort of scans the user's keyboard for input. I'm going to scan it for an integer. So just like printf, I'm going to use %i because I expect an int. And then I want to tell scanf where to put the human's integer from the keyboard. It is not correct, though, to say x. Because if I say x, I run into the same swap problem. Scanf, no function, can change the value of x unless I pass it not by value, but by reference. So we're back to our ampersand friend. And now it has like a treasure map to the actual location of x and can therefore change it. And so now at the very end of this program, let me do something simple. Like let's just go ahead and print out with printf the value of x using %i as always, plugging in x. Not ampersand x. This is now week 1 stuff. I want to print the actual integer value of x. So the only change here is that instead of using getInt, I'm now using this new function that as of today exists called scanf. So let me go ahead and run get, make get to create this program, /get, and let's go ahead and type in a value for x, 50, enter. And it just works. So it turns out getInt is pretty simple to implement. However, notice what does not work. If I type in cat, for instance, cat gets converted to 0. And meanwhile, getInt, recall, will reprompt the user. If a human does not type an actual integer, you get automatically reprompted. So that's one of the features we, for CS50, added to getInt just to make your programs more user-friendly. But otherwise, getInt is pretty straightforward to re-implement using scanf. Unfortunately, that's not true for strings. Because how do you know when you write your code what word the human's going to eventually type in, how long their greeting, like hi, is, if their name is David or Carter or anything else? You just don't know in advance how much memory you need. So how might we do this with strings? Well, let me go ahead and declare a string s. Although, you know what? There's no CS50 library, so we do char star s today instead. And that gives me not a string per se, but a pointer that will point presumably to a string. Ideally, I would use this, get string. But again, we've taken that training wheel away. So now that I have a pointer s, suppose I prompt the human for a value for s, just like before. Let me use scanf now and tell the user that I expect to read a string, %s from the keyboard, and store it in s. Now, this is subtle. I don't technically need an ampersand here, even though I did for an int, and I would for a float, and a double, and a long, and a bool, and a char. Why do I not need an ampersand in this story to pass by reference? Because s it's already an address. Again, strings are just special. Strings now are always addresses, so you don't need to additionally add an ampersand here. That's the only subtle difference here. But now if I go ahead and print out at the very end what the value of s is, using %s as before, this program looks like it's almost the same as the int version. But let's do make get. And OK, so this is not good. All right, so it doesn't like an uninitialized value. So let me make it happy. I said earlier to always initialize my variable. So let's initialize it to null so that at least something is there. That's your good default value nowadays. Now if I do /get, now we're good. And let me type in something like cat. OK, cat is not x. Well, let me try another word. Maybe it's just cat is wrong. Dog. OK, let me try David. It just doesn't seem to be working. Moreover, it's printing it as a 0. What logically, though, is the bug here? scanf worked a moment ago for integers, but it's not working for strings. And it seems to be forgetting CAT. It's forgetting DOG. It's forgetting DAVID. Why? What's happening here? Think back to our yellow pictures of memory. When yeah. It might be reading just the null itself because S is being initialized to null. And what step have I forgotten from just like a few minutes ago? What did I not actually request of the computer? Like actual memory to store the CAT, the DOG, the DAVID, right? There's nowhere have I asked the computer for some amount of memory. And so technically, it might be reading it into some garbage location. And that's really the problem here. S is initialized to null now. And so in fact, it is printing 0 as null. But I'm not seeing any of the other letters because there was nowhere to put them. CAT, DOG, DAVID, because I didn't ask for 3 bytes, 4 bytes, 5 bytes, 100 bytes. There's no use of malloc. There's no use of an array. There's no memory allocated for anything other than the pointer itself. And this is where, honestly, life gets hard with scanf. Like, I could solve this problem in a couple of ways. Let me go ahead and do this. Instead of declaring S to be a pointer, let me declare S to actually be an array of 4 chars. And now, let me go ahead and recompile the code. So make get /get, and I'll type in cat now. That now works. Why? Well, I'm allocating an explicit array of size 4, enough for a 1, 2, 3 letters plus a null character. Here's where, to someone's question earlier, it turns out that in some context, you can treat arrays as though they are pointers themselves. C will sort of do the conversion for you. But for now, just assume that S is just an array of size 4. And if you pass it into scanf, that's like a treasure map that leads to those 4 bytes. So scanf can now successfully fill it with CAT, DOG, but let's try this again. Let's type in David. And here, OK, we got lucky, but I technically touched memory that I should not. And in fact, if I typed in a long enough string, and I don't think I could do it very easily, like without typing this thousands or hundreds of times, still OK. But you'll notice that it's forgotten the rest of it now. Right? So somewhere we went beyond the boundary of the array, and we just don't have enough storage space for that entire thing. So what do you do in your program? If you don't know how long the person's name or the animal name is going to be, what do? 40, 400, 4,000, 40,000? Like at some point, you have to draw a line in the sand. And that's why like getting user input is so annoying in a language like C. And that's why getString exists. What we do, if you're curious, is we look at the user's input, and we take baby steps. We look at it 1 character at a time. And every time we see another character, we actually call malloc again and say, no, I need more than 1 byte. I need 2. Oh, wait, they typed in 3 letters. I need 3 instead of 2. Oh, I need 4 instead of 2. And we have this crazy loop, essentially, that keeps asking for more and more memory, but by taking baby steps. And honestly, if you all had to do that in week 1, my God, like we couldn't even write hello world anymore. And so that's why these training wheels exist, at least early on. And that's why in higher level languages, like in Python, you don't have to do this at all. It just works as you'd expect. So what more can we do? Well, you'll see in problem set 4 this coming week, if I open up an example like this, phonebook.c, you'll see that you can manipulate files now that you have a vocabulary for pointers. It's going to be new quickly, but here we have an example of how I have a program using some familiar libraries here. But as I claim in my comment, this saves names and numbers to a CSV file. All of my examples thus far, I type in some words, I type in some names and some phone numbers, and they disappear because we only store them in memory. But if you want to store data in like a CSV file, comma, separated values, which is like a simple spreadsheet, like Excel and Apple Numbers and Google Sheets can open, you can actually do this yourself. So just as a teaser for this week, here on line 9, I'm using a new data type, not a CS50 thing. This is a C thing called file. But if you want to manipulate files, you need to use addresses, that is pointers. So here is me creating a variable called file that's going to point to an actual file on the hard drive, on the server or your Mac or PC. fopen is going to be a new function you'll use that will open a file. And it will return effectively a pointer thereto in memory. The file name I want to open is phonebook.csv. And in this example, it's going to be append mode. It will keep allowing me to add more and more names and numbers to this file. Here's some old getString stuff, because I'm not going to reinvent getString with scanf. But down here is a slightly new function. It's not printf, but fprintf. And it turns out it's very easy to print things not to the screen, but to a file with fprintf. And it takes an additional argument. Instead of starting with the quoted string, you'll have to like say what file you want to write to. And fprintf will figure out how to get the bits into that file, passing in something like name, comma, number. So if I run this somewhat quickly here, let me do this. Let me pre-create a file called phonebook. phonebook.csv. And in phonebook.csv, I'm going to create a temporary row here, name, comma, number, just so that there's something in this file. And now let me go ahead and do this and split my screen here. If I have phonebook.csv on the right and phonebook.c on the left, let me compile, make phonebook, which is the C version, /phonebook, and now I'm prompted for a name and a number. So I'll type in David, and then, for instance, +1 949 468 2750. Enter. Oh, damn it. Bug. Pretend that didn't happen. I forgot to hit enter in the file. So let's do this again. If I run the program again, David, and +1 949 468 2750, enter, it's been saved now to the file. And if I close this file and I reopen code of phonebook.csv, you'll see that the file is persisting. And if I downloaded this to my Mac or my PC, I could double click the CSV file and voila, Excel would open up, or Apple Numbers or the like, and I've actually created an actual CSV file. If you're smiling because I keep repeating my phone number out loud, I would encourage you to call or text that number sometime. It might very well be an Easter egg of sorts. But via these functions here, do we have now the ability to write files, input and output. And among the goals then for this week, as we'll see, are to actually play with images in the spirit of something like Instagram filters or the like. And we'll introduce you, for instance, to a file format called BMPs, which, to come full circle to the start of class, are just maps of bits, but more than just single bits for white and black, but rather colorful patterns as well. And we'll give you images like this of the Weeks Bridge here across the river at Harvard. And you've run, after writing your own code in C and understanding how the data is stored in the computer's memory, you'll be able to apply your own Instagram-like filters to make things grayscale instead, or sepia in this case. You can even flip the bits around so that the thing is a mirror image. You can blur things further, or if you really are feeling more comfortable, you can even write code that finds the edges of the image and creates works of art like these. So all that and more in problem set 4. We will see you next time. This is CS50, and this is week 5, which is going to be our last week in C. But what that means is that we'll have, okay. But with this week, with last week, and really all of the weeks prior, have you been hopefully acquiring, if slowly and with some challenge, like some fundamental building blocks that are still going to underlie everything we continue doing in the semester, even as we transition to so-called higher level languages. Next week, indeed, we'll introduce Python, a very popular language that does not have pointers, does not have memory management at this very low level, but that's really just because someone else wrote the code that will do that for you, and it's going to make our lives easier because it means when you want to solve a problem conceptually up here to just get real work done or build something amazing, you don't have to really get into the same weeds as we have been deliberately this week and now last But the goal ultimately is that you better understand and can better harness then all that a computer can do, even in those higher level languages. So today we're going to focus particularly on data structures, how you might structure your data in memory, which really amounts to building things digitally, stitching together ideas and concepts in memory using this new building block from last week, which of course are these pointers. Pointers allow you to store addresses in memory, like in variables. But with those simple addresses, we can sort of leave these breadcrumbs. We can point from here to there, and we can conceptually stitch pieces of data together. But there's going to be different ways of doing that. And today we'll focus first on what's generally known as an abstract data type. And similar to a type in C more generally, it does actually have some properties in it, but the underlying implementation details of an abstract data type are ultimately up to you. That is to say, an abstract data type can represent one thing and can do something, but how you implement it allows you some discretion underneath the hood. So for instance, in the world of computer science, a queue is actually a technical term. This is a type of data structure that we could theoretically build in code in C or really any other language. But a queue has properties just like queues in the real world. For instance, if you've ever lined up for something to get food in a restaurant, or go into a store, or wait for the airport to clear you, well, you've lined up in a queue being some sort of line. But what's noteworthy about queues are specific properties. They are first in, first out data structures, either virtually or in the human world, which is to say the first person in the line should ideally be served first at the restaurant, or the first person in the line should get through airport security first. By contrast, if it weren't first in, first out, you can imagine how frustrated you would be if you have this sort of inherent unfairness. In fact, if you've ever been in line at a store, a supermarket, or the like, and all of a sudden they maybe open a new line, and now the person behind you gets to kind of cut ahead and go forward, that's because they've broken the concept of the cube. So it has this inherent potential for unfairness unless you maintain this first in, first out property. This would be true too for like a to-do list, just for productivity's sake. If you're in the habit on paper or virtually making a to-do list, ideally, you probably want to go through that list top to bottom so that you actually get the first stuff you thought of done first, rather than always focusing on your most recent thought. Now, within the world of queues, there's generally two operations, two functions, if you will, that any queue would have, either in the real world or in the virtual. Enqueue is usually the technical term to mean adding something to a queue. But specifically, it means adding it to the end of the queue so that someone isn't cutting in line, for instance, to go up front. And then dequeue is just the opposite. When it's time for the first person in line to be served, the time for the first person in line to go through security, they are dequeued, so to speak. So a technical concept ultimately as it's implemented in code, but it's really just a real world concept. And these are in contrast to another abstract data type that we might call a stack. And a stack, much like a stack of trays in the cafeteria, has sort of fundamentally different properties. You can still add and remove things from them, but consider what happens. Whenever they clean all of the trays in the cafeteria or the dining hall, they put one of the trays down here, and then the next one on top of it, and then the next one on top of it, and so forth. But of course, which tray do you presumably take as a user of that physical stack? The top one, presumably, right? Like you're not going to futz down here and try to pull one out. And so that would seem to have an opposite property. LIFO, last in, first out, is what characterizes something like a stack. And that just makes sense, certainly in the physical world, of stacking all of those cafeteria trays, because it just makes more sense to grab the most recently added one, the last added one, first. And at least in that context, the trays don't necessarily care what order they're used in. But even then, you could imagine that maybe there's some old, dirty, nasty tray at the very bottom that like never gets used because you're constantly replenishing the stack. So there might very well be side effects of these kinds of features. You might be familiar with using Gmail, for instance, or really any email program. What you're looking at in your inbox is technically a stack, at least if you've left the defaults configured. Why? You get a new email. Where does it end up? Not like 5 pages of emails later, presumably right at the top, and the next one's right at the top, right at the top, right at the top. And so if you're like me, you're guilty of eventually losing track of some emails. Why? Because you've pushed so many more emails onto the stack that you sort of lose track of the things you got earliest. Last in, first out, though, is maintained. The most recent email you get might very well be the first one you reply to, but that's not necessarily good for responsiveness to everyone else out there. Similarly, if you store like all of your sweaters in a stack like this, like a pile of black ones below which is a red and then a blue, stack might be perfectly fine for keeping things organized. It's sort of the sane way to do it if you just have a shelf in your dorm room or home. But what's going to be a side effect of using a stack to store your sweaters if they're these in this way, as opposed to a queue? Yeah. It's harder to get the red and blue ones. So presumably, you're going to much more often wear, for instance, if you will, black instead there. Now, the operations for adding things to a stack are similar in spirit, but just different vocabulary. You push something on top of a stack. Even though it's more like in the tray world, you sort of place it or rest it. But pushing means adding something to the top of the stack, and popping means removing something also from the top of the stack. So it's not a matter of enqueuing at the end and dequeuing at the beginning. With a stack, everything's happening on top. You're pushing onto the top and then popping off of the top. Now, when it comes to actual code, how might we implement something like this? Well, let's just focus on really how you might implement the data structure itself, and we won't implement any functions. You might implement the notion of a stack like this. We've seen typedef before. It just means define a new type of my own. Struct means here comes a structure, aka a data structure of one or more variables within. And let's suppose, like last time we defined already like a person data type using a separate typedef, and every person has like a name and a number or whatever. Let me just stipulate that person exists already. So here you might have, to implement a stack, an array called people of some capacity. Maybe it's an array of size 10 or 100 or whatever. This is a constant here in this context, capacity. And every element in that array is a person structure. And I now have this too, size. Now this almost seems like a synonym for capacity, but maybe intuitively, anyone want to propose why I'm apparently maintaining separately the capacity of the stack, but also the size of the stack? Why these two distinctions here? Yeah.
Capacity is how high the stack could be.
Yeah.
Size is how high it actually is right now.
Perfect. The capacity is how high the stack could be, like how much room is there for those sweatshirts in my closet, for instance, whereas size is just literally at this moment in time how many sweatshirts are in the stack. It's either capacity or fewer, presumably, in total there. So what is capacity? Well, we could implement this in, perhaps a familiar way. I might just define a const somewhere else in my code of type int that just defines it to be capacity 50. But what perhaps is going to be the downside of implementing a stack in this way, of using an array inside here? Like, what's a downside now of implementing a stack using an array and this size variable within? What's a caveat here, perhaps? Any hands? Yeah. OK, so it's going to be harder to reach elements that aren't the last one. That is the most recently added one. So there could be some sweatshirts, so to speak, way down below. So we've seen that before, too. But at some point, too, a limitation of this design is what it's going to be finite, right? I can maximally fit, in this example, 50 sweatshirts or 50 emails or 50 cafeteria trays, which is fine. But at least it's indeed finite. And at least in the computer's memory, it might be nice to use more and more and more, maybe as more things are getting added to the computer. So maybe I make this 500, or heck, why don't I make it 5,000 or 50,000? Well, what's the trade-off there? If I want to have enough room to grow, it seems like I should just crank up the value of capacity endlessly. But why might I not want to change the 50 to 500 or 5,000 or 50,000? What's the trade-off there, perhaps, just intuitively? Yeah. OK, you don't want to touch memory that you're not supposed to be touching. And in this case, that wouldn't be a risk per se, unless you indeed overflow the stack. But there's a related issue in asking for that much memory. What would another downside be? Yeah, OK, exactly. So if you've got a capacity of 5,000, but you're only using one of those elements, it's awkward, to say it non-technically, which is just to say very, very wasteful, right? That's just bad design. It's correct. It will work for up to 5,000 elements. But my gosh, you're wasting 4,999 extra spots. And that's not going to end well, especially if you're using more data structures in memory. Like your Mac, your PC, your phone is surely going to run out of memory if you ask for that much. So it'd be nice if there was a bit more dynamism there, whether it's a stack or a queue, both of which might be implemented a little similarly in spirit. But let's conclude this abstraction by comparing, thanks to a friend of ours, Professor Shannon Duvall of Elon University, who kindly put together this graphical animation that's just under 2 minutes long that paints a picture of these two types of abstract data structures. And then we'll dive in underneath to how we might implement problems like these. If we could dim the lights dramatically.
Once upon a time, there was a guy named Jack. When it came to making friends, Jack did not have the knack. So Jack went to talk to the most popular guy he knew. He went up to Lou and asked, "What do I do?" Lou saw that his friend was really distressed. "Well," Lou began, "just look how you're dressed. Don't you have any clothes with a different look?" "Yes," said Jack, "I sure do. Come to my house and I'll show them to you." So they went off to Jack's, and Jack showed Lou the box, where he kept all his shirts and his pants and his socks. Lou said, "I see you have all your clothes in a pile. Why don't you wear some others once in a while?" Jack said, "Well, when I remove clothes and socks, I wash them and put them away in the box. Then comes the next morning, and up I hop. I go to the box and get my clothes off the top." Lou quickly realized the problem with Jack. He kept clothes, CDs, and books in a stack. When he reached for something to read or to wear, he chose the top book or underwear. Then when he was done, he would put it right back. Back it would go on top of the stack. "I know the solution," said a triumphant Lou. "You need to learn to start using a queue." Lou took Jack's clothes and hung them in the closet, and when he had emptied the box, he just tossed it. Then he said, "Now, Jack, at the end of the day, put your clothes on the left when you put them away. Then tomorrow morning, when you see the sun shine, get your clothes from the right, from the end of the line." "Don't you see," said Lou, "it will be so nice. You'll wear everything once before you wear something twice." And with everything in queues in his closet and shelf, Jack started to feel quite sure of himself, all thanks to Lou and his wonderful queue.
All right. So that paints a picture of these two abstract data structures. But if we really were to dive underneath the hood, we could implement them in a number of different ways. But we really, I think, need some building blocks via which we could solve problems like those. And we'll see today, too, some others as well. So let's rewind back to week 2, where we introduced you to your very first data structure. That is an array. And an array, recall, was just a chunk of memory whereby elements were stored by design back to back to back. It's an array of contiguous memory specifically. So with an array, we could certainly store not just one thing, but 2 or 3 or even more. And so, for instance, if we treat my computer's memory as this sort of abstraction here, and pictured here are 3 bytes or some multiplication thereof, suppose we're storing in the computer's memory an array of size 3, storing the digits 1, 2, and 3. Well, remember that if we zoom out per last week, there's other stuff going on in memory. So even if we want to add another number to this array that we didn't think of when we first started the program, like the number 4, ideally we would put it right here next to it. Otherwise, it's no longer an array. So by definition, if we're using an array, it's got to end up right there after the 3. But what else is going on inside of your computer's memory? Well, assuming your program is of any length and you've got other variables, other functions, you've been running it for a while, there's a lot going on and your memory is being used and reused. So for instance, somewhere in memory might be immediately adjacent to this, like hello, comma, world, \0, the null character, just because maybe you have another variable somewhere in there that is storing that particular string alongside your existing array of size 3. And all of these Oscar the Grouches here really just represent what we called last week garbage values. Like there's obviously bits there because they don't disappear. They're always going to be inside of the computer somehow implemented, but we don't really know or care what they are. They're the remnants of those bytes having been used for other older variables, previous function calls, or the like. But the problem clearly here is that, OK, 1, 2, 3 is there, but the h is here. And unless I want to start taking a byte out of my string by overriding the h with a 4, like we just can't fit it right there. And yet, even though there's Oscars all over the place, those are indeed garbage values. And therefore, we could use that space because it's technically unused. We just don't know or care what the values are. So where could I put 1, 2, 3, 4? Well, my gosh, like I have all this memory down here that's unused. I could certainly change those garbage values to be 1, 2, 3, 4. But to do that, I might need to do a bit of work here, right? It's not just a matter of just saying boom and it happens. Now with C and with code, I'd have to do this a little more methodically. So let me abstract away everything else that's a distraction. Let me assume that there is indeed at least 4 bytes available for 4 numbers just down here, though we could have put them in a bunch of different spots. What's involved now in moving the 1, 2, 3 to this new chunk of memory so we can add the 4? Well, I think conceptually we're going to have to copy the 1 from old to new, copy the 2 from old to new, copy the 3 from old to new, and then ultimately we can get rid of the old memory. Those 3 original bytes could now look like Oscar the Grouch and just be garbage values for all intents and purposes. But now I have room for a 4th byte wherein I can put the number 4. So this is nice, but what's a downside of this approach? What's a downside of solving the problem in this way, where the problem at hand is just to grow the array, so to speak, to increase its size, to fit one or more numbers? Seems pretty straightforward, but yeah. OK, maybe it's out of order, but I think that's OK because the order is just matters that it's relative. So long it's still contiguous, back to back to back in a different chunk of memory, I think we're OK there. It's not like I changed it to 4, 3, 2, 1, but a reasonable hunch, yeah. Yeah, like I didn't really plan ahead here. Like if I have to add another number like 5 or anything else, well, I might have to jump through these hoops again. Maybe I get lucky and maybe there's space there, but not if I have other variables and other things going on. That too might be used at some point. Other thoughts? Yeah. Slow efficiency. Why? Yeah, I mean, it's just inefficient. It's sort of bad design, arguably. Why? Because I had to copy all of my original work down here. And as you note, if I want to add a 5th number, I'm going to have to copy it again and again and again and do things n times again and again. Now, maybe that's necessary. We'll soon see for sure. But it feels like this is not going to end well, especially if the array isn't of size 3 or 4, but 300, 400. Your computer ends up spending so much time just spinning its wheels. I mean, honestly, better might be this. Like if this is my same array, physically incarnated now, 1, 2, 3. It's literally on the edge of the shelf, so there's no room for the number 4. You know, maybe where we could take this story is, well, let's just find room for the 4. Like let's just put the 4, for instance, over here, replacing some available garbage value, some spare byte over here. But now, wait a minute. I've broken the definition of an array, right? I can't have 1, 2, 3, and then 4 over here. So maybe there could be a mechanism if I put this thing on again, where when you get to the end of the existing elements, maybe I just somehow digitally point to the 4th array. And maybe we can kind of stitch together all of these different values in memory so that if you follow the arrows, so to speak, we can reconstruct exactly what the order is, even without having to find or make room here or pick up all of these numbers and move all of them over there. So that's perhaps the direction in which we'll go here. So let's see how we might get to that spot as follows. Let me go ahead and open up, say, VS Code here. Let me open up a program called list.c in my terminal. And let me go ahead and whip up a relatively simple program that just demonstrates what we did back in week 2 when we introduced arrays as follows. Let me include standard io.h so we can print stuff out. Let me do int main void, no command line arguments for now. Let me give myself an array called list of size 3, and I'll just hard code it to keep it simple for lecture's sake, each of which is going to be an integer. And now, just so we have some specifics to talk about, let me put it list bracket 0, the number 1, list bracket 1, the number 2, and list bracket 2, the number 3. So I'm just translating into code what we just had pictorially on the screen and also physically here with these numbers on the desk. Now, let's just do something mildly useful for this. How about we do for int I gets 0, I is less than 3, I plus plus. Let's just print each of these numbers out just to make sure they're indeed in memory as I intended. So %i \n, comma I, and then a semicolon. And I think that's it for now. So nothing interesting, no problem solved just yet, just a proof of concept so that now when I clear my terminal and run make list, no apparent errors at the terminal. And so when I now do /list, I should see, hopefully from left to right, 1, 2, 3. But of course, if I want to add a 4th number now, there's no mechanism for such, certainly in the code that I just wrote. I could go back in here and change this to a 4. I could go down here and change list bracket 3 equals 4. I could just manually change the code, recompile the code. But of course, that doesn't give me any additional runway for the 5th or 6th number. So let me try to take a different approach, drawing some inspiration from last week. If I want to allocate memory dynamically, maybe because I don't know when I wrote the program how many bytes I want, we have another function as of last week that does not require that you commit in advance to a certain number of bytes. Via what function can you just ask the operating system for a chunk of memory? Okay, so malloc, to allocate memory. Now, an array is just a chunk of memory. And even though since week 2, we've been using this syntactic sugar, this convenience of just using square brackets and indexing into it, it's just making it easier to manipulate a chunk of memory that's contiguous, all together, back to back to back. So today, just like last week, we can take those sort of training wheels off and maybe be a little more deliberate in how we allocate memory. Let me go, for instance, and do this. Let me delete my contents of my main function here, go back into main, and let me propose now that I declare, for instance, how about my list no longer as an array, but as a pointer. So int star list, and I'm going to go ahead and initialize this to be, how about a chunk of 3 integers for now? So I'm still going to hard code it, but I'm taking a step toward more dynamism for now. So let me allocate 3 times whatever the size is of an int, but it's usually going to be 4 bytes as we know. So this is really going to be 3 times 4 equals 12, but it's a little more dynamic. And now what can I do down here? Well, this is just a chunk of memory. So I can do literally list bracket 0 equals 1, list bracket 1 equals 2, list bracket 2 equals 3. And voila, achieve the exact same effect. Because again, an array is just a chunk of contiguous memory. But malloc gives you any old chunk of contiguous memory, so you can rather treat one like the other here. Now, if you really want to be cool, you could do something like this instead. You could dereference the address in list and go there. You could go down here and dereference list plus 1 and go there. But honestly, no one really writes code like this. It's just too cryptic. It's a little too far over the line, at least for most people. And so I think the syntactic sugar, as I keep describing it, just the more user-friendly square bracket notation, does the exact same thing, figures out the pointer arithmetic, and puts each of these integers in the right chunks therein. Now, just to be super pedantic, let me make sure if something went wrong. So if list equals null, that means that something went wrong, like my computer is out of memory, which we should check for typically. So let me just immediately return 1, signaling anything other than 0, which means success typically, just to get out of this program because something's wrong. But now let me propose that I've had a, well, let's do this. For int I gets 0, I less than 3, I plus plus. Though a better design would always be to use a const, but I'm just doing this for demonstration's sake. Let's print out each of these ints too, and just make sure I didn't mess anything up. And let me open my terminal window again. Let me do make list again. OK, implicitly declaring library function malloc with type void star something something, implicitly declaring is the operative words there. What did I mess up? Yeah. Yeah, I forgot the header file in which malloc is declared. I remember now, OK, that's in standard lib.h. And it's fine to look stuff like that up if you forget. So let me include standard lib.h. Now let me clear my terminal, run make list again. OK, now we're good. /list. And now, what did I do wrong? Oh, OK. Not intended, but teachable moment. What did I do wrong? Yeah. Yeah, I'm printing the values of I instead of what is at location I in the array. So what I actually meant to do was print this out, thank you. So now let me recompile, make list, /list. And now, OK, those are the 3 values I was expecting, not the indices thereof. Now let me propose that for the sake of discussion that I regret having only allocated space for 3 integers. And maybe I really should have allocated enough space for 4. Now, this is not how you would do this in practice, because presumably if you have a change of thought, just go back in and correct the code. But let me propose that somewhere in here is a more complicated program, and time passes, ... There's a lot of other interesting code there. But at some point, I might want to give myself more memory. So how can I do this? Well, let me just ask the operating system now for 4 new bytes of memory, so that we can, at least in version 1, implement the idea on the board where I just copied the 3 bytes into the new 4 bytes and then added a 4th value. So I'm going to use malloc again, and I'm going to say here's a new pointer. I'll call it temp, TMP for short, which is quite common when you just need it briefly. I'm going to then call malloc again. I'm going to say give me 4 integers using size of. Let me again make sure. So if temp equals null, something went wrong. So let me just immediately return 1. And for good measure, before I return 1, let me free the original list so that I don't leak memory. So I'm not just immediately returning 1. I'm being a good citizen and remembering, well, if this malloc call did succeed, and indeed I got as far as line 18, but then line 18 failed, I should free the memory that I previously mallocked. So again, that's the rule of thumb. If you allocate it, you should be the one to free it, even before you're about to quit. Now, once I've done that, I think I need to do what we did pictorially on the screen, where I need to copy the 1, the 2, the 3 from the old array into the new. So how might I do this? Well, let me give myself a loop. So for int I gets 0, I less than 3, I plus plus, because the size of the original is still the same. Let me go ahead and treat the new chunk of memory called temp as an array itself. And so I can absolutely use these square brackets just like before. It's just a chunk of memory. I'm treating it like an array. And let me add to that value whatever's at the original list at location I as well. So this, again, is just this exercise of copying from old to new, step by step, the 1, the 2, and the 3. But I still need one additional step. If my goal at hand now is to have ultimately a 4th value here, well, I'm just going to hard code this for demonstration's sake. And I'm going to go to the very last location of temp, which is of size 4, which means the last element in temp is temp bracket 3, because it's 0 indexed, but there's 4 total spaces there. And I'm just going to arbitrarily, for the sake of discussion, put the number 4 there. And that is what happened when we proposed changing the final garbage value there to that 4. But now I need to do what the slide did for us sort of magically on the screen. I should now do a couple of final things. I should free the original list, which I've not